So good afternoon, everyone. Welcome to our first AP Stats virtual training. My name is Brendan Murphy, and I'm going to be one of our two presenters for the next 5.5 weeks. The other presenter you'll see tomorrow is Luke Wilcox. Luke and I have been friends for years, and so we're both excited to participate in this wonderful opportunity, and we really hope that we're going to bring some wonderful new teaching to some of you, perhaps some concepts that you didn't learn in your classroom. Equally as important, some major review for the AP Stats exam. So first and foremost, I hope you're safe. I hope wherever you are around the country, around the world, that you're healthy, and we're trying to get through hard times for all of us. I'm up in rural Maine, and we do have people in our area that have caught the coronavirus, and our thoughts are with them. So we hope you're safe. We hope you're at home, and we're going to try the best we can to continue to teach for the next 7 or 8 days, some new topics perhaps, and then we're going to do some AP review. So with that being said, I'm just going to segue right to my PowerPoint presentation. And there's our AP Stats logo. You'll probably see this every day. This will be our first slide as we get rolling. And kind of a cool little picture there. That's a normal curve there, and approximately normal looks like sort of a graph in the background. So again, today's lesson is my name is Brendan Murphy. I teach at John Baptist Memorial High School in Bangor, Maine. A great school to teach at. I've been there for 14 or 15 years. We have great kids. We're a really interesting school. It can be hard to even describe what we are. So we're a 95% publicly funded, independent international boarding school. So in a nutshell, we have around 70 students, international students from around the world. They come and live in Bangor with us for the year, and we have around 430, 440 what we call local day students. And they live anywhere from 5 minutes to an hour and a half away from Bangor, Maine, and commute back and forth each day to our school. So a really great group of kids, and we're at home now until at least April 27th. This is my second week of virtual teaching with my students at John Baptist, and I'm hopefully getting a little better with Zoom and some other technology that a couple weeks ago was sort of brand new to me. So again, I'm going to be one of the presenters. Luke Wilcox is going to be the second presenter. You'll see Luke tomorrow afternoon and Friday actually. Luke teaches at East Kentwood High School in Kentwood, Michigan. We both taught AP Stats for over 15 years. We were trying to figure out how many years we each taught yesterday when we had some of our trainings. And we've both been AP readers, so we've helped grade the AP Stats exams for years and years and years. And as we kind of dive in and do some mathematics, both of us will bring some of those helpful hints or tips from AP readers. And when we're grading, physically looking at your paper, students' paper, how can students earn points, or sometimes one or two words and they could lose a point. So we'll bring all that experience into our different sessions from now until May 1st. We're also both what we call College Board consultants. So on weekends during the school year or weekdays and in the summer, we run professional development for teachers. And so during the school year, I teach kids, and in the summer I teach teachers. We both love AP statistics. It's near and dear to our heart, and we think you made a great decision to take this course, and we hope you stick with it, and we hope these next 4.5, 5, 6 weeks can really help you guys out. So today I'll introduce some new math, but I'm really going to focus on why certain decisions were made and those types of things, and give you kind of an overview of our scheduling. So you can see me right now. You'll see Luke tomorrow. Again, we're really good friends. We were both excited for this opportunity. We're kind of jazzed up. We hope we do a pretty good job for you guys. So we also do some SAT work, and so he and I work together literally many times and spoken at conferences and whatnot. So we know each other well. So here's a quick overview of our scheduling again, right up until May 1st. So we're going to be every day, Monday through Friday, from 2 to 2:45. That's Eastern Standard Time. So perhaps we have people from around the world, and you'll just have to do the math to figure out exactly what time it's going to be wherever you are. But we're going to meet every day, and all of these sessions will be taped. They're live on YouTube. You can go back and look at them. And towards the end of my presentation, you'll see we have a little homework slide, and I'll show you where you can access those. So here's logic. And there was a tremendous amount of discussion on both sides of the aisle about what this training needed to be. So for the first week and a half, so starting today, March 25th, until next Friday, April 3rd, Luke and I are going to teach units 8 and 9 in the College Board course and exam description, what we affectionately call the CED. You may have heard that term before. You may never have heard that term before. It doesn't really matter. For all intents and purposes, perhaps the last chapter or two in your textbooks, that based upon Luke and I being on the AP Stats listserv and talking to lots of teachers, it feels like most teachers around the country, have not gotten to these 2 units yet. So we felt that this was these statistical topics were perhaps something that you haven't seen in the classroom, or your teacher just hasn't had time to teach it to you. So that was the logic. Unit 8 is what we call inference for categorical variable data, more affectionately called chi-square. We actually have 3 different chi-square tests that are in the curriculum. And then Unit 9 is what we call inference for quantitative data, or inference for regression, or inference with slopes. So some of you perhaps earlier in the year did bivariate data, and you graphed scatter plots and came up with the least squares regression line, something like y hat equals a plus bx. Perhaps other teachers haven't, though. There's sort of a 50-50 split. It seems like some teachers do that earlier in the year, and then other teachers want to kind of combine this at the end of the year. So again, we tried to make decisions based upon where we thought most teachers and students would be. For some of you, this may be brand new, and for others, it could be review, and if that's so great. So the first 8 sessions, we're going to focus on teaching perhaps new material. Units 8 and 9, starting Monday, April 6th until Friday, May 1st, is going to be just AP review, and every day there's a different topic, and we're going to publish that soon. So I can't overemphasize this enough. These 2 units, units 8 and 9, so chi-square, what we call inference for regression, these 2 units will not show up on your AP Stats exam this year. Okay, nothing that we're going to teach you right now will show up on this year 2020 AP Stats exam. So then the question is, well, why are you teaching us stuff, Luke and Brendan, that won't be on this year's test? And again, there were lots of good discussions in-house with the College Board and teachers, and we felt that the College Board wanted to just make sure that all students had access to what we call the full AP Stats experience this year. So whether you're in school or whether you were out of school for the last week and a half, and perhaps some of us will go back, and perhaps some of us will, College Board wanted to at least extend the opportunity for all students around the world to have the full AP Stats experiences. So that's why Luke and I are going to be teaching for the next 8 days these 2 units. Again, nothing from these 2 units will show up on this year's AP Stats exam, and I just want to make sure that I stress that. So I'm sure Luke will say the same thing tomorrow. We also felt that in talking to many colleges and universities that they wanted to make sure that next fall, or year and a half, 2 years, depending upon what age you are and what grade you are in high school, whenever you went to the college, next college level, that you did have the full AP Stats experience, and that you have been exposed to these 2 topics. So next year, if you're a senior, we obviously hope you're going to go to college, and clearly you all want to study more statistics, right? Because you had such a wonderful experience this year. Your college professor may say, oh, if you're taking AP Stats, we assume you've had chi-squared inference regression. And so that was kind of the twofold logic behind this. We wanted to make sure that in very trying circumstances for all of us, that we were still able to give students the full AP Stats experience, the full course. And also many of the colleges and universities said to the College Board, hats off for what you're doing. We appreciate it. When these seniors show up on our college campuses around the country, around the world next year, we just want to make sure that they've seen and have been exposed to these topics. So there's no expectation that you'll have mastered these 2 in the next 8 days with Luke and I, but we do want to do hopefully a good job of introducing them and perhaps explaining some of the logic behind these 2 units. So that's a little bit about the schedule. Again, every day from 2 to 2:45 Eastern Standard Time, Luke and I will be presenting from now until May 1st. Starting on April 6th, We're going to just review all the major topics in the AP Stats curriculum that could be on this year's stats exam. So again, from the what we call the CED course and exam description booklet, it would be units 1 through 7, basically up through confidence intervals, hypothesis tests, 1 and 2 samples, means and proportions. So we hope that you're at least have done some of that work: confidence intervals, hypothesis tests, 1 and 2 samples with both means and proportions. If not, again, because you got behind or you're out of school earlier than other places, Luke and I will cover all that in our exam review. So we're going to publish that schedule soon, and so you'll be able to plan out your next 5.5 weeks as to perhaps what days you really need to sit in. Hopefully all of them, but if you have other AP courses that are going at the same time, I think AP Calc AD is actually the same time slot. So we want to give you as much flexibility as possible. Again, all of these PowerPoints trainings will be online, and you'll be able to go and watch those on YouTube. We'll talk about different test taking strategies for the AP Stats exam. Again, both Luke and I are AP readers. We've graded thousands and thousands and thousands of AP exams over the last 10, 12, 14 years, and so as we get to different topics, we're going to say make sure that you watch out for this, or this is a common mistake that we see on the AP Stats exam. So we'll make sure that you get that as well from us. The College Board will be posting in the next week or so a schedule of all the topics and the dates and the times and what Luke and I will be covering each day, and so that hopefully will give you some better idea of how to schedule out your next 5.5 weeks. You could be having regular classes at school. I'm teaching in the mornings at John Babb, teaching virtually at for my John Babb students. So we're all busy, and again, we hope that you can make as many of these sessions as possible. So for this year's exam only, again, it will be a 45-minute test. That's compared to previous years about a 3-hour exam. So we've drastically cut the amount of time and therefore the number of topics that we're going to test. So it will be a 45-minute test. This is for all AP courses, not just AP Stats. It will be just all free response questions, FRQs. Some of your teachers may call them FRQs. No multiple choice questions at all on this year's AP Stats exam 2020. The assumption is that many students, if not most or all students, will probably end up taking this exam at home via their computer, tablet, or phone. So the test development committees, each discipline has a committee of half high school, half college that physically write your exams. AP Stats test development committee is probably working as I speak to you right now, trying to redesign the exam for this year. The 2020 exam 2 months ago was done. It was locked up in a vault and pretty much ready to go. Of course, all of our lives have changed dramatically in the last couple of weeks. So the test development committees are in the process of basically writing new exams. 45 minutes, all free response, and we're writing it so that you'll be able to write your answers, type your answers on again a computer, tablet, and phone, and then submit them electronically to the College Board. Right now, I'm not sure I know much more than that. Much more detail. If you go down a couple bullets, you'll see what will be coming on April 3rd. So again, this revised format is just for this year, the 2020 AP Stats exam and other AP exams. They're all 45 minutes. They're all free response. There could be an exception to AP Studio, but for all intents and purposes, all of your AP exams are going to follow this. There'll be 2 different what we call test administrations. One's going to be earlier, and one's going to be later. Probably in May sometime, but those decisions haven't been made yet, so stay tuned. And again, coming out a week from this Friday, the College Board is going to publish when we're going to be giving these 2 test administrations. I think there'll just be a little bit more info. How many questions perhaps on the AP Stats exam, how many free response, and those types of things. So when I met with my AP students today, they had a million questions, and unfortunately I couldn't answer all of them. So Luke and I will keep you updated on April 3rd or April 6th, who's ever presenting. We'll make sure that anything that's applicable to this course, you guys get all that information. So what do we really need to know when we talk about chi-square? Well, at this point, if I was still teaching day-to-day, face-to-face at John Babb, I'd probably be teaching chi-square. It feels like where I should be in my curriculum. Hopefully you've been studying what we call confidence intervals and hypothesis tests with your teachers probably for the last couple weeks, month or so. And so when I get here, most of my kids will say something like, boy, this feels, Mr. Murphy, an awful lot like what we've been doing. And that's your statement. So this is if you want to think about it as just another hypothesis test, that's really all chi-square is. We'll talk about how it's different and perhaps where you can use this. In this unit, there's no confidence intervals, so we just have hypothesis tests. And so again, many of my students would say something like, boy, it feels like there's only half as much work, Mr. Murphy, in this unit as the last couple chapters. And that is a correct statement. So for chi-square, we're just going to talk about hypothesis tests. We do not do confidence intervals with chi-square, at least in this course. So for the next 4 or 5 days, we're looking at doing chi-square. There's just one formula for all of chi-square. And I just took this right off of the formula and table sheet that the College Board will produce, and it will be part of your AP Stats exam. So this is right on your formula sheet. Of course, this topic, again, as I said earlier, will not be on the exam, but there's lots of other good formulas. And one of our lessons as we get into April and review will be called Know Your Formula Sheet and Know Your Tables. And so you guys will be well versed in what formulas are given and whatnot. So chi-squared statistic, it kind of looks like an x squared. It's really not an x squared. I guess it's a slanted x squared. Equals the sum. So sigma, we're going to add up. In the numerator, we have the parentheses observed minus expected, and we square that. So the numerator is always going to be positive. Sometimes if I were to do that difference, I would get a positive number, and other times we would get a negative number. So when we square it, we make it all positive. So we're going to add up a whole bunch of observed minus expected values. We square them. Now they're all positive. And we divide each one of those by what we call the expected value. So the observed that's our raw data. Those are the numbers that we're given or that we've counted or that we've done a sample. Expected, there's some formulas that we can use to calculate those. And again, those will come in subsequent sessions. So again, this formula is included on the College Board formula sheet. It's on your AP Stats exam. Hopefully when you all take it in whenever, May or June of this year, whenever those dates come out, you'll see it there, but you're not going to use it. So chi-square, again, is not going to be on this year's AP Stats exam, but we really wanted to make sure that you were at least exposed to that. So chi-square is we call it a non-parametric test. So what does that really mean? It means that we don't make any assumptions about the underlying parent population distribution. We don't need to check for normal distribution. We don't need to check for an analysis. They all basically mean the same thing. And hopefully you've been checking your conditions, right? Your teachers have been stressing things to check for to make sure that the tests we're running are valid. What's sort of nice about chi-square is we have less conditions. So that's in many ways a good thing. We don't have to worry as much about sample size being big enough to assume at least approximately normally distributed sampling distribution or parent population. So if we call it a non-parametric test, and we're just not worried about that check for an analysis. We're just not as concerned. If it's not approximately normally distributed, that's okay. And we can still run our test and we can analyze the data. So that was a quick lesson overview of chi-square. And so we actually have 3 different chi-square tests. Luke is going to do goodness of fit tomorrow. Luke will do chi-square test for homogeneity on Friday, and I'll come back and do chi-square test for independence. So we have 3 different chi-square tests. Again, it's just that one formula. So that's sort of nice, right? We just have one formula for these 3 different tests. They are different, and perhaps the one thing that's a little bit more difficult for students is, where do we use each test, Mr. Murphy? I know I just have that one formula. You told me it was non-parametric. So Luke and I are going to try and make sure that you understand where and how we can use each one of those different tests. Okay. So we have chi-square test for goodness of fit, what we call GOF. I think if you go to your calculator, you'll see GOF. So if you hear GOF, that's goodness of fit. The students of mine who are much more versed in the English language feel like goodness of fit doesn't sound very good. It's how well does it fit? Maybe it should be wellness of fit. But we all call it goodness of fit. And so we'll call it GOF. And I think you'll see I have a couple of problems as we get into the PowerPoint where you can hopefully see where we use each one of these tests. Chi-square goodness of fit, we're comparing our data to some pre-established model. It'll make more sense a little bit. We have chi-square tests for what we call homogeneity. We don't penalize for spelling mistakes on the AP exam, so don't worry about spelling mistakes. Chi-square test for homogeneity, I'm oversimplifying a little bit. I think we have 2 different populations, and we want to compare one variable between those 2 populations. Many times when we're doing a chi-square test for homogeneity, data is presented in what we call a 2-way table. But we'll take a look at that. And then we have what we call chi-square test for independence. That's maybe the opposite of homogeneity. We have one population, but 2 more variables that we're comparing within that population. So again, we have these 3 different tests. We need to, our students are required to figure out, which test goes where. When do I use chi-square goodness of fit? When do I use homogeneity? When do I use independence? That can be tricky. And I say to my students, when in doubt, just put chi-square down, chi-square test, and then try and put all the other information that we're looking for and don't stress over it. Probably the hardest thing, and we'll practice this next couple of days, is figuring out what test to use and then coming up with a null and alternate hypothesis, which is almost always in words, so that may be easier than using the correct statistical nomenclature symbols. But my students tend to struggle a little bit with the null and alternative. We do need to calculate degrees of freedom. So degrees of freedom, perhaps similar to what you did with means. I introduced the concept of degrees of freedom probably in the first or second week of AP Stats way back in August or September when we're doing standard deviation. And we divide by n minus 1. I don't know if you remember that way back in September. And then when we're doing our correlation coefficient, calculating our value that formula has it in. And at times it's a really elusive concept for students. And sometimes it's not until we get to chi-squared that the students really start to understand what does this whole concept, what do you mean degrees of freedom, Mr. What do you really mean by that? So there's a couple different ways we can calculate degrees of freedom depending upon what test we're working on here. So again, Luke and I will cover all this when we actually dive in and do some of the problems. We do need to check conditions. So when you're doing means and proportions, different teachers have different acronyms about what conditions we need to check and what assumptions are we making. None of these tests have any validity if the conditions aren't met. We're using the wrong test in the wrong place. So for chi-square, we do need to check conditions, but it's just these three. So we need to make sure that our data was randomly selected from the population. Most of the time, that's literally right in the stem of the problem somewhere. Data was randomly blah, 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 blah. So that's easy, and many times it's in the stem of the problem, and I would just instruct my students to just write it up. Data was randomly selected as stated in the stem of the problem. So without random selection, this test is just not valid. We just can't use it. All of our expected values are at least 5. So I'll just go back to the formula. You can see that in my denominator is my expected values. If that's a really small number, that's going to make the chi-squared statistic really big, and that's going to lead us ultimately to what we call a low p-value, low probability of something happening. And so if we had a really small expected value, less than 5 or decimal, it might artificially make this chi-squared statistic larger than it should be, and it might lead us to reject the null hypothesis when perhaps that may not be the best decision. So we need all of our expected values to be at least 5, and that could again show up on a multiple choice. Of course, not this year, but in previous years, we've tested that on a multiple choice. And on free response, we would just want students to list this again. No chi-squared in the 2020 exam. And again, what we call a large count, our population is at least 10 times our sample size. So if we have a sample size of 50, we want our parent population to be at least 500, and that's most likely going to be an assumption. That's probably something that you mathematically can't check. Many times we don't even know how big the parent population is, but it might be reasonable to assume that the number of M&Ms, blah 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 blah, or the number of students that go to a large college. I think I have a couple problems that will address that. So non-parametric tests, all 3 of these chi-squared tests are what we call non-parametric. We don't need to worry about that normal shape, but we do need to make sure that our data was randomly selected. All of our expected values are at least 5, and we need to check that large count, make sure that our population is much bigger than our sample size. So a chi-squared table will be included in your formula sheet and table component of the AP exam. So you're going to get a list of formulas. There's 2 pages of formulas. Chi-squared will be on that. Of course, we won't use it this year. You'll get I think 2 pages of a Z table, 1 page with a T table, and 1 page of what we call a chi-squared table. Again, I took a picture right from the AP Stats exam. I don't have the whole table, but your chi-squared table is going to look something like this. If you notice over here on the left-hand side, we have degrees of freedom. These numbers in the body are our chi-squared statistic, and then if we look along the top, we have our tail probability. And so again, Luke and I will actually walk through some multiple choice. I'll do a couple multiple choice today, and Luke will probably get into some multiple choice and free response tomorrow. Our calculators can run all of these or perform all of these tests for us, no different than means, proportions, confidence interval, hypothesis tests. Depending upon how I'm doing for time, I can show you where these are in your calculator. I mean, we do want students to use the calculators. We don't necessarily want them to do all of these computations on a piece of paper. You are allowed to use your calculator and type your data into matrices and run a chi-squared test and come up with our chi-squared statistic, degrees of freedom, the probability. Again, hopefully you were studying this before school was out, and some of these concepts hopefully make sense. But you will have a chi-squared table on your AP Stats exam, and you should be using a calculator for any problem that you see fit or any problem that's applicable. So let's actually look at a couple of AP problems, and let's see if we can figure out why these might be different than a mean or proportion problem. So if you've been studying hypothesis tests, let's take a look at a problem and see how this may be different. Okay, so let me give you just a minute or so, a couple 30 seconds to just read through this problem, and then we'll go through it. And I won't actually run the whole test, but I just want to show you what a chi-squared problem could look like. So I'll give everyone 30 seconds or a minute, read through the problem. I'll read through it as a group, and then we'll talk about why and how is this different. Okay, so this was from the 2002 multiple choice, the 2002 exam, and it was a multiple choice question. Brown eyes, green eyes, and blue eyes. I use this with my students every year. It's kind of a neat little multiple choice problem. And we actually record. People tell me what color eyes are, and we actually come up with our own data. But in this problem, a geneticist hypothesizes that half of a given population will have brown eyes, and the remaining half will be split evenly between blue and green eyes. So I read that, and I say about 50% will be brown, and 25% will be blue, and 25% will be green. Notice that the data above is in what we call counts, numbers. Many times chi-squared is given to us as percentages, so the 50%, 25%, 25%. So we need to convert at some point those percentages into counts. So for chi-squared, if you see percentages, just note to self that we need to convert those into counts numbers. In random samples, that's good. I guess we got our randomness in there. Of 60 people from this population. So we took a random sample of 60 people from a population. The individuals are distributed in the table above. So we randomly sampled 60 students at a large school. 34 had brown eyes, 15 had green, and 11 had blue. Those are what we call observed. So that's the actual data values. So those are our observed values. If my math is correct, 50% should have brown eyes. So 50% of the 60 would be 30. So I would expect to get about 30 brown eyes. 25% of the 60 people would have green eyes. So there's the 15. So we observed 15. We would expect 15. Whereas brown, we observed 34, and we expected 30. For blue eyes, again, 25% of 60 would be 15. So we observed 11 students had blue eyes, and we expected, or we thought we would get about 15. So I would just say to my students, how does that feel? Do these numbers look reasonable? Are they close? So we sort of get a good discussion going. This is day one of chi-square. They don't know how to run the test yet, and I don't expect them to. So we have some data that we collected. We have 60 people, 60 data points, and in goodness of fit, we're comparing that to some model, some determined model. And so in this case, it was the 50% brown eyes, 25% green, and 25% blue. So this feels like a goodness of fit to me. I have some observed data, and I'm comparing it to a predetermined model. So how does this feel different? Well, up until now, we had one sample, and we went to 2 samples, but we've never really been able to deal with 3 different groups or categories, right? Up until now, we've been sort of limited by what we call 1 sample and 2 sample. I guess with chi-squared, we can have multiple. We could have 10 colors of different eyes. And so chi-squared sort of opens up the door to potentially more scenarios where we don't have just 1 or 2 samples. We in this case have 3 different groups or 3 different categories. What is the value of the chi-squared statistic for the goodness of fit test? Again, we won't actually run the test. I just want to sort of throw this problem out and show you how maybe it feels different, and that's a good thing. This would be kind of a classic goodness of fit test. We have some observed data, and we want to compare it to some predetermined model. In this case, predetermined model was 50% blue eyes, 25% green eyes, 25% blue eyes. Again, percents, many times we have to convert those over to counts, raw numbers. So here's another multiple choice question. Again, let me just give you 30 seconds to read it and see if this feels different than what you studied before, and does this feel like perhaps it could be chi-squared. Okay, so this was from the 2007 table below. So looks like we have 4 different types of flowers that were crossbred. We have magenta flower with green stigma, we have magenta flower with red stigma, we have red flower with green stigma, and red flower with red stigma. So we have 4 different groups or categories. Again, we have some observed counts over here on the right. So there were 115 magenta flowers with green stigma, there were 49 magenta flowers with red stigma, et cetera, et cetera, et cetera. So these are counts over here. And again, hopefully you're saying up until now we've had 1 sample, 2 samples, but we've never sort of been able to incorporate these 4 different groups or categories. And this is where chi-squared sort of kicks in and can help us. So a biologist, expected that the ratio of 9 to 3 to 3 to 1 for the flower types respectively would result from crossbreeding experiments. So here's the predetermined model. Okay, here's the predetermined model, and we're comparing our observed values, the 115, 49, 32, and 21, to this expected ratios. So again, here's where I have to probably do some math, right? I would have to add up those totals and then put the corresponding proportion, 9 to 3 to 3 to 1, and I would come up with expected values. So chi-squared we have observed, that's the data we have. We many times mathematically will calculate what we call the expected values, and we would write those on our paper somewhere, and then I would go back to that one formula and plug it in. And again, Luke and I are going to actually walk through some problems, both multiple choice and free response in the next few days. Today was really just setting the stage and trying to give you a little bit of the logic of what we're going to try and do the next 5.5 weeks with you guys. So one more multiple choice. I think this actually might be your homework. Yes, it's your homework for this evening. So let's read through that. We'll talk about homework. You don't need to stress about your homework. This could be just something that you want to think about before tomorrow. And Luke will start out with this problem tomorrow. So he and I are in constant touch with each other. We'll be talking each day for the next 5.5, 6 weeks, and we'll be talking about what worked with and we usually leave off those types of things. So he's excellent. I think you're going to really like Luke as well, and hopefully hits the ground running and he'll start with the problem. So again, let me just give you 30 seconds or so to read it. You can look at the answer choices here, and we'll try and talk about it, and then we'll wind down for today's session. Okay, so 2012 exam, multiple choice question number 30. In order to plan its next advertising campaign, the trendy motor vehicle company is investigating whether the type of vehicle and the color of vehicle are related. Okay, so I'm going to call this a two-way table. I have 2 groups of categorical variables, and I want to see is there some relationship between the color of the vehicle versus the make of the vehicle type, cover, structure. No idea by looking at those numbers right now whether there is or isn't. Each person in a random sample of size 275 selected from the company's mailing list was classified according to the type, car, or truck, and the color of the vehicle he or she drove. Imagine if I add up all those numbers, I'm going to get 275. Again, I would call this a two-way table. Anytime you have a two-way table, we're basically looking to one of the things we're looking for is to see is there some relationship between these 2 categorical variables. Is there a relationship between vehicle color and vehicle type? In other words, are there more red trucks and red cars? Are there more black cars than trucks? Who knows? Okay. Which of the following procedures would be most appropriate to use for investigating whether there's a relationship between vehicle type and color? So I won't give you the answer. Probably it's going to be chi-squared, right? Because that's what I'm doing today. But let's look at the answer choices. A 2-sample t-test. Okay. Well, do we have 2 samples? And are we dealing with means? A 2-sample z-test. So again, do we have 2 samples and we deal with z's with proportions? So is this 2 samples with proportions? A matched pairs t-test. Again, that would be with means. And we sort of have a before and after. They're not independent. Okay. They're dependent upon each other. Chi-squared goodness of fit. So we did that a little earlier today. Chi-squared goodness of fit. We collect some data and we want to see, how well does that data line up to some sort of predetermined model or predetermined relationship. I'll leave that up to you guys. And then chi-squared test for independence. I'm going to do that next Monday, but keep in mind what a chi-squared test for independence is. We have one population and I want to compare 2 or more variables within that one population. So I'll leave that up to you guys, and that'll be your homework. All of these sessions are being recorded. They're on YouTube Live. I'm streaming live, I think, right on YouTube. They're also going to be posted at this website, www.statsmatic.com/YouTube. Luke, who you'll see tomorrow, he's one of the founding fathers, the architect of Statsmatic. I don't know if any of your classes or teachers are using it. So he's graciously said that he's going to post all of our sessions on Statsmatic, and so you'll be able to find the homework there. And if you go to that, if you're on, I think you're all on YouTube right now. If you go down and scroll under descriptions, you'll also find this link to that same website. So real quick, let's debrief and summarize what we did today. So today was set the stage. We're glad you're here. Again, I hope you're safe at home and healthy, and that we get over this as quickly as possible as a country and a world. The next 5.5 weeks, Luke and I will be running these afternoon sessions from 2 to 2:45 each day. From now until Friday, April 3rd, we're going to be reviewing units 8 and 9. And those again will not be on this year's AP Stats exam. So the 2 units that we're doing for the first 8 sessions will not be on your AP Stats exam. Anything else that you've had during the course of this year, units 1 to 7 in the College Board's CED, are clearly potential topics. And Luke and I have a 20-day plan as to how we can best help you get ready for the modified AP Stats exam this year. So I want to introduce the 3 different chi-squared tests. They're all hypothesis tests. There's no confidence interval. There's the 3 different tests, what we call chi-squared goodness of fit, chi-squared test for homogeneity, and chi-squared test for independence. And that's where we need to put our thinking caps on and figure out, looking at this problem, which of these 3 tests do we use? The formula is the same for all of them, so that's kind of neat. That makes it a little bit easier. And the assumptions and conditions that we need to check, well, there's only 3 of them, and it's a whole lot less strict perhaps than means and proportions, where we really had to make sure that we were checking lots of different things. And a little bit of a homework. We went through the schedule. We talked about the AP Stats exam, how that's modified. We did a quick overview of the 3 different chi-squared tests. And we want to sincerely thank you, the College Board, myself, and Luke, who you'll meet tomorrow for joining us. I'm sure you guys are super busy. We're busy. We're working really hard to get this hopefully wonderful training in front of you guys. And it's a little awkward to not see any faces or have any students raising their hand, Mr. Murphy. So that's going to take a little bit. Luke and I will adapt real quick and we'll figure it out. But I hope there's hundreds, if not thousands, of students and perhaps teachers watching us today. And we hope that you keep coming back day after day. We are going to post a schedule of what different things we're going to do, and that's going to be soon. And as soon as it is, Luke and I will make sure that we post that as well. So you do have a practice question. I'll just scroll back up to it real quick. That's your homework real quick. Maybe read through it again and look to see is it A, B, C, D, or E, and if so, why? How did you make that decision? That will be posted at this website, www.statsmatic.com/YouTube. And Luke will pick up tomorrow, same time, 2 o'clock. I'll see you guys next Monday. So I am right around 2:45, and that's when we said we would go to. So I timed it well, I guess, today. So thanks again. We really appreciate it. Luke and I are pretty jazzed up about this, and hopefully we get in the groove quickly, and you guys can tune in and watch this as many days as possible. So please be safe. Please take care of each other. Please take care of your families. I'm going to sign off now, and you'll see Luke tomorrow. I showed you this little picture there at the beginning of the presentation, and I'll see you guys on Monday. So thanks again. Be safe. I'll see you Monday, and you'll see Luke on Thursday, Friday. Thanks.
Oh, AP Stat students from around the country and also from around the world, and welcome to day 2 of the AP Statistics virtual instruction offered by the College Board. I sure hope that you got a chance to get online yesterday and check out my colleague, Brendan Murphy, who started us out yesterday with day 1. I'll be here with you today and tomorrow, and then we'll just be sort of switching back and forth throughout the rest of this instruction. My name is Luke Wilcox. I am an AP Stats teacher in Kentwood, Michigan. And if you're from Michigan, you pull out your map and you tell everybody where you're from. And so we're from West Michigan here, Kentwood in Michigan here. So that's where I'm from. And I'll tell you, we closed about 2 weeks ago at my school, and I was super bummed about it because some of the best lessons of AP statistics come at the end of the year. There's a lot of candy activities. Students just love the end of the year. And I was super bummed that I'm going to miss that opportunity with my own student. So when the College Board reached out to me and said, hey, would you like to do this thing online? I was just super excited about it because now I'm going to get a chance to share some of those excellent lessons. But I will tell you, I'm a little bit nervous about this whole YouTube thing, this whole YouTube live. I'm kind of old, so I'm not super familiar with this sort of thing. So I checked with my 8-year-old son, Trey, and I was like, hey, Trey, what's this YouTube live thing? Like, do you think I could teach kids AP statistics? And he said, Dad, you're gonna be on YouTube live. You are going to be YouTube famous, Dad. Well, I don't quite think that's going to happen, but I like that my son is thinking that about me. So I do have one request of all you AP stat students. So listen, if you ever see me at the grocery store, pumping gas, something like that, and I'm with my children, I'd like you to come up to me and ask me for an autograph and tell me that you saw me on YouTube, okay? Because I'd really like for my son to actually think that I am in fact YouTube famous, okay? So without further ado, let's go ahead and jump into the lesson for today. So just to make sure that everybody's in the right location, I hope that you are here tuned in to learn some AP statistics. You already know who I am. My name is Luke Wilcox. I teach at East Kentwood High School in Kentwood, Michigan. I have been a teacher there my whole teaching career of 19 years, and 15 of those years I've been teaching AP stats. So I do want to take a quick moment to give a shout out to my East Kentwood High School Falcons. So what's up to my first and second hour AP stats? Also want to say hello to Miss Dallas, 3rd hour and 4th hour AP stats. I hope all y'all are doing excellent and that you're safe in your home with your family. Now, in terms of AP statistics, I do have quite a bit of experience teaching it at 15 years, but I've also been an AP exam grader for the last 6 years. And so I'm definitely going to try and bring some of that expertise and knowledge to the lessons that I'm going to bring you. Some of the sort of insider information that you learn when you sit for 8 hours a day and grade student papers. So I'll try to share that as much as I can with you. I also do a whole lot of training with AP statistics teachers around the country. I've been a College Board consultant for AP statistics for several years now. Now, a couple of quick reminders. I know that Mr. Murphy talked to you about this yesterday, but I just want to reiterate the schedule for us. We are in the 6-hour time slot, and that means that 2 o'clock to 2:45 every day. We're going to be meeting Monday through Friday. Just to give you a heads up on the schedule, March 25th through April 3rd, we will be covering units 8 and 9, which is most likely not something that your teacher taught you before you left school. This happened to be exactly where we left off at East Kentwood High School. We did 1 day of chi-square tests, and then we were out. So that's the last 2 units here. And very, very important. I want everyone to know this. Unit 8 and Unit 9 are not going to be on AP exam for the 2020 school year. Okay, so this is intended to be out there as an optional thing for you to be able to learn, to take with you forward into college. But it is important for you to know that this content from this week and next week will not be contained on your AP exam that you're taking this year. Then on April 6th, we are going to officially start the AP exam review, and that is going to be very specific, very targeted to getting you ready for the AP exam. Really excited about that. Now, all of the resources that you might need, which would include the lessons that we're going to be teaching, as well as the very short homework assignments that we're going to be giving you, you can find it at statsmedic.com/YouTube. There's actually a link if you look in YouTube right below me here. There's a link that you can click, and it will take you to those resources. They're organized by date. So today's March 26th. You will see March 26th listed there, and you can click and get the lesson that I'm going to be teaching today, as well as the homework assignments that I'm going to be giving you at the end of this lesson. Okay, so I am going to start with your homework from last class period. This was given to you by Mr. Murphy. This is a multiple choice question from an old AP exam, and so let's just take a look. And I'm going to read it out loud for you first, so you can remember what it was about. It says, in order to plan its next advertising campaign, the trendy motor vehicle company is investigating whether the type of vehicle and the color of vehicle are related. Each person in a random sample of size 275 selected from the company's mailing list was classified according to the type, car, or truck, and the color of the vehicle he or she drove. The data are shown in the table below. Which of the following procedures would be most appropriate to use for investigating whether there's a relationship between vehicle, type, and color? So I'm going to use a little bit of a multiple choice strategy here, and that's to just go through each answer choice and think about whether that answer choice makes sense here. So when I look at answer choice A, a 2-sample t-test, that means I have to have 2 samples, and it also means that we're going to have to be calculating means for each one of those 2 samples. For a 2-sample z-test, well, that's really the same thing. 2 samples dealing with means, but this time, for some reason, we know the standard deviation of the population. The third one, a matched pairs t-test, we'd have to have some paired data there where we'd be looking at differences, and we would want to find the mean of the differences. So right away, I'm noticing that in these first 3 answer choices, we're dealing with means, which would mean that we need quantitative data. Now, this is going to be different than the next 2 that you see. They're both chi-squared, which you know that's what's coming here, right? That's what we're going to be teaching this week is chi-squared test. And chi-squared tests, both of these are going to require that we have categorical data. Now, a little bit of a preview of what's to come, because today we're going to be doing goodness of fit. You'll see the test of independence with Mr. Murphy on Monday. But here's the big distinction between those 2 chi-squared tests. For a chi-squared goodness of fit test, you're going to have 1 population, and you're going to be measuring 1 variable. And we said that variable is going to be a categorical variable. Now, a chi-squared test of independence, you're still going to have 1 population with 1 sample, but now you're going to be measuring 2 variables for each individual in the sample. So let's go back to the question here and see which one of these answers actually makes sense. So I do see here that we have a random sample of size 275 from the company's mailing list. And to me, that sounds just like we only have 1 sample here, which I think is telling us that we have 1 population that we're sampling from. So really right away, A and B are out because this is not a 2-sample problem. The next thing I notice here is that the variables that we're measuring here, vehicle type, vehicle color, 2 variables, both of which are categorical. So certainly C is out because we need some quantitative data there. And we're left with these 2 chi-squared tests to decide between. And because we have 2 variables here, we definitely know that answer choice E is going to be the correct answer here. That's 1 population with 2 variables, chi-squared test of independent. And you're going to learn a whole lot more about that test on Monday with Mr. Murphy. Now, I do want to give you one other little clue that we had in the wording of the question. It talks about the relationship between 2 variables. Another word that we could use instead of relationship there is association. And anytime you see that word relationship or association, that is an indicator to you that that might be a chi-squared test. So I hope you did okay on the homework assignment there. And I think we are ready to jump into today's lesson. And what I'm going to do is I'm always just going to start with a quick overview to let you know like sort of where we're headed within that particular lesson. And the way that I like to organize things is with very specific learning target. And the reason I like this is because we can come back to these learning targets at the end of the lesson and make sure that we've actually accomplished these 3 learning targets. So let's just check in here. Learning target number 1 is to calculate expected values for a chi-squared goodness of fit test. The second learning target is about conditions, the random 10% and the large counts condition for a chi-squared goodness of fit. And then finally, by the end of this whole thing, we need to be able to do a full significance test. And I'm going to show you the way that I organize it using a 4-step process of state, plan, do, conclude. So we will check back in with these learning targets at the end of the lesson, make sure that we've learned what we needed to. Okay, so this is the actual lesson you're going to see here, and this is available on the website at statsmedic.com/YouTube. You can download it, or if you just want to write down some notebook paper, you can keep track of where we're headed. Okay, so the ultimate question of today's lesson is which color Reese's Pieces is your favorite? And I'll tell you, my daughter, she's 11 years old. Her name is Reese, and sure enough, her favorite candy in the world is Reese's. And she actually noticed one day that she was eating Reese's Pieces, and she noticed that there seemed to be a lot of orange Reese's Pieces. And I had thought that they were equally distributed, yellow, brown, and orange. They give you the same amount of each one. So I took a look on the internet, and according to the internet, the company claims the following distribution of color. So you take a look here: 25% brown, 25% yellow, and like my daughter thought, they're claiming that actually half of them are orange. So I'm going to give you just a little bit of a heads up here. What we're starting with this distribution of color that we're looking at here. This later is going to become our null hypothesis. And we'll have a couple of different ways of writing that. And one other thing that I want to point out here is that my daughter and I, we went ahead and we took a random sample of Reese's Pieces out of one of those big bags. We have one of those huge bags. We took a random sample of 50. Those Reese's Pieces are the 1 population that we're going to be dealing with in this problem. And we're looking at the variable of color, which is a categorical variable, 1 categorical variable. And we know from the homework problem we just went over that if we have 1 population and 1 variable, that this is going to be a goodness of fit. So let me give you the details about what we found. So we took a random sample of 50 Reese's Pieces. Go ahead and let's write down our observed count. We got 13 that were brown, we got 7 that were yellow, and we got 30 that were orange. And I think it's important to know right now that the total of these is 50. That was the sample size here was 50 from this large bag of Reese's Pieces. And so right away, my daughter noticed that we didn't get a whole lot of yellow in our sample. There's only 7 in the yellow there, and we're supposed to get 25% of them that are yellow. So that seems a little bit low. That's 7. And then she also noticed that 30 was a little bit high because she knew half of them were supposed to be orange and half of 50 would be 25. So right away, because those values aren't exactly what was claimed by the company, we do have some evidence that the company was lying about their claimed distribution of color. Okay, some evidence. Now later on, we'll talk about whether we have convincing evidence by using significance. So let's take a look at the expected count here. And very important, if we're going to be calculating the expected count, we're going to have to assume that this null hypothesis is true here. So assume that the company is actually telling the truth. We want to calculate the expected count. Well, for the brown Reese's Pieces, we know that there's 50 total, and they're telling us that 25% of them should be brown. So if I take 50 and I multiply by 0.25, 25%, that's going to tell me that the expected number of brown Reese's Pieces would be 12.5. Now for yellow, of course, we're going to get the same thing because 25% of them should be yellow. So we're going to get an expected value there of 12.5. Now for orange, the company claims 50% of those. So if I take 50, my sample size, and I multiply it by 50%, that's telling me that I should be getting 25 orange Reese's Pieces in a sample of 50. So as expected, or as we sort of mentioned earlier, the number of yellow that were observed is less than would be expected, and the number of orange is a little bit higher. So I do want to point out here a formula. We calculated an expected value here, and the calculation is really the same for each one of the colors. We're taking the sample size and we're multiplying it by the proportion. Sample size, proportion, sample size, proportion. So on the margin here, I'm just going to make note of what we should have learned from that, and that's that the expected value is really just the sample size n multiplied by the proportion for that particular color, right? Where the sample size n was 50. And hopefully this formula looks familiar to you. If you think way back to the binomial distribution stuff that we did, where we were counting the number of successes, this actually gave you the expected number of successes. Now I know some students might say, well, look, we can't have a half of a Reese's Pieces there, but it turns out that because this is an expected value or a mean, the decimal is okay there, so we can definitely leave our 0.5. We don't have to round our values here. So let's see if we can calculate the chi-square statistic. Now from yesterday, Mr. Murphy told you the formula for the chi-square, which is provided for you on the formula sheet. It is the sum of the observed values minus the expected squared, all divided by the expected. So let's just go through each color and calculate, plug in our numbers here and see what we get. So for brown, the observed number of brown was 13, and the expected was 12.5, and then we square it, and then we divide that by the expected value of 12.5. Now we move over to the yellow, and for yellow, our observed was 7, and the expected was still 12.5. And then for the orange, we had an observed value of 30 with an expected value of 25. And so I actually went ahead and put these on my calculator. Let me give you the values here. So this first value is 0.02. The second value is 2.42, and the third value is 1. And the total of that is going to be 3.44. Now I do want to take a look at each one of those individual components. We call these the components of the chi-square. And you'll notice that this first component is very small, almost 0. And the reason is, if you look at the calculation, the observed value and the expected value were nearly the same, right? 13 was almost exactly the same. So when you subtract it, you're going to get a very small number there. And then you're going to divide it by the expected. You're going to definitely end up with a small component. Now let's compare that to the value right next to it, which is much, much larger at 2.42. And the reason is because our observed value is actually pretty far away from the expected value of 12.5 there. And then the third one's sort of in between. And you'll notice that the difference between the observed and the expected on this one is 5. Almost the same as what it is from the previous component, but because the expected value was higher relative to the expected count, we're going to get a smaller value for chi-square. Now I just do want to make note here. I'm trying to pull out the important information. The thing that we needed to calculate our chi-square statistic here is the formula O minus E squared all over E. So let's just make note of that in the margin. Okay, I think we are ready now to check our conditions before we can perform a significance test. Hopefully you're very familiar with checking conditions, doing that with inference for proportions and inference for means. And the first two conditions are going to look very familiar to you, the random condition and the 10%. And you probably even see the large counts condition, but it's a little bit different here. So let me get into the details of each one. So for the random condition, we know that we need to check that we have a random sample. And I told you that my daughter and I took a random sample of 50 Reese's Pieces. So let's just note that we did in fact have a random sample of 50. The 10% condition is something that we have to check anytime we're sampling without replacement. And my daughter and I certainly didn't take one at a time and replace them back into the bag before we chose the next one. So we are sampling without replacement, which means we need to check the 10% condition so that we know that the independence is satisfied. And that's to say that the sample size, which is 50, is less than or equal to 10% of the population size. Now the population here is all of the Reese's Pieces in that large bag. So all Reese's Pieces in the large bag. And we're going to have to assume that there's at least 500 of them in that bag, and I think that's a reasonable assumption. So we can say that the 10% condition is satisfied. All right, now the large counts condition you likely saw when you were doing inference with proportions, and that said something like n times p and n times 1 minus p were greater than or equal to 10. Okay, similar here, we're going to look at the expected count, just like we did for proportions. It was the expected number of successes and failures. And we need to find the lowest expected count. Well, our expected counts, if you look back up here, 12.5, 12.5, and 25. So 12.5 is the lowest of the expected counts. And we need to check that all the expected counts are greater than 5. And this is certainly true. So all expected counts are greater than 5. So we have satisfied our three conditions here, which means that we can move forward with our significance test. So let's get down here to number 3, and we're going to see if we can calculate the p-value. So for this test, the degrees of freedom is n minus 1. And I'm going to guess that this looks familiar to you because you use that same formula when you were dealing with inference for means. But there's a very important distinction to be made here, and it's about what this n represents. Because in the past, when you were dealing with means, n represented the sample size. But here, very important, that represents the number of categories. So I actually don't even like to write the formula with n in it. I would rather you just write the formula as the degrees of freedom is the number of categories minus 1. That's where chi-square goodness fit. So in this particular case, the number of categories, well, we had 3 different colors that we could get for the Reese's Pieces. So 3 minus 1 is going to give me a degrees of freedom of 2. So the test statistic, we've actually already done the work for this one, right? That's the chi-squared value, which we have from above as 3.44. Now we need to be able to turn that into a p-value. And I'm giving you the hint here that you have to use table C in order to find the p-value. Now this table C would be provided for you on the formula sheet. So I've actually just pulled up the formula sheet in the AP exam here, and this is what table C looks like. And it's likely that you've probably already done some work with table A and table B, but table C is going to be what you need for any of the chi-squared tests here. And here's the way that works. The first thing you need to know is your degrees of freedom. And we have decided already that number of categories minus 1 is going to give us a degrees of freedom of 2. Now what you're looking for is you're looking for your chi-squared test statistic. And for our data, the chi-squared test statistic is 3.44. Now you're not going to find exactly that value, but let's see if we can get close. All right, I'm looking across the row, I'm looking at degrees of freedom 2, and I see 3.22, and I see 3.79, and I know that my value would be somewhere in between there, right? 3.44. And what this is telling me is that the p-value, or the area, this area that you see in the chi-squared distribution, that area has to be between 0.15 and 0.20. So that's telling me what my p-value is. So let's go back to the activity, and let's fill in our p-value there. The p-value is going to be somewhere between 0.15 and 0.20. Now that's nice. I like table C because it gives me an idea of what the p-value is, but I'd actually really like to know like the exact p-value, and there is a calculator function which will allow you to calculate the exact p-value for a chi-squared distribution. So if you grab a calculator, or you can just follow along on the screen here, I've got my calculator pulled up. I'm going to show you where you can find this on the calculator. Okay, so the menu that you're going to need here is you're going to need to go to second vars. So second vars, that's going to give you distributions menu, and it's likely that you've used this menu in the past. I'm going to guess that you probably use normal CDF and probably even TCDF to find the area under a normal curve or area under a t distribution. But we have a chi-squared curve, so you're going to have to scroll down until you get to chi-squared, and make sure you're using CDF, cumulative distribution function, rather than PDF. Go ahead and hit enter, and sure enough, I have my numbers saved here. The lower bound for us, that was our chi-squared test statistic at 3.44. The upper bound essentially you need to go to infinity, so I've just gone to 99999. Change your degrees of freedom to 2, and then you can scroll down to paste. That'll put it on the main screen for you. You hit enter, and there is our exact p-value of 0.179, which by the way is consistent with what we said in table C, where we thought it was going to be somewhere between 0.15 and 0.20. So now we got that value from the calculator. Let's go back to the activity and record that exact p-value because I prefer to have the exact p-value rather than a range of values. So let's just record here that the actual p-value, and this is from the calculator. Make a little note to yourself that this is from the calculator, and the command that we used there was chi-squared CDF. So if you could write that down, and the p-value that we got from the calculator is 0.179, which I like that a little bit better than I like what we get from table C there, because we know the exact p-value. And we are now finally ready to make a conclusion. Now this p-value is a relatively large p-value, definitely greater than 5%. And so what this is saying is that this result could have happened purely by chance, right? Just because of the random sampling here. And it's likely that your teacher has trained you a little bit on how to write these conclusions. So let's see what this format looks like here. We're going to say because this p-value that we just calculated, the p-value of 0.179 is greater than the alpha level, which we're just going to go with 0.05 by default. Now we have to make our decision here, and this is where we're going to fail to reject the null hypothesis, which we had stated up above is the company's claim is true. That's the null hypothesis which we are going to fail to reject. And we do not have convincing evidence that the company was lying about the distribution of color. So even though at the beginning there we said that we did have some evidence that they were lying about their distribution, we do not have convincing evidence because the results that my daughter and I got could have happened purely by chance about 18% of the time. Now we got one final question here on the activity, and it's asking which color of Reese's Pieces had an observed value the farthest away from the expected. And I had commented on this already, but it's definitely yellow. It was much less than expected. We had 7 yellow in our sample. We were supposed to get 12.5, and so that one was pretty far away, a little bit farther away than the other values there. And so it does make sense a lot of times at the end of these chi-square tests to go back and like look at this chi-square calculation here and see where the largest component is. And for sure, our largest component is here because the yellow was much less than expected. We call this a follow-up analysis. So I'm just going to make a note here that this is a follow-up analysis. But I'm going to say too that it's not all that important to do a follow-up analysis if the results that you got were not statistically significant. This would certainly be more interesting if we had statistically significant results. So in general, I would say that this follow-up analysis is really only necessary when you reject the null hypothesis, right? When you have statistically significant data. Okay, so that completes the activity here. Now, the thing I'd like to do next is I'd like to try and formalize this a little bit more on the next page. So this is where I'm going to introduce you to the 4-step process for writing up a significance test. And we really have all the pieces that we need. They're all here. We just have to be careful about how we format those. So go ahead and flip to the next page. And this is where we're going to write up our full significance test using the state plan do conclude template. And I've provided some little hints here about things that we need to make sure that we include. So let's start out with the state. We're going to need a set of hypotheses here. And we're going to start with our null hypothesis. And we already said this on the previous page. It's to say that the company's claim was true. So I'm going to say that the company's claimed distribution of color is correct. And then the alternative hypothesis, this is what we're trying to find evidence for, is that their claim that they were lying about that claim. So I'm going to say that the company is lying about their claim. Now that's not the only way to write your hypotheses. You could write them in symbols as well. So let me just make note of this. The other way that you could have written the null hypothesis is to talk individually about all 3 of the proportions. Because if their claimed distribution of color was correct, then the proportion that were, let's say, brown, and write it P subscript B was 25%, and yellow was also 25%, and orange is 50%. So we could have actually written it out in symbols there. Now if you do that, you have to specify what these parameters are. So you have to say what that P is. Like P with the subscript represents the true proportion of Reese's Pieces of that color. Just a little bit more work, right, to have to identify those parameters. The alternative would be that these proportions are not correct. And so you think, well, okay, what if one of them is incorrect? Well, if one of them is incorrect, that means it's a little bit higher or lower than what is claimed. And one of the other proportions is going to have to adjust for that because the proportions have to add up to 100%. So I'm going to say here at least 2 of the proportions are incorrect. That would be the alternative. Now I'm generally going to stick with the hypotheses written in words. And you're going to see that in the next couple of days when we do the other 2 types of hypotheses. Now also included in the state here is the significance level alpha. We were given a value right here. This alpha value is 0.05. So I'm just going to carry that. Okay, name of the procedure. Well, I hope you know at this point what we're doing here is a chi-squared goodness of fit test. And you will sometimes see that written as GOF, G-O-F. And actually you'll see that on the calculator. Okay, so let's go ahead and check our conditions here. We already did this on the previous page. So I'm going to just say here, let's say C previous 8. And that's the random, the 10%, and the large count condition, which we've already done that work. Okay, now the do part is where we actually do the calculations here. So I do want to show you the work that would be required with this. I'm going to start by just writing out the formula, and this will come from the formula sheet from the exam. And we showed this work on the previous page, but I'm going to carry it over here because I'm going to connect it to the picture that we're about to draw here. We had 13 that were brown, and we expected 12.5. We had 7 that were yellow, and we expected 12.5. And we had 30 that were orange, we expected 25. And when we added that all up, we got a chi-squared value of 3.44. So I'm actually going to carry that over here. The chi-squared test statistic is 3.44. That over here. Now let's talk about the picture of this. We didn't talk too much. I showed you table C, but I didn't talk about how this chi-squared distribution is a little bit different than a normal distribution or t-distribution. And you saw it in table C in the shape of the figure. So let me just like make a little bit of a picture here to show you what a chi-squared distribution looks like. And there are several different chi-squared distributions depending on your degrees of freedom. Okay, we've got degrees of freedom 2 here, and actually with degrees of freedom 2, the chi-squared curve looks something like that. Degrees of freedom 2. Now if I were to increase my degrees of freedom, right, the number of categories increase, you're going to end up with a distribution that looks maybe something like this. That would be maybe degrees of freedom 5. And then let me draw one more for you. If the degrees of freedom was even bigger than that, it would be quite as tall, and it would go further off into the right. Let's call that degrees of freedom 10, right? And the important thing to notice here is that this value is 0, right? The lowest possible value you could get for chi-squared is 0, and that's because if you look at the formula, you're always going to get a positive value there, right? We're squaring things, and when we square things, everything becomes positive, so you can't get a value less than 0. And then the other thing to notice is that these distributions are all skewed to the right. Although I will say that as the degrees of freedom increases, it becomes a little bit less skewed to the right. Okay, now for our problem here, let's draw our picture. We have degrees of freedom 2, which we know is this one that looks like this. I'm going to clearly identify that this is a chi-squared distribution. I'm going to clearly identify that the degrees of freedom here is 2, and I'm going to go ahead and put in our chi-squared value, which we had calculated as 3.44. And this right here is the holy grail, people. This is the p-value. This is what we need in order to make our conclusion. And we actually did this work already, right? We did it on the calculator. We got a p-value of what was it, 0.179. Now I tried to get in the habit of putting a box around the test statistic and a box around the p-value. Those are 2 very, very important things in the calculation. So I just want to highlight those. And we are now ready for our conclusion. Now we did write a conclusion on the previous page, but I'm going to add one more sentence to the front end of it. And it's all about the holy grail, okay, the p-value, and knowing what that p-value actually means. Okay, so here we go. The interpretation of the p-value. Assuming the null is true, right? Anytime we do a significance test, we start by assuming the null hypothesis is true. And in this case, that means that the company's claim is true. So assuming the null is true, there is a 0.179. There's the p-value, which we know is a probability of getting. Now I'm just going to go back to my picture here, and I'm going to put it in words. The probability of getting this value for chi-squared or greater, right? Of getting a chi-squared value of 3.44 or greater purely by chance, right? When taking a sample of 50 Reese's Pieces. Okay, now that's a pretty high p-value, pretty good probability that can happen purely by chance, and that helps us with the second sentence in our conclusion, which we've already written. I'm just going to carry that over and say because the p-value, which is 0.179, is greater than the alpha level 0.05, we fail to reject H null, and we do not have convincing evidence. I'm going to give you a little bit of a trick here. When you're trying to write the end of your conclusion, if you actually go back to the wording of the question, we're looking for convincing evidence that the company was lying about the distribution of colors of Reese's Pieces. That's all I need down here. So convincing evidence that the company was lying about the distribution of color for Reese's Pieces. Okay, and that's it. That's the end of our 4-step process for significance test, chi-squared goodness of fit test. Now I do have one last question here. What parts of the usual 4-step process are missing? There's a few things to know that are different in this significance test than the ones that you've done previous in the course. Just make note of these. There's no defining the parameter if you use that first version of the null hypothesis, right? If you're writing this out in words, you don't have to define parameters. And then the other thing is that there's not what I call a general formula for the test statistic. We just have a specific formula, whereas the other significance tests all sort of follow the same general format of statistic minus parameter all divided by standard deviation. Okay, let's see if we can wrap things up here. So this is the important part, the important idea. This is where I go back to the learning target and make sure that we hit all 3 of our learning targets. So learning target number 1 was that we were able to calculate expected count for chi-squared goodness of fit test, and we did arrive at a formula for expected count, and that is n times p. Let's record that. The second learning target was that we needed to be able to check the conditions for this goodness of fit test. So we had 3 conditions here. Let's record all 3 of them. Random random, which is to check to make sure that we have a random sample so that we can generalize to the whole population. When sampling without replacement, we need to check the 10% condition. So that's that the sample size is less than or equal to 10% of the population, and the large counts condition, which for this test means that all the expected counts are greater than 5. Okay, finally, learning target number 3. This is where we got to the 4-step process for writing up the significance test, and then just a couple of things I want to highlight here in important ideas. First of all, the null hypothesis in general is going to say something like the claimed distribution of something. Now we had color, but it's just whatever categorical variable that you're measuring is correct, and the alternative hypothesis is going to say that the claimed distribution is incorrect or is different. That's in general what our hypotheses are going to look like. Just to draw a quick picture here to remind us that the chi-square distribution is different than these other two distributions we've dealt with in the course. Should be skewed to the right, starts at 0, this chi-squared. You need to know your degrees of freedom, which we've decided is the number of categories minus 1. I'm also going to record here, even though we've written this a couple of times, the formula that we need for the chi-squared statistic is observed minus expected squared, all divided by the expected. And of course, we would use this picture here to find the holy grail, the p-value, which allows us to make a conclusion to the significance. Okay, so I do have a homework assignment for you. It is one problem. It is very quick. I'm going to be with you again tomorrow, so I will actually check in on this problem tomorrow. It'll be what we start with tomorrow. It's a modified version of an old AP exam question. You can also find this to download on the website statsmedic.com/YouTube. So go ahead and give that a try before we have class tomorrow. And let's see. Okay, there's that homework problem, so you can download that. We are approaching the end of our time here, and I certainly appreciate that you have tuned in with me today to learn about this chi-squared goodness of fit. And I hope that you're going to tune in every day from here on out. I will be with you tomorrow to discuss the chi-squared test for homogeneity, and then Brandon will wrap up the chi-squared stuff on Monday with the chi-squared test of independence. Now, before you go, I have some really important information to give you about the AP exam. Okay, the College Board realizes that this is going to be an at-home exam, and you have to have access to a device with the internet in order to be able to take your AP exam. And they realize that there are some students that do not have access to that. And of course, it may not be you, but it could be one of your classmates. And listen, I want to make sure that every kid has access to taking this AP exam, regardless of whether they have internet or they have computers or a phone. So listen, if you know somebody who does not have access to a device or to the internet, can you send them this link? And there's a form that they can fill out, or you can fill it out for them, and we'll make sure that they have something, because we really want this to be equitable, and we need every kid to be able to access this AP exam in crazy times here. So please share that with anybody that you think might need. So once again, thank you all for tuning in, and I hope to see you tomorrow at 2 o'clock. Make sure you have your homework done, and we will see you then. Oh, AP Stats students, and welcome to day 3 of our virtual instruction for AP Statistics. I hope you got a chance to log in the last couple of days. Got a chance to meet my colleague, Mr. Brendan Murphy. Him and myself will be taking you through some AP Statistics content and review over the next 5 weeks. My name is Luke Wilcox, and I'm an AP Statistics teacher in Kentwood, Michigan. And if you logged in yesterday, you know that I'm working real hard here to try and become YouTube famous, and that's so that my 8-year-old son will think that I'm a cool dad. So I did have a teacher reach out to me yesterday through Twitter, from home, or a combination of both, which I'm calling hybrid. A researcher wonders if the responses would differ for high school and college students. A simple random sample of 40 high school students and a separate random sample of 60 college students gives the following survey results. And so we have the results of the survey. And I think we should pause right here and just take a quick look at the numbers and see if anything jumps out at us. And I wondered about this too, because I felt like maybe college students were more used to online learning, or I wasn't sure. But by looking at the results of the survey, I see that when we look at the students that preferred school, it definitely seems like the high school student preferred learning at school more than the college student, right? And so I do have, I would say, some evidence that the distribution of learning preference is going to be different between these two types of students, high school students and college students. We have some evidence. The question is whether that could have happened purely by chance, because these were just a couple of random samples. And of course, this is why we need a significance step to be able to answer that question. So we got a couple of warm-up questions here to just get us sort of involved with the data. The first thing it says is how many samples are there and what populations are they from? Well, very clearly, if you look at the way that this is set up, there are 2 separate independent random samples. So to answer that question, we definitely have 2 samples. Now, to think about the population, well, the first sample here of 40 high school students is a random sample of all high school students. So I would say that the first population here is all high school students. And then of course, the second sample is a random sample of college students. So the second population here, I'm going to say, is all college students. So I do want to just note here that we have 2 different samples from 2 different populations. Whereas yesterday in chi-square goodness of fit, we only had 1 sample of Reese's Pieces from the population of Reese's Pieces. So that is one difference between the test from yesterday and the test for today. Now, question number 2 is asking about variables. How many variables are we measuring? Well, very clearly, if you look up at the data here, we are measuring the learning preference for each student. So that's certainly a variable. Now, some people might argue that type of students is a variable, but the reality is that type of student is the way that we're differentiating our 2 populations here. And we took separate random samples from each one of those populations. So when we went to our random sample of 40 high school students, we didn't have to ask them whether they were high school or college and record that as a variable. We knew that up front because we took a random sample of high school. So this right here is in fact our only variable. And I do want to point out that it is a categorical variable with 3 possible categories of school, home, and hybrid. So I'm going to say that there is 1 categorical variable here. So we now have the biggest distinction between what we talked about yesterday and the chi-square goodness of fit. What we're going to talk about today, which is the chi-square test of homogeneity. And I'm going to just make note of this right now. For chi-square test of homogeneity, which is what we're dealing with here, you have 2 populations. And the reality is we actually could have 2 or more populations. If I wanted to take another random sample of, say, graduate level college students, I could do that. And we're going to be measuring 1 categorical variable. Whereas yesterday we had 1 population, 1 variable. Okay, now we are ready to write some hypotheses for this here. Right? And remember that null hypothesis generally says something like there is no difference. And in this case, we want to say that like the high school students are the same as the college student in terms of their learning preference. So the null hypothesis is going to say that the distribution of learning preference is the same for high school and the college student. And I do want to point out here a connection that, when we talk about things being the same, that's where the term homogeneous comes in. Homogeneous means the same. So you can see why this is called a chi-square test of homogeneity. Now, the alternative hypothesis is going to say that something is different, right? We don't know whether it's the students that prefer school or home or hybrid, but some of those proportions are going to be different between the 2 populations. So we're going to say the distribution of learning preference is different between high school and college student. And in terms of homogeneity here, we are now saying that the 2 groups are not the same, not homogeneous. Okay, so let's move on to question number 4 here. And it says, now we will use a chi-square test to determine if there is convincing evidence of a difference in the distribution of learning preference between high school and college students. To complete the table of expected count. Okay, first just want to point out these values that we have in the table up here are the observed counts. And what we're looking for down here are the expected counts. And remember, the expected counts have to be calculated assuming the null hypothesis is true, which says that the distribution of learning preference is the same for high school and college students. That's going to help us figure out the values for these expected counts. So I'm going to start out with this expected value right here. Just that one number, which would be the high school students who say that they prefer learning at school. And I want to talk about what we would do to find the expected value for that particular cell in the 2-way table. So we are looking for the expected value for the high school student who says that they prefer learning at school. Okay, let's think about how we can calculate this expected value. If we assume the null hypothesis is true, then the distribution of learning preference is the same for this group as it is for this group. Well, I know based on the totals what that distribution should look like. It should be 30%, 20%, 50%, right? Because that's out of 100. So that's very easy. 20% should be those that prefer school, 30% should prefer home, and 50% that prefer hybrid for both groups of students, right? So in this first position here, we know 30% of those high school students would prefer school. So the calculation would be 30%, or I'm going to write that as 30 out of 100. 30% of all the high school students sampled. Well, we sampled 40 high school students, and 30% of those 40 high school students would tell me that we expect that 12 of them would say that they prefer school. So let's go ahead and write that in as our first expected value. Now let's go through a similar reasoning in order to get the expected value below that one. So now I'm looking for the expected number of high school students who say that they prefer learning at home. Well, if we look at prefer learning at home, it's 20% of the total, right? 20 out of 100. And so now I want 20% of my sample of 40 high school students. So I do 20% of 40, and I'm going to get a value of 8. So we have 8 expected high school students who say they prefer home. Now I'm hoping now that we can actually generalize to a formula here for calculating the expected counts. So let's put this formula down here. If you're trying to get expected counts, when you have a table like this, which we call a two-way table, but look at the calculations that we did above. 30 out of 100 times 40. Well, let's look at the 30. What is that? The 30 is the row total, right? And the 40, that's actually the column total. And then the 100, that's what I call the grand total for the whole table. So it turns out that the formula for this is you take the row total for whatever row you're in, you multiply it by the column total for whatever column you're in, and then you take that whole thing and you divide it by what I call the grand total. Some people call that the table total. I call it the grand total. So we can actually use that formula for expected counts in order to find all the rest of the expected counts. I could go and find this one and this one and this one, right? But there's a little bit of a shortcut here that I'm going to show you now. And the shortcut is this. Well, we've calculated 2 of the expected values already. The rest of them are going to be really, really easy from here. And here's the reason why. If I just look at the first row, which would be the row of those that prefer school, I know there has to be 30 total. And I know 12 of them come from the high school. Doesn't that mean that the other 18 have to come here to 30 subtract 12? And can I do that same thing in the next row? I know I have to have 20 total. And I already got 8 from high school. So that's telling me this expected count should be 12. Now we're left with 2 more here. And here's the trick on this one. Now I'm going to look at this column and realize that I have my 12 and my 8, but it has to add up to 40. So that means this value is going to have to be 1, right? So what we're realizing here is if we have all of the values in a row but 1, or all of the values in the column but 1, we can get that last one by just doing some subtraction. So this last one is going to be easy here. I know that one's going to have to be 30 in order to give me a total of 50 here and a total of 50 here. So something really important to point out here. The fact that we really only had to do 2 calculations here for expected counts, these 2. And all the rest of them, I would say essentially we got for free. So this is actually going to inform us about what's called the degrees of freedom for this significant time. And in this case, the degrees of freedom is 2 because we had to actually calculate those first 2 values. But once we knew the first 2, those had freedom to vary. But once we knew those first 2, all the other values were done for us, right? We could just fill those in. And it turns out that the formula that you use in order to get this degrees of freedom is you take the number of rows minus 1, right? Because if you have all the values in the row but 1, you can figure out that last one and you multiply it by the number of columns minus 1, right? So in this case, if we were to use this formula, the number of rows in this case, we have 3 rows, right? 1, 2, 3. Don't use your total there. The total does not count as a row. So we have 3 rows. And the columns, we got 1, 2 columns there. Don't use the totals column. And so 2 minus 1. And sure enough, you're going to end up with degrees of freedom 2. So I do want to just make a quick note here. Don't use the total row or total column, right? When you're counting the number of rows and the number of columns, you don't want to include the total. Okay, so we now have all of our expected values. And it turns out that the significance test that we're about to do, the chi-squared test, is going to look very, very similar to what we did yesterday with the chi-squared goodness of fit. Same formula, very similar calculations, find the p-value the same way. But I want to make sure that we know how to write that out in the full 4-step process here. So this is the same process that I used yesterday. I'll call it state, plan, do, and conclude. So let's jump right in. All right, starting with the state, we want to write our hypotheses here. So we've already talked about the hypotheses here. We know that the null hypothesis says that the distribution of learning preference is the same, right? Homogeneous for high school and college students. That's the statement that we have homogeneous population. And the alternative is going to say that the distribution of learning preference is somehow different. And we don't know exactly which category it's going to be in, but we think that they're going to be different for high school students than it is for college students. Okay, so significance level. We actually weren't given a significance level here, and by default, we will go with the alpha level of 0.05 for our significance level. In terms of the name of the procedure, this is a chi-squared test of homogeneity. And we are now ready to check our conditions, and I hope these conditions look very similar to what we talked about in yesterday's lesson. We have 3 of them: the random condition, the 10% condition, and the large counts condition. So let me remind you of what each one of those says from yesterday. For the random condition, we need to make sure that we have random samples, actually 2 random samples that are independent here. So we're going to say that we have independent random samples of 40 high school and 60 college students. And remember, the reason why the random sample is important is because we want that sample to be representative of the population, because at the end, we'd like to make some sort of conclusion and generalize it to the population. In this case, we can generalize to the population of all high school students and all college students. Okay, 10% condition, remember, we only have to check that if we're sampling without replacement. And in this case, we were sampling without replacement. We didn't take one student out and then replace them back into the pool. And so we do have to check the 10% condition, and we have to check it twice, one for each sample. So for the high school students that we sampled, 40 has to be less than 10% the population of all high school students. Definitely a reasonable assumption because of the huge number of high school students in the country. And then for the college students, we sampled 60 of them, and we want that to be less than 10% of all college students. And I think both of these are very reasonable to assume. All right, now our large counts condition. This is where we check that all of our expected counts are greater than 5, but we need to make sure that we prove that we calculated those. And we did that on the previous page, but I'm actually going to just record each one of the expected counts. We had 12, 8, 20, 18, 12, and 30, and sure enough, all of those are greater than 5. All those are greater than 5. Now, one quick note here, another way that you could justify the large counts condition, instead of having to list out every one of the expected values, you could just look for the smallest expected value. And in this case, the lowest expected value is 12. And if the lowest value is greater than 5, well, then of course all of them are greater than 5. Just make sure you have those expected values somewhere on your paper. We've already done all the calculations of the expected value. Okay, we are ready to do some work here, right? So this is where we're going to get into our calculation. We know our specific formula at this point. It's the same formula that we used yesterday for the chi-squared test statistic, O minus E squared all over E, and make sure you are summing all of those. Now we're going to have to do that for all 6 of our observed counts and expected values there. So this is going to be a little bit of a calculation, and I've got the numbers in front of me here. So I'm just taking numbers from back here. Of course, these ones are all of our observed values, and these ones down here are all of our expected values. So I'm going to start out on the top left, which is the high school students who chose school as their preference. The observed value was 18, the expected value was 12, all divided by 12. Then I'm going to move down the column there. So in my next cell, I have 6 minus 8 squared over 8, and then I have 16 minus 20 squared over 20. And then now moving over to the next column, this is the college students now. And let's see, I've got 12 minus 18 squared over 18, and then I've got 14 minus 12 squared over 12, and then I've got 34 minus 30 squared over 30. So there are going to be 6 different parts to this chi-squared. We call these the 6 components for chi-squared, right? And I went through on the calculator and I found all these values here. So let me show you what values I got for this. I got, let's see, my first value was 3, and then I got 0.5, and then I got 0.8, and then I got 2, and then I got 0.333, and then finally I got 0.533. And then I added all of those up. This is going to give us our chi-squared test statistic, which is about 7.17. So a little bit of work to do there, a little bit of calculation. Just give myself a little bit of room here. And let's go ahead and record that for our chi-squared test statistic, 7.17. Okay, now that we have our test statistic, we should be able to calculate our p-value. So let's go back to the picture up here. And we talked about the chi-squared distribution yesterday. This particular chi-squared distribution has 2 degrees of freedom, so it's actually going to look like this. This is a chi-squared distribution with degrees of freedom equal to 2. Remember, the chi-squared distribution starts at 0. You can't have a negative chi-squared value, and it is skewed to the right. And we got a chi-squared value of 7.17. I don't know exactly where that is, but let's suppose that chi-squared test statistic is somewhere right there. And we want to calculate to the right, always shading to the right, because those would be values more extreme. And this right here, the area of that is what we call the holy grail people, the p-value, right? Now, I showed you 2 different ways yesterday on how to calculate the p-value. I'm going to remind you of that real quickly. The first way is to use table C. And table C is something that's provided on the AP exam along with your formula. And the thing that you need to know in order to use this is the degrees of freedom. And we know that the degrees of freedom for this particular problem is 2. We have done that calculation. And what you're looking for now in the table is you're looking for your chi-squared test statistic, which for us was 7.17. So what you're going to do is you're going to go across the row for degrees of freedom 2 until you find your chi-squared value. Now I'm looking for 7.17, and I don't see it. it, but I do see 5.99 and I do see 7.38, and my chi-squared value would be somewhere between those two. And so if you look above those, where it says tail probability, this is exactly what we're looking for, the tail probability. And what we know now is that the tail probability has to be between 0.025 and 0.05. So let's go back to the activity and let's record our p-value as between 0.025 and 0.05. Now that'll be enough for us to actually write out our conclusion. I did show you yesterday how to do this on the calculator, so let me remind you of what we need to do on the calculator for this one in order to get the p-value. So if you grab your calculator, or you can just follow along with what I'm going to show you here. But we want to find the area underneath the chi-squared distribution. And from yesterday, you should know that that's second vars, and the command that we want is chi-squared CDF, and the lower bound should be our chi-squared test statistic 7.17, and you want to go out to infinity 99999 degrees of freedom 2, and I'll paste that onto the main screen there. And sure enough, we knew from table C that the p-value was going to be between 0.025 and 0.05, and we see sure enough it is. It's 0.028, I suppose, if we round it. So let's go ahead and jump back to the activity and let's put in this specific p-value that we just calculated, because I like that a lot better than the p-value that we get from table C. So I'm going to write in here that my actual p-value that we calculated from technology is equal to 0.028, and then I do try to get my students in the habit of putting a box around the p-value and putting a box around the test statistic. Those are two very important calculations that we need. And I think we are now ready to write a conclusion for our significance test based on that p-value. So much like yesterday, I'm going to start with a sentence where I will interpret the holy grail, the p-value, and then we'll go ahead and actually make our conclusion. Okay, so to interpret the p-value, we have to start by acknowledging that we are starting with the null hypothesis. So assuming H null is true, and we defined the null hypothesis up here, so I don't have to write it again. There is a, and then we need our p-value here, which is 0.028, and of course that's the probability of getting chi-squared value. If you look back at our picture, we got a chi-squared value up here of 7.17, so a chi-squared of 7.17 or greater purely by chance. Now this probability is very low. It's very unlikely that this would happen purely by chance, assuming the null hypothesis is true. So that's going to allow us to make our conclusion here. So we're going to say because our p-value of 0.028 is less than our alpha level of 0.05, we are going to reject the null hypothesis. And we do have convincing evidence for the alternative, but we want to put the alternative in the context of the problem. So I'm actually just going to go back up here to remind myself of what the alternative hypothesis is saying, and essentially I'm just going to copy that alternative hypothesis down at the end of my conclusion. We have convincing evidence that the distribution of learning preference is different for high school and college students. Okay, now we do have something that's statistically significant here, and I commented on this yesterday, that when you are doing a chi-squared test and you get a result that's statistically significant and you reject the null hypothesis, it's good to think about why that happened, right? So you can go back to your calculation to try and figure out, like, why is it that we got such a big value for chi-squared here, which led us to such a small p-value? And the best way to do that is to look at this part of the calculation right here, which is where we have each one of the components that contributed to the chi-squared statistic, and you look for the biggest one. And so the biggest one here, I think, is our very first one right here, right? Is 3. And let's look back at that calculation. What that was the high school students who said that they preferred learning at school. And it appears that the observed value was much higher than what the expected value was, and that's why we ended up with this pretty large component here. So this is what we call the follow-up analysis. And I would say as part of the follow-up analysis here, I'm just going to tack this on to the end of the conclusion. I would say the observed number of high school students who preferred learning at school was much higher than expected. And I'll tell you that just warms my heart a little bit that high school students want to be at school, because I do too. So it makes sense to me that that would be the result. All right, we've got one last question here before we can summarize our learning. How is this test different than a chi-squared goodness of fit test? And this has to do with how many populations there are and how many variables. So let's just make note that this test, right, the chi-squared test of homogeneity, is for 2 or more populations, and you're going to be measuring one categorical variable, whereas this goodness of fit test, which is what we did yesterday, has one population and one variable. Okay, so let's see if we can summarize everything that we learned in that activity in the important idea. So we flip to the next page here, and this is where I'm going to tie it all back to the learning card. We had 3 learning cards. Learning target number 1 had to do with the hypotheses, and I'm going to give you just sort of a general template that you can use when writing hypotheses for a chi-squared test of homogeneity. In general, it's going to say something like the distribution of, and then you're going to have to fill in the blank here. And what you're going to fill in the blank with is whatever is the categorical variable that you're measuring. For us, it was learning preference. And we're going to say in the null hypothesis that distribution is the same, right, homogeneous for, and then you're going to have 2 different populations here, or maybe more than 2 populations. So you're going to fill in the blanks here with population 1 and population 2. Okay, and then your alternative is essentially going to say the opposite here. The distribution of whatever your categorical variable is different for population 1 and population 2. You just have to fill in the blank. Okay, learning target number 2 had to do with calculating expected counts and also being able to identify the degrees of freedom. And so we just have a couple of formulas here that we uncovered in the activity. First of all, the expected counts. Anytime you have data in a 2-way table like this and you're doing a chi-squared test, you're going to use row total times the column total, and then you're going to divide by what I call the grand total or the table total. And then the other formula that we uncovered was the formula for degrees of freedom when you have a 2-way table, just the number of rows minus 1 times the number of columns minus 1. And then the last learning target really was the 4-step significance test. And all I'm going to mention here in the important idea is the big difference between the chi-squared goodness of fit test and the chi-squared test for homogeneity. And chi-squared goodness of fit, which we did yesterday with the Reese's Pieces, we had 1 population, which was the Reese's Pieces, and we measured 1 variable, which was the color of those Reese's Pieces. Whereas today, chi-squared test of homogeneity, 2 populations, actually 2 or more populations, and 1 variable. Now, the last thing that I'd like to show you here is how you can do this whole significance test on your calculator. So if you want to grab your calculator, let's just see what this chi-squared test of homogeneity looks like on the calculator. So we still have our calculation over the p-value, but listen, the calculator will do all of this mess for you, okay? Including getting some expected values is a really nice trick. So if you go to stats and then you go over to tests and you scroll all the way down, you're going to find eventually a chi-squared test. And you may have 2 of them. You may have a goodness of fit. Some calculators have it, some don't. But all of the calculators have this, the chi-squared test. Now, if you hit enter on that, what you're going to notice here is that the calculator wants you to do something in a matrix, matrix A and matrix B. So we have to go here to second matrix, right? This button and then this button. And we're going to have to go over and edit. And you may not have any values in here, but you want to create a matrix A and you want the dimensions to be 3 by 2. And this is just going to be the observed value, right, from the activity. And so I already have those numbers copied in here. These are the observed values. So you go ahead and type those in. Then you can go back and actually perform your chi-squared test. So I'm going to go back to test. I'm going to find the chi-squared test, and I've put the observed values in matrix A. Now you'll notice I didn't put anything in matrix B. You do not have to calculate your expected values. You only have to put in your observed values, and then you hit calculate. And sure enough, you get the chi-squared test statistic, which matches with what we got by hand, and the p-value, along with the degrees of freedom. And here's the really, really cool part about it. If you go back to those matrices and you go to edit matrix B, you will notice that these are all of your expected count. And the calculator has actually figured that all out for you. And we did all that work to find these values. Turns out the calculator can do those for you. So it's a good way to check your work. So hopefully you're able to use your calculator to check the work that you did in your on your significance there. So listen, that brings us to the end of today. Now there is a homework assignment. There's one problem. It's an old AP exam from 2016 that I'd like you to take a look at before Monday. On Monday, Brendan Murphy is going to be back with you, and he's going to talk about the chi-squared test for independence. And I'll be back with you again on Tuesday. So I'm grateful for you tuning in today. And listen, I hope you enjoyed it. I hope you're helping me to become YouTube famous. If you like this video, click the thumbs up. And if you thought it was good, I'd appreciate that. And I hope to see you again next Tuesday or next Monday with Mr. Murphy.
So welcome back, AP Stats kids. It's Monday. Again, my name's Mr. Murphy. Hopefully you either sat in with me last week or Luke. Luke and I are really good friends. And our goal is last week and this week to teach perhaps some new content that maybe your teacher just never got to because of some of the school closures. This is what we call chi-square. So I'm going to finish up chi-square today. And then later in the week, Tuesday, Wednesday, Thursday, and Friday, Luke and I are going to do what we call inference for regression. That may feel familiar to you guys. It's going to perhaps feel like the least square regression line that we did earlier in the year, y hat equals a plus bx or something like that. So and then starting next Monday, the 6th, is nothing but review for this year's modified AP exam. Again, 2020 AP Stats exam is going to be modified. It's going to be 45 minutes long and just free response questions. So what we chi-square and what we're doing later this week, inference for regression, just to reiterate it one more time, neither of those two statistical concept topics will be on this year's AP Stats exam. That's okay. Don't stress over it. We just wanted to make sure that you guys have the full AP Stats experience this year. And when you go off to college, we sincerely hope that you study more statistics, and hopefully you'll see chi-square again. So thanks for coming in and sitting in today. We hope you're safe and sound at home and healthy, and let's focus on that and taking care of each other and our families, and the AP Stats exam will take care of itself. So I'm just going to shift over to my PowerPoint presentation. So I think this is going to be the first slide you guys see every single day from Luke and I. It's got kind of a cool normal curve, right? It looks like there's some sort of a histogram or something superimposed under that. So anyway, welcome back to day 4. Again, my name is Brendan Murphy. I teach at John Baptist Memorial High School in Bangor, Maine. So we're still in winter up here, although the days are getting nicer and the days are getting longer. So that's good. Luke Wilcox, he's our the other presenter. Luke and I are really good friends. He teaches at East Kentward High School in Michigan. And if you see the website there, www.statsmatic.com YouTube, that's where we're posting the homework problems every day. So if you miss a day for whatever reason, or taking AP Calc, I guess AP Calc is the same time slot as this, you can go there and see the homework as well. So this was the homework problem that Luke had assigned. And it's actually a modified problem from the 2016 AP Stats exam. It was free response number 2. When I say modified, it's the stem of the problem is exactly the same up here, but Luke did modify the sort of questions just to make it a little bit faster and a little bit easier for you guys to read. And so I'm just going to give it a second here for my document camera to zoom in a little bit. Maybe I'll give you 20 seconds or 30 seconds to read through the problem again. This is a heavier read here. There's no doubt about it. It's a little bit longer of a problem. So let me give you 20 or 30 seconds to see if you can just read it again if you're brand new and didn't get a chance to look at the homework problem. This is what we assigned. So when I'm helping my kids get ready for the AP Stats exam, I like to say for every free response, if you have to spend a couple, 2, 3, 4, 5 minutes just reading through the problem, that's perfectly fine. It feels like when we grade these exams, both Luke and I are AP Stats graders, that sometimes kids sort of dive into the problem maybe too quickly, and they perhaps don't even really understand what the problem's asking. So if you have to read it 2 or 3 times, that's perfectly fine. That's okay. The mathematics or the writing actually shouldn't take that long. So I'm just going to read it real quick. Product advertises study the effects of television ads on children's choices for 2 new snacks. So first sentence is there some relationship perhaps between television ads and what children choose for a snack? The advertisers use 2 30-second television ads in an experiment. So right now I'm thinking maybe it's experimental design, but I want to just keep reading and get an overall feel for the problem. One ad was for a new sugary snack called Cocoa Zooties, and the other ad was a new healthy snack called Apple Zooties. So I guess we have 2 different snacks that the children could choose from, and then they watch some TV ad, and I still don't know exactly what they want me to do yet, so I'm just going to keep reading. For the experiment, 75 children were randomly assigned to one of 3 groups, A, B, and C. So if I jump down to my table here, I can see the 3 groups. I haven't added either across or down, and I'm a lefty here. I apologize for that. At times you're going to see my hand and you won't see what I'm doing, but I just added across, and if I add down, I get 19, 34, 56. And so I like to call this number over here my total. Some books call it table total. That's a Mr. Murphyism. So there's my 75. It looks like they were evenly split up between my 3 groups, A, B, and C. Each child individually watched a 30-minute television program that was interrupted for 5 minutes of advertising. So we all complain about too many commercials, right? The advertising was the same for each group with the following exceptions. The advertising for group A included the Cocoa Zooties ad, but not the Apple Zooties ad. So for those 25 children who were in group A, the only commercial it looks like they saw was Cocoa Zooties. The advertising for group B included the Apple Zooties, but not the Cocoa Zooties. These are hard to read, aren't they? So B, it's the exact opposite. All these 25 kids saw ads just on Cocoa Zooties. The advertising for group C included neither Cocoa Zooties or Apple Zooties ads. So these 25 down here didn't see either one of those commercials. Looking at the numbers quickly, again, this isn't a statistical analysis, but it does appear that the children seem to like the Cocoa Zooties more than the Apple Zooties, regardless of which commercials they saw. But that's just my gut feeling, and I really need to do a statistical analysis before I can make any real decision here. So after the program, the children were offered a choice between the 2 snacks. The table below summarizes their choices. So A and B here, again, were not exactly what was on the AP Stats exam, but we've modified that. So make the hypothesis. So my null hypothesis is going to be something like the proportion of students who chose each snack is the same no matter which ad they watched. So I guess it doesn't matter which ad they watched. So let me just step back a little bit. It's clearly chi-squared, and so we have the 3 chi-square testing. I'm going to hit this again on one of my PowerPoint slides, but chi-squared goodness of fit, that feels like I have some predetermined model and I'm comparing my data to that. But this doesn't feel like it's chi-squared goodness of fit. So the next decision we need to make is this chi-squared test for homogeneity. Luke did that on Friday. I'm going to do chi-squared test for independence today. And so you need to make the decision, which one of these chi-squared tests is it? If you're struggling, and sometimes it's hard to figure that out, you can always just write chi-squared test. The nice thing is the assumptions, the formula, the mathematics, the mechanics is all the same. And so chi-squared test for homogeneity, it feels like we have 2 populations. I'm comparing one variable, and I want to see is there any difference between that. So this does feel like chi-squared test for homogeneity to me. My alternate is in many ways the exact same statement, except I add the word not the same. So the proportion of students who chose each snack is not the same, no matter which ad they watched. So we basically just add the word not the same. For the sake of time in my lefty writing here, I won't rewrite the alternative, but it's basically the same thing as I wrote in my null. And now we think they're the same in the alternative. We think proportions are not the same. And that's really what this test is designed to do. So the 3 conditions, again, I think I mentioned on Wednesday, the chi-squares we call a non-parametric test. They're actually pretty easy. I like to think of random, and I like to think of my expected values, and then what we call our 10% condition. That's it. Much easier sort of conditions, things that we need to worry about when we're doing chi-square testing as opposed to means or proportions. So random, I believe it did say up here that the students were selected randomly. Again, for the sake of time, I won't write it, but on your AP exam, you would say, students were selected randomly, blah, 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 stated in the stem above. The expected value, we can go to our calculator and get those numbers. I'll show you that when I walk through an independent problem, but those are all greater than 5. And somewhere on your exam, many times kids actually just write those expected values right next to the observed somewhere. They're all greater than 5. And so we can just say, all expected values are greater than 5. And that's a good thing. If we have a really small expected value, we can artificially drive my chi-squared statistic higher, perhaps leading me to reject the null hypothesis when we perhaps shouldn't have. 10% condition, we want our population to be greater than 10 times our sample size. Other books, other teachers may say the opposite, but it's really the same thing. And so is our population greater than 10 times 75? Is our population greater than 750? And I'm going to call that an assumption. This feels like the random. I can check that. I can read the problem again. Expected values, I can mathematically check or confirm that. This here is an assumption. I really don't know how big the population is, but we're talking about children, and let's talk about the children in Bangor, Maine or something. And clearly most populations of children will have more than 750 students. So I think we're good there. I think we've met the conditions. So again, that was the homework for the other night. Hopefully you had a chance to do that. If not, don't worry about it. And back to my PowerPoint here. And this again was just the homework problem. So let's just keep moving forward. And so what do you really need to know when you're doing a chi-square test? Chi-square is just hypothesis test. There's no confidence intervals. So sometimes my students will say, boy, Mr. Murphy, it feels like this is easier than either hypothesis testing with means or proportions because there's just hypothesis tests. Now again, we have those three tests, right? Chi-squared goodness of fit, chi-squared test for homogeneity, chi-squared test for independence. This is the only formula we're ever going to use with chi-squared. Chi-squared is the sum of the observed minus the expected squared, so the numerator is always going to be positive divided by expected. This formula is given to you on the AP Stats exam, so no worries about it. And we talked about chi-squared being a non-parametric test. So again, here are our three tests. Chi-squared test for goodness of fit. We compare our data to I call it a predetermined model. Many times these models have percentages, and we need to remember to convert these percentages to counts. I think M&Ms or Smarties or something like that. I think Luke may have done that the other day. M&Ms does publish the percentage of different colors you can get when you buy a bag of M&Ms. Chi-squared test for homogeneity, again, Luke did that on Friday. We're comparing two different populations, one variable. That's what happened in the Zooties problem. Chi-squared test for independence, which I'll get into today. We have one population and we want to compare two or more variables. So that's, I guess, perhaps a harder decision sometimes for my students. Is it a chi-squared test for homogeneity, Mr. Murphy, or is it a chi-squared test for independence? We need to calculate degrees of freedom, so we'll talk about that. We need to check conditions. I guess we just did that again. There's just those three conditions. Data was randomly selected from the population. That's pretty much going to be in the stem of the problem, or where we may not even be able to run our test. All expected values are at least 5. We'll mathematically check that later today. And then our 10% condition, our population is at least 10 times our sample size. So the conditions are easier. There's less things we have to check. So chi-squared table, once again, you'll have this on your AP Stats exam. Calculators can perform all of these tests and get all of the mathematics for it. I do teach my children, my students, how to read a chi-squared table. Some teachers do, some don't. I'll leave that up to your teachers. You can see over here on the left-hand side, we do have degrees of freedom, and then we have upper tail probability here. So let's walk through some problems here. Again, chi-squared test for independence. The data comes from a single random sample from our population. So we have one population. We have two or more categorical variables that we're interested in seeing if they are related. The single word related, sometimes associated, independent, all of those three words in many ways can mean the same thing. And those are perhaps clues. Our data is typically shown in a two-way table. Not always in a two-way table doesn't necessarily mean it's chi-squared, but almost always you'll see it. Degrees of freedom, we have the number of rows minus 1 times the number of columns minus 1, or R minus 1 times C minus 1. We calculate expected values. We do that by row total, by column total, divided by the total. So you'll probably hear me later today say total. We can use our calculators to get these expected values. But it could be faster and easier to use the formula above. On a multiple choice question, I think it would just be easier to use this formula here to calculate an expected value for a certain cell. This formula is not given to you on the formula sheet, so that may be something that you just want to keep in the back of your mind. Of course, there's no chi-squared on this year's test anyway, but for future knowledge. So here's a multiple choice problem from the 1997 exam, multiple choice question 14. I give this to my student. I actually give this to my Algebra 1 or Algebra 2 students, and I use it really early in the year in AP Statistics, and it just gets kids thinking about, is there a relationship between these two variables? So I'll give you a minute or so to read through it. I'm not going to do the math here because the math is pretty easy, and we can perhaps answer this question without even doing a chi-squared test. So I'll give you a minute or so to read this problem, and then we'll talk about it. So in this two-way table, they actually gave us what we call marginal totals out here in the margins. If those numbers aren't given to me, I'm probably going to just, as a math teacher, put them in. So sometimes those are given to you, sometimes they're not. So a survey of 57 students was conducted to determine whether or not they held jobs outside of school. Okay, so it looks like I'm comparing your class, what class are you in your high school versus your job status. So I'm comparing two variables. I assume these students all came from one school. And so this feels like chi-squared test for independence. I have one population, one school. I hopefully randomly surveyed 57 students, and I want to see if there's some relationship between your year in high school, like you were junior or senior, and or your job status. Two-way table above shows the number of students by employment status, job, no job, in class, junior or seniors. Which of the following best describes the relationship between employment status and class? I guess I'm not seeing the word random here. That I read it again. This was 1997, which was a long time ago. It was our first year running AP Stats. I think today you probably see the word random in there, but let's assume it was random. So without doing a whole lot of math, it looks like 13 out of 18 juniors have a job. Well, that feels like it's almost 70%. 72% of the juniors have a job. It looks like 13 out of 39 seniors have a job. Well, I can do that one in my head. That's pretty easy. That's 1/3, or 33%. So boy, it sort of does feel like the juniors have. Sorry about that. It does feel like the juniors have a much higher percentage of jobs than seniors. So which of the following best describes the relationship between employment status and class? There appears to be no association. That doesn't feel good. There appears to be no association. That doesn't feel good. C, there appears to be an association since there are more seniors than juniors in the survey. I think I like the first half of that. I'm not sure I like the second half of that sentence. There appears to be an association since the proportion of juniors having jobs is much larger than the proportion of seniors having jobs. Yeah, the answer is D here. And again, I like to actually give this problem to my students long before we get to chi-squared, and sometimes long before they even get to AP Stats. Just thinking about working with two-way tables, seeing if there's some relationship between job status and your year in high school. Okay, so here's another multiple choice question. I think I introduced this really quickly on Wednesday when we first met for our first session. So this is the 2012 multiple choice question number 30. Again, we'll walk through this one really quickly. I do want to kind of walk through a free response question for independence and go through all of the different steps and whatnot. But maybe while I'm reading, just think about, does this feel like a chi-squared test? And if so, is it chi-squared test for goodness of fit, chi-squared test for homogeneity, chi-squared test for independence? Let's see if you can figure out which one of the three tests it is. In order to plan for its next advertising campaign, the trendy motor vehicle company is investigating whether the type of vehicle and the color are related. Okay, well, there's a little clue right there. Is there some relationship between the vehicle color and the vehicle type? So I think I know where this is going, but let's just keep reading and see if there are any more clues here. Each person in a random sample of size 275 selected from the company's mailing list was classified according to type, car, truck, and the color of the vehicle he or she drove. The data are in the table below. So does this feel like a chi-squared test for goodness of fit, chi-squared test for homogeneity, or chi-squared test for independence? And again, independence would be one population comparing two or more variables. And so it sort of feels like to me chi-squared test for independence, and the answer is E. And I guess I'm trying to again see, is there some relationship, some association between the color of the vehicle that people selected versus the make of the vehicle, car versus truck? Again, here's another multiple choice. I went through this the other day. I'll read it real quick. This is chi-squared test for goodness of fit. So a geneticist hypothesizes that half of a given population will have brown eyes, and the remaining half will be split evenly between blue and green eyes. So there's that model I keep saying. There's some model that we're going to compare our data to. So the model is saying half the people have brown eyes, 25% will have blue, 25% will have green. And a random sample of 60 people from this population, the individuals distributed in the table above, where's the chi-squared test statistic for the goodness of this fit. So again, we won't run the test here, but this sort of feels like a classic goodness of fit test to me. I have a predetermined model, 50%, 25%, 25%. I've collected some data randomly, and I want to see how well does it fit my model. So that's kind of a classic goodness of the problem. Okay, so we're looking at free response here, and I'm going to walk through all of the four components of what we're typically looking for when we do a free response question. So this was from the 2003 AP Stats exam, and it was free response question number 5. So in a typical year, you would get 6 free responses. It's not a typical year, and right now I'm not sure those decisions have even been finalized 100%. But this Friday, April 3rd, there's going to be more information released about this year's exam. So stay tuned. We do know it's 45 minutes long, and we do know that it's just free response questions. So I'll give you a minute to read it, and at some point I'm going to switch over to my document camera, and I'm going to do the math out. I'm going to show you how to use the calculator and pretty much all those different things. So see if you can, when you're reading through the problem, see if you can figure out to yourself whether this feels like chi-squared goodness of fit, chi-squared test for homogeneity, or chi-squared test for independence. So I just switch over to my document camera, and I'll give you another minute or so if you want to just finish reading that, and then we'll walk through it, and I'll show you all the different steps, including where to find things on your calculator and all that good stuff. Okay, we have a random sample of 200 students. Boy, that's good to know, right? Was selected from a large college in the United States. That's also another clue. Each selected student was asked to give his or her opinion about the following statement. The most important quality of a person who aspires to be president of the United States is knowledge of foreign affairs. So students were asked a quote, I guess, and they were asked their opinion about that. Each response was recorded in one of 5 categories: strongly agree, somewhat disagree, neither, somewhat agree, strongly agree. The gender of each selected students was noted. The data are summarized in the table below. So here's my classic two-way table. And I need to make a decision right now, which chi-square test do I think it's going to be. Let's see what they want me to do. Is there sufficient evidence to indicate that the response is dependent on gender? Provide statistical evidence to support your conclusion. So we're looking for a full-blown inference test here. We're going to need to walk through all the different steps. And so I'm going to do all that with you guys. But does this feel like chi-square test for independence? One population comparing 2 or more different variables. So I think it is. And I gave you a little clue here. I actually wrote out chi-square test for independence. So it feels like I'm comparing the response, what your opinion of was, or whether you agree with that quote or not, versus your gender, male versus female. Now there are some clues here dependent on gender. And so there are times when in the stem of the problem, there's some clues leading us to where we want to go. So the first thing I like to talk to my students about is writing down the name of the test. So this is a chi-square test for independence. The nice thing is if we do that, and in past rubrics, assuming it will happen in the future, is students can either write down the name of the test or the formula, but they don't need both. So the formula for chi-squared isn't too bad, but again, naming the test feels like the first thing that I want to do. It feels pretty logical to me that that's the first thing. And so if you do that, then you do not need to write down the generic formula. I may do it just for the heck of it. I don't see any totals here, so I'm just going to try and do some quick math here. 30, 40, 40, 50, 40. If I add those across 70, 110, so I get 200 there. That's good. If I add across this, I get 25, 40, 65, 90. And if I females, 45, 70, 110. And so everything adds up, and that's a good thing. Would we want our males and females to be close? I think the answer is yes. Again, the data was selected randomly, so what we get. If there were 1 male and 199 females, that might bother me more. But I don't think it's going to 90 and 110 feels okay. And so we want that to be about 50-50. But again, when we randomly select that, we get what we get and we live with it. So the first thing I want to do is my null and alternative. So the null is that the response to the quote and gender are independent. There's no relationship between your response to the quote and your gender. Again, I'm a lefty. I apologize. My handwriting is atrocious. I'm working on it for years, but it doesn't seem to have gotten any better over the years. My alternative, in many ways, I just add the word not. So my response to the quote and gender are not independent. Are not independent of each other. So I guess that's what we're really trying to figure out here. Is there some relationship, association between gender and your response to the quote? And that's why we're going to run the test. And we're going to run some numbers, and we'll talk about a good conclusion on all of those things. So that's sort of my first step. Is I just do my null and alternative hypothesis. Of course, I do want to name the test right up here. That's critical, and that's really the first thing I want to do. My next step is I want to check conditions and assumptions. So what do we have? Just the 3 things, right, for chi-squared. So 200 students were selected randomly, as stated in STEM or problem. Again, it has to be there pretty much in every problem. We really can't even proceed with the problem. So it's always good to rewrite that though. Okay, my expected values all have to be greater than 5. So I'm going to do one out mathematically, and I'm going to switch over to the calculator, and I'll show you how to do that on the calculator. I'm assuming Luke did that as well. So for this cell right here, male and strongly disagree. To get the expected value, I do what? The row total times the column total divided by what I like to call total. Books call it sometimes table total or something like that. Well, the row total, there were 90 males, and column total was 30. So there's my column total, there's my row total, all over 200. So 90 times 30 divided by 200 is 13.5. So I would expect to get 13.5 males who strongly disagree with that quote. Now, this is an expected value, mean or average. So if you're saying to yourself, well, you can't get 13.5, Mr. Murphy, males. Yep, but it's an expected value or average, and so that's okay, and we do not want to round that. Okay, we do not want to round that. So I'm just going to get over to my calculator here, and I'm going to type in that data into my calculator. So let's start from scratch. I want to do second matrix. I'm not sure how much you worked with matrices, probably algebra 2, right? Maybe you've seen some matrices in algebra 2. And I want to fill in matrix A, which is our observed value. So we had 2 rows and 5 columns. So it's 2 by 5 matrix. And you hopefully have the numbers somewhere still. I'm just going to start typing in numbers, and I'm just taking these right off the table. Probably much faster typing than I am. And so hopefully those numbers 10, 15, 15, 25, 25, those numbers line up. So all I've really done is type in the observed values into a matrix. It's pretty interesting. I'm not sure if Luke mentioned it to you, but when we do chi-squared, we actually run our test first to get our expected values. And my students always feel it's sort of backwards, which I sort of agree with actually. But so I'm going to go ahead and run a chi-squared test. So stat, test, and scroll down to chi-squared. All of your calculators will have this, I believe. Some of the newer ones have chi-squared goodness of fit. If yours doesn't, don't worry about it. It's really not all that much more helpful. So if I go to chi-squared test, hit enter, calculator saying, did you, Mr. Murphy, type in your observed values in matrix A? I did. So when I actually run this test, it's going to actually put all of the expected values into matrix B. So I'm just going to run my test here again. I'm looking to see if my expected values are all greater than 5. I'm actually going to get my results before I get my expected values, but we'll come back to that. Okay, so I've run my chi-squared test. I have my chi-squared statistic. But let's go back to the matrices. Second matrix. I'm going to go to matrix B, and here are all my chi-square expected values. And so I calculated one by hand. I don't want to do that just for timing's sake, but it would be the same process. And I'm going to write these on my paper. I'll show you that in just a second. So the nice thing is all of these values are greater than 5. So I'm going to go back to my document camera here. And you see I've written in 13.5, 18, 18, 22.5, 18. I've physically written on my paper all of those expected values. As AP meters, we're looking for that. Students can't just say, down here, all expected values greater than 5. You can't do that. We need to see some of these numbers. We actually want you to go to your calculator and get all those numbers, but you can't just say they're all greater than. We need to see some of them out somewhere. So what's our third condition? That the population wants to be greater than 10 times my sample size. My sample size is 200. 10 times 200 is 2,000. Again, I would probably want a sentence like, it is reasonable to assume the population of students in a large college is greater than 2,000. I don't know that for a fact. There's no way we expect you to know that for a fact, but that's a reasonable assumption, right? So I have my 3 conditions, my randomness, my expected values, and my population, what we call the 10% check. So for our third step, teachers may have called it mechanics or math or something like that. If I've written down the name of the test somewhere, which is the first thing I want to do, I do not need to write the formula down. So I do not need to write the chi-squared formula and plug in a whole bunch of mathematics. I do not need to do that. So I think test taking strategy would not be to do that, and that will hold for means and proportions, which Luke and I are going to review next week. So if you write the name of the test, and that feels like it's the first thing I want to do on every free response question, then you do not need to write out the formula. So I'm going to go back to my calculator, which I've already done, right? When I was working to get those expected values, I run my test. So let's just run it again. Stat, test, chi-square. I observed is in A. The calculator will automatically put those expected values in B. I want want to calculate it. So my chi-squared statistic is 8.92. We don't really care about too many decimals. You want a few more decimals, that's fine. My p-value, my probability is 0.063, so that's important. And my degrees of freedom is 4. Let's go back to our problem here. I've written all those values down on my piece of paper here. So my chi-squared statistic, you need to show that. That's 8.92. My p-value, my probability, sometimes my students will write the probability or the probability value is 0.063. We'll talk about that, but I'm typically comparing that to my assumed significance level alpha 0.05, so that's going to help me make a decision here. My degrees of freedom is 4, and again, that's just rho minus 1 times column minus 1. And so I've done my null and alternative. That's my first step here. I've listed my conditions and checked assumptions. I've listed my basically numbers right from the calculator, and that's really all we're looking for as readers. Okay, all we're looking for. Again, that's only if you've named the test. So I don't need to write the chi-squared formula. I don't need to plug in numbers. I don't need to do a whole lot of math. I can go right to the calculator. I can list those key statistics, those key values. So the last thing I need to do, I guess, step 4 is some conclusion, and that always needs to be in context. And I have somewhat of a generic conclusion here. I don't know if your teachers have something like that, but since our p-value or our probability of 0.063 is greater than our assumed significance level, alpha is 0.05, we fail to reject the null. Now that's generic. I'm going to use that for every single problem, and it's somewhat boilerplate, but it does allow my kids to kind of say, okay, he does it the same way every time. And what we're really looking for is what we call linkage. We want you to link your p-value, but I'm really messing on it. Your p-value 0.063, your probability, is greater than your assumed significance level 0.05. Now 0.05 is not the only significance level. We retest where some students put 0.01, some students put 0.07. What we're really looking for is you making a conclusion based upon your probability and your assumed significance level. If your probability is greater than your alpha level 0.05, you fail to reject. So, but I do not have any context yet. There is not sufficient evidence. The evidence wasn't strong enough here. There's not significant evidence to conclude that the response to the quote are dependent on gender. It doesn't appear that there's a relationship between gender and the response to the quote. So I've listed my p-value. I'll compare that to my alpha level of 0.05. I either reject or fail to reject. We never accept. I don't like that word. That's sort of a bad word in statistics. Then I have a conclusion in context. There's not sufficient evidence to conclude that the response to the quote are dependent on gender. And in some ways, all I've done is restate the question. Is there sufficient evidence to indicate that response is dependent upon gender? And so if you're struggling with context, just go back and read the problem again. Usually sort of embedded right in that problem is context for you. So that's walking through a full free response question and all the different steps. And that's a decent amount of work. So that could take you 5 or 10 minutes to go through. And that's okay. Again, the math many times is faster than fully understanding the problem. So if you have to read through it once or twice, that's perfectly fine. You can write all over your AP exam and make notes to yourself. That's perfectly fine. So here's my 4 steps again. State my null and alternative and identify the parameter. Here I'm just saying it in words, so I don't really need to do that, but we get to means and proportions, we will. We need to list assumptions and check conditions again for chi-squared. It's just those 3 that we talked about: randomness, expected value, and our 10% rule. Mechanics math, again, that's straight from the calculator if you've named the test. And then we always want conclusion and context. That's always do we want contextual analysis of whatever problem. This is pretty much just all the work that I just did for you. Here's another free response question. I'm kind of keeping an eye on the clock here a little bit. Let me see if I can wind down here and then assign homework. Took me a little longer than I thought. Here's another free response question, 2017, so I guess a couple years ago. The table and chart below summarize the age at diagnosis in years for a random sample of 207 men and women currently treated for schizophrenia. The two-way table sort of leads me to think that maybe it's chi-squared. Do the data provide convincing statistical evidence of an association between age group and gender in the diagnosis of schizophrenia? Well, there's another little clue. That feels like it's chi-squared test for independence. Some people call it chi-squared test for association. I'm looking to see is there some relationship between gender and your age as it relates to the diagnosis for schizophrenia. So I won't walk through that for the sake of time. Here's another one, 1992, free response question number 2. I won't read through the whole problem, but it looks like we have two-way table. This is your skill of hiking. Are you a novice hiker or you're experienced? What happens when you get lost? Do you go uphill, downhill, or remain in the same space? So again, it feels like kind of a classic chi-squared test for independence. Again, sort of when we read through the problem, do these data provide convincing evidence of an association? Well, there's a little clue right there. It's not a chi-squared test for homogeneity. Okay, so at this point, hopefully you're feeling more comfortable with the 3 different chi-squared tests: chi-squared test goodness fit, chi-squared test for homogeneity, chi-squared test for independence. We want you to be able to select the correct test and use it contextually. Similar to all of our other inference test procedures, you should be able to write a clear, concise solution in context. And that was sort of my 4th step there, where I compared my p-value, my significance level, and then made a conclusion in context. So here's the homework for tonight. Luke will finish it or start tomorrow with this. The following two-way table resulted from classifying each individual in a random sample of residents of a small city according to level of education, with categories earned at least a high school diploma and did not earn a high school diploma, and employment status: employed full-time, not employed full-time. So it appears that I'm comparing your employment status versus your education level. It feels like it all came from one population, one small city. So it sort of feels like a chi-squared test for independence, but that's really not what we're looking for here. If the null hypothesis of no association between level of education and employment status is true, which of the following expressions give the expected number who earned at least a high school diploma and who are employed full-time? So I guess we're looking, we need to calculate an expected value for this cell and this cell and this cell and this cell. We can type all this data into our calculator. We can run the test and we can get the expected values from our calculator. Or if we remember the formula, row total times column total divided by total, it might be easier to do. And that's really what your answer choices are here. So that's your homework for tonight. Luke will finish that up tomorrow, and he'll get into what we call inference for regression. So I feel like we're pretty well done with chi-squared. We're going to go into what we call inference for regression starting tomorrow through the rest of the week. We do know that not all students will have access to the internet or a device to take their AP exam. We think dates are coming out April 3rd, but stay tuned. The College Board is working on solutions to help get students what they need to do the AP exam and show their best work. So if you need a computer, a mobile device, a tablet or phone or something, or you do not have internet access, you can reach out obviously to your teachers at your school, your administrators, but also the College Board. So you can reach the College Board directly at cb.org/tech. And I'm not sure exactly how, but the College Board will jump through hoops to make sure that you get some sort of a device so that you can take this year's AP Stats exam. Most likely at home. That's the thought right now. Thanks for watching. We'll see you again tomorrow. You'll be with Luke tomorrow. So please work on that practice question, that homework question that will be also uploaded to Luke's website, which I think I had right here, www.statsmatic.com YouTube. So you'll start that out tomorrow. So thanks for again sitting in. I'm going to wind down here. We appreciate your sitting in with us, and we hope everyone's safe at home. We'll see you tomorrow. Luke will start inference regression, and then I'll be back on Wednesday. So thanks. I hope I helped today, and we'll see you tomorrow or Wednesday, whenever. And again, all of these sessions are taped and they're on YouTube. So for some reason, if you missed today, you can always go back and watch it. So have a good afternoon. Be safe. Thanks.
Hello, AP Statistics students, and welcome to session number 5 of the AP Statistics virtual instruction. My name is Luke Wilcox. I am an AP Statistics teacher from Kentwood, Michigan. I hope you got a chance yesterday to tune in to my colleague, Brendan Murphy, who hopefully took you through the chi-squared test of independence. You're going to notice today that we are switching topics away from the chi-squared test into a new idea about inference for regression. So let's go ahead and jump right in. So quick check to make make sure that you are in fact in the right place here, this is AP Statistics. My name again is Mr. Luke Wilcox from East Kentwood High School in Kentwood, Michigan. Now I'm going to start out with some announcements here, and if you've been with us for the last couple of days, you have seen these. These are extremely important in case there's anyone that's new. I just wanted to make sure that all students were aware of what we're doing here with this YouTube live thing. And so the big idea is this: it's every day, Monday through Friday, 2 o'clock. You can tune in. We'll be live. And the first part of it, March 25th to April 3rd, this is what we're in the middle of right now, is units 8 and 9. And so what Brendan finished up with you yesterday was unit 8 on chi-square test, and what I'm going to be starting with you today is unit 9 inference for slopes. And very, very important, these two units, units 8 and 9, will not be on the AP exam this year because of the current situation. So on the 2020 exam for this year, you will not be assessed on units 8 and 9. Now what this means is that next week, starting on April 6th, we will have a full 4 weeks of review. That's going to be covering the stuff that is in fact on the AP exam for the 2020 school year. So starting on Monday, we will be jumping back into material that you have likely already covered within your course. Now the next reminder here is about where you can access resources for this YouTube live stuff, and any lessons that we're going to be teaching, as well as the homework assignments that we have, you can download at statsmedic.com/YouTube. There is in fact a link down below if you want to just click through the link. And then the final announcement here is for those students that might be in need of an electronic device or internet in order to take the AP exam this year. Okay, this is going to be an at-home exam that you will be taking on a device, on a computer, or on a phone. And if you do not have access to that, or if you know another student that needs access to that, we want to make sure that they are taken care of. So they just need to go to this web address here, fill in their information, and the College Board will make sure that they do have a device and they have internet access in order to be able to take the AP exam for 2020. Okay, so we are going to check back in with some work that you did yesterday with Mr. Murphy. This is a chi-square scenario, and it is a multiple choice question from an old AP exam. So let's just jump right in here. It says the following two-way table resulted from classifying each individual in a random sample of residents of a small city. Now I'm going to pause right there, and I'm going to say that the random sample of residents of a small city, that sounds to me like one sample that they're taking from one population. So I'm just going to note right here that this is one population, and then let me keep reading here. According to level of education, with categories earned at least a high school diploma and did not earn a high school diploma, and employment status, with categories employed full-time and not employed full-time. Now what it sounds like to me there is we have two different variables, level of education as well as employment status, both of which are categorical variables. So I'm definitely seeing two categorical variables here. So anytime we have one sample or one population with two variables, that is a clue to us that we want to be doing a chi-square test of association, also known as a chi-square test of independence. So let's continue reading. The other clue, by the way, is the fact that we have a two-way table here. The two-way table is sort of a giveaway to you that you're either going to be doing chi-square test of homogeneity or chi-square test of independence. So here's what the question says: if the null hypothesis of no association between level of education and employment status is true, which of the following expressions gives the expected number who earned at least a high school diploma and who are employed full-time? So we see that word association in there again. That's another clue to us. And this sounds like we're going to have to be doing an expected value calculation, assuming the null hypothesis is true, that there's no association between the two variables. Now they said for at least a high school diploma. So I know that I'm dealing with the first row here, and employed full-time, that is the first column. So what we're really looking for is the expected value in the top left cell of this two-way table. Now if the null hypothesis is true, we should be able to just look at the proportion of the total sample that earned at least a high school diploma. And I can do that by taking the row total there divided by the grand total, 92 out of 157. That's going to tell me the proportion of the sample that earned at least a high school diploma. Now if the null hypothesis is true and there's no association, we would expect that proportion to hold for this group of people as well as this group of people. In other words, the proportion would be the same within each one of those columns. Now we know we want to deal with the first column here, and so this is the proportion, and we know the total within that column is 82. So we should be able to take the proportion of the total there to get our answer. And sure enough, if you look at the answer choices, that does in fact match with answer choice B. And I just want to make note that this does in fact match with the formula that we talked about over the last couple of lessons here, which is how to calculate an expected count when you have a two-way table by taking the row total multiplied by the column total, all divided by what I like to call the grand total or the table total. And sure enough, you can see here it is the row total multiplied by the column total, all divided by the grand total. So our final answer on this one is going to be B. Hope you did all right on that one. Okay, we are now ready to shift gears. So we're going to move into the lesson for today. And I like to start always with a couple of learning targets, just so that you know where we're headed. This is also a way where we can measure at the end of the lesson whether or not we actually got what we needed to by checking back in with these learning targets here. So there are three of them. Okay, the first one is to identify and interpret parameters and statistics, which hopefully are familiar terms with you, from linear regression. So we are going to be doing some review of stuff that you likely covered very early in the class with two variable analysis, scatter plots, residual plots, all that stuff. We'll be doing some review with that, but then moving into this new realm of inference for linear regression. So the second learning target, in order to do inference, we're going to have to think about the sampling distribution of the sample slope. And then finally, the third one is to check condition for inference for slope. And that's really just going to be setting us up for the next two lessons where you're going to calculate a confidence interval and a significance test for a slope. And there are some conditions that must be met in order to perform that inference. So we'll check back in on these learning targets when we get to the end of today's lesson. So let's move right into today's lesson. And the context for today's lesson has to do with SAT scores and GPA. And my hunch is that if you knew something about a student's GPA, that it might help you to predict what their SAT score might look like. Not perfectly, but it might help us to predict a student's SAT score. So here's what it says. It says, how well can we predict SAT scores from students' grade point average GPA? Let's start by looking at data from all 330 seniors at a high school in Michigan. Now, what we're given here is some computer output, which is going to be very, very important for us. And you likely saw this earlier in your course, but there are some numbers that are in that computer output that you had no clue what they meant. But listen, by the end of the next couple of lessons, you are going to know what those numbers in that computer output represent. And then, of course, we have a scatter plot. And sure enough, as I had sort of predicted, you do see that there is a very clear positive linear relationship. I'd say a fairly strong positive linear relationship, such that the higher the GPAs, their students are more likely to have higher SAT scores. So above average GPAs tend to be paired with above average SAT scores. And of course, we can find a line of best fit for that, and we can do some analysis. So let's jump right into the question for this. So number one is just to start thinking about what the population is in this particular context. And that's given to you right up front. And I, in fact, I've underlined it already. It is all 330 seniors at a high school in Michigan. So this is something that is very rare in statistics. It's, we actually have data on every single person in the population, right? So later in the next part of the activity, we'll think about what happens if you only have a sample of the whole population. But for now, we do in fact have all of the data from the entire population here, all 330 seniors at the high school in Michigan. Okay, the next question says, what is the y-intercept of the LSRL? And of course, LSRL stands for the least squares regression line, which we're given some information about in our computer output here. And so hopefully you know what a couple of the numbers in the computer output mean. The first one that we need is the y-intercept. And that is in fact that first number in the top left that you're given there. So we can record that the y-intercept is 611.4. Now the next value that we're given in that computer output is the slope of the LSRL. That's the next value that you see there. So we can record that for the next question. The slope of the LSRL is 198.1. And in just a minute, we'll talk a little bit more about what that number means specifically and how to interpret that slope. But the next question is, what's the equation of the LSRL? Well, we know the y-intercept and we know the slope. So we can write our equation now as y equals the y-intercept plus the slope times x. Now there's a couple of things that I want to change real quickly about that line of best fit that we just wrote down there. First of all, I try to get my students in the habit of using contextual variables. And what I mean by that is instead of using x and y in your equation, why don't we write down what those variables actually represent here? And so instead of writing x, we know that x in this particular context represents the GPA. So I'm just going to put GPA as the x variable. And we should do the same thing for the y variable here. The y variable for this particular context is we're trying to predict the SAT score. And then the last thing that I think is super important here is a tiny little symbol, putting a little hat over the SAT. And what that means is predicted SAT. Because remember, the whole point of this least squares regression line is so that we can choose an x value or GPA and then hopefully make some sort of prediction about what the SAT score would look like for that particular GPA. GPA. So let me just point out a couple of things here. The y-intercept and the slope that we just got from the computer output there. I want to make note of the fact that these are values that come from data from the entire population, which is rare for us to have all of the data values from the whole population. So because these are numbers that are calculated from the whole population, these are what are known as parameters. And usually when we're talking about parameters, we have some very specific notation symbol that we use for them. So I'm going to tell you the right symbols here for the y-intercept of this LSRL. We're going to call that alpha. And let's be careful here. This is not the same as the alpha significance level from a significance step. This is totally different, a different alpha. And then for the slope, we're going to just go in order of our Greek letters here. This is beta. So we have alpha for the y-intercept and beta for the slope of the population least squares regression line. And then I want to really point out the fact that this least squares regression line that you see right there comes from data from the entire population. So this is what's known as the true population LSRL, right? That is the true line of best fit for the entire population. And let me just remind you of this notation that we use here. Equals, we said alpha plus beta F. Now, I think we're used to writing y here. And it turns out, and I'll show you how this works in just a second here, that what we should actually be writing here is the mean of y. And after we talk through question number 3, I think that'll make a little bit more sense here. But at least you know the correct notation for the true population LSRL. Okay, we are ready for question number 3. So question number 3 says predict the SAT score for a student with a 2.0 GPA, a student with a 3.0 GPA, and a student with a 4.0 GPA. So let's start out with our student that has a 2.0 GPA. Now we know that's our x value, right? And we know that we can take a line of best fit and predict the SAT score by plugging in that particular x value. So our predicted SAT score here, just using our line of best fit, 611.4 plus 198.1 times the GPA, but in this case the GPA is 2.0. And I will tell you that the predicted SAT score for a 2.0 GPA is about 1008. That's the predicted SAT score for a student with a 2.0 GPA. But I want to be a little bit careful about this. If you look back at the scatter plot on the top of the page there, and you find our x value right here, right? This is an x value of 2.0 GPA. If I go up to the data, what you're going to realize here is that there's not just one student that has a 2.0 GPA. In a large school like this, you're going to have quite a few students that have a GPA of 2.0, and each one of them might have a slightly different SAT score. We see some variability in the SAT score for that particular GPA. And so just to give you a visual perspective of this here, if we're looking at students that have a 2.0 GPA, we got 1008 as our prediction for their SAT scores. Now most of them will probably score fairly close to 1008, but there might be a few that are a little bit above, and there might be a few that are a little bit below. And what you're going to find is that appears to follow somewhat of a normal distribution. In other words, for a specific x value of 2.0, the distribution of the y values or the SAT scores is approximately normal. So I'm going to go ahead and draw a normal distribution right on top of that. And I'm going to try and draw a 3D picture here for you. I'll do my best. What we're really saying here is that when we go back to this x value of 2.0, there's really a normal distribution, and we know that the center of that normal distribution should be about 1008. So it's really like three-dimensional almost. We have like a normal distribution right there at the x value of 2.0, and the center or the mean of the normal distribution is 1008. This is precisely why we're using this notation here, right? So we're actually not just predicting the SAT score for a single student with a 2.0 GPA. We are predicting the mean SAT score for all students that have a 2.0 GPA, which we expect to be at the center of this normal distribution that we have here. Now we're going to use some similar reasoning for the next student, which is the student that has a 3.0 GPA, and we can start by plugging in that particular x value into the line of best fit. And I've done that calculation already, and it turns out that a student with a 3.0 GPA is going to have a predicted SAT score of about 1206. So if I go back to my scatter plot here and I now look at students with 3.0 GPA, you're going to find that there are quite a few students that have GPAs of 3.0, and that the mean value of all of the scores is going to be about 1206, what we predicted in the line of best fit. And so let's get a visual representation of that again. 1206 we would expect to be at the center of the distribution. Most students score fairly close to 1206, but some of them score above and some of them score below, such that the distribution of SAT scores is approximately normal, which means in my picture up here, I can draw in a normal distribution where the mean is about 1206. Now you can see where I'm going here. Let's move over to the final estimate, which is the one for the GPA of 4.0. And I'll tell you just by plugging that into the line of best fit, you're going to get a prediction of about 1404 for a student with a 4.0 GPA. We come back up to our scatter plot here and we look at the students that scored 4.0. We're going to see that the average is going to be about 1404 for all of those students. 1404. Another normal distribution here, where the center of the distribution is about 1404. So just to finish off my picture here, 1404, most values close to it, a little bit less as we get further away, and we've got this normal distribution here. And so what we actually have in the scatter plot is we have like a whole bunch of these normal distributions. In fact, for every x value or for every GPA, we have a normal distribution of SAT score. And listen, if we were to draw a line through the center of each one of those normal distributions, right? So I'm going to go ahead and try and draw a line through the center of each one of these normal distributions here. This is going to be our line of best fit, right? That's actually the population LSRL, the true population LSRL is what I've just drawn in there for you. And it goes right through the center of every one of those normal distributions. Now, one other thing I want to point out before we move away from these normal distributions here is the variability of each one of these normal distributions. And one of the ways we can measure that, of course, is with the standard deviation, right? So the standard deviation I can represent in the picture like this with a symbol sigma. And I can do the same thing in the next picture here. This would represent the standard deviation, and this would represent the standard deviation. And it turns out that one of the conditions that we're going to need to check is that each one of these normal distributions has about the same variability or equal standard deviations. In other words, that sigma value stays the same for each one of these normal distributions here. And so this value sigma, you can actually get from your computer output up here. It's labeled as S here, but that's because the computer thinks that this is a sample. It turns out that this is in fact sigma, well, very close to sigma. The calculation is slightly off, but that's a very, very good estimate of what the standard deviation of the y values is for each one of the specific x values. Okay, so we've taken care of that whole normal distribution thing. I've done my best to draw you a three-dimensional picture in the best way that I can, and we are arrived at the final question for this page, and that's to interpret the slopes in the context of the problem. And that's going to become a very big deal over the next two lessons where we're doing all of our work with slope. And so the slope here, beta, is we've already calculated it, is 198.1. And just as a real quick reminder of slope, here's a hint that you can use to interpret your slope. When you first learn slope in your very first algebra class, you may have learned it as the rise over the run, or even possibly as the change in y over the change in x. And if you put that in the context of the problem, change in y would be the change in the predicted SAT score divided by the change in the GPA. And we know that value is 198.1. I'm going to write it as a fraction over 1. And so really it's telling you that for a change in GPA of 1, we would predict the SAT score to have a change of 198.1. So we just need to go ahead and put that into words now. Okay, so here's the interpretation. It's going to say for every increase of 1 in the x value, which is GPA in this case, for every increase of 1 in GPA, we predict an increase in SAT score of 198.1. Right? We've essentially just taken this here and turned it into words. Now, a couple of things you want to make sure that you include in your interpretation of the slope. You're always going to talk about an increase of 1 in whatever the x variable is. For us, that's GPA. Very important here is that you use the word predicted for the y variable, which is SAT, so it is a predicted SAT score. And then notice here that I said that it's an increase in SAT score, and I know that because the slope is a positive slope, right? If it was a negative slope, I would expect it to decrease. And then of course here is our slope value, and we also included some units on this one here. So very important moving forward, this idea of slope, right? The slope of the least squares regression line. The next two lessons, very specifically, are going to be inference about this value for slope. But here's the thing: in order to do inference, we have to have a sample from which we can make an inference to the population. And everything that we did here on this first page, remember, was population data. We had all 330 seniors. So the next move that we're going to make, if you flip to the next page, we are now going to move into the world where we take a sample from the population, which is much more likely in the real world that we have a sample rather than all of the data from the whole population. So let's see how things change here when we now are taking a sample from the population. So it said, let's now consider the situation where we take a random sample of 10 seniors from this high school in India. And just like we had on the previous page, we've got got our computer output here, and we've got a scatter plot of the data. But you'll notice a lot less dots in our scatter plot or data point because we only have a sample of 10 seniors. So question number one, to define the population. Well, I think we did that already on the previous page. That's all 330 of the seniors at this cycle. But this time we don't have data for all of these students. We only have a sample. And so the sample in this case is the 10 seniors that have been randomly selected. Okay, so the format of this page is very similar to the previous page. So I think we can move pretty quickly through this. For the y-intercept and for the slope, we know exactly where we're going to get those. The y-intercept is the first value here. The slope is the second value here. So let's go ahead and record our y-intercept as 724.4. And let's record our slope as 169.0. And now we know our equation of the least squares regression line. It's going to say that the predicted SAT score equals 724.4 plus 169.0 times the GPA. Now, the thing that's different here is we are dealing with sample data. And so this value that we have for the y-intercept and for the slope is now a value calculated from a sample rather than a value calculated from the whole population. And for that reason, these are considered statistics, right? Remember, statistics are calculated from sample. Parameters are calculated from population. And once again, the notation or the symbols that we use is going to matter here. And this is the part that's going to look familiar to you from previously in the course. The y-intercept, we're going to call A, lowercase a, and the slope, we're going to call B. That should look very familiar to you, okay? And let's just point out here that this line that we just created the equation of, that is not the population LSRL, that is the sample LSRL. And we use different notation for the sample LSRL. And this is the part that I hope looks familiar to you. Y hat equals A plus BF, which is something that you likely studied earlier in the course. Okay, so let's move on to number 3, which says, what is the sample slope? Is it the same as the population slope? Well, we know from above here that the slope of the sample, that's B, which we know is 169.0, and the population slope, that is the beta value from the previous page. And if you look back, the true slope of the population LSRL was beta equals 198.1. So is this a good estimate? Yeah, it's a fair estimate. It's definitely not the same though. So I'm going to say right here very clearly that our sample slope is not exactly equal to the population slope. And the question is why? Okay, and the reason is when you take a random sample of 10 students, every time you take a random sample of 10 students, you're going to get a different sample of 10 students. And then sure enough, this line of best fit is going to be a different line of best fit. And every time you calculate a different line of best fit, you're going to have a different slope value, right? So at the heart of this is the idea that we are taking a random sample, and we know that random samples produce sampling variability. So we're going to say because random samples create sampling variability. So every time you take a sample of 10, you're going to get a slightly different slope value. Well, that leads us right into question number 4 here, which says suppose we selected many random samples of 10 students, and each time found the sample slope of the LSRL. Predict what the distribution of the sample slopes would look like. Okay, so I'm a big fan of the dot plot, so we're going to draw ourselves a dot plot here, and we got a slope of 169.0, and you put that dot down. But then the idea is if we took another sample, random sample of 10 students, we get a slightly different value, and maybe be a little more, maybe be a little less, and you may well predict here that if you were to do this over and over again, you're going to get a pretty nice distribution of values here. It might look something like this, right? And I'm hoping right now that you're saying, oh, that looks like a normal distribution. We could draw a normal curve on top of it. Now let's make sure that we understand what this distribution represents. If I were to pick a single dot there, okay, what that dot represents is one random sample of 10 students. Then we calculate the line of best fit for those 10 students, and then we grab the sample slope from that line of best fit, and we plot that value right here. So that is one random sample, and the slope calculated from that random sample. And this is a different random sample of 10, and the slope calculated from that sample. And this is a different sample, and this is a different sample, and this is a different sample. And so what we have here is what we call the sampling distribution of B, the sample slopes, because each one of those dots represents a different value for the sample slope based on a different sample of 10 students. Now, I'm going to hope that comes out as approximately normal. I can label that as capital N. And now let's think about the center and the variability of this distribution. Now, the center of this distribution, I would hope, would be close to the truth. And in this particular context, we actually know the true slope of the population LSRL. It's 198.1. And so hopefully these random samples we're taking are going to be pretty close to that thing that we're trying to estimate here. Now, sometimes a little higher, sometimes a little bit lower. But in general, the mean of this sampling distribution should be the true slope of the population LSRL. Now, for the standard deviation of this thing, we're going to call this the standard error of B. And it turns out there's a big formula for that you can use to calculate it. But most of the time, we're going to get that value right from the computer output here. So you see up above where it says standard error of the coefficient, and we know that this right here is our B value. It turns out that this value right next to it is the standard error of B, right? That's the value we're looking for. That's 32.0. And what that's telling you is that these estimates for the slope that we're making will typically be about 32 away from the truth. And that's what that standard error is telling you. Now, one other thing I'm going to point out just while we're here is this estimate value is what's known as the standard deviation of the residuals. And that's actually an estimate of that sigma value that I showed you on the previous page. Okay, so S estimates sigma, which is the true standard deviation of the Y values for each X value. Right? This is our best guess at it, is S, the standard deviation of the residual. Okay, let's move on back down here. Number 5, what is this graph? I'm hoping this one looks familiar to you and that you studied this earlier in the course. This is what's known as a residual plot. And just as a very quick reminder of what a residual is, if you look at your scatter plot, the residual is the difference between the actual Y value and the predicted Y value. So this student right here, if we were to calculate the difference between the actual Y value and the predicted Y value here, that difference would be the residual. So this would have a fairly large positive residual for this particular student. And you'll see that student represented in the residual plot right here. Okay, and also notice that you've got 0 at the center of all the residuals, and you got some positive, some negative, and then on the x-axis, we're actually just graphing the x value, the GPA. Now move on over to the next graph, and you'll notice that it's residual, and so students will say, oh, it's a residual plot. Well, not exactly, right? The residual plot has residuals on the y-axis and x values on the x-axis. This is a little bit simpler than that. It's simply a dot plot of all the residual values. Okay, there's only one variable there, the variable residuals, and we're looking at the distribution of those residuals. Okay, we're gonna need those when we get down here to checking condition for inference. And don't freak out, there are 5 conditions for inference. I know we're used to 3 conditions generally when we're doing inference for means or proportion, but a couple of these are gonna look very familiar to you. So let me tell you first what they are, and then we'll start with the ones that we already know how to take care of. So there is this acronym LINER, which will help you remember the 5 conditions, which are linear, independent, normal, equal, standard deviation, and random. And I'm gonna start with the ones that are easy, the ones that we already know. First of all, the random condition. We've been using this one all year long. We just gotta make sure that we have a random sample. And sure enough, we see from the question that this is a random sample of 10 seniors. And of course, this is important because we want to be able to generalize to the population of all seniors. And we also want to know that each individual senior is independent of the next, which is ensured by the fact that this is a random sample. Now, the next one that we already know how to do is the independent condition, also known as the 10% condition, which is an issue if you are sampling without replacement. And in this particular case, we are sampling these 10 seniors without replacement. So we do have to check the 10% condition. So the 10% condition here would say that the sample is less than 10% of the population, which is all seniors at this school. And actually, we know that there are 330. So I would definitely say that the independent condition is satisfied. Now, to the 3 new conditions here. The first of which is that there is a linear relationship between x and y. And well, we know that because we can look at the scatter plot and see that the scatter plot seems to be fairly linear there. So our justification for why this condition is met is to say that the scatter plot is fairly linear. Now, the other thing that we can use actually, if we look right above us here at the residual plot, if you recall from earlier in the year, we're looking for a residual plot that has just sort of a general scatter above and below the x-axis. What you don't want to see there is like a curved U pattern or an upside down U, which we don't see here. So I'm going to add that in. I'm going to say also the residual plot shows no clear pattern. So for both of those reasons, I'm going to say that for sure the linear condition is satisfied here. Okay, now for the normal condition, this goes back to what we were talking about on the previous page with these normal distributions here and with this scatter plot that has all these normal distributions. What we're trying to say is for each x value, the distribution of the y values is approximately normal. And the way that we're going to check that here is we're going to look at this dot plot of residual. Okay, and hopefully we see something that looks relatively normal there with the dot plot of the residual, but surely we don't want it to have an outlier or strong skew. So I'm going to say here that the dot plot of residuals shows no strong skew or outlier. And of course we could use the histogram or box plot. I just happen to prefer the dot plot myself personally. All right, now equal standard deviation. What we're talking about on that one is the fact that these 3 normal distributions all have similar or the same standard deviation sigma there. We want to know that that's true. There's equal standard deviation. And the way that we're going to check that is we're going to look back up here at this residual plot, and we'd like to see that the residuals have just about equal variability for each x value. So as I go through all the x values here, I'd like the variability of the y values to be mostly the same. So I'm going to say here the residual plot shows the variability of y is similar for each x value. Now what we wouldn't want to see there is like a residual plot that looks something like this, where the residual started out very close to the x-axis and then got much bigger there. Right? That would be a problem because the variability is increasing as you move to different x values. So this would be bad news. But I think we're okay in this particular situation, which means all 5 of our conditions are satisfied. We'd be ready to perform inference. Okay, so let's see if we can summarize what we learned here in today's activity. I'm going to go back to the 3 learning targets that we had at the beginning, starting with number 1, which had to do with identifying parameters and statistics. And so I think the important takeaway here is about notation, right? For the population LSRL, we say the mean of y is equal to alpha plus beta x, whereas the sample LSRL, we use different notation here, and this is the one we're more familiar with. Y hat equal to a plus b. And so what this means is that a value, which is the sample y-intercept, is going to be used to estimate the alpha, which is the true y-intercept of the whole population. B is going to be used to estimate the slope of the population LSRL beta. Then I add one more in here, which we mentioned on the previous page, that S, the standard deviation of the residuals, is going to be used to estimate sigma, which is the standard deviation of y for each x value. So very important here, all these values that we have here, because they're based on a sample, those are statistics. All these values, because they're based on the population, are parameters. Okay, that moves us to learning target number 2, which had to do with the sampling distribution of the sample slope. And I think for this one, I'm just going to draw a picture of the sampling distribution of B, and really it's a dot plot, right? So there's a bunch of dots in here, but I'm modeling it as a normal distribution. And we said that the true value, or the center of the mean, should be the true slope of the population LSRL beta, and we can measure the standard deviation using SEB, the standard error of the slope, and that generally is going to come from computer output. And we're going to need that in the next 2 lessons when we do inference or regression. All right, finally, is to get to these conditions, all 5 of these conditions that we have for learning target number 3. Remember the acronym is linear. That's going to help you remember the 5 conditions that are necessary here, which is linear, independent, normal, equal standard deviation, and random. And just as a quick reminder for each one of these on how you're going to check that, the linear condition you can check by making sure that the scatter plot is fairly linear, or that the residual plot has no clear leftover pattern. Independent condition is 10%. We check that when we're sampling without placement. For the normal distribution, you're going to check the dot plot of the residual, or a histogram, or a box plot. Equal standard deviation, you're going to check your residual plot, and what you don't want to see is those residuals getting bigger as you move to the right or smaller as you move to the right. And then random, we know this one, we just need a random sample. All right, now your homework problem is listed there. That is the problem that Mr. Murphy is going to start with in the next lesson. What I tried to do here today is I tried to set the stage for the next 2 lessons that you're going to be learning. Tomorrow you'll be with Mr. Murphy, and he's going to talk about how to make and interpret a confidence interval for a slope. And then I'll be back with you on Thursday, where we're going to try and do a significance test for a slope. So I hope you got what you needed out of this. If you enjoyed it, if it was helpful, give me a thumbs up. You will be with Mr. Murphy tomorrow, and I will plan on seeing you on Thursday. Have a great day.
So good afternoon, AP Stats kids. It's Wednesday, and it's April 1st. I live in rural Maine, and we had snow last night, which is not atypical, I guess, but depending upon where you are in the country around the world, maybe you didn't have snow. We like to call it a dusting of snow, which is just a little bit on your car, I guess, and it's already melted, but winter's still hanging around up here in rural Maine, and where the day's getting longer, and that's a good thing. So my good friend Luke yesterday introduced what we call Unit 9, and I'm going to summarize that as what we would call inference for regression. So we want to come up with confidence intervals, and we want to do hypothesis tests on what we call the slope of the least squares regression line. And depending upon how your teacher sequenced things earlier in the year, when I say least squares regression line, or I'm actually going to try and clarify that, the sample least squares regression line versus the population least squares regression line. Your teacher may have opted not to teach that earlier in the year, and many teachers kind of combine that unit in what Luke and I are doing the rest of this week. So if this is brand new to you, don't worry about it. I'll try and make the connection between what perhaps some students learned earlier in the year with what we call the sample least squares regression line versus today the population least squares regression line. Luke and I have, starting next Monday, a plan for the next month. So April 6th through May 1st, we have full weeks, and all of those sessions will be dedicated to reviewing for this year's 2020 modified AP Stats exam. So all of what we've done the last 4, 5, 6 lectures and the rest of this week will be on units 8 and 9. Again, that's not none of chi-square or inference for regression will be on this year's test. But we wanted to make sure that you guys have the full AP Stats experience. So when you go off to college next year, your professor may have assumed that you know this, and so that was our logic. But we start reviewing starting next Monday. We're going to publish a schedule of all of our daily topics for really the next month. That's probably going to come out later this week or early next week. And on Friday, the College Board is going to announce publicly some more details on this year's exam. So stay tuned. Luke and I will make sure that you guys are 100% up to speed on what's in this year's test, what isn't, how long is it, how many questions, pretty much anything we can share publicly. We're going to go ahead and share with you guys. So I'm just going to segue to my PowerPoint, and there's our daily slide. That's going to be the first slide. It's a cool kind of normal curve, right, with maybe a histogram or something below it. So you've seen that before, and you've seen both Luke and I hopefully at this point. Maybe not. Maybe you're brand new today, so welcome. So again, my name's Brendan Murphy, and I teach at John Baptist Memorial High School in Bangor, Maine. It's a really interesting school. I won't go into great detail, but great school, great kids, and I'm a lucky guy. I have a great job. My good friend Luke, he teaches at East Kentwood High School in Michigan, and he's great. I've known him for years. We're both what we call AP readers, so we've graded thousands and thousands of AP Stats exams over the years, and both he and I are also what we call consultants. So in the summer, we learn professional development from teachers, and I've learned so much from all the wonderful teachers that have taken my workshops, and perhaps I have your teachers over the years. So this was last night's homework. So if you didn't sit in on Luke's session yesterday, he introduced and pretty much set the stage for what we call inference for regression. So let me just give you a couple, 20 seconds, 30 seconds to just read the problem. I'm going to read through it again. And this is when we say modified. This wasn't the full free response. We're going to do just part A today. So maybe give you 20 seconds or so to read the problem, and then I'll walk through the homework, and then we'll get into some new stuff. Okay, so let's look at this problem again. This was from the 2006 AP Stats exam. This was question 2. I was a reader that year, and I actually think I was one of the 150 readers or so that graded this problem. It sort of rings a bell. So a manufacturer of dish detergent believes that the height of soap suds in the dish pan depends upon the amount of detergent used. So I call that setting the stage. There's no mathematics there, but it's just trying to sort of contextually give us an idea for what's going on. A study of the suds height for a new dish detergent was conducted. So I hear the word study, and I don't know if that's an experimental design or really what that is. But just setting the stage. 7 pans of water were prepared. My first gut says, well, that's a really small sample size. I would love for that to be 27, 57, 100, 5,000. As a general statement, larger sample size is always better. But it is what it is, and I guess 7 is better than nothing. And all the pans were of the same size and type and contain the same amount of water. So we're trying to keep our variables consistent. That's what makes sense. The temperature of the water was the same for each pan again. We're just setting the stage. An amount of dish detergent was assigned at random to each pan, and that amount of detergent was added to the pan. So there's my randomness. I want to look for that in almost every problem. That's sort of a good thing. It feels like perhaps we put different amounts of detergent in the pan. Then the water in the dish pan was agitated for a set amount of time, and the height of the resulting suds was measured. So that's a lot. You may have to go back and read that a couple, 2 or 3 times. That's perfectly fine. I like to tell my students, really understand the problem before you dive in and do any mathematics. Like understand what they're asking you to do. A plot of the data and the computer output from fitting a least squares regression line. So LSRL, that's what we abbreviate that as least squares regression line, to the data shown below. Okay, so there's a scatter plot. It looks like my explanatory variable is the amount of detergent. My response variable as the height of the suds, SUDS. And so it feels logical to me that if I put more detergent in and shake it up or pour more water on it, the suds are probably going to get a little higher. So we probably all experience that. And so before I do any mathematics, I want to basically try and understand the problem, see if it makes any sense. And so down below here, you'll see we call this a generic computer output here. I'm going to switch over to my document camera. We're going to be looking at the same problem here. Okay, so here's the same problem. So I call this a generic computer output. The reason we say generic is we're not trying to do some marketing for any of the software companies. There's many different software packages out there. Most of them are excellent. So hopefully you've had an opportunity to use that in the classroom. And I did watch a little bit of Luke's video yesterday. He was excellent as always. And I think he did talk about how do we read a generic computer output. So there's a lot of numbers here and there's a lot of statistics here. And as a general statement, we don't need all of them to answer any problem. And what we want to do is be able to find the information that we're specifically looking for. There's times when you're going to see something that isn't part of the curriculum and are squared adjusted. That's not part of our curriculum. So sometimes I just cross that out. I don't want it to get in the way. But there's lots of numbers here and don't be overwhelmed by that. So the homework last night was to write the equation of the fitted regression line. I guess that would be the same thing as the least squares regression line. I use the two sort of interchangeably, I guess. Define any variables used in this equation. So I'm going to show you two different ways to write the least squares regression line or the fitted regression line. Different books present it different ways and both get full credit on the AP exam. If that line wasn't here, in other words, if it didn't say define any variables, we would still want you to define the variables. So anytime you write a regression line, please define the variables, whether that line is there or not. So I like to say to my students, well, if I look at constant and coefficient, so that's negative 2.679, that feels like my y-intercept or my initial starting value for my equation for my sample least squares regression line. So constant coefficient, you see we're going to do lots of generic computer outputs today. That number is sort of always on the same spot. And so I think that's my A value up here, my initial starting value, my y-intercept. The amount, the number that goes with the amount here, I think that's going to be my slope here or my rate of change. And so we do want you to be able to find those two values relatively quickly from a generic computer output. And so if you're with me the other day, I think you realize that I write really, really poorly. I'm a lefty. I have the curse of being a lefty. And so my first equation here, y hat equals negative 2.679 plus 9.5x. That's in this form here, what we call y hat equals a plus bx. What I haven't done right now is identify the variables. So this answer right here is not complete. We would want you to identify the variables. And so over here on the right, I just said x is the amount of dish detergent in grams that we added, and y hat is the predicted mean height of the suds or the predicted height of the suds. So I need both of those if I choose not to identify my variables. That's the way my textbook presents it. There's nothing wrong with that. That would be full credit on the AP exam. You have the correct least squares regression line, and you've identified the variables. Others of you, your teachers or your textbooks, may have you write it, I guess, sort of in words. And so here you can see I have height of suds, and I have this huge hat over it. You can see I didn't do a very good job of drawing in my hat there. Equals negative 2.679 plus 9.5 detergent or detergent in grams or something like that. And so here I don't really need to identify the variables because I physically have written those in my least squares regression line. So again, both of these would be considered acceptable on this year on any AP exam. This one here is just another way to do it. And again, your teacher may have a specific way of doing it. And I follow the book, but please know that both of those are acceptable. So that's a quick review of the homework. And again, this concept here of coming up with the least squares regression line, my sample line based upon my 7 data points. And I'm going to build upon that today to come up with what we would call what I call the population least squares regression line. If you've never seen that before, or you say I don't think I've ever done a scatter plot, bivariate data, least squares regression line, don't worry about it. Luke and I are going to cover that in our review. So there was a part B and C to this problem, as you can see, and I think I may come back to this problem on Friday, what we're calling FRQ Friday. So on Friday, I'm going to do nothing but a couple of 2, 3, 4 free response questions and really dive into the rubrics and how we score and grade these things and what we're looking for, keeping in mind that this year's modified AP Stats exam is going to be nothing but free response questions. Okay, so back to the PowerPoint, and so let's take a look at perhaps what's going to be new with this lesson. So again, y hat equals a plus bx. That formula is on the formula sheet that you'll have for this year's exam. We say y hat equals a plus bx, and that's going to be the least squares regression line for my small sample of data. The equation below it is what I would call the true least squares regression line. Some books call it the population regression line, and you can see that in the top equation, I call that my sample. Those are English letters that make sense. And in the bottom equation, you'll see some Greek letters, and I'm going to switch back to my document camera and try and make a tie-in for you guys. Okay, so the first day of my AP Stats class every year, we get to count M&Ms, and so that's pretty fun. I buy a bunch of different bags of M&Ms. And on the first day of AP Stats, I really want to start to differentiate for my students what we call sample statistic SS and what we call population parameters PP. And I think Luke did something very similar yesterday. So X bar is the sample mean, and you probably worked with that earlier this year. We're going to use the sample mean to make a prediction, a forecast, an estimate for what we call mu, the population mean. P hat is my sample proportion. Again, I'm going to use that to make a forecast, an estimate, an inference prediction of what we call P, the population proportion. Some of the older books out there would actually identify this as pi. I think that's the Greek letter for P. And I have mixed emotions about this. I guess I understand it like both of those. SX is my sample standard deviation, and I'm going to use that to forecast my population standard deviation. And this kind of ties into what we call a t-table here. And X bar is a pretty good unbiased estimator for mu. P hat's a pretty good unbiased estimator for P or pi. SX is less of a good unbiased estimator for sigma X, and we need to compensate for that. That's one of the reasons we use a t-table. As my sample size gets bigger and bigger and bigger, then all of these sample statistics become better and better forecasters or estimators for my population parameters. And I like to say to my students, almost never do we know these numbers. What's the average age of every American right this instant? We don't know that, right? What's the proportion of people in the state of Maine, that drive pickup trucks? We don't know that. So it's very rare that we know these population parameters. And so we almost always have to use sample statistics to make forecast predictions for what we call the population parameters. So again, here's my equation for my, I'll call the sample least squares regression line. I showed you that, I think, on my slide. And I want to use these values to come up with what I call the true regression line or the population regression line. This little alpha is what I'm going to use that to come up with. This little a, I'm going to use that to come up with what we call alpha. It's a Greek A. And this B here, which is my rate of change or slope, I'm going to use to come up with beta. And I'll continue on with my little chart there. Little a, I'm going to use that to come up with alpha. And little b, I'm going to use that to come up with beta. And so again, on this side here, we have what we call sample statistics. And on this side here, we have what we call population parameters. And we use these sample statistics to make forecast estimates, projections, inferences about the population parameters. I like to tell my students, if it's a Greek letter that you're less familiar with, it's probably a population parameter, mu, sigma, alpha, beta. Of course, this little p here sort of ruins that little pattern for me. And again, some of the older books may actually put pi there. And if you happen to use that in your book, we would accept that on the AP exam. We know what that means, and we're good with that. So when I'm looking at my least squares regression line here, most of us feel that this slope here, this rate of change, is more powerful, more valuable than my initial starting value. Of course, both of them are important with coming up with the equation of my line, but usually slope or rate of change is considered to be the more important of those two variables. So we have sample statistics. We use those to estimate what we call population parameters. And I'll just go back and show you those two equations. Both of those equations, I believe, are on the formula sheet. This top one definitely is. And so again, don't worry about memorizing the formulas. And one of our review days, Luke and I are going to go know your formula sheet. So we'll talk about all those formulas and which ones you really need and perhaps which ones you don't. So again, I copied this formula here direct from the formula sheet, all confidence intervals. And hopefully you've perhaps been working on confidence intervals intervals with your teachers before we all headed home because of the virus. All confidence intervals are basically built the same way. We start with some sample statistic, and we add and subtract what we call a margin of error. So this margin of error is actually these two numbers multiplied, this critical value times the standard error of the statistic. The standard error of the statistic, different people identify different ways. This is a little trickier, but when I'm estimating the standard deviation from my data at hand, I call that the standard error. That's going to be dependent upon how big or how small my sample size is, and you probably might have done that when you were doing confidence intervals with either means or proportions. So I'm going to try and write down a couple of formulas that perhaps you've seen before when you were doing confidence intervals. X bar plus or minus critical t, sx over radical. And again, we call this my sample statistic, and subtract those two numbers multiplied, what we call margin of error. So those two multiplied or margin of error. This is what we call critical t value. I'm going to get that from a t table, and that's dependent upon my confidence level and my sample size. And with proportions, what is it? P hat plus or minus square root of p hat 1 minus p hat over n, and that's a critical z value. Sorry about that. So again, when I multiply those two numbers, I get my margin of error. And sample size is going to be important here in both formulas. It's really square root of n and square root of n on this formula as well. Anytime I'm doing any confidence interval, I want high confidence. So that should make sense. And I want a smaller interval. So I want this high confidence, and I want a smaller interval. And one of the ways we do that is by a larger sample size. So a larger sample size is always helpful. I always feel better about the decisions I make. And as a general statement, we tend to get more accurate results with a larger sample size. So this equation down here is newer. And that's, I guess, today's lesson is we want to build a confidence interval using my sample slope. I want to build an interval that I'm confident captures the true population mean or the population mean of the least squares regression line. And so I guess it's built sort of the same way. I start with some sample statistic, in this case b, that came from my least squares regression line. My critical t value is the same. I get that from a t table, and that's based upon two things: degrees of freedom and my confidence level, and standard error of slope. Well, that parenthesis there, that's a not nice formula. How's that? I'll come back to that in a slide or two. That formula is given to you on the AP Stats exam. I'm gonna stick my neck out and say I don't think we've ever asked you to calculate that on an AP Stats exam. It's a little clunky and it's a little cumbersome. But fortunately, technology can do it for us, and many times that's given on the form of generic compute output. Sorry, it's many times included in my generic compute output. So as a general statement, don't worry about calculating this standard error of the slope. We do expect you to come up with the critical t value, and we do expect you to come up with the sample slope given a generic compute output. Perhaps what's a little different here is my degrees of freedom, which up until now has always been df is n minus 1. Well, degrees of freedom is now n minus 2. So let me see if I can come up with a real quick example here and demystify why it's n minus 2 and not n minus 1. Okay, so earlier in the year when we were using univariate data, one variate data, I guess up until now my degrees of freedom has always been n minus 1, and we use that for standard deviation. Perhaps first couple weeks of school, it's also part of my correlation coefficient formula. We did degrees of freedom when we did chi-squared, so we use degrees of freedom again. But now we're dealing with bivariate data, so two variable data, and many times in some sort of a scatter plot here, explanatory variables down here, and my response variables up here. My degrees of freedom is n minus 2. Well, way oversimplifying, many of my students will say, oh, this is easy, Mr. Murphy. One variable, n minus 1, bivariate data, n minus 2, and that's a nice connection, and that's a true statement, that's not incorrect. But it's a little deeper than that, and I'm probably just going to quickly go over it and oversimplify it a little bit. If I just pick any two data points and graph them on a scatter plot, well, I can draw a line through those two data points, and it would hit both of those two data points, and I guess my correlation would be 1, and my R squared would be 1, but it really doesn't tell us anything. And of course, the sample size of 2 is ridiculously small. I really need a third data point here to come up with some variation in my what we call my least squares regression line. So oversimplifying, that's one of the reasons why we do n minus 2 here. Is anytime I have just two data points, I guess I have a perfect line through those 2 points, and that really doesn't help us. And one of my students will yell out, but Mr. Murphy, the third point could also follow sort of in that pattern and fall directly on the line. And that is a true statement. That's not wrong, but nothing in the real world is ever that nice or that precise. So one of the things that we have to keep in mind is we need degrees of freedom is n minus 2. Again, none of this will be on this year's AP Stats exam, but we want to do a good job of trying to teach it to you so when you head off to college, you're well prepared. So here's that same formula again, and SEB, standard error of my slope. Well, here's the formula. SEB equals S over SX times square root of n minus 1. And the S on the top is this formula here in the middle. This SX on the numerator, denominator is right here. And so if you divided this by this times that, you would get this formula, and you can see it's clunky. And yeah, I don't really want to deal with it. And the nice thing is we don't have to deal with it. But I just wanted to show you that those formulas are on your formula sheet, the AP Stats exam. We never asked students to calculate it, and I'm not sure that we ever would. So don't worry about that. And we're going to go through your formula sheet at one point. So don't worry about it. Similar to all the inference we've done so far this year, we do need to check conditions and list assumptions and whatnot. And so many of the books have this little acronym, I guess. We're dealing with linear models, least squares regression lines, think liner. I wish I had a good abbreviation for A here, and then it would be exact, but close enough. So L stands for linear. We need to kind of convince ourselves that the relationship between X and Y is linear. The explanatory and response variables are linear. I stands for independent. That hasn't changed. The individual observations are independent of each other. And we check this with our 10% condition. You're probably hopefully real comfortable with that by now. I'm looking for some sort of a normal shape for any explanatory variable X or response variable Y varies according to a normal distribution. And I can check that using maybe a dot plot or a histogram of my residuals. I think Luke did that yesterday. The E stands for equal standard deviations. The standard deviation of Y is the same for all the values of X. And here's our R for random again. The data comes from a random sample of our population or a randomized experiment. So when we're doing these problems, confidence intervals and hypothesis tests, we do need to check for conditions and list any assumptions. And so you want to think about this liner, okay? You want to think about these 5 things to talk about when you're checking your conditions. And again, if these conditions aren't met, then the results that we get are just not applicable. So here's a t-table. We're probably going to need this to do a couple problems today. Again, this is provided for you on your AP Stats exam. I'm old school, and so I still teach tables. I teach my students how to read these tables. All of this you can get from a calculator. So if your teacher has never taught you how to read a t-table, don't worry about it. I'll show you how to do that on the calculator. But I'll try and do at least 1 or 2 problems, maybe using both the t-table and the graphing calculator. So and I'll tell you why I like the table, but I'm a little old school and my kids say I'm old-fashioned. So I won't say my age, but I think I'm older than I look. So here's a classic multiple choice for this concept here, what I call inference for regression. And we're going to do confidence intervals today. Luke's going to be doing hypothesis tests tomorrow. And I know that your exam this year is just free response questions. This unit is about 2 to 5%. Well, let me rephrase that. It would have been about 2 to 5% of a normal AP Stats exam. There just aren't that many free response questions that are related 100% to this topic. So you're going to do a couple multiple choice, and I'll try and end up with 1 free response that hits on the same concept. So 2002 exam, multiple choice number 21. In a study of the performance of a computer printer, the size in kilobytes and the printing time in seconds for each of 22 small text files were recorded. Again, setting the tone. My sample size is 22, and it feels like if my file size is bigger, it's going to take longer to print. I think that's what's happening here, but I'll keep reading and see if I can figure that out. A regression line was a satisfactory description of the relationship between size and printing time. So I guess that was our first first condition there, right? We had to check that our data was linear. I could do that by looking at a scatter plot and maybe a residual plot, but we're told that it's reasonable to use a linear model to analyze this data here. The results of the regression analysis are shown below. So again, I would call this a generic computer output here. There's a lot on here, and there's a lot of stuff that we just don't need. So don't get overwhelmed by this. We want to be able to quickly find what we're looking for, use that to answer the question, analyze the data, and move on. What's interesting down here is S equals 0.6174. I think that's the standard deviation of our residuals, but I don't need that for this problem. I think Luke tackled that yesterday with 22 minus 2 degrees of freedom. Okay, well, there's your little hint that perhaps this is inference for regression, inference for our regression model. And College Boy was nice and kind of gave you a little hint here. Again, all year we've done degrees of freedom as n minus 1, and now all of a sudden it's n minus 2. Which of the following should be used to compute a 95% confidence interval for the slope of the regression line? Okay, so that's what I was talking about earlier. And I'm just going to go to my document camera and we'll take a look at this problem here. Okay, same problem here. Which of the following should be used to compute a 95% confidence interval for the slope of the regression line? So my confidence level is 95%. My degrees of freedom is n minus 2 or 20. And again, that was given to us up here, so that was kind of nice. Let's come up with my least squares regression line. Again, all this data is based upon those 22 data points. So constant coefficient, again, that's going to be my A value. So y hat equals 11.6559 plus the number, the coefficient that goes with the size. I guess that's the size of my file is 3.478. I probably don't need, I guess I'll put all those decimals down. Times x. Again, on the first response question, I would never leave my least squares regression line like that. I would identify both those variables. Since these are English letters and not Greek letters, I'm going to call this my simple least squares regression line based upon, again, those 20 data points. I want to see if I can come up with an interval that captures the true population slope. So I want to know what that true slope is. If I'm a manufacturer and I know what that true slope is, then I may be able to design my machines a little bit more efficiently. I can make my printer more efficient. And so that's why a manufacturer would want more than just the sample slope here. They want to see they come up with the population slope. So I want to use the formula B plus or minus critical T and SEB. Again, we sort of build all confidence intervals the same way. We start with some sample statistic. In this case, it's our sample slope. And I add and subtract what I call the margin of error. These two numbers multiplied give me the margin of error. So we identify the sample slope as 3.47812. So I can eliminate those two answer choices, D and E, pretty quickly. Okay, that would be confusing the initial starting value y-intercept with slope. So that's a common mistake. Just watch that. My SEB, my standard error of my slope, is actually right next to my sample slope. SE, a coefficient, standard error coefficient. So that's good to know. That's 0.294. And so if I look up here, I think my answer is A because that's the only one that has 0.294. But let's see if we can figure out where this critical T value is coming from. So again, the confidence level is 95%. My degrees of freedom is n minus 2 or 20. So if I go back to my T table here, I'm down at 95% degrees of freedom over here. I want to go at the intersection over here at 20 and 95, and I get 2.086. That's that critical T value there. So that's my answer A. And I know they didn't ask me to interpret it, but it's important that we get there. So how would I summarize those numbers? I would say something like we are 95% confident, that the interval 2.86 to 4.09. Again, I think I just did the math, added and subtracted. Captures the slope of the population regression line. Some books call it the true regression line, population regression line, relating the size of the file in my printing time. So again, that's not needed here, but that's important. And Luke and I will be using for responses. We'll make sure that you're comfortable sort of summarizing your data. What does that tell us? So I want to go back and show you how to get that critical T value using your calculators. In case you're not as comfortable reading the table, of course, you can get all this from a calculator. Most of the calculators today now have this feature. If not, you might want to spend some time learning how to read a T table. But let's do second bars. I'll scroll down to inverse T. In many ways, similar to the button right above it, inverse no. Reading a T table means I need to worry about degrees of freedom. So we wanted 95% confidence. And so this is an area where we see mistakes on the AP exam. It would be very easy to type in 0.95 here, not 0.975. I'll go back and show you where that comes from. So one of the reasons I'm a table guy is it's easy to sort of type in the wrong number here, I think. But that wants to be 0.975. My degrees of freedom is 20. That was given to us. Again, that's n minus 2. So I'm going to scroll down and gets me back to the home screen. And you can see it's not actually exactly equal to the number that I got from my table, right? I got 2.086, but for rounding errors, that's pretty close. And hopefully you can see that that's the correct answer. So my values are a little bit different, 2.086. The reason that I typed in 0.975 is this is where my normal curve here. There's my mean. I'm doing a 95% confidence interval. I'm hoping that I'm capturing about 95% of my data falls out here in the body of the table. And my lower tail is 2.5, and my upper tail is 2.5 as well. So what I'm really looking for is all of that area right here. And so I add the 2.5 and the 95 or 0.025 and 0.925 to get 0.975. So just watch that when you're using your calculator. The confidence level is not the same as the area. Quick sketch here, and it's easy for me to get there. That's one of the reasons I actually do like a table. It's pretty easy for me to find 95%. I go up here, I find my degrees of freedom, and then intersection point. I'm less likely to make a math mistake. And I do it all the time in the class, and I shouldn't as an AP stats teacher. My kids catch me every time, and they say, Mr. Murphy, be careful. So I'll just watch that. So let's do at least one more multiple choice here, and I'll take a look at free response, and we'll wind down for this afternoon. So this was from a 2008 practice exam. Raul performed an experiment using 16 wind-up rubber band single propeller airplanes. So I think I have a visual picture. Again, I'm just setting the stage here. He wound up the propeller a different number of times and recorded the amount of time in seconds that the airplane flew for each number of rotations that the propeller was wound. So I think I get what they're asking me to do here. I wind up the elastic band. Probably the more I wind it up, the tighter let it loose, the plane flies longer. But I think that's what's going on. So I call that just setting the stage here. A regression analysis was performed, and the possible computer output is given below. So again, I'm going to call this a generic computer output. It's not based upon any one software package. It's generic. It sort of looks like they're giving me the least squares regression line here, at least my sample least squares regression line. Y hat equals a plus bx. Sometimes they do, sometimes they don't. You can probably find those two numbers down here. We'll go look at the problem. I'll circle those for you. Again, there's many numbers on this output here that we're not going to use. Don't let that bother you at all. Which of the following is a 95% confidence interval for the slope of the regression line? So again, I said earlier that most of us consider the slope the more important of the two variables between my slope here and my y-intercept. That relates the number of rotations the rubber band is wound and the plane's flight time. So let's go do the problem out. Same problem here. So my confidence level is 95%. That feels like a pretty common confidence level, but please understand that there's lots of other ones. I think one of the problems that we may or may not get time to do today had 98%, so maybe we'll go take a look at that. The sample size was 16, so my degrees of freedom is 16 minus 2 or 14. So that's important. I need that, and in this problem, I don't see that anywhere up here. So that's important. I need that critical T value associated with this 95% confidence level and those degrees of freedom of 14. Again, my constant coefficient, this number here, that's my A value, 0.9241, and the coefficient that goes with the rotation, or the number that goes with the rotation, the number of rotations, 0.04625x. That's going to be my sample slope. Time equals 0.924. Okay, so we got the right equation. I'm going to use this sample slope here to help forecast estimate the population slope or the true slope of my regression line. So B plus or minus some critical T value times my standard error of slope. Again, when I multiply those two numbers, we call that the margin of error. So my sample slope was 0.04625. And again, in a multiple choice scenario, I like to try and eliminate some answers, and this year's test is all free response, but it's always good to eliminate answers, right? Well, the standard error of my slope is usually right next to the slope. So that's this number SEB. I showed you that one slide, and it's no picnic to calculate on a piece of paper or even with my calculator. So and again, I don't think we would ever ask you to do that. Formula is given to you on the formula sheet, but I don't think we would ever ask you to do that. So my critical t-value for 95% confidence with 14 degrees of freedom. Let's go see if we can find that on my calculator. So second bar is scroll down to inverse t. Again, I don't want to make a mistake of 0.95. Notice they say area, not confidence level. There's a difference. My degrees of freedom we said was about 14. I'll go back to my home screen. So it looks like 2.144. 2.144. That's my critical t-value. So let's go see if we can figure out what's the correct answer here. So we had it down to A, C, and E. We did say that my standard error was 0.01565. Well, this one has 0.01. Okay, so I can't eliminate anything there. We did say that my critical t-value based upon 95% confidence and 14 degrees of freedom was 2.144. And so I think the answer is A. And again, I think there's just a rounding issue here that I maybe did, or they rounded a little bit differently. For the sake of time, I won't show you where those two critical t-values, which are incorrect, they're probably coming from something like degrees of freedom of 15 or typing in 0.95 in the area or something like that. So just be careful when you're coming up with that critical t-value. We need the confidence level again, and we need degrees of freedom. And degrees of freedom is N-2. So I'm watching the clock here, and boy, time flies when you're having fun, I guess, as an AP Stats teacher. There's a few more multiple choice that are basically sort of the same thing, coming up with either the margin of error or the actual interval. So they're all similar in some ways. This was an free response question that had to do with just the sample least squares regression line, correlation coefficient. Maybe I'll try and hit that on Friday when we do nothing but free response. So here's some AP exam practice, and I'll see if I can do this really quickly and get you out of here on time. So John believes that as he increases his walking speed, his pulse rate will increase. That makes sense? For walk or run, the pulse goes up. He wants to model this relationship. John records his pulse rate in beats per minute while walking at each of 7 different speeds in miles per hour. Looks like we've graphed that. Speed is my explanatory variable. My pulse rate is my response. Again, I wish I had way more than 7 data points, but that's what we have, and we need to make a decision or do an analysis based upon that. I always feel more comfortable with more data in the real world. Scatter plot, regression output are shown below. So keeping conditions in mind, the data does look linear. I might want to do a residual plot. I would do the 10% condition. I would check all of those. Think liner again. Here's my generic computer output. Again, there's definitely way more numbers and statistics on here than we need. So it's up to us to kind of pick out what we need. We should go to my document here. We'll finish up this problem and I'll wind down for the day. Thanks for staying late. If you're still with me. So same problem. Part A, use the regression output, write the equation of the fitted regression line. So again, constant coefficient. There's my A value, speed coefficient. There's my B or my slope. And so down here quickly, I said pulse hat equals 63.457 plus 16.2809 speed. There's my least squares regression line. They didn't ask me to identify the variables, but I would always do that. Do the estimate of slope and intercept parameters have meaningful interpretations in the context of this question? Yeah, I think so. If my speed was 0, I probably hopefully still have a pulse, right? So that's what makes sense. And this sample slope here, I could use to come up with my true slope or my true or population regression line. So yes, again, for the sake of time, both of those seem to make sense. Okay, part C I wanted to do real quick and we'll wind up. John wants to provide a 98% confidence interval. Oh, good. So different number.
Students, and welcome to day 7 of our virtual instruction for AP Statistics. I hope you got a chance to check in yesterday with my colleague Brendan Murphy, where he talked about confidence interval for slopes yesterday. And listen, I've got some big news for today. The lesson that we are about to cover today would very likely be the last lesson of the school year. It is at the very, very end of the content. So essentially what you're going to be seeing today is the last lesson of AP Statistics. And then of course tomorrow Brandon's going to take you through a couple of AP exam practice questions. And then starting Monday, we are going to jump into AP exam review. So let's go ahead and jump right into what we have here for you today. Just to make sure that everybody is in the right place, you should be in AP Statistics. I hope you are here right now. My name is Luke Wilcox. I am an AP Statistics teacher at East Kentwood High School in Kentwood, Michigan. And I do have some other announcements to share with you. If you've already been with us for a couple of days, you've seen these announcements, but we just wanted to be careful in case we have anybody that is new with us. I just want to check in on a couple of important ideas here. I'll let you know some schedule things. Of course, our meeting time, Monday through Friday, this time right now, 2 o'clock till 2:45 Eastern Standard Time. The first set of lessons, which we're just in the middle of, just approaching the end of, is Units 8 and 9. And we've already been all the way through Unit 8. And Unit 9 is actually what we're going to finish today, the inference for slope. And the most important thing you need to know about Units 8 and 9 is that they will not be covered on this year's AP exam, the 2020 exam. Now, starting Monday, that is Monday, April 6th, we are going to be covering content that will in fact be assessed on the 2020 AP exam. So that starts our AP exam review. We will definitely talk more on Monday about calendar. By the end of the day tomorrow, there actually be an official calendar that will get announced from College Board, so you can check to see what every single one of the lessons is going to look like for the AP exam. Now, in terms of resources, if there is every day we have a lesson, we have a homework problem. If you want to be able to see those or to print those out, you can go to statsmedic.com/YouTube. There's a link. If you look down below, you can click right through to the link. It's organized by day, so you look for today, Thursday, April 2nd, if you wanted the lesson that we are about to be going through. And then finally, if you are a student or know a student who needs a device or needs access to the internet in order to take the AP exam this year, we will be at home. There's a website here that you can go to, and there you can request a device or request internet access. So certainly, if you have a classmate, a friend who might need access to technology, please write that down and get that to them so that we want everyone to be able to take the AP. Okay, so let's check back in with what you learned yesterday with Mr. Murphy. He left you with this homework problem, which is quite a lengthy one. So let's just jump right into it. Okay, so here's what it says. Windmills generate electricity by transferring energy from wind to a turbine. A study was conducted to examine the relationship between wind velocity in miles per hour and electricity production in amperes for one particular windmill. For the windmill, measurements were taken on 25 randomly selected days, and the computer output for the regression analysis for predicting electricity production based on wind velocity. So I'm actually going to pause right there because they've given away the two variables for this problem, and I think I can identify which one is X and which one is Y, because I know that we are typically trying to predict the Y value from the X value, and here they're trying to predict electricity production. That means that's going to be our Y variable based on the wind velocity. That's going to be our X variable. Okay, let me continue on here. The regression model assumptions were checked and determined to be reasonable over the interval of wind speeds represented in the data, which are from 10 miles per hour to 40 miles per hour. So I think what they're saying here when they say assumptions were checked is that what we've been calling the conditions, and remember there are 5 of them, those have been met, so we don't actually have to go through and check the conditions, which is kind of nice. So we have our computer output here. Let's identify a couple of things here in the computer output. First of all, I do want you to know that the X variable will always be represented below the word constant, and we actually knew that the wind velocity was going to be the X variable. And then that first column of numbers is going to tell us two things that will likely be very important for us: the Y-intercept for the LSRL and the slope for the LSRL. And I hope you learned with Mr. Murphy yesterday that this value right here is one that we just might need. That's what's called the standard error of the slope, or SEB. Now there are some other numbers there that we haven't really talked about, but I'm hoping by the end of the lesson today that some of these numbers make a little bit of sense. So let's jump into part A here. Okay, part A says use the computer output above to determine the equation of the least squares regression line. Identify all variables used in the equation. Okay, we know our Y-intercept, we know our slope. This is easy. It's Y equal the Y-intercept, which is 0.137, plus the slope, which is 0.240 times X. Now it does say identify all variables used in the equation, and what they want there is to know what X represents and what Y represents. So I actually try to get in the habit, instead of writing X, I'm going to write what X represents, which is wind velocity, and instead of writing Y, I'm going to write what Y represents here, which we know is the electricity production. So I'm just going to write it as electricity. Now the other thing that I think is really important here is that we are trying to predict the electricity from the wind velocity. So I'm going to put a hat on top of the electricity showing that is a predicted electricity value based on the wind velocity. Okay, let's move to part B. How much more electricity would the windmill be expected to produce on a day when the wind velocity velocity is 25 miles per hour, then on a day when wind velocity is 50. Show how you arrive at your answer. Okay, there are two different approaches to this particular problem. I'm going to show you the long way, and then I'll show you the short way. Okay, the long way is to just go ahead and figure out what the predicted electricity would be for each one of these speeds. So let me start with a speed of 25 miles per hour, and I know I can predict the y value or the electricity using the line of best fit. So 0.137 plus 0.240 times the wind velocity, and we want to check that for 25 mile per hour wind velocity. That's going to give you about 6.137 amperes is the electricity that would be produced. Now that's for a 25 mile per hour wind. Let's now check it for a 15 mile per hour wind. And all that means is I got to plug in 15 for x time. So same equation, but now I'm just plugging in my 15, and that's going to give me a value of 3.737. And we want to know how much more electricity was generated on the day with 25 miles per hour. So we just need to take the difference between the two. So I would do let's see, 6.137 minus the 3.737, and that's going to give me about 2.5 ampere. I'm sorry, 2.4 ampere. So that would be my final answer. That is the additional electricity from 25 miles per hour than 15 miles per hour. Now that's a long way. I told you there was a short way, and the short way has to do with this value right here, which is the slope of the line of best fit. And if you think about the interpretation of that slope, it tells you for an increase of 1 in x. So for an increase of 1 mile per hour in the wind velocity, we would predict that the electricity would increase by 0.240. Now that value, that 0.240, is the predicted increase in the electricity if we increase by 1 mile per hour. Well, we want to increase by 10 miles per hour from 15 miles per hour to 25 miles per hour. So we would have to take that value and multiply it by 10. And sure enough, you're going to get that same answer of 2.4. So you actually could have justified this in two different ways. You could use the slope, or you could have just plugged in values into the line of best fit. All right, let's look at part C. Part C says, what proportion of variation in electricity production is explained by its linear relationship with the wind velocity? Now, I'm hoping that this one rings a bell. This is an interpretation that you just sort of have to know. It is the variation in y that can be explained by the linear relationship. And what we're looking for there is the r squared value, okay? And you want to make sure that in your computer output, you're picking the r squared value, not the adjusted r squared value. And we see that r squared is equal to 0.873. And sure enough, what that's telling you is that 87.3% of the variation in y can be explained by the linear relationship. And that's really all we need as a percent. Well, I suppose they're asking for proportion, so scratch that. We could write it as 0.873 if they ask for a proportion. Okay, last part here, part D. Is there statistically convincing evidence that electricity production by the windmill is related to wind velocity? Now, you see this convincing evidence, and that is a very big clue to you that you're going to need a significance test. And we have not yet talked about how to do a significance test for a slope. In fact, that's what today's lesson is all about. So I'm not going to answer this question yet. You will see this question again later. So I think that's a perfect segue into today's lesson. We are ready for the lesson overview. This is where I will talk through the learning targets, and then at the very end of the lesson, we will come back to these three learning targets just to check to make sure that we hit everything that we needed to. So here we go. Learning target number 1: check conditions for performing inference for the slope of a population LSRL. Well, lucky for us, we've been doing that for a couple of days now, and I think that part's going to go fairly quick. And then the big one here, learning target number 2, we got to be able to do a significance test for slope. And just like we're getting in the habit of at this point, I'm going to use the 4-step process of state, plan, do, conclude. And then finally, we're going to make a connection between what Mr. Murphy taught you yesterday and what I'm going to teach you today, and that's to make the connection between a confidence interval and a conclusion for a significance test, because they are very closely related. So we will check back in with these three learning targets at the very end of the lesson, but I believe we are now ready to jump into today's activity. So here we go. The question of the day today is, does seat location matter? And honestly, this is a real thing that teachers think about, right? We have to make our seating charts. Who should we put where? Who do we sit next to who? And some teachers think, it doesn't make any difference where the students sit. Well, there are some teachers that think very, very carefully about where they sit. And my hypothesis has always been that the front seats, right in the front of the room, those are the best seats in the house, because that's where the best learning occurs. And so this whole experiment was done to see if that's actually true. So let's dig right in and see what it says here. Okay? Do students who sit in the front rows do better than students who sit farther away? Mr. Wilcox randomly assigns students to rows at the beginning of the semester and then measures their exam scores at the end of the semester. Following are the results. So I did this a couple years ago. This is real data. This is what I found. And you see the scatter plot there. Now, just to be clear about row number here. If you look at this little picture at the top, if this were the front of the room, then I'm thinking that the front rows are the best rows. That's going to be row 1. So I think that row 1 is going to be the best seat in the house. Okay, and then we just count backwards from there. So this is row 2, this is row 3, and so on. Now I only had 5 rows in my particular classroom, so you're going to see in the data when you look down here at the x-axis that is just the row thing. Okay, so let's take a look at the data. Now the scatter plot here, you can see that we are graphing row on the x-axis. That's our explanatory variable, and the exam score at the end of the semester, that is our response variable. And I think you can see here from the scatter plot that we have a fairly weak negative linear relationship, but there certainly does appear to be a negative linear relationship here, even though it's not super strong. And you can look at the computer output here in order to confirm some of that stuff. And certainly we're going to be needing some of the values in this computer output here. So let's just identify first of all that score is our y variable and row is our x variable. We know that this first number that's being given to us is the y-intercept, and we know the second value that's being given to us is the slope. And hopefully from yesterday, you know that this value right here is the standard error of the slope. We just might need that for some of the work that we're going to be doing. So as I predicted, you can see from the data that there is a negative relationship. The further back you are in the classroom, it appears the lower exam scores you get at the end. So let's dig into a couple of questions. Okay, question number 1: is this an observational study or an experiment? Okay, definitely for this one, it is an experiment. And the difference between an experiment and an observational study is that the researcher or whoever's collecting the data has to randomly assign treatments to the subject. And I did assign row numbers to the students, right? I randomly assigned them a row. So we're going to say here the big difference between an observational study and an experiment. The experiment, the teacher or the researcher is imposing a treatment. And I'm going to identify what the treatment is here. The treatment for the students that they were randomly assigned was a row. Right? Each student was randomly assigned to one of the 5 rows. Now, second question related to that: why is it important to randomly assign the students rather than letting each student choose their own seat? So why is it important that we do this? Well, if you think about it, if I just let students sit wherever they wanted to, some people might say that the more studious students who really want to do well would come right up front, and those students that are trying to hide out or maybe want to goofball, they would sit way in the back, right? And then at the end of the semester, if I noticed that the students in the front rows were doing better than the students in the back rows, I wouldn't know if it was because of the row that they were in or if it was because of some other variable, like how motivated they were to learn, right? So that's why we need random assignment, is to help us out with all of these other variables that are there. And the idea is that when we randomly assign students to their row, we're also sort of randomly distributing all of these variables throughout the room. So there might be some super motivated kids that end up in the front and some in the middle and some in the back, but we're sort of evenly distributing them so that each group or each row is roughly equivalent, right? So that the only difference between those groups is the row number. So let me try and capture this. The big idea here is about the purpose of random assignment. And the reason we want random assignment is because it creates roughly equivalent group, right? So all the students in row 1 and row 2 and row 3 and row 4 and row 5, those 5 groups should be roughly equivalent in terms of all these variables, right? So that if there's a difference in the end, I know that the difference happened because of the row, not because of some other variable. This is what allows us to show causation, right? That the row caused the scores to go down. So I'm going to add that into my solution here. I'm going to say which allows us to show causation. So there's an important connection that we're making here. This is a really important connection about the purpose of random assignment. And the purpose of random assignment is so that in the end, if we have statistically significant results, we can say that there's some sort of causal relationship between x and y. Okay, the equation of the least squares regression line. We're getting really good at this. We know what our y-intercept is. We know what our slope is. I'm going to go right to you using the variable. The y variable here is the exam score, and it is what we're trying to predict. So the predicted exam score equal. And then I'm going to go with my y-intercept, 8.07 minus 2.53. That's my slope. And then my x variable here is the row that they are in. Okay, so my x variable is row. Now I'm noticing one thing that I'm going to want you to fix real quick here. This right here. This should not say score. We're going to get rid of that. That should definitely say row. That will always be your x variable. And we definitely know the x variable here is row. All right, so we got our equation here, the least squares regression line, and we are ready to interpret the slope. Well, the slope here, we know what the slope is. It's negative 2.53. And we've already had some practice with interpreting the slope. So I'm going to go right into it here. For each additional increase of 1 in x. Now in this case, it's the row. So for each additional row, when we move back 1 row, the predicted exam score decreases by 2.53 points. Now just to check in here, why did I say decreases? Well, that's because of the negative slope. And actually we knew that by looking at at the scatter plot, we have a negative relationship here, right? So for each additional row, that's for each additional x value, make sure you have the word predicted, and then you got your exam score, that's the y value, right? My x, this is my y, decreases by 2.53, and then I've included some units here. Okay? So we have a negative slope. It appears that each time you move back a row, your exam score goes down by about 2.5 points. Right? Now that could make all the difference for your final exam score here. Okay, now we got two final graphs here, and these are graphs that we've looked at for the past couple of lessons. But the question says, what information does each of the following graphs reveal? Okay, so first of all, let's identify what each one of these graphs is. The first one, of course, is a residual plot. There's actually some really important information that we're getting from this residual plot. The first of which is that we don't see a real clear leftover pattern. You don't see like a U shape or an upside down U shape. I call it a smiley face or a frown face. You're seeing pretty even scatter above and below. And so I'm going to say no clear leftover pattern. And so what this is telling me is that this relationship that we started with in the scatter plot is somewhat linear. Right? We have a linear relationship here. So I'm going to say that this indicates linear relationship is appropriate. All right, that's the first thing. Now the second thing that's important that we see in the residual plot here is that for each x value, if you look at each one of the x values, the distribution of the y has about the same variability. Right? There's like sort of the same spread on each one of these. We're not seeing like a big increase in spread as we move to the right or a big decrease in spread as we move to the right. So I'm going to say here for each x value, which is for each row, the variability of the y variable, which is the scores, is about the same. Right? We have about the same variability. So those are the two important things that we get from that first residual plot. Now the second picture that you see there, you see residuals, but this is not the same as a residual plot because it's not a scatter plot with two variables. It is one variable residual. This is just simply a dot plot of the residual. Now here's what we want to look for in the dot plot of residual. We want to check to make sure that we don't have strong skew or outliers, so that it appears that this could have come from a somewhat normal distribution. And certainly it doesn't appear that we have any outliers or strong skew. So I'm going to say no strong skew or outlier. Now of course the reason we're looking at these two graphs here is we're setting up for inference for slope, and what we're really doing is we're checking some of the conditions. So let's make clear which condition we were checking. In this first one, no clear leftover pattern indicates a linear relationship is appropriate. That's going to become the linear condition when we get to the significance step. The second one, for each x, the variability of y is about the same. We're going to call this condition the equal standard deviation condition. And then the third one here, no strong skew or outliers, that's what's going to become the normal condition, which says that for each x value, the distribution of y values is approximately normal. So I think we've done most of the legwork here in preparation for inference, for significance test, and we are now prepared to do a full significance test, 4-step state plan to conclude. All right, so here we go. Question says, do the data provide convincing evidence of a negative linear relationship between row and score? Now, before we jump right in, let's talk about this idea of convincing evidence. And maybe before we talk about having convincing evidence, we want to check to make sure that we just have some evidence to begin with. So the question is, do we even have some evidence of a negative linear relationship between row and score? And certainly we saw on the previous page that we do have some evidence, right? The slope that we were given is a negative slope. So I'm going to say some evidence because the slope value, which was negative 2.53, is negative, right? It's less than 0. So that's telling me that I do have some evidence, right? But maybe that slope value of negative 2.53 happened purely by chance just because of the random assignment, and row doesn't really have any relationship with exam score. So in order for us to check whether we have convincing evidence, this is why we need a significance test, right? This is what we need the p-value for, so be able to make a decision about convincing evidence. So let's jump right in. All right, in the state, we're going to start with our parameter, and actually the statistic here, we just identified the statistic. The statistic is our b value, which is negative 2.53. Now that is a statistic based on a sample or based on a particular random assignment. The parameter that we're trying to estimate is the true slope of the population LSRL, which we call beta. So let's clearly identify what beta is here. It is the true slope of the population LSRL, and then I need to get some context in here. So I'm going to say for x equals row and y equals score. Right? That's the parameter. And then of course we're going to use that parameter to write our hypotheses here. Okay, and the null hypothesis is going to say that there is no relationship between row and score, and we're going to try and find evidence against that claim. Now here's how we're going to write it. If there is no relationship or no linear relationship between those two variables, then that slope would be 0. Right? A beta equals 0 would say that there is no linear relationship. Now the alternative hypothesis is the claim that we're trying to find evidence in favor of. In this case, the question says, is there convincing evidence of a negative linear relationship? Well, a negative linear relationship would mean that beta is less than 0. So in words, this would be a negative linear relationship. Now that alternative hypothesis can be one-sided or two-sided. That's always going to depend on the wording of the question. We've clearly identified from the wording of the question that we want a one-sided less than 0 alternative hypothesis. Okay, our alpha level is not given to us, so by default we're going to go with 0.05. Quick note, this is not the same as the alpha, which is the true y-intercept of the population LSRL. This is the significance level alpha, right? 0.05. Okay, let's move to our plan. First of all, the name of the procedure. Okay, this is a one-sample procedure. Right? We don't have two different samples here, and this is a t-test for slope. So we already end up with a t-distribution. When we get down to finding our p-value, we'll need to use a t-distribution for this one. And you did a t-interval yesterday, right, for slope, for estimating slope. Okay, I think we're pretty good with these conditions here, so let's just move pretty quickly through that. For the linear condition, we're going to say that the scatter plot is fairly linear, and I'm going to provide a second justification, which is based on the residual plot. Remember, the residual plot had to even scatter above and below with no clear pattern, so I'm going to say, and the residual plot shows no clear pattern. All right, independent. Well, we know that's the 10% condition, which says that the sample size of 30 is less than 10% of the population of all students. But hold up, why are we checking the 10% condition? We check the 10% condition when we are sampling without replacement, and we're worried about independence. And in this context, are we sampling without replacement? No, this was a problem that dealt with random assignment, not a random sample. Okay, so we don't have a random sample here, which means we are not sampling without replacement, which means we do not check the 10% condition here because there is no sampling without replacement. Right? We have random assignment here, but we didn't have random sample. Okay, moving to the normal condition. That's where we check the dot plot of the residual, and we said on the previous page that dot plot had no strong skew or outliers, which means for each x value, the distribution of y values is approximately normal. Okay, equal standard deviation. That's where we looked at the residual plot, and we wanted to check to make sure that for each x value, that the variability was about the same for each one of the y values. So I'm going to say that it shows similar variability for each x value. All right, and then finally the random condition. We've talked about this one a little bit here. Not a random sample this time, but we did have random assignment, and this is what introduces the variability into the statistic, is the fact that every random assignment would produce a different value of the statistic. So with our condition satisfied, we are ready to actually do a calculation. Right? Now this is going to look very familiar to some of the work you've done previously in the course. The general formula is always the same. This is given to you on the formula sheet on the AP exam. If you're looking for the standardized test statistic, it is equal to the statistic minus the parameter, all divided by the standard deviation of the statistic, or the standard error most often. So the specific formula here. All right, we know we're going to have a t-test statistic here because this is a t-test. Let's think about the correct notation here. The statistic is the sample slope. The parameter is the population slope. And then we want the standard deviation of the statistic, but in this case we're going to have to use the standard error of the statistic, or the standard error of p. And I think we're ready to plug in some numbers. We already know our sample slope, negative 2.53. Now for beta, we're going to assume the null hypothesis is true, and so we're going to plug in 0, 0 for beta. Now the standard error for b, we need that from the previous page. That is right here at 1.11. So that is my standard error of b, 1.11. And if you plug that in your calculator, you will get a t-test statistic of negative 2.28. So let's go ahead and record that as our test statistic, negative 2.28. Here are 2.28 standard deviations or standard errors below them. Now for the picture, I'm going to give you two pictures here, the unstandardized as well as the standardized. So let me start out with the unstandardized, which is the sampling distribution of b, and it is approximately normal. And we are going to assume the null hypothesis is true, which says that beta is equal to 0, so the mean is 0. And then the standard deviation of this, if I were to just use notation, it's the standard deviation of b, or the standard deviation of the sampling distribution of b. The reality is we don't know that, and we're going to have to use our sample to try and estimate that. And so what we do is we use SED to estimate that standard deviation. And in doing so, when we standardize and we use the standard error of b, the distribution turns into a t distribution. It's a little bit more spread out, not quite as tall. There's our standardized distribution, which is a t distribution. And we need to know the degrees of freedom. Mr. Murphy talked about yesterday for our two variable analysis is n-2. We had 30 students in the sample, means our degrees of freedom 28. There we go. This is a standardized distribution, so 0 is at the center. Now, in order to get the p-value, we need to know how likely is it that just because of the random assignment, we would get a sample slope that we got, or farther farther from what's expected. Now, the sample slope that we got was negative 2.53. So this right here is the p-value that we're looking for, right? Shading away from the center, consistent with the alternative hypothesis less than 0. Now, in the standardized picture, once we standardize that p-value, we got a t-test statistic of negative 2.28. And so now this area should be the same as the area in the unstandardized picture. That's our p-value. Now, in order to get that, this is a t-distribution. And to get the area underneath the t-distribution on your calculator, you can use TCDF, and you would give the lower bound negative 9.999, the upper bound negative 2.28, and then the degrees of freedom, which is 28. And I'm going to tell you what that comes out of the p-value here is going to be about 0.015. And I try to get in the habit of making the test statistic and the p-value really stick out, because those are the important things that we need there. So I put a box around them. Now, real quick, look at that t-test statistic and that p-value. Let me go back to the previous page in this computer output here. And I'm hoping you notice something here. Right there, that's your t-test statistic, right? The computer output actually did that for you. And you would think that the next thing over right there is going to be your p-value. But it doesn't match because we had 0.015. But here's the deal. The p-value that you see in the computer output is always a two-sided p-value. Think about it. If we double our p-value, there it is, 0.03, right? So the t-test statistic and the p-value are actually given to you in the computer output. All right, we're ready to write our conclusion here. And remember, I always write two sentences for my conclusion. First is interpreting the p-value. All right, so here we go. Assuming the null is true. In this case, beta is equal to 0. There is a, and then we give our p-value 0.015 probability of getting a sample slope b of negative 2.53 or lower purely by chance, right? All I'm doing there is I'm interpreting this p-value. It's this area in the curve there, right? So make sure that you have your assuming the null is true, you got your probability, you got your or lower. And then the second sentence is probably the one you're more familiar with. This is where we're going to make a decision. Because the p-value, which is 0.015, is less than the significance level alpha 0.05, we are going to reject the null hypothesis. And we do have convincing evidence. And now I'm just going to go back to the wording of the question here, right? Convincing evidence of, I got all this here, negative linear relationships between rho and gorge. Okay, so that concludes the significance test. Now, I do want to show you how you can do this on your calculator. So if you want to grab your calculator, you can do so. If you want to just follow along, you can see on the screen what I'm doing with the calculator. The calculator will do all of this stuff for you. It's a nice way to check your work. So here we go. Now, the first thing you would have to do is to input the data. So you go to stat and then edit. And I've gone ahead and already put the numbers in. So you see all of the rows in list 1 and all the scores in list 2. And then I go to stat test. And if you scroll way down, you're looking for the linear regression t-test. So there we go. The linear regression t-test here. You hit enter. It's going to ask you where you put your x and your y value. That's going to ask you for your alternative hypothesis. And I've got it at less than 0 here. You can leave this one blank and you can go right to calculate. And sure enough here, we get our t-test statistic, which matches with what we had in our calculation, and then the p-value, which matches with what we had, along with some other things, the degrees of freedom, the y-intercept, slope, standard deviation, the residual, even your r squared and your r values are given to you there. So this is a great way to check your answer. Now, the other nice thing that you have on your calculator, which I know is coming up in the next question, is to do a confidence interval. So I'm going to go down now to linear regression. Test. I'm going to go to test. I'm going to find the linear regression t interval, just right below the test. There's the test. There's my t interval. Can I ask you for the same things, right? Which list? I'm going to want a confidence level of 95%, and I'm going to hit calculate. So go ahead and write these numbers down. We got negative 4.805 and negative 0.2615. That is our confidence interval. So I want to jump back into the activity here, and let's just finish up with this confidence interval and see if we can see the connection between the confidence interval and the significance test here. So here we go. Last question. My confidence interval, which I got from the calculator, is negative 4.81. I'm going to round it a little bit to negative 0.26. That was my confidence interval. And we want to show that this is consistent with the significance test. Well, if I were to interpret this interval, I would say we are 95% confident that the true slope of the population LSRL is between negative 4.81 and negative 0.26. Now, these are all of the plausible values. And what I notice here is that all the plausible values are negative, right? So we're fairly confident that this slope is negative. And the value that I don't see in there is the null hypothesis value, which is 0, or any positive values there. So clearly we think there's a negative value here. So the decision we would make, because that 0 is not contained within the interval, I'm going to write this down, because 0 is not in the interval, that means we don't think 0 is a plausible value, and we would reject the null hypothesis here, right? Because the null hypothesis says that beta is equal to 0. And sure enough, reject the null hypothesis is precisely what we said when we did the significance test. Now, just to be clear, when you're making this connection, you should really be making it with a two-sided test, right? And we had a one-sided test, but if you think about it, the two-sided test would have given a p-value of 0.03, and we would have made the same decision, right? Reject the null hypothesis. So whether we use a significance test or a confidence interval, in either case, we're going to reject the null hypothesis. Okay, I think we are ready to try and summarize what we learned here. I'm going to go back to the 3 learning targets that we started with at the beginning. So let's start with the condition. So learning target number 1 is the conditions. I'm hoping at this point, after a few days of doing this, you feel pretty comfortable. You know the acronym LINER is going to remind you of what your 5 conditions are. That is the linear condition, the independent condition, or the 10% condition, only for sampling without replacement, the normal condition, the equal standard deviation condition, and the rainbow condition. So I'm hoping those feel pretty comfortable for you at this point. Learning target number 2 was to be able to do the significance test as a full 4-step. I'm just going to highlight a couple of parts of this. Okay, first of all, the null hypothesis is going to say there's no linear relationship, beta equals 0. Now, the alternative hypothesis could be one-sided or two-sided depending on the wording of the question. So it might be beta is greater than 0, it might be beta is less than 0, it might be beta does not equal 0. You got to look at the wording of the question for that. All right, the other thing that I think is important in this 4-step process is the formula that you need for this. So we know the general formula for test statistic is statistic minus the parameter all over the standard deviation of the statistic, or the standard error. And for us, it's going to be a t-test statistic here. We're going to use the sample slope b minus the population slope beta all over the standard error of b. And I'm going to point out a couple of things here. This value most likely going to be 0 from the null hypothesis, right? And this value right here, it's not likely you'll have to calculate that. You'll be able to get that right from the computer output. And then we've got our last learning target number 3, which is connect the confidence interval to the significance test. So here's the deal. You're always looking for the null hypothesis value when you make a confidence interval. If it is not in the interval, right, which was the case here, if it's not in the interval, we don't think that is a plausible value, and we will reject the null hypothesis. Now, on the other hand, if that null hypothesis value is in the interval, well, then we think that it is a plausible value, and we fail to reject the null. And I guess I'm going to make a little point here. This is for a two-sided test, right? If you're comparing confidence intervals to significance tests, you want to make sure you're looking at two-sided. Okay, that brings us to the final question here, which is the check understanding. This is your homework problem. Should look pretty familiar to you. We maybe even talked about it earlier today, but you're going to answer the final question of it, right? And Mr. Murphy will check in with you on this one tomorrow. I appreciate y'all checking in today. I hope you learned something. If you feel like you got something out of today's lesson, make sure you give me a thumbs up down there. That'd be excellent. Please check in with Mr. Murphy tomorrow. We'll be doing some AP exam practice with you, and then I will see you again on Monday when we officially start our AP exam practice. Have a good night.
Good afternoon, AP Stats kids. It's Friday, April 3rd. If you're brand new to us, I'm Mr. Murphy. I teach and live in Bangor, Maine. And so today our goal is to do some just pretty much free responses. So no new material today. We started last Wednesday, and so for the last 7 days, Luke Wilcox and I have been trying to teach, I guess, the last 2 units in AP Stats, units 8 and 9, chi-squared, and what I call inference for regression. Neither one of those 2 units will be on this year's AP Stats exam. So we just wanted to make sure that everyone had the full experience. And then when you go to college next year, 2 years, whatever, that you take more statistics, and that you will have been at least exposed to those 2 major themes or threads in the AP statistics course. So starting this Monday, April 6th, we're going to do 4 full weeks of review for this year's modified AP Stats exam. We'll talk more about that. I think that schedule for the rest of our the month of April will be posted soon, if it already isn't, on AP Central. And so you should be able to take a look at that and hopefully pick and choose which sessions will be the most advantageous for you. So welcome back. I sincerely hope all of you are safe and healthy at home. These are trying times for all of us. Let's be positive. Let's keep working hard. And I do have some information that I can share with you guys this afternoon about this year's AP Stats exam. I'm just going to pull up my PowerPoint here. So again, I don't know why I like this picture, but it's a cool picture. So as a math geek, I guess it's just a cool picture. I sort of like that. So again, my name is Brandon Murphy. I teach at John Baptist Memorial High School in Bangor, Maine. My partner is Luke Wilcox. Luke and I have known each other for years and years and years. Have worked together many times on AP Stats, SATs, whatever. And so pretty much every other day you see one of us. He teaches at East Kentwood High School in Kentwood, Michigan, and he has a website here where he's sort of posting all of the homework. So each night we try and give you a little little bit of homework, something to look at, something to review, and then we start the next day going through that problem. So here's the problem, but let me just jump ahead one more slide. So effective today, around noon, the College Board released much more information about this year's AP exams. So I'll just hit upon the major points and then kind of dive into the math. That's what today's about. But please talk to your teachers and your fellow colleagues and students, your admin folks, whomever, because there's some dates and there's some really important things that are in these two websites here. I won't open these up. I'll just let you know where to go look for your slides. So as of today, around noon, hot off the presses, this year's AP Stats exam will be Friday, May 22nd. Everyone will be taking the same exam at the same time. So when you go to these websites here, you'll see that there's Hawaiian time and there's Pacific time and there's Central time and whatnot. I believe on the 22nd of May, I'm on the East Coast, so Eastern Standard Time. My kids will be taking that exam at 2 o'clock. So there's more information about the number of problems on the test. It'll be about a 45-minute test. There'll be 2 free response questions that they'll be modified, perhaps a little bit longer than in the past. In the past, we give kids around 15 minutes free response, and so they're going to be modified a little bit. But please go to these websites, spread the word. Please let your teachers know and your friends at school and whatnot. All of that I think will be super helpful. So let's go back to our problem here. So I think Luke assigned this last night, so let me just give you a minute or so to read it, and then I'll go ahead and tackle it. I think I'm going to do the whole problem too, but if you wanted to just do the last part, so let me give you a minute or so to read that, and then we'll go ahead and get started. Okay, so hopefully everyone can see this problem here. It's the same problem, right? It was from the 2011 AP Stats exam, problem number 5. So I'm just going to go ahead and read it. And I think what we asked you to do last night was part D, but I don't want to do the whole problem. Today's free response Friday and FRQ Friday, and I'm just going to walk through this whole problem, touching upon other concepts that hopefully you have learned earlier in this year. Part D was specifically to what I'm calling inference for regression. So windmills generate electricity by transferring energy from wind to a turbine. So just setting the stage. The study was conducted to examine the relationship between wind velocity and miles per hour electricity production in amperes for one particular windmill. So I might circle the word study. Is this an observational study? Is it an experiment? Right now, I don't know. It feels like wind velocity is going to be my explanatory variable. Electrical production is my response variable. And that makes sense. It's pretty windy outside in Maine today. You can hear my house shaking maybe. It's probably gusts of 40 miles an hour. If I had a windmill out back, I wouldn't be paying for my electricity today. For the windmill, measurements were taken on 25 randomly selected days, and the computer output for the regression analysis for predicting electricity production based upon wind velocity is given below. So again, I've been calling this a generic computer output. I'm sure Luke is using very similar language. Hopefully you've studied this in your class. If not, hopefully the last week and a half, you've seen enough of these from Luke and I. You're starting to get pretty good at finding the information that we need from this output. And again, a lot of what's on there you will not need. So don't worry about every number for now. The regression model assumptions were checked and determined to be reasonable over the interval of wind speeds represented in the data, which were from 10 miles an hour to 40. So I think that's going to kick in part D. The conditions were met. So if we go ahead and run a test, it's going to be valid. Okay, part A, use the computer output to determine the equation for the least squares regression line. Identify all variables used in this equation. So I'll try and do it in words. Electrical production. I'm going to put a hat on that. That's predicted, right? Equals constant coefficient, 0.137, plus the number that goes in front of wind velocity, 0.240, wind velocity. That's part A. Even if they didn't say identify all variables used in this equation, I would always identify the variables used in this equation. And so part A feels pretty straightforward to me. And hopefully at this point you guys can find those relevant numbers on that table as fast as I could. So far so good. We're doing well. Part B. How much more electricity would the windmill be expected to produce on a day when the wind velocity is 25 miles per hour than on a day when the wind velocity is 15? So if it's windier, I do anticipate theoretically producing more electricity. Show how you arrived at the answer. So when I was doing the problem this morning, I clearly found that the hard way to do it. I actually found the 2 different values for the 2 different speeds, and I was going to subtract those. So I said 6 minus 3.6 is 2.4, and that was clearly the hard way. What I should have done, but it works, and I get the correct answer. So what I just should have done is said, well, if the wind speed increases by 10, I just could have done 10 times 0.240 to get 2.4. So that probably would have been a little faster, but I did figure out the answer. And then I think I would always, have a contextual sentence. So 2.4 more amperes were produced when the wind was 25 miles per hour than on a day when it was 15 or something like that. So show your math and then finish up with a good sentence. So that felt okay. I felt like I was doing okay. Part C, what proportion of the variation in electricity production is explained by the linear relationship with wind velocity? Well, that sounds like R squared. So I was kind of thinking R squared, right? The coefficient of determination. What percent of the variation? And that was the word that sort of jumped out at me here was variation. So I'm looking for R squared. It's right there on my table. So that's pretty good. 0.873. We don't have to worry about R squared adjusted in this class. So I usually just cross that out. It feels like that's just going to be some noise, and I don't really need to worry about that. So I'm just going to cross it out. And again, I probably want a full sentence. And so 0.873 is the proportion of variation in electrical production that can be explained by the linear relationship with wind velocity. I think I said this the other day many times. I just repeat the question and somehow get that in contextually. So I don't want to leave my answer just like that. I want to have a sentence with that. So just kind of get to the habit of always sort of writing that. For the sake of time, I won't do it. Part D, I think, was what Luke was talking about yesterday in inference regression hypothesis tests. So is there statistically convincing evidence that electricity production by the windmill is related to wind velocity explained? So those 3 words were my key to me: statistically convincing evidence. That was really what sort of sent me to think about doing hypothesis tests. So I think another problem today, we're going to see very similar language. So that's kind of what jumped out at me. So I think is what you guys did yesterday with Luke. Again, this is just part D. So I wanted to do an inference test to see if the relationship between my 2 variables, wind speed and electrical production, is actually linear. I don't have the 25 individual data points, so I can't look at a scatter plot. I can't do a residual plot. I really want to do what we call a hypothesis test for the true slope beta to really see if the relationship between those 2 variables is linear. So my null hypothesis is beta is equal to 0. I'm sure Luke went through that yesterday. If the slope of my true regression line or my population regression line is 0, well, it would just be a horizontal line here, right? It feels like there wouldn't be any linear relationship between my variables. It doesn't matter what x is, y is always going to be the same number. So that's why we want this at 0. One day I had too much time on my hands at school, so I decided to type in perfectly circular data into my calculator. So you just came up with a bunch of points and it was perfectly circular, and then I asked the calculator to come up with the least squares regression line. Of course, it did it really fast, but maybe in my mind I thought the calculator was going slow, and it actually didn't come out with a perfectly horizontal line, but it came up with something really, really close. So even my calculator, which does exactly what I tell it to do, it was sort of struggling with, well, why can't you pick any one of those lines? It picked a line that was almost horizontal. There was nothing in the stem that led me to believe direction, so I just said my alternate beta is not equal to 0. And over here, I almost forgot, but I probably should identify that parameter. So where beta is the population or the true slope of the regression line between my 2 variables, wind speed and electrical generation. So we need to identify those parameters when we write those for a null and alternative hypothesis. So So since I didn't have any data to type in my calculator, I said, well, this information hopefully is somewhere in my table because I don't know anything about these individual 25 data points. So when I was doing confidence intervals, we were looking at that, the standard error of the slope, right? SEB the other day. Well, if we keep going over, it looks like my t statistic is 12.63. Boy, that's quite a few standard deviations above the mean, right? That's almost 13 standard deviations above the mean. That doesn't feel like it's going to happen very often, right? So if I keep going to my right, I see that my p-value or my probability is 0. It may not actually be exactly equal to 0, but it's really small. How's that? So I said my p-value is approximately 0 down here. And so now I can go ahead and make a decision. And again, the other day when I was doing a hypothesis test, I said, sometimes my first sentence is pretty generic. So since our p-value of approximately 0 is less than our assumed significance level alpha is 0.05, we reject the null hypothesis in favor of the alternative. That's my way of saying it. I'm sure you guys have heard other ways from your teachers. And if you have something that pretty much is getting those things in there, that's perfectly fine. I never like to use the word accept. I never accept the null. I don't accept the alternative. I just like to say we reject or fail to reject it in favor of the alternative, EHA. I don't think I have any context in there, so my second sentence really needs to be contextual about this problem. So the sample data provides evidence that there is a linear relationship between wind speed and electricity production. And so there's my contextual analysis of that problem. So we start out with beta 0. Again, there's nothing leading me to one direction versus the other. So I said not equal. A pretty high t statistic here, right? And really because of that, a really small p-value. So that was the homework that Luke had assigned. So now I'm going to jump to a chi-square problem here, which was I think the end of last week and beginning of this week. So this was in one of my slides, but I'm pretty sure that I had not walked through this one. So let's take a look at this. This is from the 2017 exam. Up here in the upper right-hand corner, you'll see that's a mu is 1.51. So the national average on this problem in 2017 was about 1.5 points out of 4. We don't expect every kid, every student around the world to get every single point on these. So I call that demystifying the exam. I want you to realize that these problems are difficult. I'm not sure I get every single point every single year when I take the AP Stats exam. And so we want you to maximize your scores, but please realize that if the national average is 1.51 and you're consistently getting 2 out of 3 of the 4 potential points, you're actually doing a pretty good job. So I'll try and share that as we do some free response. So let me give you just 20 seconds to read it or so. Maybe think about the graph down here. First, I wasn't sure why the graph was even here, but then it sort of made sense to me. And so anyway, let's go ahead and read the problem, and then we'll go through this one. Okay, so this is again from the 2017 question number 5. The table in the bar chart below summarizes the age at diagnosis in years for a random sample of 207 men and women currently being treated with schizophrenia. So I like random samples, so that's good. I like 207, that feels like a pretty good number. I'd love that to be 2,000, 20,000, 200,000, but I can live with 207. So we have a two-way table here, and it sort of feels like I want to see if there's a relationship between gender and maybe age. So I want to see if there's some relationship between gender and age. I don't know by looking at those numbers quickly. They give us a bar chart down here, and what jumped out at me was this kind of shaded region keeps getting smaller, and the shaded region above here, the dashed, seem to be getting bigger. So I had to think about that for a second and say, what's that trying to tell me? It appears like the percentage of males is going down, the percentage of females perhaps is going up. Still don't know what they want me to do. So do the data provide convincing statistical evidence? Boy, that language there feels almost identical to what I read on the first problem, if not identical, right? Do the data provide convincing statistical evidence of an association between age group and gender and the diagnosis of schizophrenia? So it feels like it's probably going to be a chi-square problem to me. And I just need to think about, which chi-square test is it going to be? So let me just go back to my slides here and we'll take a look and see if we can just go through those 3 chi-square tests again. So here's the chi-square formula. This is the slide I was looking for. So we have to make a decision. Is it a chi-square test for goodness of fit, chi-square test for homogeneity, or chi-square test for independence? Homogeneity and independence, sometimes it's not easy for me to figure out which one it is. Homogeneity compare 2 different populations and I'm comparing 1 variable. Chi-square test for independence, we have 1 population and we want to compare 2 more variables. So after I thought about it for 20 seconds, a minute or so, I was sort of leaning towards chi-square test for independence, right? All these people have come from 1 population and see if there's some relationship between gender and age when you're first diagnosed with schizophrenia. So the first thing I think I want to do is I want to call this a chi-square test for independence. Again, the word association was sort of a little clue as well. That sort of jumped out at me. Some people might call this chi-square test for association. I think we would accept that. I think that sort of feels okay to me. So my null hypothesis, chi-square, we usually just do in words. There's no association between gender and age at first diagnosis. Again, my penmanship is terrible. I apologize. I have the curse of a lefty, and that's just never been good. I never had good penmanship, so I apologize. My alternative, there is an association between gender and age at first diagnosis. For the sake of time, I won't write that, but on the AP exam, please make sure you do that. So I've named my test. Super important. If I name my test, then when I go down to the mathematics component, I don't need to show any formulas. I don't need to memorize any of these formulas. So I always think it's easy to do that. Of course, when I teach it to my students, I make them use the formula. But on the AP exam, anytime exam, you want to use your time effectively. And as long as you have the name of the test, we're not asking that you do any more mathematics. So I need to check my conditions and assumptions. And when I was teaching chi-square, I think we only have 3 that we really need to worry about. It's a non-parametric test, and so in some ways the conditions here are much easier than with means or proportions. So one thing about random selection of my data, well, up here at the stem it said that. So data was randomly selected as stated in the stem of the problem or something to that effect. So that's a good thing. Random is good. I need to worry about my large counts. So I need to make sure that all my expected values are greter than 5. I'm going to go to the calculator in a minute to do that. So right now, I guess I don't know that, but I need to check that. And usually we ask you to write those expected values somewhere on your paper. Sometimes students have a different table of box down here. As long as those are on your paper somewhere, the readership should be able to find that and you'll get credit for that. So let's come back to that one, but I'm pretty sure that we're going to beat that. And then my last one is my 10% condition, my independence. I want my population to be greater than 10 times your sample size. I want my population to be greater than 10 times 207. My population greater than 2070. That's an assumption, I guess. Like I have no way to confirm that. So I'm just going to write, it is reasonable to assume that the population in this county or wherever where these people came from, it's reasonable to assume that the population is greater than 2070. Again, there's no way for me to confirm that. I can't prove that. I can't mathematically do anything other than tell the reader that you're thinking about it. You know that that's important. And again, these tests are not valid unless we've met the proper conditions. So I'm just going to go find my calculator here, and we're going to go ahead and run the test. And we need to check our expected values. So if I was organized early this morning, which I was, I typed in those values. It's a 2x4 table, 2 rows by 4 columns. So that's good. I think I mentioned this the other day. Sorry, I just need my stat button. It almost feels like this is backwards. I'm actually going to go ahead and run my chi-square test. I'm going to get all the math that I need. And I honestly haven't even checked my conditions yet. So it feels like this is backward, but this is just the way the calculator operates. And I don't know if there's any way around that. So I did type all of my observed values from my table, put those in matrix A. The calculator will do the math for me. It will find all of those expected values for me. It's going to put them in matrix B. So I just need to scroll down to calculate. And so I'm going to write these numbers down and then go back to my problem. My chi-squared statistic is 10.883. My p-value or my probability is 0.0123. My degrees of freedom is 3. Let's go back to our problem. And so this is the mechanics or the math component. And if you've labeled the name of the test somewhere, chi-square test for independence, that's the math right there. So we're good. But let's go back and check those expected values, right? I'm pretty sure that they're all greater than 5, but I need to confirm that. I'm going to be writing those numbers down. So back to the calculator, second matrix, want to go to matrix B, and the calculator has automatically put in all of those expected values. And so we can see here that they're all greater than 5. So that's a good thing. That's a good thing. I'll show you where I put those on my paper. So I wrote, it may be really hard to see, but 56.9, 36.2, 17.2, 8.6. I literally wrote all those expected values right next to my observed. They're on my paper. The reader will be looking for those. And if they're there, then we've met all of our conditions. It was a random sample. It is a random sample. Expected values are all greater than 5. See table above. That sometimes helps the reader go find them. We confirmed, or we feel that the population is greater than 2,070. So again, I probably followed up with a sentence. And again, those are my three critical numbers here that I need for what we call the mechanics and math component. The chi-squared statistic is 10.883. My p-value is 0.0123. It's a pretty small p-value. Degrees of freedom is 3. That was what rows minus 1 times columns minus 1. That's where that number came from. And so now I need, I guess, my conclusion, and I'm going to again be somewhat boilerplate here. Since our p-value of 0.0123 is less than our assumed significance level alpha is 0.05, we reject the null hypothesis in favor of the alternative. Again, there's many ways to say that. Hopefully your teacher has gone over and over sort of their preferred way of doing it. So by no means is this the only way to say it. But when we're reading your exams, we're looking for, has the student made some what we call linkage between their p-value and their alpha level? Have they made a decision? In this case, I'm rejecting the null hypothesis in favor of the alternative. But you can see I don't have any context here. So right now, my conclusion is not good enough. I need to somehow contextualize it or make it specific to this problem. This is somewhat boilerplate in my classroom, and I tend to say that a lot over the course of the year. So based upon our evidence, so we've rejected the null, we've gone with the alternative. It appears that there is an association, a relationship between gender and age of diagnosis. So again, we state our p-value, we state our assumed significance level, we make a decision, I rejected the null hypothesis, and then down here in plain old words, it does appear that there is some relationship, an association between gender and age of diagnosis. And I think that's what this bar chart here was trying to tell you. When I thought about that a little bit longer, I said, boy, I can almost see that graphically, right? Like there is some relationship, there is an association going on here because the shaded area was getting smaller and smaller and smaller. So again, hopefully we burned 4 to 4. I burned 4 to 4 here. I hope so. But you can see the national average was 1.51. So this was our hard problem for kids. This wasn't so easy. And so hopefully you're feeling a little bit better about chi-square and inference regression. Of course, neither of those topics is going to be on this year's exam, but Luke and I are going to try and make a point of listing all the things that we're looking for as readers and sort of exam tips. And one of them clearly is if you put the name of the test, you'll notice I nowhere have listed the chi-squared formula. Nor do I need it. I name the test. I can literally just write down those 3 values that I got from my calculator. So hopefully that makes a little bit more sense. I'm going to tackle this problem here. I think I started this the other day. Perhaps I did part A, part B, or something like that. I forget exactly what I did, but this is from the 2006 exam. The national average that year on this problem is 0.46, so that's mu out of 4. So the average student who took the exam that year couldn't get a half of a point out of 4. So this is a hard problem. This is clearly a hard problem. So let me give you a minute or so. Go ahead and read the introduction there, and we'll try and tackle this. And maybe we'll talk about why was this so hard for students? What made this problem excessively hard for students? Again, the average student couldn't earn half a point out of 4. So this was a low scoring problem. Okay, so again, 2006, number 2, a manufacturer of dish detergent believes the height of soap suds and the dishpan depends upon the amount of detergent used. We're just setting the stage. The study of the suds heights for new dish detergent was conducted. So again, it feels like language we've seen before, right? Study, I might circle that or underline it and say, what's going on right now? Is this an experiment? Is this an additional study? Is we have to do an inference test? What's going on here? 7 pans of water were prepared. So I guess my sample size is 7. Well, I would want that to be bigger, but this is the data we have in hand, and so I need to do analysis based upon that. All pans were of the same size and type and contain the same amount of water. So we're trying to keep as many variables the same as possible. So that's a good thing. I felt good about that. The temperature of the water was the same for each pan. Okay, again, we're just trying to control for variables. The amount of dish detergent was assigned at random to each pan, and the amount of detergent was added to the pan. So each one of these 7 pans, I guess, has a different amount of dishwashing detergent or soap water, and the dishpan was agitated for a set amount of time. That makes sense. That's where the suds came from. So far, I think I get it. And the height of the resulting suds was measured. So here's my 7 data points of my 7 pans. The plot of the data in the computer output from fitting a least squares regression line to the data are shown below. So we've done a scatter plot. It looks like my explanatory variable is detergent. My response is height of suds. That sort of makes sense, right? More detergent, higher suds. The data clearly does look linear here, but I would at least want to do a residual plot. And if the decision was important enough, I might even want to do a hypothesis test, what I just did in the last problem there, to see if the relationship between these 2 variables is really linear. I don't know if I have any data to do that, but it appears at least from this scatter plot here that my data does appear to be a linear relationship between my data. Okay, here's my generic computer output. Probably going to need some of that. It probably feels like I'm going to use these 2 numbers here. I was coming up with a confidence interval. I might need that standard error of slope. I think I need that later in the problem. Wait, again, a pretty high t statistic and a pretty low p-value, so probably a similar conclusion, although this problem doesn't ask me to do that. Feels like probably a similar conclusion, but let's do what they asked me to do. So write the equation of a fitted regression line. Define any variables used in this equation. So hopefully at this point, after the last couple of weeks with Luke and I, predicted height. There's my initial starting value, minus 2.69. There's my sample slope, 0.950, dish detergent or something like that. So there's my regression line. I've identified the variables. I think I'm done in part A. It feels like if that was all the work I had on this problem, that I probably wouldn't have gotten more than 0.46. My gut says probably 1 point maybe out of 4. And so it feels like students weren't even able to do that because that mean is just so low. So part A felt pretty good. Like I knew what I was doing. Okay, part B. Note that S equals 1.99. So I guess this here in the computer output. Interpret this value in the context of the study. So S equals 1.99821. I'm pretty convinced that was a standard deviation, right? SSX, something like that. It's actually the standard deviation of the residuals. And sometimes we put a little E there, SE, that would have made it a little bit easier for me. I definitely would have quickly said, oh, that's the standard deviation of the residuals. That little E is a symbol sometimes we use with residuals. It's not there and it isn't in most generic computer outputs, but that little S down here in the corner is what we call the standard deviation of the residuals. So my residuals is what? Actual Y value minus my predicted Y value. And I like to say, well, that's easy to remember, right? A minus P, it's an AP course, so AP always goes first, and it seems to help my kids. My little jingle, so it helps them as opposed to predicted minus actual, it's A minus P, and that's an AP course, or an AP course, so that's what makes sense. The residuals look at least visually very small here. The little residual there, this vertical height, that vertical height right there in red. So the actual Y values for those 3 is less than or lower than the predicted value. And so for these points above, the actual Y value is higher than my predicted. The sum of my residuals is always 0. And so the standard deviation here is a standard deviation of the residuals. And so it says interpret. So this value is a typical amount of variability in the vertical distance for the observed heights the slope size, something like that. So we see that there is variations. Some of these residuals are a little bit smaller. This point feels like it's pretty close to the line, but that number is giving me a rough value of how much these residual heights do vary. That was hard for kids. That's a hard interpretation for kids. That's not easy. When I teach it, I usually put the little SE down here and say to kids, well, that's the residuals. We know that these vertical distances vary, and we just want to get an idea of, well, how much do they vary? So that's all that value represents. And I can see why this national average is so small. Part A felt pretty straightforward, pretty typical. Part B was trickier. This was 14 years ago, and I'm not sure textbooks were as good as they are today, and we probably had less practice with these generic computer outputs. So I can see why that was difficult for students. C, identify and interpret the standard error of the slope. Well, if you're with me the other day, SEB, we were using that number, right? 0.7553. We were using that number to come up with the confidence intervals, right? When we were doing confidence intervals for the true slope, or we were trying to come up with an interval for the true slope. So again, this is a hard interpretation. So that number represents maybe how much we would expect the sample slopes to vary from experiment to experiment. So we do know that these slopes will vary. These sample slopes will vary. If I pick 7 different hands and did this same experiment again, or the same process again, I know that it would vary. And that's really what this number is trying to tell us, is how much would we expect the sample slopes to vary from experiment to experiment. So looking at this value here and seeing how low this was after I did parts B and C, it sort of felt like those were really hard questions for me. And I struggled with both of those the first time I did this problem, part B and C. So this would be considered a really hard problem. Part A, pretty straightforward. Hopefully part B and C maybe feel a little bit better for you guys. So get close to that magic hour, but let me see if I can just walk through this problem real quick, and then we'll call it a day. So for the sake of time, I'll just go ahead and read it. This is from the 2004 exam. Question number 5. A rural county hospital offers several health services. The hospital administrators conducted a poll to determine whether the resident satisfaction with the available services depend upon gender. Okay, so starting to think, is there some relationship between how satisfied you are with the hospital and your gender? I don't know. A random sample of 1,000 adult county residents was selected, so I'm real happy with the random, and I'm real happy with the sample size. The gender of each respondent was recorded, and each was asked whether he or she was satisfied with the services offered by the hospital. The resulting data are shown in the table below. So again, two-way table here. Is there some relationship between your gender and your satisfaction level? So I was kind of leaning towards chi-square, and I then say to myself, is chi-square goodness of fit? No, I'm not comparing these percentages or something to any sort of model. Is a chi-square test for homogeneity? 2 populations, 1 variable. Chi-square test for independence association, 1 population, 2 or more variables. So I was pretty convinced that it was going to be a chi-square test for independence. Some books call it chi-square test for association. I won't go ahead and run the test, but I would do my null and alternative here, right? I would check my 3 conditions. I would go to my calculator. I would type those values in. It's a 2x2 table, I guess. I would check my expected values, all those things. I would get a chi-square statistic. And so I would do the same steps that I had done all the other problems. Let's look at part B here, and then I'll go back to my slides and kind of wind down here. So part A feels like it's pretty standard chi-square test, and want you to go through the 4 steps, right? Null and alternative, check your conditions and assumptions, do your mechanics math, conclusion and context of the problem. Part B felt a little different here, that's good. So is 800 divided by 1,000, so is 0.8, a reasonable estimate for the proportion of all adult county residents who are satisfied with the services offered by this hospital? Explain why or why not. So we have 1,000 people in our study here. 800 are pretty satisfied. So that was my sample, right? So P hat was 0.8. Can I use that to make a forecast for P, the population proportion? And I think the answer is yes. I think we can. And the reason we can do that is because this was a random sample of 1,000 adults in that county. So since it was a random sample, I think I can take my sample results and infer them, use them, estimate my population proportion. And again, without running a test, I would think it's probably around 0.8, but I don't know that exactly. I have to go do a test. But the randomness here was what sold me. I was pretty happy with the sample size as well. So when I put those two together in my brain, it felt like, yeah, I think I can use that sample proportion to go ahead and make an inference prediction, or whatever you want to say, for the population. So let me just go back to my slideshow here. We'll kind of wind down for the day. Boy, time goes really fast here, at least from my perspective. So that was what I did the other day. I guess my sample least squares regression line, that would be my population. We did that with confidence intervals. Luke did this yesterday, my null and alternative. I guess my first problem I did that. I didn't check my conditions because I didn't ask me to, but keep that in mind for inference for regression. We need to think linear, we need to think linear, independent, normal, equal standard deviations, random. So don't forget those conditions, they're super important. We just did that problem, we did that one. Yeah, I think we did all 4 of those. So that was good. Time did well. So hopefully by now you're feeling more comfortable with the chi-square test and inference for regression. Again, this is units 8 and 9 from the course of CED, course and exam description. Those are teacher words. You don't really need to worry about any of those. So what Luke and I did from last Wednesday, the 25th to today, none of these are on. None of these topics will be on this year's modified exam. Hopefully you leave feeling like you got the full course though, and some of the things that we talked about will be helpful for answering any free response question. Should be able to select and correctly use the right chi-square test or construct confidence intervals hypothesis test for the slope of a regression model. We always want to have a clear, concise answer and context, so that should be pretty basic. Your homework for tonight, Luke will post that on his website. So if you have a chance between now and Monday, Luke will be with you Monday, Wednesday, Friday next week. I think you're with me on Tuesday, Thursday. Again, I've had this slide a couple times. I just want to stress how important this is. Your AP exam will be on Friday, May 22nd at 2 p.m. Eastern time. It's going to vary depending upon where you are in the world or the country listening to me. The College Board knows that not all students are going to have access to the internet or device. We don't want that to prevent you from taking this year's AP Stats exam. You've worked hard all year. We hope you're ready. We hope you do real well. College Board is working on solutions to help students get what they need to show their best work. So if you're one of those students, please talk to your administrators, talk to your teachers, and the College Board will bend over backwards to help you get a device or get some connectivity. There's a website for that. So please, if that's a problem, reach out to someone, and College Board will do their best to make sure that you're able to take the exam this year. So again, thanks for watching. And I'm going to wind down here. It's almost a little after 2:45. I guess I keep going in overtime here on Friday afternoon. Sorry, I just get so excited, right? Teaching statistics. Again, I hope you're safe. Hope everyone's healthy. Let's be positive. Let's keep working hard. We have another month of review, Luke and I. So 4 more weeks starting on Monday, which will be review for just this specific this year's AP Stats exam. It'll be Monday, the 22nd. I gave you those 2 websites earlier in the presentation. Much more detail there, and please make sure you go read that, share with your colleagues and your teachers. So thanks for listening. I hope Luke and I have helped with these 2 units that will not be on this year's test. Starting Monday, everything we do will be focused on getting you guys ready for the modified 2020 exam. So have a great weekend. Please be safe, and I'll see you next week. Thanks.
Hello, AP Statistics students from around the country, and welcome to the College Board Virtual Instruction for AP Statistics. My name is Luke Wilcox. I am the AP Statistics teacher at East Kentwood High School. I'll take a quick moment to just give a shout out to my first and second hour AP Statistics classes, as well as Miss Dallas's 3rd and 4th hour AP Statistics classes. I hope you all are doing well, and I hope you all are safe. And listen, we've been doing this College Board YouTube live thing for a couple of weeks now, but today is a big day for 2 big reasons. Okay, reason number 1 is that today, officially, we are going to start AP exam review. No more new content. This is all content that is going to be covered on the AP exam for 2020. So please join me and my colleague Brendan Murphy over the next 4 weeks, Monday through Friday at this time, 2 o'clock, so that we can help prepare you for the AP Statistics exam. Now, reason number 2 why today is a big deal is because I finally get to explain this this ridiculous beard that I'm wearing here. So here's the deal. Back in November, first day of November, I had a clean shaven face, and I told my students that I was going to do no shave November. And at that moment, I told them that I was going to take this beard all the way until the AP exam. So this is my playoff beard. And I will tell you today, officially, the playoffs are starting. Right now is the time when we start to review for the AP exam. We know the date now. May 22nd is the day of the AP exam. So we're going to take this playoff beard all the way to May 22nd. And we're going to make sure that you all are ready to take this AP statistics. So I think we should just jump right into things today. So let me go ahead and just get started here, just to check to make sure that we are all in the right place. You should be an AP statistics student preparing for the AP statistics exam at this point. I've already mentioned that I'm Mr. Luke Wilcox, East Kentwood High School in Kentwood, Michigan. All right, now a couple of basics here, just to make sure that everybody knows. There was some information that came out last week. I just want to make sure everybody's clear. We do know the day of the Super Bowl of the Stanley Cup. What this playoff beard is all about is Friday, May 22nd, 2 to 2:45. Now, for some of you maybe realizing that this is much different than AP statistics exams in the past, which have been 3-hour exams. This is going to be a 45-minute exam. And so let me give you just a couple more details about this here. The first of which is that the AP exam will be taken on a computer or a phone, most likely at your home, unless for some reason school comes back in session, in which case this would be done at school. But most likely it is going to be taken on your phone or on a computer. You'll need a device for this and internet access. Because of the shortened time period, there is only going to be 2 free response questions here, and they've actually predetermined the amount of time that you're allowed to spend on each one of those. So 25 minutes for question number 1, 15 minutes for question number 2. Now you do a quick math there. That does not add up to 45 minutes, and the reason is because you will have, after the question number 1, you will have 5 minutes to upload that before you start question number 2. So you are either going to be typing up your responses or writing them on a piece of paper. I would anticipate that most AP statistics students are going to want to be writing this down on paper. You'll have 5 minutes to take a picture of that and upload it before you start question number 2, and then at the end of question number 2, you'll have another 5 minutes to upload your answer to question number 2. Next important thing here is that the AP exam is not going to cover everything that is typically covered on an AP statistics exam, because it's most likely that your teacher did not get through the entire course before you had to leave school. So it is only going to cover units 1 through 7, which means the last 2 units, chi-square and regression inference, will not be covered on this year's AP exam for 2020. Last note here, very important, that the College Board has gone through great lengths to make sure that we can maintain the integrity of this exam. So please do not attempt to cheat, collaborate in any way with your friends or colleagues. Please maintain the integrity of this exam. Now, a couple other basics here for you, and if you've been with us the last couple of weeks, you know these details, but we are meeting on a daily basis, 2 o'clock Eastern Standard Time. All of these videos, though, are available afterwards, after the live feed. And let me talk about what this AP exam review is going to look like. That we're starting today, right, April 6th, and this week we're going to be covering units 6 and 7, and then after that, the following 3 weeks, we're going to go back and fill in units 1 through 5. So some of you may wonder, why didn't we just do it in order? And here's the reason. There are a lot of classrooms around the country that did not get to units 6 and 7 in their classroom, and we want to make sure that students have that instruction. So we're just starting with that. Now, those 2 units are covered on the AP exam, so technically this is part of our AP exam review. And then the following 3 weeks, we will just go back and fill in those units 1 through 5. So by the end of this whole YouTube live thing, you will have been taken through all of the content that will be covered on the 2020 AP statistics exam, which we know now happens on May 22nd. Now, just so you know, any of the resources that you see in these videos, the lesson, the homework problem, those are all available. You can download them, you can print them at statsmedic.com/YouTube. There should be a link down below for you to be able to click into that. And then final note here, if you are a student or you know a student who does not have a device to be able to take the AP exam or does not have internet access, this is the website that you can go to request technology. The College Board is very committed to making sure that every student has access to being able to take the AP exam. Okay, so we're going to jump back to the homework problem that Mr. Murphy assigned you last class period, and this is a wonderful lead-in into what we're going to talk about today, which is confidence interval for report. So let's go ahead and jump right in here. It says a researcher has conducted a survey using a simple random sample of 50 registered voters to create a confidence interval to estimate the proportion of registered voters favoring the election of a certain candidate for mayor. Assume that the sample proportion does not change. Which of the following best describes the anticipated effect on the width of the confidence interval if the researchers were to survey a random sample of 200 rather than 50 registered voters? Okay, so here's the first thing to recognize. We started out with 50 as a sample size, and we are moving to 200. So very clearly, the sample size is increasing. And more specifically, I can see that the sample size is being multiplied by 4. So the question is, how is that going to affect the width of the confidence interval? Now, in order to answer that, we have to know something about confidence intervals. So I'm going to start with what I call the general formula for any confidence interval, which is the point estimate plus or minus the margin of error. Now, that's the general formula. The specific formula, if you're trying to estimate a proportion, looks like this. P hat is your point estimate. Your margin of error has 2 parts: the critical value Z star, and then the standard error of the statistic, which in this case is P hat 1 minus P hat all over N. And so let's think about what happens as the sample size increases, right? So if we have N increasing, right, N is going up. Well, you'll notice that N is in the denominator of that formula. And if the denominator is getting bigger, that means that the whole thing is going to be getting smaller. So that means that the margin of error is going to get smaller. And if the margin of error gets smaller, you're going to have a narrower confidence interval. So we know right away that this confidence interval is going to be narrower rather than wider. And so I think I can get rid of answer choice C says the same width, answer choice D says twice the width, and answer choice E says 4 times the width. So I can immediately eliminate those 3 answer choices. And we're left with only 2 possible choices now. A, which says that your interval is going to be 1/4 of what it started out at, and B, which says that it's going to be 1/2. Now, by instinct, you might say, well, look, we're multiplying by 4 and it's in the denominator, then the width of the interval should be 1/4. And you might think that answer choice A looks kind of appealing. But here's the thing. Look at the equation. If I take N and I multiply it by 4, right? So I'm having a 4 now in the denominator. The other way that I could write this, instead of putting a 4 in the denominator, I could put a 1/4 out in front. And you will notice that this is underneath the square root. So when you take the square root of 1/4, you are going to get 1/2. And you will now have 1/2 times the old standard error, right? This is exactly what it was before. Everything else remains the same. And so what this is telling you is that your margin of error is going to be 1/2 of what started out at, which means that it's going to be narrower by a factor of 1/2. And so sure enough, answer choice D is the correct answer. So hopefully you did okay on that. I think we are now ready to jump into the new lesson for today. So the way that I typically go about this is I like to give you an overview just so that you know where we're headed in this particular lesson. And we've got 2 learning targets for today, both of which are about confidence intervals. So the first one says construct and interpret a confidence interval for a population proportion. Okay, that's one proportion. Whereas learning target number 2 says construct and interpret a confidence interval for a difference of 2 population proportion. Okay, so the first learning target is going to be 1 sample inference. The second learning target is going to be 2 sample inference, where we're looking for the difference in the population proportion. And you'll notice that for each one of these, we're going to use the familiar 4-step process in order to write up our solution. And I will do my best to try and point out some very key AP exam tips that I've learned over the years of grading AP exam. All right, so let's jump right into the activity for today. And here's the ultimate question that we're trying to answer in today's activity. Do you want to take the AP exam? We are going to make a little bit of comparison between AP statistics students and AP calculus students here. So here's what it says. I'm just starting out right at the top here. A random sample of 300 AP statistics students revealed that 92% of them wanted to take the AP exam. All right, let me pause right there. That 92% comes from my sample, and it is a proportion. So I'm going to use the correct notation here, and I'm going to call it P hat for sample proportion. And I'm going to write it as a proportion rather than as a percent. So we do have a sample proportion right now. Construct and interpret a 95% confidence interval for the true proportion of all AP statistics students who want to take the AP exam. All right, so you'll see our state plan to conclude, and I've given us some hints about what needs to be included in each step. So let's start with the state here, and we need to first identify what is the parameter for the population that we're trying to estimate here with our confidence interval. Well, we know our statistic is P hat. The parameter that we're trying to estimate is just P. No hat on this one, just P, which is going to represent the true proportion of all AP stat students who want to take the AP exam. Now, very important here, there's a couple of words that I've used here to make it very clear the parameter is referring to the population of all AP stat students and not this sample of 300. And the words I'm referring to are true and all, just to make that crystal clear that we're referring to the population, trying to make inference about population. All right, now our confidence level here is given to us in the problem, and probably the most common confidence level that we're going to see is 95%. All right, we can move to our plan now. First, to identify the name of the procedure. So first thing I want to reference is the fact that we only have one proportion here because this is based on one sample. Because we are estimating proportions, we're going to be using normal distributions, which means this will be a z interval. And then I'd like to make it very clear what it is that I'm trying to estimate here, which is a single proportion p. So we are now ready to check our conditions, and there are three of them that we would like to check here, starting with the random condition here. And we want to check that we have in fact a random sample. And this is where I like to actually just steal the words right from the question here. And the question says that we have a random sample of 300 AB stat students. So you'll notice I'm putting these in quotes just to make it very clear that I have just stolen those words right from the stem of the question. Now we should check in on why we are checking these conditions here. The random condition says that we have a random sample, and the reason why that's important is because if it is in fact a random sample, it should be representative of the population, and therefore we can generalize our results to the whole population. So let's say that condition there is satisfied. Now the next condition, the 10% condition, is one that we have to check only when we are sampling without replacement. Well, it's most likely that this sample was a sample without replacement. They probably didn't take one student out, sample them, and then put them back in the pool so that they could get selected again. So I do think that we need to check the 10% condition here, which is to say that the sample size 300 is less than or equal to 10% of the whole population, and the whole population here is all AP Stat students. And we know that there are over 200,000 students that take the AP Stats exam every year, so definitely we are safe with the 10% condition. And the reason why that's important is that's telling us that sampling without replacement is okay here. We don't have to worry about the independence condition not being satisfied because we're sampling too much of the population. All right, we are ready for our third condition, which I call the large counts condition. You may see it as the normal condition depending on your textbook. And this is the one that says that n times p and n times 1 minus p are both greater than or equal to 10. Except one small thing that we need to make sure of here. N times p, well, p is the true proportion of all AP Stat students who want to take the exam. We don't know the true proportion. In fact, that's the whole reason we're doing a confidence interval, is to try to estimate that. So very important here. This should be a p hat because we're going to use our sample proportion because we don't know what the population proportion. So let me plug in some values. 300 is our sample size. The sample proportion is 92%, 0.92. That's going to give me 276. And then 300 times 1 minus p is 0.08. That's going to be 0.4. Now, what we're really getting there is the number of successes, 276 students who want to take the exam, and the number of failures, 24 that do not. And we need to check that both of them are greater than or equal to 10. And sure enough, they are. Now, let's check in with why we need to check the large count condition. And the reason is because we want to be able to say that the sampling distribution of p hat is approximately normal so that we can use a z star critical value when we get to the calculation. So with our three conditions satisfied, we are ready to move on to the actual work of calculating the confidence interval here. So we're going to start with the general formula, which I actually showed you on the homework from the previous day. Point estimate plus or minus margin of error. Now, there is another general formula that's given to you on the formula sheet for the AP exam. It looks like this: statistic plus or minus. Now, they're going to break the margin of error down into its two components, which is the critical value multiplied by the standard error of the statistic. Now, we would like to be able to make this a specific formula for when you are trying to estimate a single proportion. All right, so let's be careful of our notation here. The statistic is the proportion based on the sample, which is our p hat, plus or minus our critical value. We know is going to be a z star critical value, which comes from a normal distribution. And then the formula for the standard error of the statistic here is the square root of p hat 1 minus p hat multiplied by n. And we are finally ready to plug in some numbers for this thing here. We know our sample proportion p hat was 0.92. Now, we need a z star value, the critical value, which tells you how many standard deviations or how many standard errors away from the mean we need to go in order to get that 95% confidence. And for this, we are going to need either table A or table B, which is given to you on your formula sheet. I'm going to start a shortcut a little bit here and use table B, which is for t distribution. But if you scroll all the way down to the bottom, where you have degrees of freedom infinity here, that is actually a normal distribution because the t distribution approaches a normal distribution. And what we have down there in that last row is the z star critical value. And sure enough, 95%. I'm actually really hoping that you already know this one because you've seen it so much. Is 1.960. So I'm just going to go ahead and put that in for my z star value. And then my standard error is the square root of 0.92 times 0.08 all divided by the sample size 300. Now I've already done a little bit of the calculator work here. So 0.92 plus or minus, and we end up with our margin of error 0.031, which will allow us to write our final confidence interval. I'm going to put this in parentheses here as 0.889 up to 0.951. And we are ready to make a conclusion to interpret this confidence interval. And there's a pretty standard interpretation that we're going to use anytime we're interpreting or making a conclusion for a confidence interval. And here's how it's going to start. We are 95% confident that the interval from, and then we need to give our interval here, 0.889 to 0.951, captures the true, and now here's the thing, we need to write out what our parameter is here, and I've already identified it up here. So essentially I'm just taking that word for word, which by the way, just came from the stem of the question. So a little AP exam tip here is if you just use the words from the question, you're not likely to make a mistake with that. So let's just finish this one off with the true proportion of all AP Stat students who want to take the exam. Now, a couple of things I want to highlight here in the conclusion. One is to make sure that we are using the word confident here. You're not saying 95% chance, you're not saying 95% probability. And then the other thing is to make clear that we're trying to estimate something about the population. So once again, we're using true and all, and we've made it very clear that the thing we're trying to estimate is a proportion. And then you'll notice at the very end of this, there is some concept there. So we're putting the concept of the question. Okay. So last thing I want to mention here before we move on, I looked back through a couple of rubrics in the past couple of years, and I want to let you know specifically what needs to be included on. Okay. The first thing is to identify the correct procedure. And there are two ways that you can do this, identifying the correct procedure. The easiest way is to just identify the procedure. One sample z interval for p. But you can also get credit down here where you've written the formula for that. That also gives you credit for identifying the correct procedure. Don't have to have both. Have to have one out of the two. Okay. The next thing that you're going to want to make sure you do is to check condition. If you look at rubrics from years past, you're probably going to see this one, the random condition, and this one, the large counts condition, but you might not see the 10% condition until last year. 2019 was the first time that we saw the 10% condition. I think in line with the new College Board CED. This is something you can expect to see on the rubric. So if you're sampling without replacement, make sure you're checking the 10% condition. And then the next thing is that you have the correct interval. And honestly, this right here is really the thing that the graders will be looking for, is that you have the correct interval. All of this other work here, I'm going to say is not required, but I really like to see it because a lot of times students can catch their mistakes if they're writing out all their work. But according to the rubric, the interval is the thing that they're going to be looking for. And then of course, they're going to look at your conclusion and make sure you have a good conclusion there, which includes the word confident, includes inference about the population, is very clear that you're trying to estimate a proportion, and then somehow includes context. Now, I do want to check to make sure that you can do this on the calculator. I love using the calculator as a way to check my final answer here. So let's go ahead and get out your calculators if you have one, or you can just follow along with what I'm going to show you here. No need to have a calculator in front of you. Fairly straightforward in terms of using the calculator for this. So you go to stat and you go over to test, and you start scrolling down, and we definitely want an interval here. We want an interval with one proportion in it. So there it is. Choice A, the one proportion z interval. So I'm going to hit enter on that. Now, what the calculator wants here is the number of successes and the number of trial. And we have, remember, 276 successes out of 300, and that number of successes always has to be an integer. Right? You can't have a decimal here. So 276 out of 300. Confidence level is already set at 95% for me. So I go ahead and hit calculate, and sure enough, the interval that the calculator is giving us here is exactly the one that we got by doing it by hand within a rounding there. So we had 0.889 to 0.951. That's a great way to check your work there. Now that takes care of the one sample confidence intervals for a proportion. The next thing that we need to take a look at is a two sample where we're trying to find the difference between two proportions. So let's jump back into the activity here. And I'm going to add one more layer to the context that we already started with here. So here's what it says. A random sample of 380 stat students revealed that 92% of them wanted to take the AP exam. Okay, this is not anything new. This was on the previous page. Once again, I have a p-hat of 0.92 for my AP statistic students. But let's continue on. A separate random sample of 208 calculus students revealed that 89% of them wanted to take the AP exam. Well, now we've got another sample here and another proportion. So another p-hat value, which is 0.89. Now to distinguish those two proportions, I'm going to call this first one P1 and the second one P2. And the question says, construct and interpret a 90% confidence interval for the true difference of proportions of all AP stat students and all AP calc students who want to take the AP exam. So what we're actually interested in here is the difference between the two proportions. So if we look at our sample proportions, 92% for AP stats, 89% for AP calc, we have a difference of proportions of 0.03 based on these two samples. Now the parameter for the population that we're trying to estimate here now is the true difference in proportion. So this is going to be P1 minus P2, which I'm going to define as the true difference of proportions of all AP Stats and AP Calc students who want to take the AP exam. Now, I want to make it very clear right here the order with which I'm subtracting these two, because you could do statistics minus calculus or the other way around. And the way that we're setting this up is we are taking the AP Stats proportion and we are subtracting the AP Calc proportion. I'm just going to make that very clear here in my parameter. Now, the confidence level is given to you in the problem at 90%. All right, we are ready to name the procedure, which will sound almost like the one we just did, except that now we have two samples rather than one. Now, because we are estimating proportions, it is still a Z interval because we're using a normal distribution. And the parameter that we're trying to estimate this time is the true difference of proportions P1 minus P2. Now, you're going to notice here that the conditions are going to look strikingly similar to the confidence interval that we just did, random 10% and large counts. The difference here is that now we're going to have twice as much work to do because we now have two samples in two populations rather than one. So, random condition, we need random samples of each one of the populations. And also very important here, those two random samples must be independent of each other. And I'll explain why when we get down to the formula for standard error. But we need independent random samples of, and we had 300 AP Stat students and 200 AP Calc students. So we do have two random samples, they are independent. We can say that condition is satisfied, which means we can now generalize to the population. Now, 10% condition, the sample size is less than 10% of the population for the AP Stat student, which we've already checked this. Certainly that's true. But we also want to check that the sample of AP Calc students is less than 10% of the population of all AP Calc students. And certainly both of those are going to be true, which means that sampling without replacement is going to be okay here. Large counts condition, well, we already did the large counts for the AP Stat student. Remember, we got our counts as 276 successes and 24 failures. But now we need to check this also for the AP Calculus students. So n times p hat here, 0.89, 178 successes for calculus, and number of failures is going to be 22. And all of those counts are greater than or equal to 10, which means that our large counts condition is satisfied. And remember, that means that the sampling distribution is going to be approximately normal. And we can use a Z star for a critical value. Okay, let's move ahead to the general formula, which is going to look exactly the same as it did on the last interval point estimate plus or minus margin of error. But then we have the other version of that general formula, which is the one that we get from the AP exam, which says the statistic plus or minus the critical value multiplied by the standard error of the statistic. Now, a little bit more to the formula this time because we now have the difference between two proportions. So the statistic this time is the difference between the two sample proportions, P1 hat minus P2 hat. The critical value still have a normal distribution, which is Z star. Now, the standard error of the statistic is this big long formula that is available on your formula sheet here, which says P1 hat 1 minus P1 hat all over N1 plus P2 hat 1 minus P2 hat all over N2. And what we're really doing here is we're adding the two variances together and then square rooting to turn it back into the standard deviation, which we are allowed to do because we have independent random samples. So let's put some numbers in here. P1 hat 0.92, P2 hat 0.89 plus or minus. Now I need a Z star value for a 90% confidence interval rather than a 95%. So let me see here. 90% is my 1.645. So 1.645 is my Z star. I got to plug in some numbers here. 0.92 times 0.08 all over 300 plus 0.89 times 0.11 all divided by 200. So a little bit of calculator work here. I've got our answer. 0.03 was the difference in sample proportion, and the margin of error is 0.045. And so that is going to give us a final answer over here of negative 0.015 up to 0.075 as our final answer for the confidence interval. And we are ready to make a conclusion. So we know the general format of this. It's going to say we are 90% confident that the interval from, and then here's our interval, negative 0.015 to 0.075 captures the, now the thing that we want to capture, remember, is the parameter, which really just comes from the sum of the problem word for word. I'm going to copy that down here. The true difference of proportions of all AP Stats and AP Calc students who want to take the AP exam. And just to highlight a couple of things to make sure that you have them, we're definitely using the word confident there. We are referring to the population by using true and all. We're making it clear that we are trying to estimate the difference of proportion, and we are also including context of the problem there. Now, before we move on here, I just want to make a quick point. A question has come up about what happens if you switch the order of your subtraction. And so maybe instead of doing AP Stats minus AP Calc, you did AP Calc minus AP Stats. This is certainly okay, but it's going to change a couple of things here. When you look down at the work, this part right here is going to be switched around because you're switching the order, which means that this 0.03 is actually going to be a negative 0.03. And what you're going to end up with for your interval here is negative 0.075 up to positive 0.015, which is really telling you exactly the same thing as the interval above it. So either one of those is correct, as long as up here you make sure you identify the order with which you are subtracting. All right, final question here. Based on the confidence interval, do we have convincing evidence that there is a difference in proportion of all AP Stat students and all AP Calc students who want to take the AP exam? Well, if we look at this interval, which goes from negative values up to positive values, those are all of our plausible values for the difference of proportion. Some negative, some positive, which means that 0 is one of the plausible values. So the answer here is no, because 0 is contained in the 90% confidence interval. It's plausible that there's no difference, right? It is plausible there is no difference in the proportion. So to wrap this up, we do not have convincing evidence of a difference of proportion who want to take the AP exam. Okay, and I would like to show you this one on the calculator as well, just so that you can see how you can check your work. So if you grab your calculator, or if you just follow along with what I have here, I want to show you a 2 proportion Z interval. So you're going to have to go back to stat, go over to test, scroll down. There's our 1 prop Z in, but we want the 2 prop Z in. So let's go ahead and hit enter there. And once again, we need the number of successes and the number of trials. So we know for AP Stats it was 276 out of 300, and for AP Calc it was 178 out of 200. And we already have to change our confidence level to 0.90 this time. We want a 90% confidence interval, and we hit calculate. And sure enough, without rounding, we got by hand negative 0.015 and 0.075, which matches exactly with what we see on the calculator here. So now that you have seen both types of confidence intervals for 1 sample and 2 sample, I'd like to try and just go back to those 2 learning targets from the beginning of the lesson and make sure that we have everything that we need from this lesson to wrap up. So we're going to do that on the last page here, where it shows the important idea. So I'm going to do this just by learning target. And number 2, the first learning target, LT number 1, was for the 1 sample Z interval for a single proportion P. I'm just going to split this right in half here. And learning target number 2 was for the 2 sample Z interval for the difference of proportions P1 minus P2. And I'd just like to remind you of a couple of important differences between these 2 confidence intervals. So let's start with the parameter, the thing that we're trying to estimate from the whole population. Well, for a 1 sample Z interval, it is a single proportion that we're trying to estimate. So we would say the true proportion of, and then we'd have to put some sort of context into the problem, but it is just 1 proportion, a single proportion. Whereas for the 2 sample Z interval, we're trying to estimate the difference between population proportions, which I would identify as the true difference of proportions, and then some sort of context of the problem. Okay, next, let's make a quick list here of the conditions that must be checked for each one of these intervals. For a 1 sample, there are up to 3 conditions that would need to be checked: the random condition, the 10% condition if we're sampling without replacement, and the large counts condition. Now, when we move over to the 2 sample stuff, you're gonna have the same 3 conditions here, but we need to be a little bit careful about this here. Okay, first of all, you have to realize that you're gonna have to check all 3 of those conditions for now 2 samples from 2 populations. So I'm gonna just put a little note here that this really have twice the amount of work to do, right? And the other thing I want to mention here is that for the random condition, if you have random samples, you do want to make sure that you say that there are independent random samples. And the other possibility here too is that you could have an experiment that utilizes random assignment, which would satisfy that same condition of the random condition. Okay, the last thing I want to make sure that we capture here is this, what I call the specific formula, because they are a little bit different from the one interval to the next interval. So for 1 sample, we have our sample proportion, that's our point estimate, plus or minus the margin of error, which is the Z star critical value, times the standard error, which is P hat 1 minus P hat all over N. Now for the 2 sample stuff, you're going to have the difference of sample proportions as your point estimate, plus or minus the Z star critical value, and then this formula for standard error is a little bit bigger calculator here. P1 hat, 1 minus P1 hat all over N1 plus P2 hat, 1 minus P2 hat all over N2. So there is a check understanding problem. This will be your homework problem, one homework problem that you'll have to have done before Mr. Murphy starts class tomorrow at 2 o'clock. I'm super grateful that you all have checked in with me today. I hope that you're going to stick around for the entire AP exam review. Mr. Murphy and I have been working like crazy to make sure that this is going to be valuable for you. If you found this video valuable, please give me a thumbs up, click a thumbs up there for me. Give me some feedback, and I sure hope that you're going to join Mr. Murphy tomorrow, and then I will be back on Wednesday. Have a great night.
Good afternoon, AP Stats kids. It's Tuesday, April 7th. Good to see you guys again. I hope you were with Luke yesterday, and as of yesterday, we are now reviewing topics that could be on this year's 2020 modified exam. I hate to say will be because Luke and I have no idea what's on this year's exam, but as of yesterday, from now until Friday, May 1st, we are going to be covering topics that are in the revised curriculum, in the revised exam, and so hopefully these sessions are laser focused on again what you guys could see on this year's exam. Again, I have no idea, no inside information what's on this year's exam, so Luke and I tried to pick topics that we felt were the major topics of themes of the course. So again, welcome back. Tuesday afternoon is our intro slide like you've seen before. Again, my name is Brendan Murphy. I teach at John Baptist Memorial High School in Bangor, Maine. I was just talking to an old friend this morning who emailed me. He's an AP Stats teacher in Florida. He's an awesome teacher. He and I go back about 20 years ago, and as soon as he heard me open my mouth, he knew it was the same person. So I have a Boston accent, born and raised. I've lived in Maine for the last 20 or so years, and so it's probably a combo of Boston Maine accent. So if I talk funny, I apologize. I hope you guys can understand what I say. Luke is our other presenter. Luke and I are good friends. We work together for years, and he does an awesome job. I actually like to sit and listen to his sessions as well. So welcome back. Here's your homework that he gave last night, and I'm just going to zip ahead to a slide and then come back to this problem, and I'll explain why. So anytime when I start teaching inference to my own students at John Baptist, what students I think struggle with perhaps is what we call picking the right test. We teach them all these different confidence interval tests, hypothesis tests, and my students always say, I have a hard time, Mr. Murphy, figuring out what test I should use and then finding it on the calculator. And so I came up with these 4 questions, and every time we do an inference problem, literally for 2 or 3 months in a row, after we read the problem, I'll call in a student and say, let's answer these 4 questions and see if these 4 questions help us, 1, identify the correct test, and 2, perhaps finding the right test on the calculator, all of which we'll practice today. So the first question is, does this problem feel like a confidence interval or a hypothesis test? And sometimes the wording is very easy in the problem, and sometimes it isn't quite so easy to figure out exactly what they want. Other teachers may frame it in a different way for confidence interval, find some values or something like that, or for hypothesis test. Is there evidence that this is stronger than that, or yes, no? So lots of different ways to do that. But my first gut reaction is, is this problem going to be a confidence interval or a hypothesis test? My second question is, do we have 1 sample or 2 samples? So that's going to be important. Have we just 1 set of data or 2 different sets of data that we need to analyze or compare? Third question, are we dealing with proportions or means? And so I will always say, we got to be on the right highway, guys. Do we want to be on the proportions highway or do we want to be on the means highway? We want to switch highways here in the problem. And then finally, do we need to read a Z table or T table? Or again, you could clearly go to your calculator and find the right values or whatever. But some students like to read tables. I think last week I said that I was a little old school perhaps, and I still teach reading a table. But if you're good to the calculator, good using a calculator, that's okay too. So again, if we can answer these 4 questions correctly, it helps them to quote unquote name the test, and I'll model that later today. Perhaps get into the problem, and again, hopefully we solve it correctly. So I'm just going to go back to Luke's homework problem. I'll give you 20 seconds to sort of read the problem, and then we'll dive into it. So I think this is what he was doing yesterday: confidence intervals with 1 sample or 2 samples with questions. So researchers are studying the distribution of subscribers to a certain streaming service in different populations. Just setting the table, I guess. From a random sample of 200 people in city C, 34 were found to subscribe to the streaming service. From a random sample of 200 people in city K, 54 were found to subscribe to the streaming service. So there's some numbers, so it feels like 2 samples to me, but let's keep reading. So all the conditions for inference are met. So that's important. This is a multiple choice, and again, we can't run any of these tests. They have no validity unless the conditions have been met. So in a multiple choice, many times you'll see that. Which of the following is a 90% confidence interval for the difference in population proportions? City C minus city K who subscribe to the streaming service. Just a little side note, we've been reading the AP Stats exam in Kansas City for the last, 8, 10, 12 years. When I read that, I kept reading Kansas City, although there's no Kansas City clearly at all. So here goes with my 4 questions. I would say to my students, does this feel like a confidence interval or hypothesis test? And clearly it's a confidence interval, so that feels easy for my students. Do we have 1 or 2 samples? And students might read it again, but it feels like we have 2 different samples, Mr. Murphy, 1 from city C and 1 from city K. My next question is, are we dealing with proportions or means? Which we get on the right highway. So what highway do we get on? And we want to get on the proportions highway. It feels like, right, we have 34 out of 200 or 54 out of 200. And then I might say to students, if we need to, are we going to go read a Z table or a T table? And so hopefully they would say Z table. And by naming by answering those 4 questions, hopefully they quote unquote named the test. And so here's the same problem. And so it feels like I was doing a confidence interval. We agreed that we had 2 samples. We were dealing with proportions, and I'm going to read a Z table. And so that's the name of the test. Now there's lots of other ways to correctly name that test. That's my way of doing it. I do try and stay away from the calculator speak of the problem. I just don't like it. It feels like that's not the name of the test. That's what Texas Instruments calling it, but that's not what I want to call it. So I don't use calculator speak kind of at this point here. And so I did a little math down here. P hat for city C was 34 over 200 to 0.17. P hat for city K was 54 over 200 to 0.27. And so unfortunately, I cannot eliminate any problems because all of those have the correct difference of the 2 cities. And again, the problem said city C minus city K. They did tell me 90% confidence. So if I go to my calculator, I can probably get that critical Z value, right, that I need. So let's clear this off. Second bars, let's try that. Inverse norm. Now be careful here. I think we talked about this last week, and I'm sure Luke did as well. For 90% confidence interval, my area is actually 0.95. It's the 90% in the middle, and adding 5 for the lower tail. And so my critical Z value is 1.645. You maybe have memorized that, but just be careful with that. It's really easy to type in inverse norm 0.90. It's really easy to do that. And so once I got that critical Z value, I think I was able to cross out a couple of my answers here, right? Because I'm looking for the 1.645 rounded. So I felt like I was pretty quickly able to get rid of those 2 problems. I did write down the formula for a confidence interval with 2 samples with proportions, P hat 1 minus P hat 2, plus or minus critical Z, and the square root of P hat 1 times 1 minus P hat 1 over N1 plus P hat 2, 1 minus P hat 2 over N2. And that formula probably isn't given to you on the AP Stats exam. You probably won't need to ever write the formula, especially on free response if we've named the test. But as a math teacher, it's not that hard for me to memorize that. I've been teaching the course for a good 20 years or so, but we don't necessarily expect you to memorize that. But you can see up here that the format of all of those is basically the same. So I just had to plug in some numbers down here. And so there was my 2 P hat 1 minus P hat 2, and there's my 1.65 again rounded. And so I did P hat 1.17 times 1 minus P hat 1, 0.83 over 200, and did the same for my second sample. And when I looked above, I actually didn't see that answer. And so at first I thought, like, I think I'm doing it right. Like, I don't know why, what's wrong here. And so clearly wasn't A based upon that. And so I was really down between C and E. And I had to think for a second. And then I said, well, going back to my formula here, down the bottom here, I guess we have the same denominators, right? And so I just kind of get rid of that plus sign here, keep that plus sign. I just have a common denominator of 200. And so that left me with answer E, which we hope is the correct answer. So that's a nice little problem that Luke gave you guys for homework. Again, I was using process of of eliminations to my benefit there. I was trying to get rid of answers that didn't make sense, and literally by finding the critical z value, I was able to, I think, get rid of two different answers. So thanks no problem for Luke last night. Hopefully you guys were able to perhaps take a look at that, or maybe make some more sense right now. Again, I think I showed you guys these two websites last week. As the College Board is releasing more and more information about this year's exam, when, what time, all of those things, these two websites I think will be super helpful to you and your teachers. So please feel free to share with your teachers. If they're not going to these websites, it will help them figure out exactly what's on this year's modified exam, and therefore help you guys do well on the exam this year. And so I'm going to talk about today hypothesis tests for both one sample and two samples with proportions. So the tested statistic for population proportion is z equals p hat minus p sub naught. All of this square root of p sub naught times 1 minus p sub naught over n. So that's the formula we're going to use for one samples. And I took this right off the what we call the CED course and exam description, probably more for teachers than you guys. But little clarifying statement here, which I thought I just wanted to read to you guys. The formulas for many of these test statistics do not appear explicitly on the AP Stats formula sheet during your AP exam. However, don't let that bother you. These formulas do not need to be memorized. You can probably do all of these problems without even having to write down the generic formula, as long as you name the test. And they can be structured. We can put those together pretty easily by having a rough idea of what we're trying to do. And of course, the relevant standard error formulas are provided for you. So that sometimes it's the hardest for my kids. And there's a subtle nuance probably Luke talked about yesterday when we actually do two sample hypothesis tests. So here's the formula for two sample hypothesis tests with proportions. Again, we have p hat 1 minus p hat 2 minus 0. I'll explain where that 0 comes from when we walk through a problem. What's a little different here is the denominator, the standard error. I call it p hat combined, and I'll walk through the math of where this comes from and why is this different here with two samples. That's not probably what the formula you used yesterday with Luke if you did a two sample confidence interval with proportion. So there's a subtle but important difference here, and I'll explain why we have a p hat combined. So some books call it pooling. I think I like combining better. That's just maybe my preferences. So p hat combined is we're taking a look at both of our samples. Okay, so I think I went through this again. Each time we do a problem, I'm going to try to do at least a couple, 2 or 3 later in the presentation. I like to ask my students these 4 questions, and they get pretty used to them. And if they can answer those 4 questions correctly, hopefully they've one named the test, and 2 are kind of heading down the right path to solving it. Okay, so here's a $64,000 question. Like, why do we need to calculate this p hat combined, and what does it really mean? Like where does it come from, and what's its relevance? So I have sort of a hypothetical here. We're going to come up with some numbers that are pretty easy. So if I decided that I need to do a 2 sample hypothesis test with proportions, my null hypothesis is probably p1 equal p2, and of course I would want to identify those parameters either in words or in symbols. So we think that the 2 population proportions are the same. That's the claim that I'm making, and that's my null hypothesis. And of course my alternative could be any one of my 3 options. They're not equal, greater than, or less than, and that really isn't identifying what the p hat combined is. But I'll try and tackle that and show you why we come up with it. So let's say p hat 1 is 20 over 50, or 0.40. So my first sample from some population is 0.40. My second sample, I try to pick relatively easy numbers here, 30 over 60, 0.50. So I really know nothing about my population parameters at this point. I've taken 2 smaller samples. First sample was 20 over 50 or 40%. The second sample was 30 over 60 or 50%. But again, what's the first thing I wrote down on my paper was, well, those 2 population proportions. The problem is I don't know what this is. I don't know what that is. Of course, whatever they are, I'm saying they're equal. So what we do is we take our 2 samples. And we want to combine them. So my total successes would be the 20 over 30. My 2 sample size would be 50 over 60. So I get 50 over 110 or 0.454. And so I think that's sort of my best guess as to what that number is and or what that number is, where they're both the same, based upon my 2 samples. And again, I don't actually know what that is or what that is, but I've made the claim that they're the same. The only information I have is my 2 small samples here. So I kind of combine those to come up with what I think is perhaps my best guess estimate as to what either one of those 2 numbers are. Now, the first question my students ask is, Mr. Murphy, why isn't it just 0.45? Why isn't it right in the middle of those? I understand that you have 2 samples and you're trying to come up with what you think is the best number here, Mr. Murphy, but why isn't it right in the middle? And the reason is those 2 sample sizes are not the same. And many times they won't be the same. And so it's, I kind of call it a weighted average. Perhaps I don't know if that's 100% correct, but sort of weighted average based upon the 2 different sample sizes. How's that? So I think one of the problems that I do today has these 2 the same, and another one has those different. And so that's what this p hat combined means, or p hat c means. We've taken 2 samples. We actually know nothing about the 2 population parameters, although we're claiming my knowledge that they're the same. And that's all I did here was combine those 2, the 20 plus 30 or the 50 plus 60. So hopefully that helps you a little bit as to where that formula comes from and why we need to use that. So let's go look at some problems here. I found a couple of free responses that we can take a look at. So the first one's an oldie, but it's a goodie. So this is from 1998, which was our second year of business. It was the second year of our AP Stats exam. And I think I'm only going to do part A here. Is that Boston accent, right? Part A. Part B we'll talk about real quick, but I wanted to do a 1 sample test. So let me give you a minute or so to read that, and then I'll ask my 4 questions again, right? That gets us into the problem. Hopefully helps us name the test and head down the right path of trying to solve it correctly. So go ahead and read the problem if you want and see if you can figure out what type of test we're going to need to do. And one of our review sessions, I think towards the end, maybe closer to the May 1st date, is going to be name that test. And so again, Luke and I are going to come back after we've gone through all of the different tests. Yesterday and today were proportions. I think tomorrow and Thursday are means. And at some point, we're going to come back and say, well, what are the clues on the problem to help us name our test? So a large university provides housing for 10% of its graduate students to live on campus. So that's just setting the stage, I guess. The university's housing office thinks that the percentage of graduate students looking for housing on campus may be more than 10%. So I think they're kind of giving me the null alternative, but let's just keep reading and see if we can figure that out. Housing office decides to survey a random sample of graduate students. Well, that's always a good thing. That random, I sort of always like that. And 62 out of the 481 respondents say that they're looking for housing on campus. Okay, so I think I know where we're going, but again, I think I would ask my students those 4 questions. Does this feel like a confidence interval hypothesis test? Again, some other teachers say things like, are we looking for a number, an interval, or are we looking for a yes, no? So this feels like a hypothesis test to me. There's nothing in there leading me to think that it's a confidence interval. Do we have 1 or 2 samples? Oh, you said 1, so that's good. We're going to get on the right highway, right? We're going to get on the right highway. So we're dealing with proportions or means or averages, and it feels like 62 over 481 is a proportion and not a mean or average. And at some point, if need be, I would probably go read a z-table or do a z-test on my calculator. And so that's the first thing I want to do is literally name my test. So again, lots of different ways to name this test. I call this a 1 sample hypothesis test with proportions. I'm sure you have some wonderful teachers who taught you other ways to name it, and that's perfectly fine, but that seems to work with me and my students. And it's going to be pretty easy for me to hopefully go find that correct test on the calculator. When I start to punch the numbers in and try and get some values, I think naming that test will be very helpful to me. Okay, so part A, on the basis of the survey data, would you recommend that the housing office consider increasing the amount of housing on campus available to graduate students? I need to make a decision. Should we build more housing? Give appropriate evidence to support your recommendation. So of course, at this point, you guys fully understand that yes and no answers are just not what we're looking for at this level. And so I'm probably going to need to run a full-blown hypothesis test. But I know what I'm doing. It's a 1 sample hypothesis test with proportions. So to me, the first step is, come up with my null and alternative. So my null hypothesis is p equals 0.10. So that's the population proportion of students. And there were a couple clues in the problem here leading me to feel like my alternative needed to be greater than. So my alternative is that the proportion is greater than 10%. Right now, we don't really think that's enough right now. So I'm sure Luke talked about it. We need to identify that parameter. What does p mean? Like, what does p mean in this problem? So over here, I said p is the population or true proportion of graduate students students at this university who would prefer campus housing. So I sort of identified that, and we want to make it clear that that's a population parameter. So that's always my first step, is come up with my null and alternative hypothesis. Came up with my p-hat, or my sample proportion. There were 62 out of 481 students who did say that they would be interested in perhaps living on campus. And so I did a little math on that 0.129. Well, that number is greater than the 0.10, but at this point I'm in no position to really make a decision without running a test. There's so many other factors that impact it, but it does feel like that is greater than the 0.10, and so maybe we do need some more housing, but I'm in no position right now to make that decision. So my step two is always listing my assumptions and checking any conditions. So my first one, the data was randomly selected as stated in the stem of the problem. That's always a good thing, and that probably pretty much needs to be there. For some reason, if that wasn't part of the stem of the problem, I think on the AP exam I would write something like, I'm going to make the assumption that the data was randomly selected. So if you're ever bothered by a condition that you don't think has been met, as opposed to just not doing the problem, down here you can always say, I'm going to proceed with caution, or I'm going to proceed with the problem based upon blank. And that's what we want students to think about the problem. What conditions do we need to check for us to run the test? So my sample size times piece of knot, I call these, the NP checks. Okay, and we actually need to see your numbers in math. So you can't kind of just stop here and put a check mark and a check mark. We want to see that you plugged in the correct numbers and done some math. So I said 481 times 0.10, 0.1, that was 48.1. Well, that was greater than 10, so that's good. N times 1 minus piece of knot is greater than 10, so 480 times 0.9 is, I think I rounded it to 433. That was greater than 10. Well, clearly both of those are greater than 10, so I'm happy with my sample size based upon my null hypothesis. Now, be careful here when we're doing hypothesis tests. That value there and that number there are based upon your null hypothesis, which is sort of the first thing I wrote. Yesterday, maybe Luke used the sample proportions and hypothesis test, and the first thing I wrote after the name of the test was the population proportion was 10%. So I want to use those numbers. So the sample size looks pretty good. I want my population to be greater than 10 times my sample size. Again, we want to see you plug in some numbers. We want you to do some math. So the population is greater than 10 times 481. Is the population greater than 4,810? Again, I have no way of confirming this. This feels like it's an assumption, whereas it felt like that was a condition that I could mathematically check. So I said it's reasonable to assume that at a large university, or that this large university has more than 4,810 graduate students. I don't know that for a fact. There's no way I can prove it, but we still want you to address it and make an assumption. And it's reasonable. It did say large university. The University of Michigan, they have 100,000 students. I don't know how many graduate students, but they probably have way more than 4,810. So it feels like step two. I'm good. I've checked my conditions. So now I want to go to what I call step three, is my math or mechanics. Again, different teachers may call it different things, but it's pretty much all the same thing. Now, I do not need this formula on the AP exam if I've named the test, which was the first thing I did. And again, the name of that test came out off of those 4 questions that I asked. So when I'm teaching it, I do ask my kids to write the formula down. I think it's good practice. But as we get closer and closer to the AP exam, I say, guys, if you've named the test, you don't really need the generic formula. Excuse me, you can see I'll plug in my numbers over here, but I really want to go to a calculator right now, and I want to get those 2 values from my calculator. So I'm just going to go back to my calculator. We'll try and find the right test. Again, if I've answered those 4 questions correctly, then I think finding the test hopefully isn't that difficult. So I think I called it a one sample hypothesis test with proportions, a one sample hypothesis test with proportions. So I think it's test 5 here. Now that's not exactly what the calculator is saying, but I think I can find it pretty quickly. And my kids seem to be able to find it relatively quickly by answering those 4 questions. So that's good. Again, that name there feels what I call calculator speak. Like if you don't use the TI series, you might not know what that means, but probably all statisticians will understand what a one sample hypothesis test with proportions represents or means. So it looks like I probably typed in my numbers here, piece of knot. So that was 0.1. That was my second thing I wrote after the name of the test. I hit 62 out of the 481 said they wanted graduate housing. So that was my p-hat. My alternative was greater than. Again, I got that wording straight from the problem. It said, does the university need to build more housing? So it was greater than the 0.10. So I'm going to go ahead and just get my numbers right from the calculator. So my C value is 2.11. My P value is 0.017. You don't need all those decimals. If you want to write them, you can. P-hat, I think I had 0.129. That was pretty close. So I'm going to write those 2 numbers down on my paper. And again, if you've named the test, that's it. That's all you need for the math or the mechanics. And so those 2 numbers are critical, and they need to be on your paper somewhere. So probably the most important thing now is conclusion and context. So my first sentence is going to be somewhat generic here. I could use it probably on every problem. Since our p-value of 0.0173 is less than our assumed significance level alpha 0.05, we reject the null hypothesis and favor the alternative hypothesis. So that rolls off my tongue. I've taught the course for the better part of 20 years, and I've said that thousands and thousands of times. But there's no context there. So my first sentence is somewhat generic. I want to compare my p-value to my assumed alpha significance level, and I want to make a decision. So I've rejected the null in favor of the alternative. I don't like the word except, so I'll never use that in any of my conclusions. But my next sentence really has to tie it into this problem. So the data provides convincing evidence that the population proportion of graduate students at this university looking for housing on campus is greater than 10%. I haven't said I've definitely proved or anything. That's not what a hypothesis test does. But the evidence that we collected is leading me to believe that perhaps the university does need to build more housing, and or that it's more than 10%. So that's a nice little problem. One sample, and I'm going to try and do a 2 sample here in our remaining 15 minutes. And this was a lot of work. This took me 2 or 3 pages here, so I hope I have enough time. I think I'll have enough time to go through this. So this was from the 2012 exam. I was actually part of this what we call Rubric team. So I was part of the team that actually came up with the scoring rubrics and trained all the readers. And so I spent probably 5 or 6 days of my life on this problem and know it well. And so it's one of my favorites, and perhaps I'm a little biased because I worked on the problem. So this was from the 2012 exam, problem number 4. I'll give you a minute or so to read it, and then we'll kind of dive right into the problem. And I think I'll have enough time to finish it. Okay, so a survey organization conducted telephone interviews in December 2008, in which 1,009 randomly selected adults in the United States responded to the following question: at the present time, do you think television commercials are an effective way to promote an economy? Okay, so at this point, it almost feels like experimental design to me, but I obviously need to keep reading. Of the 1,009 adults surveyed, 676 responded yes. Okay, so that feels like a proportion to me. In December of 2007, 622 of 1,020 randomly selected adults in the United States responded yes. So now I have 2 different years, 2007, 2008. Feels like 2 different proportions, and so I'm sort of changing my mind here. I think I know where we want to go, but let's keep reading and see if we can figure out exactly what this problem's asking. Do the data provide convincing evidence that the proportion of adults in the United States who would respond yes to the question changed from December 2007 to 2008? So again, I think I know where we're going, but I'm going to ask my students these 4 questions. Does this feel like a hypothesis test or a confidence interval? Feeling more hypothesis test, convincing evidence, or convincing statistical evidence? That's probably a hypothesis test. I've got one sample, 2 samples. Well, I've got to have 2 samples. Right? I have the first sample here from 2008 and then the second sample here from 2007. Are we dealing with proportions or means? So again, proportions. These aren't averages. These are one number over another number. Proportions. And at some point, am I going to read a Z table or a T table or go do a Z test or a T test on my calculator? And I think the answer is Z. So based upon those first four questions, I'm going to call this a 2 sample hypothesis test with proportions. Again, the teachers have probably taught you lots of other good ways to phrase this. That seems to work with me and my students. And if I can answer those 4 questions correctly, I think I can name the test. And that's important. It's super important in this problem. If I've named the test, then I don't need to write the generic formula. So again, first thing I want to do is my null and alternative. alternative. So I said P of 2007 equals P of 2008. So those 2 years, the population proportions were the same. My alternative was P of 2007 is not equal to P of 2008. And I think I got that right up here where it said change. It didn't say greater than, it didn't say less than or anything. It just said, where's there a difference? Did it change? But yeah, I spent a good part of my summer that year working on this problem. If students had put in those numbers here, we felt that was enough to define the population parameter. But let's get real. Let's write really strong answers here. So over here, I'm going to define that parameter. So P of 2007 represents the population proportion of adults in the United States who would have answered yes to that survey question in 2007. P of 2008 represents the population proportion of adults in the United States who would have answered yes to that survey question in 2008. So again, only because I was on this rubric team, that was considered enough that year. I would get into the habit of writing over here, really identifying that parameter in a much better way. So far we're heading down the right path, I think. So I came up with the first sample. P hat of 2007 was 622 over 1020 or 0.6098. P hat of 2008 was 676 over 1009, 0.6699. Again, I really don't know what that number is or that number. I have my 2 samples. Well, probably somewhere in between here, but I don't know exactly where. And so this is probably going to be that P hat combined that I mentioned a little bit earlier. Okay, so I need to check some conditions. Both samples were randomly selected as stated in the stem of the problem. Super important, right? We have 2 different samples and they both needed to be randomly selected. So students, if they said here, random sample check, they didn't get full credit here. We wanted them to say both samples or something to that effect. If they said samples, they felt more than one. But if students just said, random sample check or something like that, that wasn't enough. We really want you to think about these conditions and write or communicate about them well. So I want to make sure my population size is big enough. So is the population in 2007 greater than 10 times my sample size? Is the population in 2007 greater than 10 times 1020 or 10,200? It feels like yes in the United States, but we'll come back and address that. Is the population in 2008 greater than 10 times my sample size? 10 times 1009 or 10,090? Again, we need to see this math. We need these numbers on your paper somewhere. And so down here I've said the population of the United States in both years is probably much greater than these 2 numbers. And so we're safe there. We're safe there. And so my third one I call my NP checks. This was a lot of work here, and I'll try and explain why I did it twice. So in 2007 there were 622 yeses, 398 no's. Add those two up to get this number. 2008 676 yeses, 333 no's. I'll add up to 1009. So all of these counts are greater than 10. So we're pretty convinced that my sample size is big enough based upon my proportions. I remember having discussions about the best way to do that, and this was years ago. It feels like we're now leaning towards a different way of doing it, and this was in the revised curriculum that the College Board came out with this year. So I did figure out P hat combined. I added my 2 successes over my 2 sample sizes, and I got 0.6397. Well, that does feel like it's kind of between these 2 numbers here. So that's probably a better estimate as to my population proportion for either year. Again, I'm making the assumption that they're both the same. So that feels like it's a better number than either one of those 2 samples. So I multiplied my sample sizes times that number. I get 652 and 367. I did that for both years, 2007, 2008. And again, you'll see that all 4 of those numbers, all 4 of those counts are much greater than 10. So we're good. I think moving forward, we want students to use this P hat combined here as opposed to the 2 different samples up here. But I'll leave that up to you and your teachers. That's how I'm stressing with my kids now. And I remember having great discussion at that with college professors. And we went round and round on that. But today I'm pretty convinced that I want to be using this P hat combined here. So now I need to do some math and mechanics. You can see I've written out the formula here for 2 sample hypothesis test. Z equals P hat 2008 minus P hat 2007. You could have subtracted the other way, but I think this number was bigger than that number, and I don't like negative numbers. So it doesn't really matter how you do that. Here's my standard error, and this is a little tricky here. P hat combined times 1 minus P hat combined times 1 over n 2008, 1 over n 2007. The whole thing's square rooted. I would suggest not trying to do that on the AP exam if you don't have to. That can be a little tricky, and that's hard to memorize. So as a math teacher, I'm good with it. But again, if we've written the name of the formula or the name of the test, which I did, that's the first thing I did, then I don't need that. I don't need that formula. So let's go to our calculator, see if we get some numbers here. So let's go to our tests. So I think I call this a 2 sample hypothesis test with proportions. So it feels like 6 is going to be my the correct test. Again, it's not exactly how I named it, but I think I can find it pretty quickly. Again, that to me is calculator speak, and I want to use good statistical communication. So my first sample, I think I had 622 out of 1020. When we were grading this, we did see kids messing up the numbers. As long as we could follow along with the math, I think we were pretty lenient that year. There were a lot of numbers. 2008, I think, was 1009. My alternative was they were not equal. I'm going to ask the calculator to do all the math that I don't want to do. My Z statistic is negative 2.82. Again, if you subtracted the other way, it would have been positive. My p-value is 0.00476. That's a pretty low p-value. P hat 1, P hat 2. And this here is like this third P hat is my P hat combined. So that's, I think all those numbers feel like the same numbers I got. So I wrote down my Z-score here and my p-value. So I put that on my paper. So I wrote those down here on my paper. Again, if you had the positive or the negative, it just meant you subtracted differently than I did. My p-value was 0.0048. Well, that's pretty small. I think I know what my conclusion wants to be. And so I said something to the effect of, again, my first sentence will feel generic because I can use that year. Since our p-value of 0.0048 is less than our assumed significance level, alpha is 0.05, we reject the null hypothesis in favor of the alternative. So again, that's sort of half of a good conclusion. I've stated my p-value, I've compared or linked it to my significance level, and I made a decision. Okay, but there's no context, and I really have to make a decision as it relates to this problem in that original quote. The data provides convincing evidence that the proportion of all adults in the U.S. who would have said yes to the question of effective TV commercials changed from December 2007 to December 2008. Again, lots of ways to say that correctly, but I need to get in my p-value, I need to link that to my significance level, I need to make some decision, I either reject or fail to reject, but I want some conclusion and context here. So that's a lot of work. That is a lot of work for one problem, and I think the 2 sample hypothesis test with proportions is some way harder than the 2 sample hypothesis test with means. I think I'm doing that on Thursday afternoon. I think Luke's doing confidence intervals tomorrow. So that feels like those are sort of the longest problems, at least for me. So I'm just going to go back to my PowerPoint here. We did that problem. That's the one we just finished for the sake of time. From 2015, it felt like this was, if you want another practice problem, that I think is another 2 sample hypothesis test with proportions. So if you want to practice that tonight, feel free. 2015 FRQ number 4. So at this point, you're hopefully feeling more comfortable with both confidence intervals and hypothesis tests with proportions, both 1 and 2 samples. And Luke did confidence intervals yesterday, and I did hypothesis test today. We weren't sure exactly if your teachers had taught you these again before all our schools closed down. So we wanted to get this kind of a sort of a quick, fresh review. And if it's new to you, great. Hopefully we taught you some few things. If your teachers got here, hopefully it was a good review. Similar to all the other inference tests or procedures, you should be able to write a clear, concise solution in context. I can't overemphasize how important that context is. Relate your answer to the problem at hand, not some generic statement. Although my first sentence and my conclusion is somewhat generic, I always follow up with a contextual answer. Here's your homework for tonight. It's a multiple choice. It kind of looks like a confidence interval to me, and probably it's with means, but I'll let you guys read that yourself, and Luke will start out tomorrow with that. So let's find out. We'll call it an afternoon. I appreciate your staying through again. The College Board knows that not all students have access to the internet or device. That's just a fact of life. The College Board will do anything humanly possible to help you out. So the College Board is working on solutions to help students get what they need to show their best work. So the assumption is that you'll be taking this test at home. You'll be taking it on a computer, tablet, or phone, and you have to submit your answers that way. So if you need mobile tools or connectivity or know someone does, feel free to reach out directly to the College Board at that website. website below. Feel free to notify your teachers. Please let someone know that you want to take the test, but for some reason there's an issue with technology, and College Board will bend over backwards to try and help you out. So again, thanks for watching. Tomorrow, Luke's doing confidence intervals with means. The next day I'm doing hypothesis test with means. We hope you're all safe. We really appreciate your sitting in, and we hope you're helping. So take care of yourself, please. Stay healthy. Take care of your families. These are hard times for all of us, and we really appreciate your sitting in. So I hope I helped today. Enjoy the rest of the afternoon. It's sunny up here in Maine, but cold. And I just watched the news at lunch today. We're going to get 6 to 12 inches of snow on Thursday night, so we're still in winter up here. So anyway, be safe. Hope you enjoyed today. We'll see you later this week. Thanks. Afternoon, AP Stats kids. It's Thursday, April 9th. I'm Mr. Murphy, and I'm talking to you from Bangor, Maine. I hope everyone is at home safe and healthy and able to kind of keep up with their work, and let's all stay positive, and let's hope we can beat this virus. Hopefully you can't hear the wind, but we're going to get what they call a nor'easter. We're going to get a good 8 to 18 inches of snow tonight, and it's a heavy wet snow, so we could lose power. But I think it'll be fine this afternoon. The wind's picking up a little bit. No snow yet, but we have a winter weather advisory from now until tomorrow night at 6, so maybe good timing. You'll do my good friend Luke tomorrow. He's going to do type 1, type 2 errors and power. Those are concepts that are perhaps a little bit more difficult for kids, and Luke will do a great job of that. So hopefully you can tune in tomorrow to hear Luke. Maybe I'm shoveling snow tomorrow. So yesterday he did confidence intervals with means, probably both 1 and 2 samples, and today I'm going to do hypothesis testing with means, both 1 and 2 samples. And hopefully at this point you're really starting to see that how we build confidence intervals is pretty consistent no matter whether we're dealing with means or questions or inference regression and slope. Hypothesis testing, probably the same thing. You're starting to see over and over again. They have certain things that they're looking for, and they always shout out the name of the test and those things. So we hope that this has been good review. Again, the first 2 units that we did chi-squared inference regression, those are not on this year's modified AP Stats exam. So if you want to forget about those for this year's exam, that would be okay. We decided to continue on with inference, not knowing exactly where you were perhaps in your classroom with your teachers. We weren't sure exactly how much your teachers had covered with you, and so while we were doing inference, we decided let's just finish inference. Let's do a good job of inference and proportions and means, 1 and 2 samples, confidence intervals, hypothesis test, power, all that. Starting next Monday, we will kind of go back to the beginning of the year. Chapter 1, exploratory data analysis, graph types, those types of things, mean, median, mode. And the schedule for the rest of the year is published, and that's on AP Central, and I'll show you that in one of my slides. So let's go ahead and look at last night's homework, and we'll dive into today's session. So again, I don't know why I like this picture so much, but I do. It's just a cool little graph, right? Again, my name is Brandon Murphy. I teach at John Baptist High School, Bangor, Maine. And the principal sent out a kind of a funny email today and said, teachers, probably tomorrow's going to be a snow day, but I guess we've had a snow day for the last month. But we're going to get pretty good snow up here. We're going to get some good snow. And hopefully you've been able to watch my good friend Luke. Luke and I worked with each other literally for years. We're pretty good friends, and he's awesome. And actually like to listen to him some afternoons when I don't have much going on. He's a great teacher, so I enjoy listening in with him. So here's last night's homework. Hopefully you had a chance to look at it. I'm just going to go to my overhead projector here. We'll take a look at it. So a soda manufacturer claims that its cherry fizz soda has more carbonation than a competitor's cherry eclipse soda. So it feels like I'm going to compare 2 different types of sodas here. Bottles of both types of soda are opened, covered with a balloon, and then shaken. Science experiment, maybe. I don't know. The diameter of each balloon is then measured. The mean balloon diameters are 2.3 inches for the cherry fizz soda and 2.1 inches for the cherry eclipse soda. So they're similar, I guess, in diameter. But is that difference enough to say that there is a difference? And of course, I can't look at those numbers anymore. You can look at them. I have to run some sort of test or a confidence interval. A 90% confidence interval to estimate the difference in mean diameters in inches is -0.8 to 1.2. So there's my interval. I typically almost always want high confidence. Of course, as I get higher confidence, the interval tends to get bigger. And so it's sort of a trade-off, right? Which of the following claims is supported by the interval? So if you listen to any of my sessions on inference, I typically have 4 questions that I like to ask my students to kind of get into the problem and maybe name the test. So question 1 is, does this feel like a confidence interval or a hypothesis test? And it's a 95% confidence interval. 90% confidence interval. So pretty convinced it's a confidence interval. Some teachers have rephrased that to me and said, Brendan, as opposed to saying hypothesis test or confidence interval, are we creating some numbers in an interval, or do we want a yes or no decision? I really like that. So I think I'm going to maybe improve that next year when I teach it with my kids. So it feels like a confidence interval. Do I have 1 or 2 samples? Well, it feels like I have the 2 different types of sodas, and so it feels like 2 samples. Then I say something like, are we dealing with proportions or means or averages? And it feels like we're dealing with means, right? It says that the mean diameter is 2.3 and the mean diameter is 2.1. And then I say something like, we're going to go read a T table or a Z table or something to that effect. And by naming the test, it really helps my kids kind of get into the problem, set the stage, hopefully answer it correctly, and going and finding the right test on the calculator. There's one button, and we'll go there later today, and there's a whole bunch of tests there, and it gets confusing. So those 4 questions have helped my students get into the problem, write the name of the test. It's the first thing I do. You'll see me do that a couple times today. And then when I go to the calculator, it does help me find the right test. And we'll talk about when we do hypothesis testing. If you do the name of the test, you don't need the formula. So that's a good thing. So I need to look at that interval, -0.8 to 1.2. Which of the following is supported? Because 2.3 inches is larger than 2.1 inches, the manufacturer is correct, and cherry fizz has more carbonation. I don't know if I can say that. We've taken a small sample here, and 2.3 is definitely bigger than 2.1, but I don't know if I can make some claim about these 2 different types of soda. Because the interval has more positive values than negative values, cherry fizz has more carbonation. I don't think that's a true statement either. It doesn't really matter how much is positive and how much is negative. Hopefully you're already zooming in and saying, we're looking for 0. We're looking for 0. Is 0 anywhere in that interval? So I don't think A and B makes sense, because 2.3 and 2.1 are very similar. There's no difference in the mean carbonation levels. The first half is a true statement, but I don't think I can make the leap to the second half. So right now, I don't think any A, B, and C. The interval cannot be interpreted because negative measurements are not possible. That doesn't feel good either. It just depends upon how much you're tracking. So let's hope B makes sense, because A, B, C, D doesn't make sense. E, because the interval contains 0, it is possible that there's no difference in the mean carbonation levels. Yeah, that's a great sort of 1-sentence analysis of interpreting 2-sample confidence interval. Looking for 0 anywhere in that interval. It doesn't have to be right in the middle of this interval. It literally can be anywhere in the interval. So I got the answer E. I think that's correct, and hopefully Luke did a good job of that yesterday. So I'm going to go back to my PowerPoint here, and we'll get started with today. So there's the homework problem again. We just went through that. If you've been with me before, you've seen these first 2 web addresses. I added the 3rd one down here, and this currently has online AP Central the schedule for the rest of our 3.5 weeks that Luke and I are going to do. So we've got emails for both teachers and students, which is really cool. People have seen our name and somehow looked up our emails at our school websites or something. You can go and see what we have planned literally for the next 3.5 weeks. We realize that you're busy and lots of work going on, and I think AP calculus goes at the same time as us. And so if you're taking more than 1 AP course, you may want to sit on them both. So you can go there and see exactly what we're going to be discussing literally for the rest of our time together until May 1st. So if you go to this bottom website, you'll have the schedule kind of at the top of all the different classes. Keep scrolling down until you get to math and science. We'll have all the math and science AP courses. Click on AP Stats, expand all, and then you'll see the schedule that we given to the College Board. So tomorrow Luke is doing type 1, type 2 power. And then I think the last week when we're kind of really zooming in and laser focusing on helping you get ready for this year's modified AP Stats exam. One of the days, and I can't remember if he's doing it or I'm doing it, is name that test. Here's a problem. What type of test do we want to do? So that's good. That schedule's out. Please share that with your friends and colleagues and your teachers and whatnot. And hopefully that can help you just prepare better for this year's AP Stats exam. So I'm going to be talking about hypothesis tests with means, both 1 and 2 samples. And so here's kind of the first formula that we need with a 1 sample t-test, I guess. And anytime we're dealing with means, we need to be concerned about degrees of freedom. And I'll tackle that one. There's sort of a little nuance there about degrees of freedom when we get to 2 samples. And I copied this right from the College Board CED course and exam description book, but that's something that we as teachers should look at. You will not find this formula exactly on the AP AP stats formula sheet. But typically, the difficult thing here is, the standard error here, the standard deviation based on sample size. That's sort of what my kids struggle with the most. So hopefully, you're feeling more comfortable with all these formulas. There's no reason to memorize them. The calculator will do all of these. And of course, this year's test is going to be open book, open note, and maybe you have these highlighted in your book or something. So I'll leave that up to you. So that's sort of a one sample hypothesis test with means. This one is a little bit more intimidating. This is for 2 samples. And again, I just copied this right from this College Board CED. The note down here, though, t-distribution with degrees of freedoms that can be found using technology. So I'll tackle that one. I'm not sure if Luke did it yesterday, but what do we do in 2 samples if I have 2 different sample sizes? How do we figure out the degrees of freedom and whatnot? So that was on my list of things to do this afternoon, and we will be good there. Let's not worry about this flutter stuff on the curriculum. I'll come back to it really quick when we do a problem. So here's kind of the 4 questions again that I always ask my students anytime we're doing inference. So at this point of the year, if I'd been in school with them last month, they would honestly probably be sick of me and sick of these 4 questions. But does this problem feel like a confidence interval or hypothesis test? We have 1 or 2 samples. We're dealing with proportions or means. The other day, I like this, which highway are we on? Are we on the proportions or mean highway? Once we get on that highway, we don't get off it on that problem. And do we need to read a Z table or a T table? Again, your teachers may have shown you how to do it on the calculator, which is perfectly fine. I'm a little old school. I still like tables and I like to show my students both. But if you're not comfortable with a T table or a Z table, don't worry about it. Your calculator can get all these values. If the students can answer all these questions correctly, I think it helps them name the test, which is super important on a first response, and then get into the problem and hopefully solve it correctly and find the right test on the calculator. So those 4 are really designed to help my kids sort of quickly get into the problem. So I'm going to look at at least one multiple choice and a couple of free response today. So let me give a minute to read this one. This was a multiple choice from the 2012 exam, and I think so the goal of this problem was can you identify what type of test are we going to do? What's the name of this test? So I'll give you 30 seconds to sort of read this. I'm going to go over to my document camera and we'll walk through it together. Hopefully you can still see that. Okay, so a manufacturer claims its brand A battery lasts longer than its competitor's brand B battery. Okay, we want to compare 2 different batteries and see which one lasts longer. So pretty real world problem. Right? 9 batteries of each brand are tested independently. Well, that's kind of an important word here. I might underline that if I was a student. And the hours of battery life are shown in the table below. I'm looking for the word random and I don't see that, but hopefully it's coming later or something. So I picked 9 batteries from brand A and see how long the batteries last or something like that. And done the same for B. So it feels sort of like I have 2 different samples here. Actually, excuse me, I have 2 samples here. But I have the same number of tests, I guess, or same number of data points for each. And so anytime I see that, I just make a little note to myself. Could this be a matched pairs? It's not that simple. And again, I'm going to tackle that a little bit later. But it feels like I have two things I'm comparing brand A and B. Could this be a matched pairs problem? And I'll try and talk about the difference between matched pairs with means and a 2 sample t-test. Provided that the assumptions for inference are met. Okay, so that's good. So I think I'm covered here with my randomness and sample size and all those things. Which of the following tests should be conducted to determine if brand A batteries do in fact last longer than brand B batteries? Okay, so here's my 4 questions again. Does this feel like a confidence interval or hypothesis test? Sort of feels like a test, right? That's my little keyword there. I have 1 or 2 samples. I have 2 samples, but again, I need to be kind of thinking about this matched pairs test here in the back of my mind. Are we dealing with means or proportions? Well, I think we're dealing with means, right? Average hours. And am I going to read a Z table or a T table? So when I answered those 4 questions, I came up with a 2 sample. My rating is atrocious, isn't it? Hypothesis test with means. Okay, so that was the name of the test. And I didn't need to do this, but I felt it was going to maybe help me. So I just came up with what my alternative hypothesis. So mu of A equals mu of B. So that would be the population of both those brands' batteries and how long did they last. And I think up here it says, does A last longer than B? And so that gave me a little clue for my alternative. And so I said mu of A is greater than mu of B. Of course, on multiple choice, perhaps you don't need to do this. If it helps you, great. If it doesn't, that's okay. It's not needed in the problem. So I went up here and it sort of felt like I could get rid of D and E. Those are talking about Z tests. And usually when I hear Z, I think proportions and T, I think means. A 2-sided 2 sample T test. Well, it is 1-sided, so I was able to sort of get rid of that one too. So the question is it A or is it B? And again, when I have the same number of sample size is the same, I at least think about matched pairs. The more important decision about whether it's a matched pairs or I guess what we're calling a paired T test versus a 2 sample T test are those independent of each other or are they not independent of each other? So it feels like brand A and brand B are independent. They're not related to each other. Brand B is not going to work longer or less than brand A. So because those were independent, that led me to a answer B here. So answer B, I'm pretty sure is the correct answer. Is a 1-sided U A is greater than U B 2 sample T test. So I'm going to do my next problem's going to be matched pairs. Hopefully you can kind of see the difference here. So brand A and brand B are independent of each other. The batteries aren't in cahoots. A's not working longer than B. They're totally separate. And that led me to the 2 sample T test. So hopefully that helps. And so I found a free response from 2006, and hopefully these free response multiple choice that I'm doing and we're giving you for homework are helpful. Again, this year's modified AP Stats exam is all free response questions, so we really want you to get in the habit of reading them and analyzing them and hopefully coming up with some really good solid what I call free response answers. So you haven't seen this one before, so let me just give you a minute to read that one. A lot of data here, and I think I hopefully typed it into my calculator already, so I'll try and save some time. But to see if you can perhaps tell if this is a 2 sample T test or a matched pairs T test, and the key decision that I need to make are is in this case the before and after independent of each other or are they not independent of each other. So I'll give you a minute to read this, and then we'll dive in and I'll work through my solution. Okay. The developers of a training program designed to improve manual dexterity claim that people who complete the 6-week training program will increase their manual dexterity. Okay, so just setting the stage. That's what I say. We want to get you to the problem. A random is always a good word. Sample of 12 people enrolled in the training program was selected. Random sample of 12 people enrolled in the training program was selected. Okay, I like random. That feels a little low to me. I always am more comfortable with a larger sample size. But 12 is what it is, and I have to do my analysis that way, and we'll have to address that with conditions or something. So I like the random. The 12. I wish that were 24, 120 or something. A measure of each person's dexterity on a scale from 1 lowest to 9 highest was recorded just before the start and just after the completion of the 6-week program. So it looks like that's what all of these numbers are. So for person A, we measured their dexterity. Again, I don't really know what 6.7 manual dexterity means, but higher numbers better. You're more flexible. And at the end of the program, or 6 weeks later, for person A, their dexterity had gone up. It doesn't mean anything. One person goes up, next one could go down. And I think that's what you're seeing here for those 12 people. So we have the before. This is when they were manually selected at the beginning. We somehow measured their manual dexterity. And they went through some 6-week program that was designed to improve their manual dexterity. And then we took a measurement here afterwards. So again, anytime when I have the same number, I at least think, could this be a matched pairs test? Okay, so same 4 questions. Let's feel like confidence. So excuse me, I don't know what I'm supposed to do yet. Sorry. Can one conclude that the mean manual dexterity for people who have completed the 6-week training program has significantly increased? Support your conclusion with appropriate statistical evidence. So statistically significantly increased. I'm leaning towards a hypothesis test here. I think there's no confidence level here. So I think it's some sort of hypothesis test here. So that's my first question. Does it feel like confidence level hypothesis test? I'm going to go with hypothesis test here. Do I have 1 or 2 samples? It clearly looks like I have a bunch of data here and a bunch of data here before and after. So it's very easy to say 2 samples here. So for now, let's say I have 2 different sets of data here, and I somehow need to compare them or something. Are we dealing with means or proportions? These look like averages or means, not proportions. So I'm going to go with the means. And I'm going to read a Z table or T table. So I think I'm going to go with T table with means. So here's the decision. Is this a matched pairs test or is this a 2 sample T test? If these 2 sets of data are independent, like we saw in the last multiple choice, it's a 2 sample T test. If they're not independent of each other, they're related to each other in layman's terms, then that's what we call matched pairs. So anytime the sample sizes, for lack of a better term, are the same, I at least think of matched pairs. If the two sample sizes are different, it can't be matched pairs, at least in our course here. So anytime I do the same, think of matched pairs. I think I'm going to go with matched pairs here because it feels like the before and after aren't independent. If I scored well here, I'm probably going to score reasonably well here. So those before and after do not feel independent to me at all. It feels like I have some manual dexterity and they measure me, and then I go through training and they measure me again, and those feel like they're related. So I wanted to call this a matched pairs t-test with means. Lots of other ways to phrase that. That's just sort of my way of doing it. It's based upon my 4 questions. And again, if my two sample sizes, for lack of a better term, are the same, at least think matched pairs. The bigger decision is, are they independent or not independent? So my null hypothesis is mu of the difference. So that's a little d is 0. There's no difference. The program didn't work. No difference between 4 and after. Going back up here, has the 6-week training program has significantly increased. Okay, well then the mu of difference is greater than 0. So people have become more, the dexterity has improved over that 6 weeks. Always identify a parameter. So null alternative, name of test. That's sort of how I always do all of these problems. Mu of d is the mean difference before and after, and the dexterity scores for the population of people enrolled in this program. Again, I don't know how many people are enrolled in this program, but so null alternative, always identify your parameters. Naming the test is helpful. That allows me not to come up with what I call the generic formula. So we're heading down the right path. I want to check my conditions and assumptions. So it did tell me the 12 people are a random sample of people in the program, so that's good. I did actually subtract my after and before. I'll show you that in the calculator in a second. So when I'm doing matched pairs, what I'm really doing is usually taking the difference of my 2 different groups of data. And so the first person went up 1.1, the second person went up 0.5. This person, nothing happened. These people, the program didn't work at all. They actually went backwards. And so I came up with those. I'll show you those in the calculator in just a second. Well, I think I said earlier I was a little bit worried about that sample size of 12, right? I want that to be bigger. You may have the number 30 in your brains with means. Well, usually when we test matched pairs, you got to type these numbers into your calculator, and 12 times 2 is 24. And so if we had 30, it would be 30 times 2 and 16. It just takes too long. So for these problems, we understand that you're racing the clock and trying to do them. And so it's not atypical that you might only have 8, 10, 12 again times 2. And so I decided to do a quick dot plot of the differences. So I put a little dot plot together here. And I'm looking for huge skewness, obvious skewness, or any outliers. And I didn't see that, so I just made a little note over here. There's no obvious skewness or outliers, so we'll assume approximately normal. That's the best I can do with 12 data points. Again, I would like that to be way higher, but if we had 20 or 30 in 2 columns, boy, it would take you forever to type that in. So this is a really old problem. We really weren't worried way back then about population and 10% condition, but moving forward, starting 2019, we do think it's important. So is the population greater than 10 times the sample size? Is the population greater than 10 times 12? Is the population greater than 120? And I don't know that for a fact, but I would probably just put a few words over here that it's reasonable to assume that the population of these people is greater than 120. Again, I absolutely no idea, but we want to at least think about that. And so this one here is an assumption. I can't check that. I don't know that for a fact. So I think we go with conditions. Again, here's my general or generic formula. I do not need that. You do not need that anywhere on your paper. If you've named the test correctly somewhere on your paper, and my kids always find that easier. So I'm going to go back to the calculator and show you where I got all of those numbers. We'll run the test. So I think that in my list 1 and list 2, yeah, I was efficient earlier today. I listed those 12 values. This is the before and this is the after. And I'm interested in the difference. So I subtract those two. And so for list 3, I said, list 2 minus list 1. And now list 3, I'm almost going to run this test like it's a 1 sample t-test. I have my two sets of data that I've combined. I've subtracted the difference. And now I'm going to, at least from a mathematical point of view, I'm going to run it like a 1 sample t-test. So I have all those numbers typed in. That's good. I'm going to run a test. So again, there's no test here for matched pairs. That's what I wrote on the first page of my answer. But I'm going to handle this like a 1 sample t-test. And so I think I can run my data. Okay, sorry about that. I have the data in a list, so I'm going to run data as opposed to stats. My null is equal to 0. My difference, there's no difference between my 2 groups. My data is in list 3. I think my alternative was greater than, so I need to change that one. And I'm going to get some numbers here. So these are the key numbers that I need to write on my paper. So I'm going to go back to my paper here. So this t statistic, this p value, those are important. Again, if you've named the test correctly, that's really all we're looking for math and mechanics. Now I have a little bit more. X bar of the difference was 0.375. The calculator gave me that. SD was 0.367. The calculator gave me that. I don't need this. Plug my numbers in. My sample size was n equals 12. It was 12 people. Degrees of freedom was 11. So my t statistic was 3.54. My p value was 0.0023. And again, if I'm naming the test, that's all I need on my paper. So you don't need this. You don't need this. When I'm teaching it to my students all year, I have maybe stricter rules all year. But as we get closer to the AP exam, we want you to maximize 1 year time and 2 year score. So you name the test. You don't need this here. So again, if you've seen any of my sessions, it's probably going to feel somewhat generic. But since our p value of 0.0023 is less than our assumed significance level alpha is 0.05, we reject the null hypothesis and favor the alternative. So that I pretty much say for all hypothesis testing, that sentence is sort of the same. I've got my p value in there. I've got my assumed significance level. I've compared them. I've linked them. And I've made a decision. I'm rejecting the null hypothesis and favor the alternative. What I don't have is any context. So I need that second sentence. The data provides convincing evidence that on average, people who complete the program have increased their manual dexterity or something like that. So I'm sure Luke's talked about it as well. Those are kind of the 4 steps we need, and that's a full-blown inference-free response. And that can take a little bit of time to do. So hope that helps. I'm going to come up with a 2 sample hypothesis test, and this is going to be even more work. So this is probably going to finish up the rest of the afternoon here. So hopefully you can read that okay, and let me just give you a minute or so to read that, and then we'll dive right in. And we'll probably finish up today's session with that. So this is from the 2002 exam. This is free response question number 4. Okay, baby walkers are seats hanging from frames that allow babies to sit upright with their legs dangling and feet touching the floor. I vaguely remember having one of those as a kid, and I remember it being kind of fun. Walkers have wheels on their legs that allow the infant to propel the walker around the house long before he or she can walk or even crawl. So I think little kids think it's fun. They can move around. They can't walk yet or crawl, but they can get around the little thing, a little walker. Typically, babies use walkers between the age of 4 months and 11 months. Staying the same, just giving you a little bit of background on the problem. Because most walkers have tray tables in front that block babies' view of their feet, child psychologists have begun to question whether walkers affect infants' cognitive development. So they can't see their feet. Is that somehow impacting how their brain develops? I'm a math teacher, no idea. But I can analyze the numbers probably. Right? So that's what we want to do. One study compared mental skills of a random sample. I like that word. That's a good word. I'm going to underline that. Of those who use walkers with a random sample of those who never use walkers. So I'm trying to compare 2 groups. A group of babies who had used walkers and a group of young children. Mental skills scores average 113 for 54 babies who use walkers, standard deviation 12. So that's probably important. I'm going to write that down somewhere on my paper. And 123 for babies who did not use walkers, standard deviation of 15. So one group had mental skill score of 113. The other group had 123. I don't know exactly what those numbers mean, but we don't need that for the problem. Sample size of 54 for the first group and sample size of 55. That's good. I'm pretty happy. These are decent sample sizes. They're randomly selected, so I'm feeling pretty good about both of those. This one has standard deviation of 12. This one has standard deviation of 15. So this one has a small standard deviation. Again, I can look at those numbers any faster than you can and make some decision here. Is there a difference between the 2 groups? I honestly don't know right now. So I'm going to have to probably run a test here. Part A, is there evidence that the mean mental skill score of babies who use walkers is different from the mean mental skill of babies who do not use walkers? Explain your answer. answer. So again, here's my 4 questions. Does this feel like a confidence interval or hypothesis testing? I think I'm going to lean with hypothesis testing here. Do I have 1 or 2 samples? I have my 2 samples. Are we dealing with means or proportions? Well, 113 and 123 feels like means. At some point, I'm going to look at a t-table or a z-table, and with means, I'm typically looking t. So I think the first thing I want to do is name that test. A 2-sample hypothesis test with means. Gets me in the problem, can help me perhaps find it when I go to the calculator. So that's the first thing I want to do. Always in those 4 questions, hopefully get my kids kind of in the game and looking at the problem. So of course, first thing I want to do is my null and alternative, right? So I said my null hypothesis mu of w, the population mean of those with walkers, is equal to mu of nw non-walkers. And my alternative was mu of w walkers was not equal to mu of nw non-walkers. And I got that right up here is different. So there was no direction there. So it's a 2-tailed test or 2-sided test. Always identify your parameters. So I said mu of w is the population mean mental scale for babies who use walkers. Mu of nw is the population mean mental scale for babies who never use walkers, or something like that. There's lots of ways to do that. But super important that we have a correct null and alternative. We've identified my parameter. These are the numbers that they gave me. So the sample mean for walkers was 113. There were 54 children in that group. The standard deviation was 12. X bar of nw non-walkers was 123. There were 55. Standard deviation of 15. Those are pretty good numbers. I like those. Those seem to be large enough. Always want more, but I'm pretty happy with those 2 numbers. We'll come back to part B here. I really like this problem because of part B, but for now, let's just sort of continue on with hypothesis testing. Okay, so the first thing I need to think about is my degrees of freedom. Okay, so with degrees of freedom here, sorry, I'm on the wrong page. Let's do our conditions. Both samples were randomly selected as stated in the stem of the problem. Okay, that's good. We don't want just random and check. That's not checking the conditions. That's putting check marks. So just say that in words. That's pretty important here. Both sample sizes are greater than 30. 54 greater than 30. 55 greater than 30. That's good. I'm pretty comfortable about that. Population greater than 10 n. Again, this was an older problem, and this was not part of the rubrics, but it is now, so I want to get that in. Is the population for the walkers greater than 10 times 54, 540? Yeah, it feels like that's a reasonable assumption. Is the population greater than 10 times 55 or 550 for the non-walkers? Again, probably follow that up with some words over here. Is reasonable to assume that the 2 populations are greater than 540 and 550. So I think we're good. I've correctly named the test. I hope. You do not need that formula right there, and that's not an easy formula perhaps to come up with. It's not provided on the formula sheet, so we can avoid that if we want. And I stress to my kids as we're getting closer to the AP exam to not worry about that. Go to your calculator, get these numbers. You name the test correctly. You do not need this. Plug the numbers in. Again, I don't need that. I've got my critical information here, so let's go to the calculator and see if we get those numbers. So we got to figure out what test to use. I think I call this a 2-sample hypothesis test with means or something. Well, that's not exactly what the calculator calls it, but I think I could find this pretty quickly, right? I don't like 2-sample t-test. I don't allow my kids to do that. That feels like calculator speak to me, and that's not good statistical communication. So I'll call it something different. We have data here, and so my x bar 1 was 113. My standard deviation, again, this was just given to me. I'm just looking back on my paper here. Sample size 54. My mean for non-walkers was 123. My standard deviation was 15. My sample size was 55. My alternative was not equal. So if the calculator asks you to pool, we'll say no. Let me give me a minute or two, and I'll come back to that. If the calculator says pool, say no. And I'm going to run my test. So I think these are the critical numbers here. My t-statistic is negative 3.846. My p-value, when we do see this on the AP exam, is not 2.077, right? Probability is always between 0 and 1. So that's scientific notation here. So I just need to just be careful. We do see sometimes 2.077 in students. I just think I've forgotten this or haven't seen it. So my degrees of freedom, this is a weird number here, but I'm going to write that down in my paper, and I'm going to go back and finish up that problem. Okay, so I wrote down the t-statistic, my degrees of freedom, and my p-value. The p-value is really pretty small, so I think I know what I'm going to do here. But where the heck did this number come from? 102.83. That's a weird number for degrees of freedom. So years ago, before we had calculators, we had to kind of make some assumptions that perhaps weren't great, but it was the best we could do. So we have options with degrees of freedom, and I'll tell you personal opinion what I like the best. We could take the smaller of my 2 samples. So the number of walkers minus 1 is 54 minus 1 or 53. Or the numbers in the non-walkers is 55 minus 1, 54. So I could use that smaller of degrees of freedom, go to t-table, go to my calculator, get that number. That's pretty conservative, and that's not very realistic in the real world. And with technology, I'm not sure I would do that, but that's an option. Pooled is basically adding the 2 sample sizes and subtracting 2, or n minus 1 plus n minus 1. So I got 54 plus 55 minus 2 is 107. Again, we did both of these years ago when we didn't have technology and we were trying to make our lives easier. Neither one is perhaps the best way to do it today or the most accurate. To pool here, I think we need to assume that the 2 population variances are the same, and that's a huge leap. That's something that I can't get from this problem and from that data. So I tend not to like either one of those 2. The calculator is using what we call say-to-white formula. You don't name of that. One of my slides had a really ugly formula. I glossed over that. But that's where that number's coming from. I just wanted you to know that that's not magic. It's coming from formula that's not in the scope of the course. You may never have seen it. Your teachers may never have brought it up, and that's perfectly fine. But if you said to yourself, where does that number come from? It's coming from, we'll call it, I think I'm saying correctly, the say-to-white formula. Okay, what I do know is we had a really small p-value, right? 0.0002 when I took that scientific notation and made it a decimal. So I need to make some conclusion here. Again, first sentence is going to be pretty generic, pretty general. Since our p-value of 0.0002 is smaller than our assumed alpha level, assumed significance level alpha 0.05, we reject the null hypothesis and favor the alternative hypothesis. That's a good first sentence, but it has no context. It's not related to our problem at all. So here's my conclusion in context. The data provides convincing evidence that the mean mental score of babies who use walkers is different than the mean mental scale of babies who did not use walkers. And that's really what we were trying to figure out as being a problem. Okay, so hopefully that's feeling better, and maybe I've demystified a little bit with this whole degree of freedom. Again, we're not sure exactly where you were in the course with your teachers and how much they taught you. So I guess 3 different options, and I always like going to the calculator. It's the most accurate, and it's the best we can do. What I didn't do, and I really wanted to, and I think it's going to end up maybe time is better today, is part B of this problem. So part B says, suppose that a study using this design found a statistically significant result. Well, it sort of feels like we did, maybe a really small p-value. Would it be reasonable to conclude that using a walker causes, well, I'm going to underline circle that word, that's a strong word in statistics, right? Would it be reasonable to conclude that using a walker causes a change in mean mental scale? Explain your answers. When I give this problem in practice with my kids, I use this every year. Unfortunately, almost all of them will say, yes, we can make that assumption, and it does cause. When I hear the word cause, I think causation, I think experiment. And this is not an experiment. This was an observational study. We had 54 babies in one group and 55. It doesn't feel like this was an experiment, and so I don't think I can talk about causation here. I think that low p-value sometimes leads students into, we've proved it. There's definitely causation. It's so low. We have strong evidence, but we can't talk about causation here also. It would not be reasonable to conclude that using a walker causes a change in mean mental scale because this was an observational study and a causal relationship cannot be inferred. So we just can't do it. It doesn't matter how big or how small that p-value is. We just can't talk about causation unless it's an experiment. So I'm getting close to that magic hour. Let me just wind down real quick. Okay, so we did that problem. We did that. This was another match pairs that I unfortunately just didn't have enough time. But to get to it, if you want to take a look at another match pairs, it's 2000 for response number 4. That's the problem we just did. So hopefully by now you're feeling more comfortable with both confidence intervals and hypothesis tests with means, both 1 and 2 samples. Guess what Luke and I did the last couple of days, right? In proportions on Monday and Tuesday. Similar to other inference test procedures, you should be able to write clear, concise solution in context. It's so important. Readers will be saying, is there any context? Is there context? We want you related to our problem. The term we use is the student in our problem. You can see I have some generic interpretations, so those are great, but I always want to make it specific to our problem. That's the context. Here's the homework for tonight. Luke tomorrow is going to do type 1, type 2, super important in power. That's a little trickier concept. So Luke will do a great job with that, but tomorrow Luke will do type 1, type 2 power. So here's your homework problem. He posted on his website. So for the sake of time, I'll let you guys guys go ahead and do that. But again, this was modified. It wasn't, there's a part A to the problem, but part B says in the context of this situation, describe the type 1 and type 2 errors and describe the consequences of each of these for the law firm. So I've graded some type 1, type 2 problems. Students tend to be pretty good about telling the difference. What is a type 1 versus type 2? Sometimes though the consequences of making a decision or making an error in this case, they struggle with. So make sure you talk about type 1 and type 2, but what's the consequence or what are the ramifications of making the wrong decision here? Okay, so this is typically one of my last slides here, but we know that all students do not have access to the internet or device. I'm struggling with my students. I have 4 different classes this year, jump apps, and some of our students are struggling with internet connectivity or they don't have a device, and it's a real issue. And we're trying to help you solve that. So the College Board is working on solutions to help students get what they need to show their best work. If you need mobile tools or you have issues with connectivity or know someone who does, please reach out to the College Board. They'll bend over backwards to help you guys. We want you to take this year's modified AP Stats exam. Luke and I want you to do a great job. We want you to take more statistics in college. And so if that's a problem, please let somebody know, and we'll try and help you out. So again, thanks for watching today. It's getting worse out as I'm looking out my window. It's rain now. It's going to turn into some snow, and hopefully you couldn't hear the wind and I didn't lose power, and I was a little worried about that. But anyway, have a great afternoon. I hope everyone's safe and healthy. Let's stay positive. We can beat this thing. Keep working hard. And on the website there, I gave you that link to, you can look at the schedule for the rest of, I guess, 3.5 weeks with Luke and I, and you plan your review accordingly. So be safe, enjoy your afternoon, and I'll see you next week. Thanks a lot.
Hello, AP Statistics students, and welcome to the College Board Virtual Instruction for AP Statistics. My name is Luke Wilcox. I am an AP Statistics teacher at East Kentwood High School in Kentwood, Michigan. I'd like to start today by just saying Happy Friday to everyone. We've had a whole lot of new students that have joined us this week, and I know that Mr. Murphy and myself are thrilled that you all have been joining us here at 2 o'clock every day, and we hope that you will stay with us through the remainder of this AP exam review over the next couple of weeks. So let's jump right into things here. And first of all, make sure that everybody is in the correct place here. This is AP Statistics. As I've already mentioned, my name is Luke Wilcox, and I do want to give you a couple of quick reminders. If you've been with us for the last couple of weeks, you may already know this. If you are brand new, this is some important information for you. The first idea of which is to know that we meet every day from 2 o'clock to 2:45. That's when we go live. We have split up the AP exam review in an interesting way here, and I want to make note of this. We are currently at the end of this week, April 6th through the 10th, and we have been covering units 6 and 7. So today, I will finish out units 6 and 7 with you in today's lesson, and then starting on Monday with Mr. Murphy, we're going to go back to the very beginning of AP Statistics, unit 1, and we're just going to take you through units 1 through 5. And remember, for the AP exam for this year only, 2020, units 1 through 5 and 6 and 7 are contained on this year's AP exam. It is units 8 and 9 that will not be on the 2020 AP exam. Now, we do know the dates now for the AP exam for 2020 is May 22nd. That is our Super Bowl. That is our Stanley Cup. That is what we are preparing for at this point. A couple of reminders to you. If you want to access the lessons and homework problems that we're doing in these YouTube videos, you can get those at statsmedic.com/YouTube. You can download those as PDFs. They're organized by the date. And finally, one other note here. If you or another student that you know is in need of a device or internet access in order to be able to take that AP exam on May 22nd, there's a place where you can request that technology, and that is cb.org/hack. So if you or someone you know is in need, please let them go to the site, put in their information. The College Board is very committed to making sure that every student has access to technology to be able to take that AP exam on May 22nd. Okay, we are going to start by checking in with the homework problem that Mr. Murphy gave you yesterday, which is going to be a great lead into what we talk about in today's lesson. So let's jump right in here. It says, when a law firm represents a group of people in a class action lawsuit and wins that lawsuit, the firm receives a percentage of the group's monetary settlement. That settlement amount is based on the total number of people in the group. The larger the group and the larger the settlement, the more money the firm will receive. A law firm is trying to decide whether to represent car owners in a class action lawsuit against the manufacturer of a certain make and model for a particular defect. If 5% or less of the cars of this make and model have the defect, the firm will not recover its expenses. Therefore, the firm will handle the lawsuit only if it is convinced that more than 5% of the cars of this make and model have the defect. The firm plans to take a random sample of 1,000 people who bought the car and ask them if they experienced this defect in their car. So in the context of this situation, describe a type 1 and a type 2 error and describe consequences of each. Okay, before we can even talk about type 1 and type 2 errors, we need to make sure that we're clear on what the hypotheses would be for the significance test. So let's see if we can identify the null and the alternative hypothesis. Now, from the context of the question, I know that we're dealing with proportions here rather than mean, and it sounds to me like they're only going to take one sample. So it is likely that they're going to take that sample and calculate a proportion. And so the parameter for the whole population that we're trying to estimate here is a proportion, and it is the true proportion of cars of this make and model that have the defect. Right? That's what the firm is trying to estimate when they take their sample of 1,000 people. Now, the null hypothesis says that percent is 5%, right? And if it's 5%, then the firm doesn't really want to take this case because they're probably not going to make their money on it. But the alternative hypothesis says that the true proportion of cars with a defect is big, it's greater than 5%. In which case, they would want to take this case because they'll be able to make some money here. So let's talk about type 1 and type 2 error. So first of all, the definition of a type 1 error is that the null hypothesis is true, but we've made an error, and the error here would be to decide to reject the null hypothesis. So let's think about what that means in this particular context. So I need to start out with the null hypothesis being true. So the null hypothesis says that the true proportion of cars with the defect is 0.05, 5%, right? So the truth is the null hypothesis. Really, that 5% of the cars have the defect. But the firm makes an error, they make a mistake, and they decide that the alternative is true. And the alternative is that the true proportion is greater than 5%. Well, if they thought that the proportion was greater than 5%, then they would take the case, right? So the error that they make here is we're going to say, but the firm takes the case anyway, right? They really shouldn't have taken the case, but they took the case anyway. That's a type 1 error. Now, we also need to make sure that we talk about the consequence of that error. Well, in this particular situation, the firm really shouldn't have taken the case, right? They take the case, they shouldn't have. They're very likely going to lose some money here. They're not going to be able to recover their expense. So the consequence is that the firm does not recover its expense. So the firm is going to end up losing some money here. That is a potential consequence if they were to make this particular error. Now, that's a type 1 error. Let's now talk about a type 2 error. The definition for a type 2 error is that now the alternative is actually true, and the mistake now is to fail to reject the null hypothesis. So let's go ahead and put that in the context of the problem. Now we need the alternative hypothesis to be true. In other words, the true proportion of cars with the defect is now greater than 5%, greater than 0.05. But the firm makes a mistake and they go with the null hypothesis, which says that it's only 5%, in which in that situation they would not take the case. So the mistake or the error that the firm would make here is we're going to say, but the firm doesn't take the case, and they really should have. Now, what's the potential consequence of this? Well, they don't lose any money because they didn't take the case, but they are missing the opportunity to have made money. So I'm going to say that the consequence here is that the firm is missing a chance to make some money. Now, if that all came pretty quick to you and you're still a little bit fuzzy about type 1 error and type 2 error, don't worry. That's what today's lesson is all about. So we're going to dig into this idea of type 1 and type 2 error as well as the idea of power of the significance. So let me give you the overview, and that means that I'm going to go to my learning targets for the day, and there are going to be 3 of them. And the first one is what we just talked about in the homework problem. We're going to make sure you know how to describe these errors in the context of the problem, think about the consequences of those and how we might impact those potential errors. The second learning target has to do with what's known as the power of the significance test. And then we also want to know how we can increase the power. And we're going to go with 3 different ways where we can see the power increasing for significance test. And then the last learning target is a little bit more general. It's to understand the relationship between the 3 things: the type 1 error, type 2 error, and the power. And specifically talking about probabilities of type 1 and type 2 error. So I will make sure that we check back in with these learning targets at the end of the lesson today, and we'll try to summarize what we learned for each one. Okay, so let's jump right into today's activity. I think you might be able to relate to the particular context here. The question that we are trying to answer today is, do you have senioritis? The senioritis 20 virus. And so here's what the problem says, if you can follow along with me here. It says, a large high school in Michigan is concerned that too many of the seniors have contracted the senioritis 20 virus. The administrators have decided that if more than 30% of the seniors have the virus, they are going to cancel spring break. To make this decision, they will select a random sample of 50 seniors and have them tested. Okay, I have a quick review right at the beginning of this, just to make sure that we know our definition for the errors and the power. And I've organized it in this nice little chart here, good way to keep track of things. And here's how it works. If you look on the left-hand side, there is the conclusion, right, based on the sample. And when you do a significance test, like you've done with Mr. Murphy all week, there are only two choices in the end. Either you get a p-value that is small and you reject the null hypothesis, or you get a p-value that's large and you fail to reject the null hypothesis. Those are the only two choices. If we look up here, this is the actual truth. And once again, there are only two possibilities. Either the null hypothesis is true or the alternative hypothesis is true. And so there are four different scenarios that we need to think about here for each one of the four boxes and try to decide first, is that a good decision or did we make an error there? And so I'd like to start in the column where the null hypothesis is true. So let's just assume the null hypothesis is true and let's think about each one of these decisions and try to decide which one is the correct decision. Well, if the null hypothesis is true, we don't want to be rejecting the null. We want to fail to reject the null. That would be the good decision, right? So when we reject the null, this is a mistake or an error. In fact, this is exactly what a type 1 error is. Go ahead and label that in the top left box there. Now we said that if we fail to reject the null, that's a good decision. Well, we don't have a specific name for that. So I'm just going to put a big smiley face here because that means we made a good decision, right? Now let's move over to the second column where now the alternative hypothesis is true. And in this case, rejecting the null hypothesis would be the right thing to do. If the alternative is true, we would want to reject the null. So our smiley face goes here. And then the bottom right would be a mistake, right? If we fail to reject the null, and sure enough, that is a type 2 error. Now we do have a special name for this one in the top right. This particular smiley face that we have here is what's called the power of the significance test. And we're going to talk a little bit more about that at the end of the activity today. But I want to start by thinking about this type 1 error and type 2 error. And so one of the ways to remember the definitions is to know this chart. Now, you can see this chart. The other way that I try to help my students is just with like what I call the short definition. So let's give the short definition of each one of these errors. Okay, the short definition of a type 1 error. Type 1 error is that the null is true and we made a mistake. And the mistake here would be to reject the null hypothesis. There's your short definition of a type 1 error. For a type 2 error, now the alternative is true and we made an incorrect decision or an error here, and that error is to fail to reject the null. Now, how do you remember this? The way that I remember the short definitions is really all you have to know is that a type 1 error means the null is true and a type 2 error means that the alternative is true. And that's in the same order that we typically write our hypothesis, right? Null hypothesis first, alternative true. The reason why I think you only need to know that first part of the definition is because you can get the second part of the definition by just thinking about what the error would be. If the null is true, the error would be to reject the null. If the alternative is true, the error would be to fail to reject the null. So the only part you really have to remember is what's actually true for each one of those. For a type 1 error, the null is true. For a type 2 error, the alternative is true. Okay, with that quick review out of the way, I think we are ready to jump into the concept here about this high school in Michigan where they've got the senioritis problem and the administrators are going to go take a sample and do a significance test to decide what they want to do about spring break. So we're going to start with the hypotheses here in alpha level 0.05. Now we're definitely in the world of proportions here rather than the world of means, and it is a one sample problem rather than a two sample problem. So the parameter in this case is going to be a proportion and only one. So we're going to say P represents the true proportion of all seniors at this high school with senioritis. Right? That's the parameter that we're trying to estimate for the whole population of all seniors at this school. And the null hypothesis here is going to say that the proportion is 30%, and the administrators are trying to find evidence that the true proportion is greater than 30%. In which case we're in trouble and we need to cancel spring break. So I think it's important to just think for a moment about what these hypotheses actually mean in words. And so for the null hypothesis, if we're saying P equals 0.30, that means that all is safe, right? If 30% have senioritis, that's okay. It's when it's greater than 30% that we're in trouble. So I'm going to say down here for the alternative, danger. That's the dangerous situation, and that's where the administrators are going to decide to cancel spring break. Now, if the null is true and all is safe, they're not going to cancel. So I'm going to add here that they don't cancel spring break. Okay, now that we have our hypotheses clearly defined, we are ready to talk about errors, type 1 error and type 2 error. So let's start with type 1 error. And remember, for a type 1 error, the short definition is the null is true and we made a mistake. The mistake would be to reject the null hypothesis. So here's the way I think about it. The null is true, which means this part is true, but we've made the wrong decision. So I'm going to draw an arrow down to the wrong decision here. This is a type 1 error. When the null is true, but we've made the wrong decision and gone with the alternative hypothesis. Now we do need to be able to put that all into words here in our answer. So let's put that into words, starting with the null hypothesis. Right? The null hypothesis says that the true proportion with senioritis is 0.30. Right? The null is true, that the true proportion is 30%, which really means all is safe. But we make a mistake, and the mistake here is they're going to go with the alternative hypothesis. So that means that the administrators are going to carry out the significance test, and they're going to get a p-value that's really small, and they're going to reject the null because they have convincing evidence for the alternative. So I'm going to say the administrators find convincing evidence for the alternative, and they reject the null. So if they reject the null and they find convincing evidence of the alternative, they are going to cancel spring break. Now I can only imagine that the seniors at this particular high school would be outraged by such a decision, that the administrators would decide to cancel spring break when they really shouldn't have. Right? Really all was safe, but they made the incorrect decision to cancel spring break, and now all of the seniors are completely outraged. Okay, now let's look at the idea of a type 2 error. So quick definition for type 2 error: remember that the alternative is true, but we made a mistake, and the mistake would be to fail to reject the null. So once again, let me go back up to my hypotheses. This time the alternative is true, but we've gone with the wrong conclusion here, saying that all is safe. This is the type 2 error. We just have to put that all into words now. So let's start by stating that the alternative hypothesis is true, which says that the true proportion with senioritis is greater than 0.30. Right? Greater than 30% with senioritis. This is the dangerous scenario. So that's the truth. The truth is that we're in a dangerous scenario here, but the administrators are going to make the wrong choice here, and they don't find convincing evidence for the alternative, and they fail to reject H null. So that means we're up here. This is what they decide. They decide not to cancel spring break. So don't cancel spring break. Now, from the perspective of the seniors, they would be completely fine with this error. Even though senioritis is high, they're still allowed to go on spring break. But let's flip our perspective now and think from the perspective of the administrator. It says from the administrator's perspective, which error has more serious consequences? Well, definitely here, type 2 error is the one that the administrator wants to avoid, because that's the case where senioritis is actually very high and it's dangerous, and they still send kids off to spring break, where we know the senioritis is going to get much worse. So we're going to say here that the type 2 error is the one with the more serious consequences. And the reason why is that senioritis is at dangerous levels, but they do not cancel spring break. And we know if that were to happen and all the seniors would go off to spring break, when they come back, the senioritis will be even worse. Right? So the consequence is that senioritis will get even worse. All right, so hopefully that gives you a good idea about how to interpret, how to visualize these ideas of type 1 and type 2 error. But I would like to give you an even better visual of this with some sampling distributions, show you with some graphs here. So let's go ahead and flip to the next page, and I think this will help solidify some of your understanding of the type 1 error and the type 2 error. So here number 3 says, draw a picture of the sampling distribution under the assumption that the null hypothesis is true. Okay, listen, the null hypothesis is true. As a quick reminder, the null says that everything is safe and that the true proportion is 30%. Right? That's our null hypothesis there. And we want to draw a picture where the null hypothesis is true. All right, so this picture I'm about to draw is a picture where the null hypothesis is true. And we know that the null hypothesis says that P is 0.30. So I know that has to be the center of the sampling distribution. And we have this normal condition that we can check, which would check the expected number of successes and failures, both of which would be greater than or equal to 10, which is telling me that I'm going to have a relatively normal distribution here. So I'm going to do my best to draw in a normal distribution, and I want to make sure that it's centered at 0.30. So I'm going to be careful here. I want it to be centered about 0.30. So it looks to me like 0.30 is about the center of this normal distribution. I'm doing my best there to make sure that the center is at 0.30. So there is the sampling distribution under the assumption that the null hypothesis is true. Now let's think about this. The administrators, they go out, they take a sample of 50 seniors, they get the sample proportion back, and they do a whole significance test, and they have to get a p-value. Now, if they go out and they get a sample proportion of say 50% when they take their sample, right? Well, that's very high, and the test statistic is likely to be very high, and the p-value, which is this little area here, is very likely to be small. And so what would the administrator do in that case? Well, in this case, they would definitely reject the null hypothesis, right? If they had a small p-value. And actually, the p-value maybe could be even a little bit bigger than that, as long as the p-value is less than 5%, right? And so 5% would be this area right here. Now, we can actually figure out what would be the cutoff value, and it turns out the cutoff value is like right here. If you got a p-hat value of about 0.407, anything bigger than that would give you a p-value less than 5%, and you would reject the null hypothesis. Anything less than that, and you would fail to reject the null hypothesis. So let me make this clear in my picture here, that anything to the left of that value, we would fail to reject the null hypothesis. So the green section there is where we would fail to reject the null. The red section is where we would reject the null hypothesis. Now let me just pause for a second here. If the null hypothesis is true, and we reject the null hypothesis, that is a mistake. That is an error. In fact, it is a type 1 error. And so the area that you see represented in red here, it represents the type 1 error. Now the area in green, well, that would be a good decision, which I've been calling smiley face. So I'm just going to draw in my little smiley face. That means we made a good decision on that, right? So the one thing that I want you to take away from this picture is this red region here where we reject the null hypothesis. We know the area of that would be equal to the alpha value of 5%, right? So it turns out that the probability that a significance test makes a type 1 error is just equal to the alpha value, which for us is 5%. So you have two parts of that picture. On the left part in green, you have smiley face. On the right side, you have a type 1 error. So what we're talking about in this chart here is where the null hypothesis is true. So where the null hypothesis is true, there are two possibilities, one of which is smiley face, one of which is a type 1 error. And you can see that represented by the green and the red regions in the picture. Now let's move to the second sampling distribution, number 4, which says suppose the true percent of seniors at the school with senioritis is 50%. Draw a picture of the sampling distribution under the assumption that the alternative hypothesis is true. Okay, now hold on here. The alternative hypothesis on the previous page said that the proportion with senioritis is greater than 30%. But in this problem, they're giving us a specific value for that proportion as 50%. So we're going to write the alternative hypothesis as p equals 0.50, a specific value of the alternative hypothesis, right? So let's see what that picture would look like. Where now, not the null is true, but the alternative is true, and it's a specific value of the alternative at 50%. Well, now we need 50% to be at the center of our sampling distribution. So once again, I'll do my best here, try and draw a normal curve that has a center. Look, I did it again. Let me move it over just a little bit. I need the center of it to be right at about 50%. We'll put it like right about there, and say that 50% is at the center of that sampling distribution, right? So that's when the alternative hypothesis is true. So let's think about that decision that we made up above, where 0.407 was the cutoff value. Anything to the right of it, we rejected the null. Anything to the left of it, we failed to reject the null. Now let's carry that down to here, and I'm going to write in p hat equal 0.407 here. Now we know that to the right of it, we're going to reject the null. Well, in the case where the alternative hypothesis is true, rejecting the null is actually the correct decision to make. And so everything to the right of that value over here, this is a good decision. So I'm going to put it in green because it's a good decision, right? The bad decision or the error here would be if we failed to reject the null, and that's going to the left. So now this area going to the left here, this is where we're making the mistake of failing to reject the null. So fail to reject the null is now on the left there. Here's where we reject the null. One of those is a good decision. One of those is a bad decision or an error. And sure enough, if you look at our table back here, we're now in a scenario where the alternative is true. And if it's a good decision, we call it power. And if it's a bad decision, we call it type 2 error. And so this means that in green, we have what's called the power of the significance test. And in red, we have a type 2 error. So good decision, power, bad decision, type 2 error. Well, one other thing to recognize here, for this sampling distribution, we know the total area underneath the normal curve is 1. And so there's a relationship now that we see between the type 2 error and the power that if you were to add those two together, it would have to add up to 1. And so the probability of a type 2 error plus the power of a significance test, we know has to add up to 1. We can see that right in the picture there. Okay, so let's talk about this idea of power, that green region that we see there, which is a good decision when the alternative is true. So in this setting, the power of the administrative significance test is 0.91 interpret. Okay, so for power, we know that the alternative is true, and we've made the correct decision here, which is to reject the null hypothesis. And we know that's going to happen 91% of the time. So let's just put that into words, all right? So let's start with the alternative hypothesis being true. So we will say if the true proportion with senioritis is 0.50, and you'll notice here that I'm giving the specific value of the alternative. I'm not saying greater than 30%, I'm saying 50%. That's the value that was given to us, right? So if the true proportion with senioritis is 50%, there is a 0.91 probability that the significance test will correctly reject the null hypothesis, right? And find convincing evidence of the alternative. So that's a pretty good chance, 91% chance that if we really are at dangerous levels of the school, there's a 91% chance that the significance test will make the correct decision here to cancel spring break. Now, I'd like to show you an applet here, which is going to combine these two pictures where the null is true and the alternative is true. We're now going to combine those into the same picture here using this applet. So this applet is, there's a link on the activity here, or you could just certainly follow along with what I have on my computer here. So this applet is going to allow us to see the power represented in a picture format here, okay? So the first thing we need is the null hypothesis, and we know the null hypothesis is 30%, so I can input 30%. And the alternative hypothesis we know is greater than. And display, I'm going to leave that blank for now. The true value of p, that's the alternative, well, it's already at 50% for us, that's good. The sample size is already at 50, that's good. And the type 1 error, the alpha is at 5%, that's all good. And so you can see here, this red distribution is the distribution where the null hypothesis is true, and the blue distribution is the one where the alternative is true, just like we drew it in our pictures in the activity. Now let me start by showing you the type 1 error here. And when I click that, you'll notice this red region right here, which matches with what we have on our paper, right? And we know that the probability of that type 1 error is 5%, which we said is the alpha value. So notice, if I start to increase my alpha value, watch what happens to that red region as I increase alpha. You'll notice that the area is increasing, and sure enough, the probability of the type 1 error is also increasing all the way up to 9% now. So you can see visually that the probability of a type 1 error is equal to the alpha level. Now let me take that back down to 5%. And now let's talk about the type 2 error. Well, notice the type 2 error is using the distribution where the alternative is true, and this is where we would fail to reject the null hypothesis. So you see that represented in blue, and it actually shows you the probability there as 9%, right? And the power is 91%. So we go ahead and click power, which is represented by the green region there, okay? And you'll notice that the probability of a type 2 error plus the power is 1, right? Or 100%, which we know because that's all the area underneath that. So you can clearly see the probability of a type 2 error plus the power has to equal 1. Now I'd like to focus in on this idea of power for the last part of the activity, and that means that we're going to focus in only on the region that is green in the picture here. So I think we should draw this into our notes here, and then let's talk about how we might be able to increase that power. So for our picture here, we're just going to take the two pictures that we have up above, and we're going to drop them onto the same picture here. So the red distribution has a peak at 30%, that's where the null is true, and the blue distribution has a peak at 50%, and that's where the alternative hypothesis is true. And specifically now we're trying to focus in on this idea of power. And the idea of power is this region right here that we're going to represent in green, which you see represented in the applet as being green. And we know, well, currently the power is 91%. So we want to know, are there ways that we can increase the power, which would be important to the administrators, right? Because if there really is a problem with senioritis at the school, they want to know about it so that they make the right decision and cancel spring break. So the administration wants to increase the power of the test. How can they adjust each of the following factors to increase the power? So let's go back to the applet now, and this is where the applet becomes really powerful. You can see dynamically how things are changing when you change other things within the applet, right? So let me start with the sample size, and you can probably guess what's going to happen here. If you want your significance test to make the correct conclusion at the end, do you think it would be better to have less or more in your sample size? And I hope you say that you want a higher sample size. So notice what happens when I start to increase my sample size. As I increase the sample size, what's happening to that power? Now I've got power all the way up to 99%, right? So clearly increasing the sample size is going to increase the power. And the two things that are happening, now notice this again, we go back to 50, and watch what happens as I get a bigger and bigger sample size. What's happening to the distributions is they are getting skinnier, right? So there are less area in the tails. And you also notice this cutoff value is actually moving to the left, which is also increasing our green area there. So number one way that we can increase the power of the test is just increase the sample size, right? That's number one. Number two is what can we do to the alpha level? Well, let me go down to the alpha level here, and let's look what happens when I increase the alpha level. So watch what happens, increasing the alpha level. Well, you'll notice that the distributions are moving, but this cutoff value where we reject the null hypothesis is moving, and it's moving further and further left, which is increasing our power. And the reason is because when we move this cutoff value to the left, it's increasing the chances that we would reject the null hypothesis, which if the alternative is true is a good decision. That's our power. So it's becoming easier to reject the null know, which increases our power. So number 2 way that you can increase power is to increase the alpha level. Now the third way, and this isn't something that we necessarily have control over, but I'd like to think about this alternative value for p, which is 50%. Watch what happens if the alternative value for p is bigger than that. Well, very quickly the power gets very, very strong, 100%, right? By the time I'm at 0.71. And this seems to make sense, right? If the true proportion of the seniors that have senioritis is 70%, I sure hope our significance test will be able to detect that by rejecting the null hypothesis. So the idea here is that the alternative value is getting farther and farther away from the null value, right? Which is increasing our chances of making a good decision. So that's number 3, is to increase the distance between the null and the alternative value in our hypothesis. So let's capture that idea in the last question here in the activity. Sample size, what do we want to do with the sample size? We want to take n and we want to increase it, okay? Alpha level, we decided if we want to increase the power. Increase the alpha would increase the chances that we reject the null, which would increase the power. And then for the alternative, we decided the further it was away from the null, the better our chances of making a good decision power would be. So I'm going to say farther from the null hypothesis. So those are the 3 ways where we can impact the power of a significance. All right, I think we are ready to try and summarize our learning. So this is where I'm going to go back to the 3 learning targets from the beginning of the lesson, and let's just put down some quick notes about what we should get out of each one of them. So starting with learning target number 1. So for learning target number 1, that was for us to understand how to interpret or describe a type 1 error and a type 2 error. So let's capture that idea here. Starting with the type 1 error. Okay, the definition for a type 1 error is that the null hypothesis is true, but the test finds convincing evidence for the alternative. Finds convincing evidence for HA, right? That would be an error, right? That the null is true, but the test finds convincing evidence for the alternative. Make an error there. That's type 1. Type 2 error. Remember now the alternative hypothesis is true, but we make an error, and this time the test does not find convincing evidence for the alternative. So the test does not find convincing evidence for HA. So if you're asked to do that in a free response question, you always want to make sure that you do that in the context of the problem. All right, learning target number 2. For this one, we talk about power and how to interpret power, as well as how we increase the power of a test. So let's start with the interpretation of the power, right? Remember, for the power, we were in the second distribution where the alternative is true. So if the alternative is true, and I want to make note here that you don't give the generic alternative, you give the specific value of the alternative. So I'm going to say here, use specific value, right? For us, it was 50% of the seniors had senioritis. There is a, and then this is where you would put whatever your power is, and that is definitely a probability. We want to describe that as a probability of correctly rejecting H null. And what that really means is that we find convincing evidence for HA, right? So notice there that I'm using the word probability, and in fact, it's a conditional probability. It's that the condition comes right up front, right? Assuming the null hypothesis is true, or given the alternative, given that the alternative is true, it's the probability of correctly rejecting the null hypothesis. That is a conditional probability. Now let's make note of the 3 ways that we talked about where we can increase the power of a significance, right? We had 3 different ways to do this. Number 1, this is probably the easiest way and most intuitive, is to increase the sample size. Number 2 was to take that alpha value and increase it. And number 3 was to take the distance between the null and the alternative and make that distance bigger. So the distance between the null and the alternative, make it big, increase. And finally, learning target number 3 was to understand the relationship between all 3 of these things that we're talking about. So here are the important things you need to take away. First of all, the probability of a type 1 error. We know that that is just equal to the significance level alpha. The other thing that we determined was that the probability of a type 2 error added to the power of the significance test has to add up to 1. So if you're given the power, you should be able to find the probability of a type 2 error. If you're given the probability of a type 2 error, you should be able to find the power. I want to make one final note here. It's this idea of increasing the alpha, right? We have the decision to make about what the alpha would be, and let's suppose that we decide to increase alpha. I want to think about what impact that would have on some of these other things here. Well, the first thing we know is that if we increase alpha, the probability of a type 1 error, of course, is going to go up because the probability of a type 1 error is the alpha level. But here's the other thing we decided, that if we increase alpha, that also increases the power. So the power would actually go up. But then go back here and think about it. If the power goes up, what has to happen to the probability of a type 2 error if those two are going to add up to 1? Well, the type 2 error has to go down, right? So the probability of a type 2 error actually goes down. And so the thing I want you to notice here is that when you're trying to decide your alpha level, whether to increase it or decrease it, it's having the opposite effect on the probability of a type 1 error and a type 2 error. And so depending on the consequences of the type 1 error and type 2 error, that might help you make a decision about your alpha level, right? For example, the administrators really didn't want to make a type 2 error, so they might have increased their alpha level in order to decrease the probability of type 2 error. All right, so there's a check your understanding problem. This is your homework problem for the weekend that will be due on Monday. Mr. Murphy will start his lesson on Monday by taking you through this practice problem. It's also available to download at statsmedic.com/YouTube. So listen, I hope you got something out of today's lesson. If you did, make sure you give me a thumbs up there in YouTube, and I hope that you will join Mr. Murphy on Monday, and I will be back with you all on Tuesday. So have a wonderful weekend. All right, hello AP Stats students from around the country, and welcome to the College Board of Virtual Instruction for AP Statistics. My name is Luke Wilcox. I'm an AP Stats teacher at East Kentwood High School in Kentwood, Michigan. I hope that you were able to log on yesterday and check in with my colleague, Mr. Brendan Murphy. He and I will be sharing the duties of covering these lessons, and I think we are ready to jump right into things today. So we're going to go ahead and get started here. So just to check to make sure that everyone is in the right place, this is AP Statistics. As I have mentioned already, my name is Luke Wilcox, proud teacher at East Kentwood High School. And I'm going to start with a couple of reminders. If you've been with us for the last couple of weeks, you may already know this, but if we have anybody that's new to us today, I just want to make sure you know where we are in the sequence of instruction here. We are meeting Monday through Friday on a daily basis at 2 o'clock. All these videos are also available afterwards as recorded videos. And right now, we are in the middle of our AP exam review. We just started on Monday, and we are currently in this first week of April 6th to the 10th, where we will be covering units 6 and 7 from the College Board CED, which would be the inference for proportions and means. There's a good chance that your teacher already got to this content, but there is also the chance that your teacher did not get to this content before the end of the year. So that's why we're starting our AP exam review with units 6 and 7, which will be contained on the AP exam for 2020. It's the final 2 units of 8 and 9 that will not be covered on this year's AP exam. Now, after we finish unit 6 and 7 this week, then starting next week, we're going to go way back to the very beginning of the course and go in order units 1 through 5. And we actually have 3 weeks to get through all of that stuff there. So by the time we are done on May 1st, we will have taken you through all of the content that will be covered on the 2020 AP Statistics exam, which we now know is going to be on May 22nd. That is your AP Statistics exam. A couple of other quick reminders, all the resources that you might need for these lessons, you can find at statsmedic.com/YouTube. That's where you can download the lessons if you want to print those out. You'll also have access to the homework questions that you'll see available on this website. And then finally, if you or someone that you know might be in need of a device or internet access in order to be able to take that AP exam on May 22nd, there's a website here that you can go to, or you can have your friend go to. The College Board is very committed to making sure that every student has access to a device and internet access on the day of the AP exam, because these exams will be taken at home. Okay, now that we have those reminders out of the way, I think we can jump into the homework problem that Mr. Murphy gave you yesterday, which is also a very good preview of what's to come in the lesson that you're going to see here today. So let's jump right in. Follow along with me here. It says a test engineer wants to estimate the mean gas mileage. So right away, I know that I'm trying to estimate a mean rather than a proportion in miles per gallon for a particular model of automobile. 11 of these cars. Okay, sounds like our sample size is 11 here. Are subjected to a road test, and the gas mileage is computed for each car. A dot plot of the 11 gas mileage values is roughly symmetric and has no outliers. The mean and the standard deviation of these values are 25.5 and 3.01. Okay, let's pause right there. Let's make sure that we know exactly what we're getting here in the problem. This 25.5 is a mean, but because it's a mean calculated from a sample, we're going to call that x bar. And then the 3.01 is a standard deviation, but it is the standard deviation of a sample, so I'm going to be using s there. And it says assume that these 11 automobiles can be considered a simple random sample of cars of this model. Which of the following is correct? And very clearly, when I look at the answer choices here, they're wanting us to think about calculating a confidence interval here for the mean gas mileage. And so I'm going to remind you of a couple of general formulas that are always true for any confidence interval that we're trying to calculate. The first of which says that the general way you construct a confidence interval is to take some sort of guess, which we call our point estimate, and then to add and subtract a margin of error to account for sampling variability. Now, there's another version of this that you will get on the formula sheet for the AP Statistics exam. It looks like this. It says statistic plus or minus the standard error of the statistic. Now, let's try and make this formula more specific for the thing that we're trying to estimate, which is a mean. So for us, the statistic is going to be the mean of the sample. That's our best guess, plus or minus. Now this, oh, I'm sorry, I missed the value in here. The standard error of the statistic, there's another value that comes before that, which is the critical value. So the critical value times the standard error of the statistic. I need that critical value, which tells me how many standard errors away from the mean we need to go in order to capture 95%. So that's T star, and then the standard error is S over the square root of n, which you can also find on your formula sheet. So that's the format. Now you look, all the answers sort of follow that format, except answer choice E, which says the results cannot be trusted. The sample is too small. Well, I do have a sample of only 11, and I seem to remember that we would like to have a sample size of 30 or more in order to know the sampling distribution is approximately normal. But if our sample size is small, we can look at the sample data to check that there's no strong skew or outliers, which sure enough, they tell us that the dot plot is roughly symmetrical and has no outliers. So our normal condition is going to be satisfied here, and the sampling distribution will be approximately normal. So this really isn't an issue. That's not going to be one of our possible answers. Now, as I look at the four other answer choices, right away, I'm noticing that in the bottom, underneath the square root, I see 11s and I see 10. And I know that it's supposed to be my sample size, which we know is 11. So this right here is incorrect. So I'm going to get rid of answer choices C and D. Now I'm left with just answer choices A and B, and I notice the only difference between those two is this T star critical value. And here's the deal with the critical value. In order to calculate the critical value, we have to know the degrees of freedom, which is given by n minus 1. So for us, the degrees of freedom for this problem is 10. Now we would take that and go over to our formula sheet here, which is the formula sheet that's given to you on the AP exam. And I'm going to go over until I find table B, which has my critical values, the T distribution critical value. And the way this table works is that you have to know your degrees of freedom. Well, we know our degrees of freedom is 10, and we know the confidence level that we want is 95%. So if you find out where those come together, they come together at 2.228, which is how many standard errors we need to go away from mean to capture 95% of the data. That is our T star value. So let me go back and check which one of those has the correct value, 2.228, which is answer choice A, because answer choice B has the wrong critical value there. So our final answer in this multiple choice question should be A. So I hope that you did all right on that homework problem, and you are now ready to jump into some new learning for today, which is going to be related to this homework problem that we just did. So let me give you a quick overview of things. This is where I give you the learning targets for the day, and they are very straightforward here. There are two of them, okay? And both of them are about constructing and interpreting confidence interval. But you'll notice that the first one is to construct and interpret a confidence interval for a population mean, and I'm talking about one mean there. Whereas the second learning target is a confidence interval for the difference of two population means. So there you are going to have a two-sample problem or an experiment that utilizes random design. Now for both of these learning targets, I'm going to use the familiar, hopefully familiar to you, four-step process of state, plan, and do conclude. So here we go. Here is the activity for the day, and it is an AP statistics versus AP calculus battle here. And the question that we're trying to answer today is how will you prepare for the AP exam, or more specifically, how much time will you spend preparing for the AP exam? So here's what it says: a random sample of 20 AP statistics students from last year was asked to share the number of hours they spent preparing for the exam. Here are the results. Okay, so right away I got this number 20. That sure sounds like our sample size. I'm going to call that n. And let's take a look at the results here. Okay, so we get a dot plot, and I notice in the dot plot it looks like it's maybe fairly symmetric. Doesn't appear to be any outliers there, but I'm also given some summary statistics here. And sure enough, here's our sample size of n. Here's the mean of the sample. So let's be careful with our notation here. This is x bar because it is a sample mean, and then the standard deviation that's next to that, that is a sample standard deviation, which is s. So let me pause right here and make note of one thing. This is going to be different for estimating means than for estimating proportions like we did earlier this week. And here's the issue: not only are we trying to estimate the mean of the population, but we are now also having to estimate the standard deviation of the population because we don't know sigma, the standard deviation of the population. So when we standardize a statistic, we now have two values that are varying according to the sample, which is the sample mean as well as the sample standard deviation. And this is why we are going to be left using what's called a T distribution rather than a normal distribution. And so that's why that critical value is going to be a T star critical value rather than a Z star critical value. And just to be clear, the reason why we're having to use that is that we don't know sigma, which is the standard deviation of the population. All right, so here we go. Construct and interpret a 95% confidence interval for the true mean number of hours spent preparing for the AP exam for all of last year's AP stats. Okay, we're going to start by identifying the parameter, which is mu. This is the thing that we're trying to estimate here, and that is the true mean number of hours spent preparing for the AP exam for all of last year's AP stats students. Now, one thing I want to point out here is I'm being very careful with my language here to make sure that I'm referring to the population and not the sample. And so I use the word true and I use the word all to make it very clear that I'm referencing the population. We're trying to estimate something from the population. Now, our confidence level, of course, is given to us in the problem. This is the familiar 95% confidence level. All right, as far as the name of the procedure, first thing to notice is that we only have one sample here. So this is a one sample. It is an interval, and we have to decide whether it's a Z interval or a T interval. We've already talked about why this has to be a T interval. And then let's also specify what it is that we're trying to estimate here, which is a mean, a true mean. All right, so we are now ready to check conditions, and these are going to look hopefully very familiar to you. We're going to start with the random condition, which is where we check that we do in fact have a random sample. And this is given to us right in the wording of the question right up top here. So I'm just going to steal the words right from the question, which tells me that we have a random sample of 20 AP stat students. Now, the reason why this is important, I call this the so what. We need a random sample so that it is representative of the population so that we can generalize our results to the population, right? That's the value of having a random sample. All right, next up is the 10% condition, which we need to check if we are sampling without replacement. And in this case, I'm sure that we didn't take one AP stat student and then put them back in the pool after we sampled them, right? So once they're taken out, this is without replacement, which means that we do need to check the 10% condition here. And so we would check that our sample size is less than 10% of the population, which is all AP stat students from last year. And well, we know well that there are hundreds of thousands of AP stat students, and so definitely the 10% condition is going to be satisfied. And the so what here is, so this idea of sampling without replacement is okay. That's not an issue. We don't have to worry about independence because the sample size is small relative to the population. And the third condition, which I'm going to call the normal or the large sample condition, is where we're checking to make sure the sampling distribution is approximately normal. And ideally, I'd like to have a big sample size of say 30 or more, but in this case, we do not. We only have a random sample of 20 students. So when your sample is smaller than 30, you have to look at the sample distribution to make sure that it appears like it could have come from a population distribution, which is approximately normal. So specifically, you're looking for no strong skew and no outliers, which I think we see here definitely in the dot plot. And so the way I'm going to justify this is I'm going to say that the sample distribution, notice I'm saying sample distribution, not sampling distribution, because I'm just talking about the distribution of our sample of 20 students. The sample distribution shows no strong skew or outliers, which means it's reasonable that this sample data may have come from a population distribution, which is approximately normal, which then allows us to say that the sampling distribution is approximately normal. So that's the so what. The sampling distribution is approximately normal. So with our three conditions satisfied here, we are now ready to actually go ahead with the calculation. So let's move down to where it says a general formula here, and I will start with the most general formula for calculating a confidence interval, which is to make a guess from our sample, that's our point estimate, and then to add and subtract a margin of error, which will allow us to account for sampling variability. Now on the formula sheet for the AP exam, you have a different version of this, which is statistic plus or minus your critical value multiplied by the standard error of the statistic. And we are ready now to give us our specific formula. The statistic here is x bar, that's our sample mean. We know the critical value has to be a T star value, and then the standard error, which is also on the formula sheet, is s over the square root of n. So we're ready to plug in some numbers now. We know our x bar, if I look back up here, it is 11.4. Now I do need my T star value here. In order to get that, I need table B, and I need to know the degrees of freedom. And we said that the formula for the degrees of freedom is n minus 1. Our sample size here was 20, which means that our degrees of freedom is 19. So if I go back over to my table B here, and now I'm looking for, let's see, degrees of freedom 19, and once again, I want 95%. So it seems to me that 2.093 is my T star critical value there. So let's go back and fill that in, 2.093. My standard deviation S, I can look up above, is 3.719, all over the square root of n, which is going to be 20. Now, I punched these numbers in my calculator already here. 11.4 plus or minus a margin of error of 1.74. And that's going to allow us to arrive at a final answer of 9.66 up to 13.14 as our confidence interval. Now, as far as interpreting this confidence interval in our conclusion, it's going to look very similar to what we did when when we were estimating proportion. So here we go. It says we are 95% confident that the interval from, and this is where we give the actual values of the interval here, is 9.66 to 13.14. But let's be careful to include units here, right? We didn't have to worry about that with proportions because proportions don't have units. But here we do have units. We're trying to estimate the number of hours. So this is going to have the units of hours. And then we want captures the. Now the thing we're trying to capture, remember, is the parameter, which really just comes from the wording of the question. So I can literally steal these words from the question and bring those down into my conclusion here. So I'm going to say the true mean number of hours spent preparing for the AP exam for all of last year's AP Stats. So let's talk real quick about what the rubric might look like. So I went back and I perused a few of the old rubrics on the College Board website, and it tends there's some tendencies, the things that you'll always notice they're looking for on the rubric. First of all, somewhere you have to identify the correct procedure, and of course the easiest way to do that is by mentioning the name of the procedure. But you can also get credit for identifying the correct procedure right down here where we've shown the formula that we're using. Now you don't have to have both; you gotta have one out of the two. That identifies the correct procedure. Next up on the rubrics typically is that you have to check your conditions. Now if you look back at most of the rubrics, they will talk about the random condition and they will talk about this normal large sample condition. It was only last year where we first saw the 10% condition show up on a rubric, which I think now will be the standard if you are sampling without replacement. So in this case, you want to make sure you have all three of those conditions. And then of course the rubric is going to check to make sure that you have the correct interval, which is your answer here. So realize that this answer is the thing that is going to be graded, and some of this work that we have here is not necessary in order to get full credit. Although I really like having it, I like showing it. It helps you catch mistakes if you're going to make a mistake, but it is not required in order to get full credit there. And then finally, you have to have the correct conclusion. And there's a couple of things that we want to look for in this conclusion. First of all, let's make sure we're using the word confident and not the word chance or probability there. We want to make sure that we have the correct units here because we're estimating a mean. We need to make sure we're referencing the population here, which I use the words true and all, and then also make it clear that we're trying to estimate a mean here rather than a proportion. And then you want to make sure that you have some context of the question somewhere in your conclusion. Now, I'd like to also show you how you can do this on your calculator. So if you want to grab your calculator, you can do that. If you want to just follow along, I'm going to show you everything that you need from the calculator in order to check this confidence interval. Okay, so here we go. We need to go to the stats menu. So go to stat and then go over to tests, and you'll notice that most of the first ones are tests, and then you get down to the interval. And sure enough, here we want a t interval. So this number 8 here is a t interval for a mean. That's exactly what we want. A one sample t interval for a mean. So I'm going to hit number 8, and you have the choice of inputting all the individual values of the data by putting that into a list. We actually have the summary statistics, so I'm going to go that route because it'll be just a little bit quicker here. So let's start with the x bar value, which was 11.4, the sample mean. The standard deviation was 3.719, and we know the sample size was 20, and the confidence level that we want for this one is a 95%. Let me change that to 95%. I'm going to go ahead and hit calculate here, and sure enough, the calculator answer matches with what we had in our work. We had 9.66 to 13.14, which is precisely what you see here on the calculator. So I think this is a great way to check your answer. If you made a mistake somewhere in your work, you know to go back, look at that work, make sure that it matches up with what you see on the calculator. All right, I think we are ready now to jump into our second type of confidence interval here, which is now going to be a two sample problem. So if you flip to the next page there, let's take a look at what we have here. All right, so it says random sample, 20 AP Stat students from last year revealed they spent an average of 11.4 hours preparing for the exam with a standard deviation of 3.72. Okay, we already knew that from the first page, right? A separate random sample, 40 AP Calculus students from last year revealed an average of 9.1 with a standard deviation of 2.94. So very clearly here, we have two separate independent random samples. So let's get our notation down right away here. 20 is our sample size, but it's the sample size from the first sample, so I'm going to call that N1. 11.4 is the mean x bar of the first sample, so I'm going to call that x1 bar. And then the standard deviation over here is S1. And then we go to the AP Calculus students. 40 is going to be my N2 value, 9.1 is going to be my x bar 2, and 2.94 is going to be S2. So here's what we're trying to find. Construct and interpret a 90% confidence interval for the true difference of mean number of hours spent preparing for the AP exam for all of last year's AP Stats and AP Calculus. Okay, difference of means is what we're looking for here. All right. So in terms of our sample means, the difference of the means would be x1 bar minus x2 bar, which would be 11.4 hours for AP Stats, 9.1 hours for AP Calc, which is telling us that AP Stats student from our sample spent about 2.3 more hours on average. Now that's from the sample. Now we want to try and estimate what that difference would be for the whole population. So the parameter we're trying to estimate this time is the true difference in means, mu1 minus mu2. So I'm going to call that the true difference of mean number of hours spent preparing for the AP exam. And listen, this is where I'm going to make it clear which way I'm subtracting. We did AP Stats minus AP Calc, so I want to make sure that that's clear in my solution here, right? Because we could have done it the other way around, but I like doing it in the order that was presented here. So confidence level was given to us in the problem here. We're going to go 90%. All right, as far as the name of the procedure. Okay, what's different here than the previous confidence interval is that now we have two independent samples. So this is a two sample t interval, and the thing that we're trying to estimate here is mu1 minus mu2. Now the conditions are going to look very familiar to you. We are going to check the random condition, the 10% condition, and the normal large sample condition. The thing here is we're going to have to do twice the amount of work because there are two samples here. So the random condition, we do have two random samples. It's also very important to state that those two random samples are independent of each other. And that'll become important when we look at the formula for the standard error. So independent random samples of 20 AP Stat and 40 AP Calc. So we would say that that condition is satisfied, making note that we have included the word independent there. All right, 10% condition, sampling without replacement. Both of the samples got to check twice here. We already did it for AP Stats, but let me just record that. 20 was less than 10% of all AP Stat students, but now we need to also check the 10% condition for the AP Calc students. So 40 less than or equal to 10% of all AP Calc students. So our 10% condition is satisfied here. For the normal large sample, we have to check it for each sampling distribution here. We already did it for AP Stats, so I'm just going to write down what we had on the previous page, which was to say that the sample distribution, right, that dot plot that we had on the previous page, had no strong skew or outliers. Now for AP Calc, we have a much bigger sample size here of 40, which is beyond our value of 30, right? So this is a large enough sample that we'd be comfortable to say the sampling distribution is approximately normal for the sample means for the AP Calculus students. So we're just going to say here that the sample size is large, and to make that very clear, by large we mean that it is greater than or equal to 30. So our normal large sample condition is satisfied, and we can say the sampling distribution of the difference in sample means is approximately normal. All right, let's move to the do. And the general formulas are going to look exactly the same as they did on the previous page. Point estimate plus or minus the margin of error, and then we have our formula from the formula sheet, which says statistic plus or minus the critical value times the standard error of the statistic. Now the specific formulas we're going to have to do a little bit of work here. The statistic this time is the difference in the sample means, x1 bar minus x2 bar. Critical value, because we're still dealing with means and we have to use the standard deviation of the samples because we don't know the standard deviation of the population, it's going to be t star. Now the standard error, I just want to quick show you on the formula sheet where this is. Formula sheet here, it's on the second page. You can see on the right hand side we've got the standard error, and so here I'm looking at standard error, and we want two populations, and so look, this is it right here. So we're just going to copy that over for our standard error, which is the square root of s1 squared over n1 plus s2 squared over n2. What we're really doing there is we're adding the variances of the two sampling distributions, which we are allowed to because they the independent random sample. Now let's plug in some numbers here. 11.4 minus 9.1 plus or minus. Now t star, we need to know our degrees of freedom, but we have two different sample sizes here. So you might say, well, maybe the degrees of freedom is 20 minus 1, or maybe the degrees of freedom is 40 minus 1. Now, oops, I'm sorry, 40 minus 1, which would give us 39. Now there's two different ways that we can approach this. I'm going to show you the way sort of to do it by hand. We call this the conservative approach. It is more conservative to use a lower degrees of freedom here, and so we're just going to take the lower of the two degrees of freedom, and let's start with that, and then later I'll show you how we can use technology to get an exact degree of freedom. But for now, let's use 19. So I'm going to go back to my table B, and now I have degrees of freedom 19. Okay, so we're back at 19, but now I need 90% confidence interval. So I'm seeing a 1.729 as my critical value. So let me go back and we fill in our t star 1.729, and plug in some numbers here. It's going to be 3.72 squared over 20 plus 2.94 squared over 40. So I did these calculations already. I got 2.3 for my point estimate, and I got 1.65 for my margin of error, and that's going to give me final answer of, let's see, 0.65 up to 3.95. And I think we are now ready to make a conclusion here. All right, so here we go. We are 95% confident that the interval from 0.65 to 3.95, once again, we need units here because we're trying to estimate a difference of means. Units are hours again. And we're going to say captures the, and now we're just going to go back to the wording of the question, and word for word, we're trying to capture the true difference of mean number of hours spent preparing for the AP exam for all of last year's AP Stats and AP Calc students. And we have one final question to be able to answer, hopefully using this confidence interval. It says, based on the confidence interval, do we have convincing evidence that AP Stats students study more than AP Calc students on average? Well, listen, take a look at our interval here. These are the plausible values. These are the values we think are plausible for the true difference in means, all of which are positive, right? And a positive value here would indicate that AP Stats students are better. I mean, AP Stats students study more than AP Calc students, right? All positive values, no negative values here. So, of course, the answer is yes. And we'll say this, because all of the plausible values in the 90% confidence interval are positive, that means we have convincing evidence that AP Stats students studied more than AP Calc students on average. All right, now I do want to show you quickly how you can check your answer here on the calculator, and also show you something new that the calculator is going to give you that we don't have in our work shown here. So let's take a look at the calculator, and now we're going to be not doing a one sample t interval, but a two sample t interval. So go over to stat and then test, and you're going to have to scroll down until you can find a two sample t interval, right, which is 0 here, two sample t interval. Once again, you can input data to this, or you can use your summary statistic, and we have our summary statistic, so let's go ahead and use those. So the sample mean for AP Stat students was 11.4 with a standard deviation of 3.72 and a sample size of 20. Now for the AP Calc students, they had an average of 9.1 hours with a standard deviation of 2.94 and the larger sample size of 40. Now where it says pooled by default, oh, I'm sorry, let's get our confidence level. We want that to be 90% here, don't we? 0.90. Now for pooled by default, it should be on no. You should leave it there, okay? The reason you use pooling is if you, for some reason, thought that the standard deviation of each one of those populations was the same, then you might pool two samples together. But for AP statistics, you will not be making that assumption. So just leave that on no. And then go ahead and hit calculate. Now you're going to notice that this interval is slightly different than the one that we got by hand, and it's because of this degrees of freedom right here. Okay, the calculator has this big long fancy formula that it uses to find the actual degrees of freedom, which is going to change your interval just a little bit here. Okay, but for the most part, we had 0.65 to 3.95, very, very close. So let's go back to our activity. Let's at least record these values that we got from the calculator, just so that you have this in your notes here. It's a slightly different interval. Okay, so I'm going to record this down here. The interval that I got from the calculator was 0.69 to 3.92. Okay, this is from the calculator, and I should also indicate the different degrees of freedom that were used there. The degrees of freedom that the calculator gave us 31.24. Now listen, if you're going to use that answer, then some of your work now would be incorrect, right? This t star value isn't quite right. So if you are going to use your calculator work there, you're going to want to, you're not going to want to show this work here, right? Or you know what you could do is you could just leave this as a t star value, and that would be everything else would be correct. And you would have to recalculate this margin of error here, right? So that's up to you on the AP exam. Both the conservative approach to the degrees of freedom as well as the fancy approach using the big one formula, either one of those will be accepted on the exam. All right, I think we are finally ready to try and summarize hopefully what we learned here in the important ideas. And I'm just going to go back to the two learning targets that we started with at the beginning of the lesson. We're just going to split this thing in two here. And I'm just going to make a little table to remind us of some things here. Okay, learning target number 1 was about calculating a confidence interval, but for one sample. So that was a one sample t interval for mu, a single mean. Learning target number 2, we had two samples, and we were trying to find what's called a two sample t interval for the difference of proportion, or difference of mean, sorry, which is mu1 minus mu2. Now the way I'd like to organize this table, let's start by identifying the parameter for each one of these confidence intervals. For a one sample, it's just going to be one mean here, mu, which is going to be the true mean of something, right? Like some sort of context. Whereas the two sample, the parameter we're trying to estimate is mu1 minus mu2, which is the true difference of mean, and then some sort of content. All right, next up is to make a quick list of the conditions that are necessary, and there are 3 of them. We have the random condition, we have the 10% condition if sampling without replacement, and then we have what's called the normal large sample condition. And I think it's worth making a quick note about this normal large sample condition. There's actually 3 different ways that this condition could be satisfied. The easiest way is sometimes in the problem they will tell you that the population distribution is approximately normal, which would automatically mean that the sampling distribution is approximately normal. The next best way that you can get it is if your sample size is large, and when I say large, I mean that it's greater than or equal to 30. And the third way, which we had to utilize with the AP stats sample, was that the sample data shows no strong skew or outliers. All right, so let's move over to the two sample stuff, and let's see, the conditions there are the same, but they're twice as much work, right? Because now you have to check each one of these conditions 2 times. So I'm just going to make a note here that each one of these has to be checked twice for each one of the random sample. And the other thing too is that for the random sample, we want to make sure that those 2 random samples are independent of each other. Quick note too on the random condition, we could also have an experiment that utilizes random assignment into 2 groups, in which case it would be a 2 sample sample. Okay, the final thing that I'd like to record here is the specific formula for the confidence interval. For one sample, you got x bar plus or minus t star times s over the square root of n. For the two sample, we have x1 bar minus x2 bar plus or minus t star times this big formula for standard error, which is s1 squared over n1 plus s2 squared over n2, and then square root that whole thing. So the check understanding problem you see there is your homework problem. That'll be the first thing that Mr. Murphy will do tomorrow, is to go over that answer with you. I hope that you enjoyed the video today. I hope that you got something out of it. If you did, give me a thumbs up there. Please check in with Mr. Murphy tomorrow at 2 o'clock, and then I will be back with you again on Friday. See you then. Have a great night. Hello, AP Statistics students, and welcome to the College Board Virtual Instruction for AP Statistics. It is Monday, April 13, and my name is Luke Wilcox. I'm an AP Statistics teacher at East Kentwood High School in Kentwood, Michigan. And listen, I hope you've been looking forward to today's lesson, because today is the day where we go all the way back to the first week of AP Statistics, to some stuff that's very likely going to be pretty easy for you, but stuff you haven't thought about in a very, very long time. So I'm hoping to give you some important reminders today from some of the material that you learned very early on in the course. So let's go ahead and jump right in. First things first, let's make sure that we are all in the correct spot here. This is AP Statistics. As I mentioned already, my name is Luke Wilcox from Kentwood, Michigan. And I'm going to give you a couple of reminders here up front. And listen, if you've been with us for the last couple of weeks, you probably already know this, but we very well might have some new people with us today, because we are doing our review all the way back to the beginning of the year. So hopefully you know that we meet every day, Monday through Friday at 2 o'clock Eastern time. We are in the full AP exam review mode at this point, and starting today, April 13, we are going all the way back to Unit 1 in the CED, all the way through Unit 5, and that will take us up through May 1st. So that is the next 3 weeks of review here. Will take us Units 1 through 5. And we are preparing ultimately for the May 22nd AP Statistics exam. Now, any of the resources that you might need for the lessons, which includes the actual lessons themselves, as well as the homework problems, you can find at statsmatic.com/YouTube. All the lessons are organized there by date, so you would just look for April 13 for today, and you'll have access to a PDF of the lesson as well as the homework problem for today. And the final announcement here is for any student who does not have a device or internet access to be able to take that AP exam on May 22nd, can request access to those from the College Board at cb.org/tech. So if you or someone else that you know is in need of a device or internet service, please give them that address so that they can make that request. I do know that the College Board is very, very committed to making sure that every student has access to take the AP exam on May 22nd. Okay, so I'm going to jump back to the homework problem, which actually I assigned you on Friday. On Friday, we talked about type 1 errors, type 2 errors, and power. And this is an example question of something that you might have to think about on the AP exam here. So let's just jump right in and see how well you did. So here's what the question says. A one-sided hypothesis test is to be performed with a significance level of 0.05. So I'm going to pause right there and recognize the fact that we are given the alpha level, the significance level, 0.05. Suppose that the null hypothesis is false. Okay, this is important. If the null hypothesis is false, I'm going to say that another way, that has to mean that the alternative hypothesis is true. And that's probably going to be something that we'll need to know to answer the question. So if the significance level of 0.01 were used instead of a significance level of 0.05, which of the following would be true? So it appears to me that the question is saying, what would happen if we were to decrease the alpha level there? Now, I'm going to remind you of a couple of things from the lesson on Friday. First is just a quick overview of the type 1 error, type 2 error, and power. And I think the best way to organize this, we had a little bit of a chart that we looked at on Friday. And in this chart, on the top, we knew that either the null hypothesis was true or the alternative hypothesis is true. And because we were given in this problem that the alternative hypothesis is true, that's sort of a hint to me that I'm going to be looking at this column within this particular table. Now, the other thing that goes over here is our decision from the significance. And we know there are two possible decisions. Either we reject the null hypothesis or we fail to reject the null hypothesis. Now, if you recall from Friday, this top left here is what's called type 1 error. That's when the null is true, but we reject the null. The one below that doesn't have a fancy name, but I like to give it a smiley face because it is a good decision there. And then on the right-hand column there, when the null hypothesis is true and we reject the null hypothesis, well, that's a good decision. And in fact, we call that power of the significance. And then bottom right, this is another one of the errors, but this is called type 2 error. And listen, by the setup of this problem, because the alternative is true, we know that we're going to be dealing with this part of the chart here. And one thing to remember from Friday is that power and type 2, the probability of a type 2 error, are related to each other because those are the only two possibilities, which means that those two probabilities have to add up to 1. So the way we wrote that on Friday was we said the probability of a type 2 error plus the power has to equal 1 because those are the only two possibilities here. Now, one of the other big things that we talked about on Friday was how to increase the power of the significance. We mentioned 3 different ways that you could increase the power. So let's make a quick note of these here. Number one, probably the easiest and makes the most sense. If we're trying to increase the power, which is a good decision from our significance, it certainly makes sense that if we had a bigger sample size, that would probably help. So we could increase that. And one of the other things that we found on Friday was that if you increase alpha, that will also increase the power because it increases the probability of rejecting the null hypothesis, correctly rejecting the null. And then the third one had to do with the distance between the null hypothesis and the alternative. And if you make that distance greater, then your power is also going to go up. Now, very clearly here, this is the one that matters in this particular multiple choice question. But we have to recognize that we're going in the opposite direction here, right? That the alpha value is actually going down. Well, that means that the power has to be going down, right? Decrease alpha, decrease the power. But here's the other thing. If you look at this equation, if the power is going down and this equation has to add up to 1, doesn't that mean that the probability of the type 2 error would have to go up? And so when you look at our answer choices here, they're all about type 1 error and power. And we need the one that says that the type 2 error is going up and the power is going down, which I believe to be answer choice E. The type 1 error would increase, the power of the test would decrease. So the correct answer here is E. So I hope you did okay with that now. And you are ready to jump into the new lesson for today. And so I'd like to start with my lesson overview. But listen, I started thinking about planning this lesson and I had to go way back to the very beginning of the school year. And actually, I found this picture from the very first day of school, 2019-2020. And the reason why I'm showing you this picture here is I'm going to make the argument that there has been quite a bit of time that has elapsed since that first day of school. People might even look a little bit different than they did at the beginning of school. There's a lot of things that have happened in the world since the first day of school. And so this is the reason why I think that today's lesson is so important, is that we have to go all the way back to August or September 2019, and there's very likely some things that you have forgotten since then. So here's where I'm going to take it in today's lesson. The learning targets. First one, describe and compare distribution of quantitative variables for one or two groups. Learning target number 2, compare the distribution for a categorical variable for two groups. So we're going to be dealing with both quantitative and categorical variables in today's lesson. And then the last learning target is use graphs to decide if there's an association between two categorical variables. And I am also in today's lesson going to try and make some connections to stuff that you did way later in the course, dealing with inference, specifically significance. So let's go ahead and jump right in. All right, here we go. Now, today's question that we're trying to answer, the context for today's lesson, is about which AP class has a higher GPA. And we've got this classic battle between AP Calculus and what we all know to be superior AP Statistics. So here's what the problem says. A university admissions officer wonders if grade point average differs between AP Calculus and AP Statistics students. To find out, she selects a random sample of 20 AP Calculus and 10 AP Statistics students. Here are the results for the 20 AP Calculus students. And it looks to me like we're given a dot plot of the results, as well as some summary statistic there. Now, here's the first thing that we want to recognize here is the variable that is being measured by this data. And very clearly, the variable that we're measuring here is GPA. GPA is our variable. And the next question I want to consider is whether that is a quantitative or a categorical variable. Well, because the student's answer to this question is a number, that's a good hint to us that this is in fact a quantitative variable. Another way of thinking of that is a variable where it actually makes sense to calculate an average or a mean. And certainly we can calculate an average GPA or mean GPA. So we know for sure that the variable that we're measuring here is a quantitative variable. So everything that we do on this page is going to be dealing with an analysis of quantitative data. All right, so let's jump right into question number 1 here, which is describe the shape of the distribution. And we have a couple of choices when it comes to shape. I think the first thing to always address is whether it appears that the distribution is symmetric or skewed one way. And certainly this is not a symmetric distribution. It does have a skew to it. In fact, it looks like definitely skewed a little bit to the left. Okay, so I'm going to say that this is skewed left. And I usually like to give a word out in front of that, like slightly, moderately. This is a fairly strongly skewed left distribution. So I'm going to say strongly skewed left. Now here's where I'm going to pause. I'm actually going to give you a very important AP exam tip. And that is when you're answering free response question, you want to do your best to always include the context of the question. And so if you just look at our answer right now, strongly skewed left, it doesn't say anything about the context of the problem here. And so I'm going to add in something here. I'm going to say the distribution of GPA is strongly skewed to the left. So now here very clearly I've included the context of the problem. So make a little note here. What I'm doing is I'm including context. Now on the AP exam, in a particular question in one FRQ, if you establish context once, you don't have to continue to say it over and over and over again. So it's very good to do that right off the bat. So question number 1, we've taken care of the context here. All right, question number 2, is the mean or the median a better measure of center of the distribution? Well, the answer to this question depends on the shape of the distribution, and we know that this is a strongly skewed distribution. So the issue with a skewed distribution is that if you have a skew with possible outliers, like say this value down here, it's going to have a very strong impact on the mean. It's going to drag the mean way down, whereas the median is going to be a bit more resistant to that change. So in this particular case, the median is going to be the better choice for the measure of center for this distribution. And to give my explanation, let's talk about the fact that the mean is non-resistant. And I'm going to say non-resistant to skew and outliers. In other words, those outliers on the left, that skew to the left, that's going to draw the mean down quite a bit because it is non-resistant. Whereas the median is much more resistant. So even with that outlier in there, the median is not going to change too much. So because the median is resistant, that's the better choice, and that has to do with the shape of the distribution. So I'm going to say because the distribution is skewed left, we're going to go ahead and use the median as our measure of center here. And you can actually get that right from the summary statistic. The median is 3.9. So we're calling 3.9 the center of the distribution here. And you'll notice if you look at 3.9, it is not the center of the x-axis there, right? It's just what we're calling the center of the distribution of the value because the median, the middle value, lies within that stack of dots. Okay, let's move to question 3, which is asking for the most appropriate measure of the variability or the spread of the distribution. And we actually have 3 pretty good choices of things that we could use for variability. The simplest would be range. We could also use standard deviation. We could also use IQR. And the answer to which one is most appropriate, once again, has to do with the shape of the distribution. We have a skewed distribution. And the problem with the skewed distribution is that the standard deviation is just like the mean in the fact that it is non-resistant to skew or outliers. What that means is that the outlier is going to have a big effect on the standard deviation, likely increasing the standard deviation quite a bit, right? Increasing that typical distance from the mean. Whereas the IQR, which is actually calculated using the median of the first half of the data and the median of the second half of the data, is much more resistant to change. Less affected by that skew and that outlier there. So almost with the same reasoning as above here, it's based on the shape of the distribution. So we're going to say because the distribution is skewed left, we're going to use the IQR. Now we should go ahead and actually calculate the IQR here, which is the third quartile minus the first quartile. And if you look up above, we know that let's say Q3 is 4, Q1 is 3.7, and that's going to give me an IQR of 0.3. So that leads us into question number 4. Are there any outliers? Well, certainly this 3.1 down here GPA looks like an outlier, but we want to actually test that using the outlier rule. So here's what the outlier rule says. If you're looking for an outlier on the low end, which I call a low outlier, which we think we might have here, in order for it to be a low outlier, it has to be less less than Q1 minus 1.5 times the IQR. So we're gonna have to do a little calculation here. Q1 we know from our summary statistics there is 3.7 minus 1.5 times the IQR, which we already figured out is 0.3, and that number is 3.25. Now that 3.25 is giving us the cutoff value, and it's saying that anything lower than 3.25 here would be considered an outlier. So sure enough, that GPA of 3.1 is an outlier. Okay, so I'm gonna say 3.1 is an outlier here. Now we should check on the other end. I really kind of doubt that there's a high outlier here, but just to go through the motions here and see what the formula looks like. In order for us to have an outlier on the other end, on the high end, it has to be greater than Q3 plus 1.5 IQR. So our Q3 here is 4 plus 1.5 times the IQR is going to give us a value of 4.45. Very clearly, there are no numbers that are greater than 4.45, so we certainly do not have a high outlier. We're left with just the low outlier of 3.1. Now I'm going to pause right here and make note of something. These 4 questions are highlighting 4 of the most important features when you are describing a distribution. Okay, so this idea of describing a distribution, if you're given a free response question that says something like that, you want to make sure that you address all 4 of the things that you see here. So let's make note of them. In number 1, we talked about the shape of the distribution. In number 2, we talked about the center of the distribution. In number 3, we talked about the variability or the spread of the distribution. And in number 4, we tried to see if there are any outliers. So those are the 4 things you want to make sure that you address when you are asked to describe a distribution. Now, one way that you can remember that, if you look at the first letters of all 4 of these, and you do a little bit of rearranging here, the acronym to remember is SOX, which stands for shape, outliers, center, and spread. And then I also like to add on the fact that you better include context, because that's very likely going to be part of the rubric on the AP exam. So SOX plus context is the acronym that we use to remember what features we have to describe for a distribution of quantitative data. All right, we're ready to move to the next part now, which says here's a side-by-side box plot of the result from both samples. Okay, now not only do we have the results for the AP calculus students, but now we also have the result for the AP statistics student. And we are now given a box plot instead of a dot plot, along with all the summary statistics as well. And it sure looks to me like these summary statistics are the same as what we see at the top of the page, but now we have the same values for the AP statistics student. Okay, so number 5 says compare the distribution. Okay, very important here. We just talked about describing a distribution. You want to talk about exactly the same things when you are asked to compare distributions. So this whole idea of SOX plus context, that's exactly what we need to address here when we are comparing the 2 distributions. So I'm going to make it very, very clear in my answer here that I'm addressing all 4 of them. And we're going to start with the shape. Okay, well, we already know about the shape for the AP calculus student. So let's just state that again. And once again, I'm going to get context out of the way right at the beginning here. The distribution of GPA for AP Calc is, and we said strongly skewed left. But now we need to compare that to the shape of the distribution for AP Statistics. Well, AP Statistics looks to be a bit more symmetric there, right? There's not a big long draw on one side or the other. So I think I'd be comfortable saying fairly symmetric. Now, we don't know exactly what's happening within each one of these quartiles. There could be some peaks and valleys within each one of these quartiles, but sort of generally speaking, this box plot to me is saying fairly symmetric. So I'm going to say, while it is fairly symmetric for AP Stat. So we definitely compared the 2 shapes here by noting that they're not exactly the same shapes here. Okay, next thing we want to address, I'm just going to go in the order of SOX here. So outliers would be next. And we've already determined that there is in fact an outlier for AP Calculus. So we're going to say AP Calc has 1 outlier at 3.1. And based on the box plot here, we don't see any outliers, right? An outlier would be indicated with a little dot or a star of some sort. We don't see any outliers for AP Statistics. So I'm going to say, while AP Stats has no outlier. All right, so we've taken care of outliers. Well, next is the center. Well, we looked at the center for AP Calc and we decided that we would use the median there. And so the median was 3.9. Well, very clearly the median is lower for AP Statistics. Even if you compare the means, you'll notice that the mean for AP Calculus is higher than AP Statistics. Now, the important thing here is that we are trying to compare the center, which does not mean that we need to actually list the values of each one. We have to make some sort of comparative statement between the center of AP Calc and the center of AP Stat. And very clearly, the center is higher for AP Calculus students than for AP Statistics students in these. So I'm going to say the center of the distribution for AP Calc is greater than the center for AP Stat. Now, notice I didn't even have to indicate what measure of center I was using, which would be true whether I was using the mean or the median. I also haven't indicated the exact values of those centers. What's important here is that we compared the centers. So I'll tell you this part of the solution right here is an important part of the solution. The fact that we're saying that the center is greater for AP Calculus students. All right, for the spread, we're going to have to do the same thing here. Compare the spreads. And we could do it using range or IQR or standard deviation. We might choose IQR because the AP Calculus distribution is skewed to the left. But if you look at all measurements of spread, you're going to see the standard deviation is lower for AP Calculus than it is for AP Statistics. If we calculate the IQRs, it would also be lower for AP Calc or the ranges. All 3 of those measures. So very clearly here, we can say that the spread for AP Calc is less than the spread for AP Stat. And I'm going to highlight again the fact that the comparative word is the important word here. So definitely when you're asked to compare the distributions, you want to use less than, greater than, similar to. That's the type of language that we want to see when we're comparing those 2 distributions. All right, and let's get to the last question here. Number 6. Do the data provide convincing evidence that AP Calculus students have a higher GPA than AP Statistics students on average? Now, this certainly sounds like something from much, much later in the course, namely significance test, right? Anytime you see convincing evidence, you think that you might need a significance test to answer that question. But before we talk about convincing evidence, let's just see, first of all, do we have some evidence that AP Calculus students have a higher GPA? Well, if you look up at the data, the average, which I'm going to call X bar for the calculus students, is 3.805. The average for the statistics students is 3.16. So based on these 2 samples, we can see that the X bar for the calculus students is in fact greater than the X bar for the stats students. So we certainly do have some evidence that AP Calc has a higher average. But do we have convincing evidence? Maybe the fact that these were both just random samples, because of random variability, we just happen to pick some high GPAs for AP Calculus and some lower GPAs for AP Stats. And it's not actually true when we look at all AP Calc and all AP Stats. Well, in order to answer that question, we need a significance test. So I'm going to say here for the last question, possibly, right? We do have some evidence. In order to know if we have convincing evidence, we would need to do a significance test. And specifically here, let's think about what test we would need here. Well, are we in the world of means, the world of proportion? Hopefully you said the world of means. Do we have 1 sample or 2 samples? Definitely have 2 samples here. So we're going to need a 2 sample, and this is going to be a t-test for the difference of means, mu1 minus mu2, to find out. Now, if you're interested in knowing how to do that particular significance test, we do have a separate video on YouTube that you can check out for significance test for means. All right, so I think that's it for this particular part of the activity, and we are ready for page 2. So if you want to slide on over, and we've got a little bit different context here to start on. All right, so here's what it says. It says, one of the other questions that University Admissions Officer asked the AP Calculus and AP Statistics student was their college plans for after high school. The table summarizes their responses. Okay, so I notice here in the table that we've got the course listed on the left. We have our 2 groups, our AP Stat students and our AP Calculus students. And then up here, we are talking about their college plans, which looks like they had 3 choices. They could say none, or community college, or university here. So the first thing I'd like to do is to identify the variable that's being measured here. And you might say course is a variable because there are 2 different possibilities there, but we really like selected samples from 2 different groups there. And this is really the thing that we're asking though, the sample, right? What are your college plans? So the variable here is going to be college plans. Now let's think just for a second here. Is that variable a quantitative or a categorical variable? Well, college plans has 3 different categories that they can select there, right? This is most definitely a categorical variable. Okay, much different than the first page of the activity where we were dealing with quantitative data, which involved numbers. Instead here, we're talking about categories, the category of none, community college, and university. So let's see what the analysis looks like for a categorical variable, which is going to look a bit different than the analysis we did for a quantitative variable. So here we go. Number 1 says calculate percent of AP Statistics students for each category of the college plan. Okay, we got 3 different categories. So let's start with the category of none. And very important here, we're only looking at the AP Statistics students in order to calculate this percent. So that means that I'm only looking at these values here, that very first row in the table here. So the percent of AP Statistics students that were none, well, that's 2 out of the 10 total, which is 20%. 20% for that first category. Now the second category is the category of community college. And once again, we are only going to be looking at the first row, which is the AP Statistics students. And for community college, I see 3 out of the 10, which is telling me 30% of AP Stats students want to go to community college. And then the final category here is that of the university. And once again, again, only looking at the first row, I have 5 out of my 10, which is going to be 50% of AP statistics students planning to go to university. So as a quick check here, we can make sure they add up to 100%, and sure enough, 20 plus 30 plus 50 is going to get us there. So we're all good on that. All right, let's move to number 2, which is now to calculate the percent of AP calculus students for each category of college plan. So now we are only dealing with the AP calculus students, which is the second row in the table, and we want to find the percent within each category. So starting with none, I have 1 of my AP calculus students. That is only 1 out of 20. That is 5% of AP calculus students that do not have college points. Move over to the next category of community college. Look up in my table here, and it looks like there are 4 out of the 20, which is going to give me 20%. And then finally, the last column we have is the university, and based on the values here, it looks like 15 out of 20, and that is going to give me 75%. So now we're going to try and take those values and make a graph with them. And specifically, we're going to make a segmented bar graph to display the distribution of college points. So let's start with the AP statistics students, and we know, let's see here, 20% of those students said none. So I'm going to make a little bar chart here, and I'm going to try and go up as close as I can to about 20%. I'm trying to stay consistent with my colors here. We have blue to represent none, and then for community college, we have 30%. So I need to stack 30% on top of 20%, which should take me up to 50%. Those are the students that are planning to go to community college, and that last 50% is going to take me all the way to the top here. 100% is going to be those planning to go to the university. Now that's AP statistics. Now let's do the same thing for the AP calculus students. So 5% planning to go or with no college plans, and 20% planning to go to community college. So if I stack 20% on top of this here, it's going to put me at about 25%. So I should be right about here. Doing my best to try and keep this as accurate as possible. And then the remaining 75% planning to go to the university, that should take me right up to the 100%. So there is our segmented bar graph. I will say that you do want to have a key to go along with your segmented bar graph so that the reader knows exactly what each one of those sections represents. And well, we sort of listed it above, but the blue represents no college plans, the red represents community college, and the green represents university. And so there we have a segmented bar graph to show the distribution of the college plans for each one of the groups of students. All right, that leads us to number 4. Is there an association between course and college plans for the sample? Explain. So when we're asking if there's an association, another way of putting that is to say, if we were to know one of the variables, would it help us to predict the other variable? So if you knew a student was AP Stats or AP Calc, would it help you to predict what their college plans are? Well, based on this graph, I would say definitely, because these two distributions do not look the same, right? So we're going to say that the answer here is yes. And the reason is because knowing a student's course, right, or whatever class they're in, so knowing a student's course helps us predict their college plans. Now we should go into a little more detail here to explain. Specifically, like if I knew they were AP Statistics, I can see, well, when I compare the blue to the blue is much larger for AP Statistics students. So I'm going to say AP Stats students are more likely to have no college plans. And the other sort of big difference here is that when you compare the green to the green, the AP Stats students are much less in the green category. So we're going to say, and less likely to be going to university than AP Calc students. So we provided further evidence of why we do in fact think that there is an association between those two variables. Now that takes us to question number 5. What information is missing from the segmented bar graph? Well, here's the thing. If you look at the segmented bar graphs, they show you percents, right? Percents of the total. But what we don't really know is what the total is. And it turns out that these two totals are not the same. We did not have the same number of AP Stats students in our sample as we did AP Calc. And if you recall, the AP Calculus had twice as many in the sample size than AP Statistics. And you don't necessarily see that in the segmented bar graph. Okay, so the thing that we don't see, the information that's missing, is the fact that the AP Calculus sample size is double the AP Stats sample size. Now we do have a way of fixing that, and is using a new type of graph which is called the mosaic plot. And essentially the mosaic plot is the segmented bar graph, but somehow we want to show that there were twice as many AP Calculus students in the sample as AP Statistics. Well, check this out, very easy. If I want it to be twice the size, I'm going to make the width of the bars twice the width of the bars for AP Statistics. So all I'm doing here is I'm doubling up my bars, and now I have what's called a mosaic plot. And from the mosaic plot, you can actually tell the difference in the totals based on the width that you see of the bars. Okay, final question here. Number 6, do the data provide convincing evidence of an association between course and college plans for all AP Stats and AP Calc students? Now that sort of sounds like a question we've already answered here, right? Number 4, but if you look closely, there's a difference in the wording here. In number 4, we were asked about college plans for this sample or for these two samples, whereas in number 6, we are asked for all AP Stat and AP Calc students, right? So now this is doing some inference. We're taking our sample and trying to make an inference about the population. And sure enough, in number 4, we said there's an association for these two samples. But remember, these are random samples, and there's a lot of variability in the results that you get from a random sample. So maybe the same will not hold true for the whole population. So in order to answer that question, once again, we need a significant step. So I'm going to say, well, possibly we do have some evidence, but in order to decide if we have convincing evidence, we need a significant step. And let's think about what type of test we need here. Categorical variables instead of quantitative. So that puts us in a whole new bucket of possibilities in terms of inference. And hopefully you'll remember that this would require what's called a chi-square test. And specifically, this is going to be a chi-square test of homogeneity. Now, quick note here for the 2020 AP exam this year, you're not required to know the chi-square test. That was one of the topics that was taken off the AP exam for 2020 only. Okay, so let's see if we can summarize the learning that we had here. So go to the next page where we have our important ideas. And this is where we're going to go back to the 3 learning targets that I started with at the beginning of the lesson. So the first learning target was everything to do with quantitative variables. So let's start there. Okay, the first thing that I want to point out are the types of displays that you can use for quantitative variables. And we saw 2 of them in the activity, right? We definitely had a dot plot, in my opinion, the superior graphical display for quantitative data. And we also saw a box plot. But there are a couple others that you should be familiar with. You should know how to interpret a stem plot as well as histograms. Now, here's the big takeaway for quantitative variables. If you are asked to describe or compare distribution, this is where you're going to want to use socks plus context. So a quick reminder of what you need to make sure that you address: the shape of the distribution, whether or not there are outliers, the center of the distribution, and the spread. Let me make a couple of side notes on this one here. For the center, we generally are going to use the mean or the median, depending on the shape of the distribution. If it's skewed, you're going to want to go with the median. If it's fairly symmetric, the mean will be best, or the median actually be very similar. In terms of spread, we have a few choices here: standard deviation, IQR, and a very basic measure of spread is also the range you could use. Now, a couple of quick notes: when you're doing this whole socks thing, you must always use context. And once you've established context once within a free response question, you don't have to continue to say it over and over again. And then the other thing I'm going to make note of here is when you are asked to compare. So when you are comparing two distributions, you want to use terms like less than, greater than, similar to, right? Comparative language, rather than just listing out the center and the variability for each one of the distributions. Okay, let's move to learning target number 2, which had to do with now categorical variables. And let's first talk about the types of displays that you can use for categorical variables. And we saw both of these, the segmented bar graph, and then we actually turned our segmented bar graph into mosaic plot. Another choice that you might have here is to look at a pie graph or a pie chart. All right, now what should we take away here? Well, I just want to draw a quick picture here of what the segmented bar graph looks like. And a couple of things that hopefully you noticed on the segmented bar graph. First of all, the y-axis is going to be the percent. And I sure hope you noticed that the very top of that segmented bar graph was 100, started at 0, went all the way up to 100. Right? And typically you're going to have 2 groups, although you could have more than 2 groups. And you're going to look at the distribution of that categorical variable in that segmented bar graph. So you might have something like that and something like this, and maybe the distributions look different. And you would also include some sort of key. Now, that's a segmented bar graph. If you want to turn that into a mosaic plot, you're going to need to scale the widths of the bars. So I'm going to say here, mosaic plot, scale the width of the bars. And let's get to our last learning target number 3, which very specifically was about the idea of association between 2 categorical variables. And let's just go with the definition on this one. Association means knowing the value of one variable helps us predict the value of the other variable. And you can really answer that question by looking at the segmented bar graph. If those 2 distributions are different in any way, then there is an association. If there were no association, then those segmented bar graphs would look identical for each one of the groups. All right, I do have a homework problem for you here to check your understanding. It is an old AP exam question, 2016, number 1. So if you could try that problem before class tomorrow. Tomorrow, Mr. Brandon Murphy will be with you, and he will be talking to you about normal distribution calculation. And then I will be back on Wednesday to talk with you about 2 variables mathematical data analysis. So listen, if you got something out of today's lesson, it was helpful to you, please give me a thumbs up there on YouTube. I sure hope you'll be joining my colleague tomorrow, and then I will see you back here on Wednesday.
Okay, good afternoon, AP Stats kids. Mr. Murphy, it's Tuesday the 14th. We've had some interesting weather way up here in Maine, and we've lost power, but there's been bad weather all around the country. So I hope wherever you're listening to us around the world that you're safe and the weather has come down a little bit and you're healthy. And let's stay positive. Let's keep working hard. Luke started yesterday, sort of back at, I guess, chapter 1 in most books. One variable data, univariable data. I'm going to do standardizing scores, Z scores today. Luke is back with you tomorrow for 5 variable data or 2 variable data. And for the next 3 weeks, we're going to kind of start at chapter 1 and get it right to inference. So anyway, welcome back. My name is Mr. Murphy, and I'll get to our PowerPoint. Here's our opening slide again. Here's the normal curve. I guess we'll be using that today, so that's kind of cool, right? I've been in love with this slide since day one. Again, my name is Brandon Murphy. I teach at John Baptist Memorial High School in Bangor, Maine. We've had some really tough weather, but spring's coming. Hopefully you've listened to Luke as well. Luke teaches at East Kentwood High School in Michigan. Luke and I are good friends, and he's an excellent presenter. I always enjoy working with him. So here's the homework from last night. And again, this is from the 2016 free response questions. It's not the whole question, as you can probably imagine. It's just part A. And theoretically, of course, this is related to what Luke was talking about yesterday. So I'm just going to get to my overhead projector here. We'll walk through this problem together. So Robin works as a server in a small restaurant where she can earn tip money, extra money from each customer she serves. So you heard me say we're setting the table here. We're just setting the tone. We try and understand that students, English may not be your primary language, your first language. So any words that are not very common, we try to find those. And so we want everyone to have sort of an equal footing on this. The histogram below shows the distribution of her 60 tip amounts for 1 day of work. So I would spend a minute or so just sort of really understanding the problem and equally important understanding the graph down here. Now with 60 data points, there's no way we want you to type that into your calculator. So I think that would be the wrong approach here. And when I really look at this histogram here, I guess I know that between $0 and I guess that's $2.50 here, right? $7.50. There were 25 tips over that interval, but I really don't know what each one of those 25 were. Were they all $1? I don't know. Were some $1, some $1.50. So I think typing these in would not really be helpful here, and it would be a huge time constraint that we wouldn't want you to do. So it looks like there's 25 from 0 to 250, 22 from 250 to 5, etc. I might really quick add those up and I get my 60 tip amounts. So part A, very typical. We've seen this a lot on previous AP exams. Write a few sentences to describe the distribution of tip amounts for the day. So I want distribution and tip amounts. You can underline keywords. You can do pretty much whatever you want. It's your exam. So I'm sure you've all heard shape, center, spread. I think our books do a really good job with that. And I can remember a former reader, a friend of mine, saying, the kids are good with this. They're very robotic. They know how to do this. I've expanded on that in my room classroom just a little bit. We call it GSOCs. And so the S is still shape, that's still center, and that's still spread. But the G stands for other gaps. Are there holes in the data? And clearly there's a gap here for some reason. And of course, the O is the outliers. So again, scoring guidelines in the past have traditionally asked for shape, center, spread. Just from a good statistical analysis point of view, I do think if there's gaps or holes in my data, that's important, and I need to address that. If there's any outliers, I want to address that. So let's do shape first. The distribution of Robin's tips are skewed to the right. So I've actually done 2 things here. I've actually done 2 things here. I talked about the shape; it's clearly skewed to the right, and I've also gotten sort of tips and Robin, and so I have context, and that was strategic. I wanted to get that in, one sentence and maybe get 2 things at once. There is a gap in the tips from $15 to $20, and the 1 tip amount from $20 to $22.50 could be an outlier. So I guess in my little acronym here, I've addressed the G and the O, right? The gaps and the outliers. And anytime I try and do them together, for some reason there were no tips in this sort of interval right there. I don't know why. There's 1 tip here. Again, that could be $20, it could be $22.50, or anywhere in between. I don't know. I don't want to type all those numbers in. I don't even know if I could type them all in here. So I don't want to sort of definitively say it's definitely an outlier or it definitely isn't. But I addressed both of them, and it could be an outlier and it could not. And so I'm going to keep moving on. So I've talked about gaps, I've talked about shape, I've talked about my outliers, center. I'm going to go median here. Again, I don't really know if I can even calculate the mean, so I'm going to say the median tip amount. So it's somewhere around 30, right? So 25. It's in the second bin here, right? So the median tip amount is between $2.50 and $5, something like that. And that's all I need to know. It's in the second bar here, the second interval. And again, I don't know exactly where it is, and we didn't want students to do that. And so let's talk about spread. The tips vary from 0 to 250 to 20 to 22.50. And that's one way to talk about the spread of the data. Again, I don't know exactly where those 25 tips lined up from 0 to 250. I don't know that, but I've somehow talked about the spread of my data. So that's it. That's part A. Again, most scoring guidelines in the past have required that students talk about shape, center, spread. I checked the scoring guideline this morning, and of course, we wanted shape, center, spread. We also wanted some context here. So we needed to talk about Robin's tips or tip money or something like that. And I think I've got that in. And gaps and outliers, to me, they're just super important, and we need to talk about them. So I got those in. And as we get closer and closer to the AP stats exam, Luke and I are going to talk a little bit more about how we score the exams. And there's one day where I'm going to ask you guys to become AP readers. We're actually going to score some student papers. We wanted students to address 4 of those 5. So shape, center, spread, context, Robin's tips, and gaps and or outliers, either one of the 2. And if you had 4 of those 5, you got what we would call an E, essentially correct. And that's you're well on your way to starting out the exam on a good note. So that was the homework from last night, and I'm sure Luke did a great job. So let's go back to what we're doing today. I'm going to do standardizing scores, or Z scores. The Z score is a standardized score. So real quick, you can find some updated information on the AP stats testing, and hopefully more is coming. Luke and I will give you everything we know as soon as we know it. The last link here will actually get you to the schedule of all of our events for the next 3 weeks, and so hopefully you can kind of make a plan as to what sessions you want to watch and which ones you don't need to. So I'm in topic 110. Again, this is really more for the teachers than you guys, but we're talking about standardizing scores. So one example of a standardized score is a Z score, which is calculated as your Z score equals xi, your individual score, minus mu, your mean, over sigma, some standard deviation. A Z score measures how many standard deviations a data value is from the mean. You can be positive or negative. You can be 3 standard deviations above the mean, or theoretically minus 5 standard deviations below the mean. So that's all it is. We can always calculate a Z score if we have those three inputs, your score, the mean, and a standard deviation. But we can only read a Z table, or we can only use the percentiles from a Z table if our data is at least approximately normally distributed. And so when we did inference, the first couple of weeks, we really needed to check that condition. And I always like to say to my students, there's no data set in the real world that's 100% perfectly normal. So we shoot for approximately normally distributed or something like that. The standardized test statistic, this white box here, is right from your formula sheet that you'll have on the AP Stats exam. And so some sample statistic, that would be my xi, minus some parameter mu, over standard error of the statistic. And so earlier in the year, we were just using whatever our standard deviation was, and we didn't really worry about sample size. And as we got into inference, of course, the sample size started to make a bigger input. And so I like to call that the standard error is the standard deviation based upon my sample size. Bigger sample size is all bigger. Always better, excuse me. Okay, so I've done a couple of multiple choice questions, and we'll start out with those, and then we'll go to a free response or 2 if we have time. So the lengths of individual shellfish in a population of 10,000 shellfish are approximately normally distributed with a mean of 10 centimeters and a standard deviation of 2 centimeters. So there's a lot of good information in that. You know what the mean is, you know what the standard deviation is, and a pretty big, population here of 10,000. Which of the following is the shortest interval? And boy, that's such a key word right there. Which of the following is the shortest interval that contains approximately 4,000 shellfish lengths? So go back to my projector. So that's the same problem right here. So I clearly would have underlined shortest interval, and that's so key here. I like to give this problem my students pretty much every year, and a lot of them, I like to say swing and miss. They get the wrong answer because they sort of overlook that. So anytime I'm talking about standardized scores or z-scores, and I've been drawing some terrible normal curves here. I don't know why. I think I'm used to standing at a board, not writing on a piece of paper sitting down. I like to sketch a normal curve. I have these 3 rows here, and this first row is always what I call sort of my raw data. This is going to be, height in inches, something like that. Okay. My second row is always my z-scores, and my third row is the area under the curve, my percentile, my probability. At different times of the year, sometimes I'm using area, sometimes I want percentile, and sometimes I want probability. So you'll see me kind of draw a normal curve, or at least attempt to draw a normal curve. It's a pretty bad normal curve. And I always have these 3 rows. I always sort of start out the same way. And there's a lot of numbers on a lot of these problems, and I think it just sort of helps my kids get into the problem, and it helps them kind of line things up, I guess. So you can see that I did that on this problem here. So I tried to draw a normal curve. Again, it's really a bad normal curve, but we don't penalize that on the AP Stats exam. So my first row is my length in centimeters. So it said that the average length was 10 centimeters. Second row is z-score. Third row, area, probability, or percentile. I see all 3 of those as really the same thing. Again, at different times during the course, I may use area more, I may use probability, or I may use percentile, but I really see those all as the same thing. I tend to always sort of draw in 1 standard deviation above the mean and 1 standard deviation below the mean. You calculus guys out there, that always falls at your point of inflection where your second derivative is equal to 0. Above beyond the scope of this course, but if you're into calculus, kind of fun little second derivative. So if I add 0.2, I get up to 10.2, and if I subtract 1 standard deviation, I get to 9.8. Well, I know what the mean, my z-score is 0, and I know I'm at the 50th percentile, so that just sort of gives me a starting point. If I add 1 standard deviation, my new length is 10.2 centimeters. I'm 1 standard deviation above the mean, and then the 84th percentile, or roughly. And again, if I subtract 0.2 or 1 standard deviation, I'm at 9.8 centimeters. I'm negative 1 standard deviation or 1 standard deviation below the mean, and I'm around the 15th or 16th percentile. You'll see me do this on every problem. It really helps my students to sort of get into the problem. So this problem specifically asked for the shortest interval, and so hopefully logic dictates that it's probably going to be centered around the mean. And I'm just eyeballing here. Hopefully that's around 40% of my 10,000 shellfish. So if you understand or see that logic, well, it can't be A because that's not centered at the mean 10. It can't be B. That's not centered at the mean 10. Sort of feels like that one might be centered at 10, so that's okay. It feels like this one might be centered at 10, so I don't think I can throw that one out. And this one here, I don't know if that's centered. So I was able to get rid of 2 of them right away. Well, if I add 1 standard deviation above and below the mean, that would be what, 68% of my data from the empirical rule, or about 68%. So I know I don't want to go out quite so far to 10.2, and I don't need to go down to 9.8. And so I think I eliminated C because those values were on either side of those. And so now it's really just between those 2. And I don't think E is centered perfectly, but let's go to the calculator and see if D makes sense. I want to see if I can type that into my calculator, and I'm looking for around 40% here. Just because I've done this problem a number of times with my students, I think 3 of those 5 answers, if you were to type those into your calculator, get you 40%. So 40% is really not the most important thing here. It's the smallest interval. So I want to go down to normal CDF, normal cumulative distribution function, and I want to start at 9.895. I want to go up to 10.105. The mean is 10. We knew that. That was good. Standard deviation, I think we said, was 0.2. Back to my home screen, and there's my 40%. So the answer for that one was D. And if I was able to sort of understand conceptually what was going on, I was able to eliminate a couple of answers relatively quickly. I was able to get rid of A, B, and C without doing a whole lot of math or without doing a whole lot of work. E doesn't work either. The correct answer is D. But if you just literally went back to the calculator and typed that interval, I think it gives you 40%. I think if you type that interval, it gives you 40%. But that's not answering the question. The question that I wanted was the shortest interval, and so that had to be centered around the mean. So it's a really nice problem. I give it to my students every year, and I like the fact that there are some sort of strong distractors get you to the 40%, but not the shortest interval. So here's another multiple choice, and then we'll do a free response. This is from the 2007 exam. So the distributions of diameters of a particular variety of oranges approximately normally distributed with a standard deviation of 0.3. So that's good sense that there's some information there that I'm going to go ahead and put down in my little picture soon. How does the diameter of an orange at the 67th percentile compare with the mean diameter? Okay, so you can see I've drawn my normal curve here. Well, I've attempted to draw a normal curve. It's not very good, but that's okay. The first row here is my diameter, but unfortunately there's nothing up here in the stem that's allowed me to plug a number in. I can't type in 10 centimeters or 2 feet or something. I don't know. So I had to leave that blank, unfortunately. There's my mean. My second row is always a z-score. My third row is always area, probability, or percentile. So I'm consistent. I teach it that way. Hopefully my students are pretty good. It just helps them sort of get into the problem. So I don't know what the mean is, but I know at the mean my z-score is 0, and I know I'm at the 50th percentile. So that's good to know. I can fill that in real quick. Again, I like to typically draw in 1 standard deviation above the mean, so a z-score of 1. I know that's in the 84th percentile, so that's good. And I went 1 standard deviation below the mean, or -1, and I know that that's 0.1864. And I do know that 1 standard deviation is 0.3 inch. I do know that. Well, they wanted me to compare the diameter to 67th percentile. So again, there's a lot of numbers floating around here, and my students at times get confused. So what number goes away, Mr. Murphy? So 67th percentile, I typed that into this third row here. I went to my calculator, did I think inverse norm. So if you're at the 67th percentile, your z-score is 0.44, or your 0.44 standard deviations above the mean. And that was pretty important. That pretty much opened up the problem for me. So down here I just set up a simple proportion. I said, well, I know that 1 standard deviation is 0.3 inches. So 0.44 standard deviations is how many inches? I cross multiplied, did a little math, and I got 0.132 inches. So if you're at the 67th percentile, your z-score is 0.44, and you're 0.132 inches greater than the mean, and I still have no idea what that number is. So that's a nice little problem. It scored actually lower. This year in 2007, this multiple choice, only 42% of the kids who took the exam that year got this problem right. So I think what makes this a little bit trickier for kids is that we didn't give you the diameter, we didn't give you what the mean was. In many problems we do. So putting these 3 rows here really seems to help my kids just get into the problems, and there's lots of numbers around. And I do every problem like this on the board, and I think after a while they sort of just get into the habit of doing that as well. So let's go back and we'll take a look at a free response here. So we've done that one. This is another good problem here, 2012 number 7, but for the sake of time, we'll move on. So here's a good free response from the 2003 exam. We'll do parts A and B. Part C, I think, is a binomial probability, and Luke's doing that next week, I think. But anyways, men's shirt sizes are determined by their neck sizes. Okay, we're just setting the stage. Suppose that men's neck sizes are approximately normally distributed with a mean of 15.7, the standard deviation of 0.7. That's good to know. I know the average neck size. I know the standard deviation. So that's good. A retailer sells men's shirts in size small, medium, large, XL, with the shirt size are identified in the table below. So they give me some numerical values for each of those 4 sizes. I know it's really hard to tell by watching me, but I'm 6'6" and about 215, 220 pounds. So I'm a big guy. I'm tall and thin, and I can buy basically no clothing off the rack. Just nothing fits me. So if you ever meet me, or if you don't even know me, they'll say, yeah, he's a big guy, and all of my clothing is long and tall. So I'm probably going to be in the XL, but it might not fit. I might have to go tall. Anyway, it's nothing to do with the problem. Part A, because the retailer only stocks the sizes listed above, what proportion of customers will find that the retailer does not carry any shirts in their sizes? Yeah, that could be me. So if I'm making shirts, I would love to sell them to 100% of the population. I would love to sell to every single person. Well, we know there's going to be some really tall people and some really short people and whatever, people with big necks and small necks. So the manufacturer probably can't sell to everyone, but they'd love that that to be 99, 99.5, 99.8 or some percent of the population. They would love that number as close to 100% as possible. And so that's probably what we're going to see is a number that's pretty close to 100%. They love to sell shirts to me. People like me. Whether that happens or not, who knows? In part B, using a sketch of a normal curve, illustrate the proportion of men's whose shirt size is medium. Well, we have some numbers for medium, so medium is between 15 and 16. So we'll be able to sketch that, I think, pretty quickly, and then calculate this proportion. Again, we'll skip part C. I think that's a binomial probability, and we'll let Luke do that one of these sessions coming up where we do probability. Okay, so here's the same problem, and you can see as always, I've attempted to draw a normal curve, and I haven't done a very good job. There are my 3 rows as always. That's my neck size. We know that 15.7 is the mean, or average neck size. That's good to know. Here's my Z-score, and my third row is area, percentile, or probability. Again, I really see those 3 as really the same thing. Depending upon where we are in the course, I may use one word over the other, but I really see those as the same thing. So if your neck size was 15.7, you're at the mean, your Z-score is 0, you're in the 50th percentile. Again, I like to add 1 standard deviation above and below the mean. So if your neck size is 16.4, your Z-score is 1, you're 1 standard deviation above the mean, you're in the 84th percentile. If I subtract 1 standard deviation from the mean, your neck size is 15, my Z-score is -1 or 1 standard deviation below the mean, and I'm around the 16th percentile. Again, it just gets me into the problem, sets it up, and allows me to hopefully answer correctly. So up here, I want what's the probability that your Z-score is less than, here's my lowest neck size or smallest neck size, 14 minus 15.7 over 0.7. So it feels like 14 is going to be way down here, right? You have to go another standard deviation in a little bit. So more than 2 standard deviations below the mean. So it feels like it's going to be a small percentage of males out there whose neck size is smaller than 14. Similarly, what's the probability that my Z-score is greater than my largest side, 18 minus 15.7 over 0.7. Again, that's over, I think, almost 3 standard deviations above the mean. So it's way up here in my upper tail. Really, really small. You might not even see it if I went to my calculator. So I added those 2 probabilities. This first one was 0.00757. Oh, that's really pretty small, right? We knew this one was going to be even smaller than that, right? 0.00051. I added those together. And so the proportion of customers who can't fit in this neck size 14 to 18 is really pretty small, right? It's less than 1%. That makes sense. I want to sell shirts to pretty much every male out there, and I want to sell a lot of shirts, and I'm trying to manufacture them so that they sell. So let's just go to the calculator, and I'll kind of show you where I got those numbers from. So I think I'm going to do my normal CDF again, so I'll just clear that out. Second bars, normal CDF. So I want something lower than 14, right? So I think I can just pretty much pick any number lower than 14. So let's do a neck size of 10 or something like that. So upper here wants to be 14. Well, my mean we said was what, 15.7. My standard deviation was 0.7. And that's where I got that 0.00757. Really small number. Real quick, I'll do the same for my upper neck size. So normal CDF, I want to add up, accumulate. So in this case, my lower was 18. What's my upper going to be? You can pick pretty much any number you want. Way above 18, you can pick 30, 20, 50, 5,000. It doesn't really matter. No one's going to have a neck size that big. So let's do 25. I have no idea what the neck size of 25 means, but it's probably pretty good. The mean hasn't changed. The standard deviation hasn't changed. So let's go back to my home screen. And that's so small, the calculator doesn't even give me a decimal. It puts it in scientific notation. So all I did was add those 2 percentiles or probabilities, and we got a very small number. Makes sense. I want to sell shirts to pretty much everyone if I can. And so I got those 2 numbers from my calculator. We want you to use the calculator, but we also need to see your work here. So make sure that when you're going to the calculator, which we want you to do, we need to see some work, some backup, some supporting statistical work. And I'm sure your teachers have all been sort of saying that all year long. Show your work. Okay, part B says using a sketch of a normal curve, illustrate the proportion of men whose shirt sizes is medium. So again, I've tried to do my best to draw a normal curve here. Here's my mean of 15.7. And I'm just eyeballing 16. I know that my standard deviation is 0.7, and so that's less than 1 standard deviation. So I just eyeballed it. And my lower neck size to be medium was 15. So that's 1 standard deviation below the mean. So that was a little easier for me to eyeball, right? There's your sketch. That's it. A reader is going to look at something like, your upper is greater than the mean, but we're not going to measure this. We're not going to get carried away with it. And we want this to kind of eyeball be around 1 standard deviation above the mean. But again, we're not going to spend a whole lot of time on your sketch. Quick sketch, show your information, and move on. So I want to know what's the probability between 15 and 16, right? Those are medium sizes, 15 to 16. So here's sort of my supporting work. But I think I'll go back to the calculator and try and get that number. I want to use the calculator effectively. I want to use it efficiently. And so I'm going to see if I can get that number relatively quickly. And again, I'm thinking, just by eyeballing it, it's going to be 40, 50% or something like that. So back to normal CDF. Hopefully you've been using this all year. I want to know between 15 and 16. The mean hasn't changed. The standard deviation hasn't changed. Let's go back to my home screen. And it's about 51%. So one of the things that we find when we grade students' exams is many times they don't AP. They don't address the problem. They don't answer the question we're asking. So in part B, it says use a sketch. Here's my sketch. Illustrate the proportion of men whose size is medium. I've done that. Calculate this proportion. So many times we see one or the other, but many students just seem like they forget to answer both of those. So before you move on to the next problem, just make sure that you really address the problem AP, right? And answer the question or questions we've asked. And here there were sort of 2. And so sometimes I say to my kids, underline both and make sure that you've addressed both of those. So that's a really nice problem. And I actually do like part C quite a bit. And I think we'll come back to that and just address it later when we're doing some probabilities. So that was from the 2003 exam. I did another free response from the 2004 exam. Form B, years ago, the College Board would release 2 different exams. One was what we call the operational one was what we call the international exam. The things have changed, and the College Board releases just 1 exam now. But so you see in Form B, we used to release the 2 exams. When I say modified, it doesn't have parts C and D here. That's all. And those were not, standardizing scores. So trains carrying bauxite ore from a mine in Canada to an aluminum processing plant in northern New York State in hopper cars. Okay, I envision a railroad car train. Filling equipment is used to load ore into the hopper cars. Okay, car pulls in, they drop a bunch of bauxite ore into it, pulls forward, and keep doing it. I'm just envisioning in my own mind what's happening. When functioning properly, the actual weight of ore loaded into each car by filling equipment at the mine are approximately normally distributed. That's good. With a mean of 70 tons and a standard deviation of 0.9 tons. So that's a pretty big standard deviation, right? Almost 1 ton. But when you think about it, we're dumping bauxite ore into railroad cars. There's no way they all weigh exactly 70 tons. I know that for a fact. I'm pretty convinced of that in my own mind. So they will vary, like everything in life. That's a big standard deviation in one respect, almost a ton. But we're putting in 70 tons. That's a lot of bauxite ore, and we know it's not going to be exact. And probably the filling mechanism has it down to a science, and it's probably relatively accurate. But we know it's going to vary, right? If the mean is greater than 70 tons, the loading mechanism is overfilling. Right? If I own the bauxite ore company, I don't want to overfill all the cars. I would love it if every single car was exactly 70 tons. I don't want to go less than 70 tons because then my customers make it mad. I don't really want to go way over. So they do say it's approximately normally distributed, and so that's good. Probably some of them will be 70 tons, and some of them will be 170 tons, and realistically probably some of them will be a little less than 7 tons. We just live with that in life. That's just life. So here's the same problem. So part A says if the filling equipment is functioning properly, okay, 70 tons, what is the probability the weight of ore in a randomly selected car will be 70.7 tons? So a little greater than 70 tons. Show your work. Always show your work whether we ask for it or not. So you know what I'm going to do, right? There's my attempt at my normal curve. My first row is tons of ore, tons of bauxite ore. The mean was 70 tons. Second row is Z-score. Third row area, percentile, or probability. Again, they also mean the same thing to me. At 70 tons, which is the mean, your Z-score is 0. You're in the 50th percentile. Again, just so it helps my kids get into the problem. There's lots of numbers floating around here. So if I add 1 standard deviation above the mean, I'm at 70.9 tons. My Z-score is 1. I'm in the 84th percentile. Okay. Well, they told us what? We were at 70.7. So I know it's going to be less than 1 standard deviation above the mean. And I know that my percentile is going to be between 0.5 and 0.8. 0.413. So what's the probability that my z-score is 70.7 minus 70 over 0.9? Let's go back to our calculator. See if we can type that in. So let's do normal seed second bar. Yeah, I want to start at 70. No, let me just calculate the z-score here. Sorry, I'm just gonna calculate my z-score here. So 70.7 minus 70. Well, that's 0.7. That's easy. I want to divide that by my standard deviation of 0.9. So I'm 0.777 standard deviations above the mean. We knew that one standard deviation was 0.9, right? So if I multiply that by 0.9, I get 70. So I'm at the 70th percentile here. Let me go back to my problem. I think I just lost you guys, unfortunately. Maybe I didn't. Okay, so what's the probability? 70.7 minus 0.9. I got 0.218. So that's going to happen around what, 22% of the time? That's not all that rare. That's going to happen roughly 1 in 4, 1 in 5 times. And so in part B, I think that's what they're asking me to do. Suppose the weight of ore in a randomly selected car is 70.7 tons. So we know that's going to happen fairly often, right? About 77% of the time. Shading above that's going to happen. That's my 0.218. That's a probability that was greater than that. So that's around 22%. I don't think it's that rare, right? So that's 0.77, 22% of the time. Again, I don't think it's all that rare. I think that's what they're asking for in part B. So part B says, suppose the weight of ore in a randomly selected car is 70.7 tons. Would that fact make you suspect the loading mechanism is overfilling the cars? Justify your answer. Well, it's clearly 70.7 tons is clearly more than the 70 tons, but we know that's going to vary, and they said it's going to vary approximately normally distributed. So I would not suspect that the loading mechanism is overfilling the cars if a randomly selected car was filled with 70.7 tons. This would occur about 22% of the time, or about 22% of the cars would have 70.7 tons or more. So this would not be an unusual occurrence. So we know that it's going to at times overfill the cars, right? That 70.7 tons is going to happen around 22%. Again, I'll just round it to 0.218. We don't think that's that rare. We don't think that's that rare. So clearly at 70.7 tons, we have overfilled the car. We know that we're putting in 70 tons, and it's got a pretty big standard deviation. So we don't think it's that rare. So we're going to wind down here. I think I'm right around like 45 minutes. I think I had one more pre-response from the 2011 exam. I actually worked on the Rubric team on this, and this was kind of interesting. We got students to come up with some z-scores in part A. Someone's running the 40-yard dash, and we want to know what's the probability that they ran less than 4.4 seconds. And then in part B, they were lifting some weight, and we wanted to know what was the probability that they lifted over 370 pounds. Let's do part B real quick. I think I can squeeze it in. Strength is measured by the amount of weight lifted, with more weight indicating more desirable greater strength. What was a little confusing for kids was in part A, we wanted them to run fast or smaller time was better. And in part B, we wanted higher or larger weight. From previous strength data for all players in this position, the amount of weight lifted has a mean of 310 pounds and a standard deviation of 25 pounds, shown in the table below. Calculate and interpret the z-score for a player in this position who can lift a weight of 370 pounds. That's way more than I can lift. Perhaps some of you, if you're real athletic, maybe you can lift 370 pounds. That's way past my prime here. So again, I'm going to draw my little picture. Excuse me, I didn't draw the picture in part B. I just found the z-score. So 370 pounds was my score, minus the mean of 310 over standard deviation of 25. I got a z-score of 2.4. That was the first part, and they asked me to interpret it. So a player who can lift 370 pounds is 2.4 standard deviations above the mean. That's really strong. Yeah, most of us cannot lift that weight. So anyway, that's pretty much it for today. Let's kind of wind down, and we'll call it a day. Luke will be back with you tomorrow. So hopefully by now you're more comfortable calculating, interpreting a standardized score. And in our class, or in this class, many times when we standardize, we look at what we call a z-score. Hopefully by now you're saying to yourself, in all problems in AP statistics, you should be able to write a clear, concise solution in context. So we really want good communication. Relate your answer to the problem that we are. Always use context. And it's so valuable. And hopefully Luke is. I know Luke's saying the same thing. So your homework for tonight, Luke will post on his website. I think that's bivariate data. It looks like a least squares regression line or something. And we're asking you to interpret slope and context. So again, like I say this every time, but I think it's important. We really mean it. We know that not all students have access to the internet or a device. If you're one of those students, please reach out to someone, your teacher, someone at your school, an administrator. And the College Board will bend over backwards to make sure that you get a device. College Board's working on solutions to help students get what they need to show their best work. If you need mobile tools or connectivity or know someone who does, you can reach us directly at this website here. So anyway, thanks for watching. I appreciate it. I hope I helped today. Please be safe. Please take care of yourselves and your families. You'll be back with Luke tomorrow. I think I'm back on Thursday. And we're going to just keep going through the course and trying to hit the major topics. Not quite chapter by chapter. And of course, there's many different books out there, so different chapters. But I think Luke's doing bivariate data tomorrow, and I'm doing experimental design and data collection on Thursday. So thanks for watching. Have a great afternoon. Be safe, and we'll see you on Thursday.
Hello, AP Statistics students, and welcome to the College Board virtual instruction for AP Statistics. My name is Luke Wilcox. I am an AP Stats teacher at East Kentwood High School in Kentwood, Michigan, and today is Wednesday, April 15th. We are going to waste no time today and jump right in. So let's see what we have up for today's lesson. First of all, let's check to make sure we are in the right place. You should be looking for AP Statistics, I hope. I've already introduced myself. My name is Luke Wilcox, East Kentwood High School. I do have some quick reminders here. If you've been with us for the last couple of weeks, you probably know this already, but if you have anybody that's new with us today, we are meeting on a daily basis, Monday through Friday, 2 o'clock Eastern Standard Time every day. You will either see myself or my esteemed colleague, Mr. Brendan Murphy. We're sort of working on mostly every other day schedule. Currently, we are right in the middle of our AP exam review. We are the week of April 13th, this week, next week, and the week following. We will be reviewing stuff from the very beginning of the course, units 1 through 5. And of course, this is all in preparation for the AP exam, which we now know is going to be on May 22nd. So if there are any resources that you need for these lessons, which is the actual lessons themselves, as well as the homework problems that we are assigning, you can download those as PDFs at statsmedic.com/YouTube. You'll just look for today's date, April 15th, and you'll see the resources that go along with today's video. Final reminder here, if you are a student or you know another student who will be taking this AP exam on May 22nd, which is an at-home exam and requires a device as well as internet access. If that is a problem for you or for someone else that you know, please give them this website address, cb.org/tech, so that they can make a request to get a device or to get internet access so that they can take that AP exam. I do know that the College Board is deeply committed to making sure that every student has access to taking that AP exam on May 22nd, so please utilize that if you need to. All right, so I'm going to go back to the homework problem that you got from Mr. Murphy yesterday, which is going to be a bit of a preview of what we're going to talk about today in terms of analyzing two variable data. So hopefully you got a chance to try it, but let's go ahead and see how we did here. So here's what it says. A wildlife biologist is interested in the relationship between the number of chirps per minute for crickets, y, and temperature. Based on the collected data, the least squares regression line is y hat equals 10.53 plus 3.41. I'm going to pause real quick right there and remind you of some general notation, which we're going to be seeing a lot of today. Anytime you have a line of best fit, typically we're going to call that a plus bx. And the important things to remember is that the b value is the slope and the a value is the y-intercept. Now, I think it's also important to note right now what the variables x and y represent in this context. And so they've told us already that this y variable represents the number of chirps for the cricket, and the x variable is the number of degrees Fahrenheit by which the temperature exceeds 50 degrees. So this is a certain measure of temperature. So we're going to have to know that x is temperature, which is the explanatory variable, and y is chirps, which is our response variable. Now let's get down to the question here. All right, it says, which of the following best describes the meaning of the slope of the least squares regression line? Well, first things first, we need to know what the slope is. And we know that is the b value, or the value that is attached to the x. So 3.41 is our slope value. So right away, if I look at the answer choices, I can actually get rid of a couple of those choices. Answer choice A is making some sort of interpretation of 10.53, which we know is the y-intercept. And I'm seeing the same thing here on answer choice C. So I'm going to get rid of that. Now, answer choice B and answer choice D have that 3.41 that I want. But let's look at answer choice E here. It says the slope has no meaning because the units of measure for x and y are not the same. Well, when it comes to slope, you do not have to have the same units for x as you do for y. This is certainly not the answer that we're looking for. So we either know it's answer choice B or answer choice D. Now, the way that we're going to arrive at the correct choice here is to go way back to your algebra days when you first learned slope. And my guess is at some point one of your algebra teachers called it rise over the run. And maybe even better than that, the change in y over the change in x. But if we put that in the context of this particular problem, when I say change in y, that's the change in the number of chirps. And if we want to get technical here, it's not just the number of chirps, it's actually the predicted number of chirps. That's why we include that hat on top of the y. And then on the bottom, the change in x is really going to be the change in temperature. Now, we know what the slope is. We know the slope is equal to 3.41. But I'm going to write that as a fraction of 3.41 over 1. And here's the reason why. When it comes to interpreting slope, we see it right here. It's saying if we had a change in temperature of 1, an increase of 1 degree in the temperature, we would expect or predict the number of chirps to go up by 3.41. So which of the two answer choices says that? Well, I think it's right here, answer choice B. For each increase in a temperature of 1 degree Fahrenheit, the estimated number of chirps increases by 3.41, which is exactly what this is saying right here. And if you look at answer choice D, for each increase of 1 chirp per minute, there's an estimated increase of temperature of 3.41. They've actually switched the x and the y. That's why this one here is incorrect. So definitely say that answer choice B was the correct answer here. So I hope that you did all right on this one. All right, let's go ahead and jump into today's lesson. The way that I always start these lessons is by giving you a quick overview of the learning targets for this particular lesson. And there are 3 of them. And we've got a lot of ground to cover here in today's lesson. All right, so let's take a look. Learning target number 1 is to describe the relationship between 2 quantitative variables. Okay, last time I was with you on Monday, we talked about describing 1 variable data. Today we're going to talk about the relationship between 2 variable data. Next up, calculate and interpret residuals as well as residual plots. So we'll definitely look at an example of that. And then the last one is sort of a catch-all. There are a ton of interpretations that you just have to know in this particular lesson. Namely, you have to be able to interpret the slope, y-intercept, standard deviation of the residual, and the coefficient of determination. So we're going to go through each one of those, being very specific about what the language should look like when you're interpreting those values. So let's go ahead and take a look at today's activity. And specifically, let's start with the context here, which may be one that's fairly familiar to you, and that's the SAT score. And what we're trying to do here is to predict an SAT score from a student's GPA. Most definitely, I would think that there would be some sort of relationship between a student's GPA and how well they do on the SAT. Not an exact relationship, but at least some sort of connection between the two. That's what we're going to investigate. So here's what the context of the problem says. It says, how well can we predict SAT scores from students' grade point average GPA? Let's start by looking at data from a random sample of 10 seniors from a high school in Michigan. So we actually have the data here, first of all, represented as a scatter plot, which is the most common way of displaying 2 variable data. So let's look at each one of the variables. The first variable is GPA, the second variable is SAT score. And the first thing we want to recognize here is that each one of those variables is a quantitative rather than a categorical variable. So we will only use a scatter plot when we're trying to represent the relationship between 2 quantitative variables. Now, the other thing that we might want to know is which one of the variables is explanatory and which one is the response. Well, the explanatory variable is the one that's going to help you make the prediction for the other variable. In this case, we think if we know a student's GPA, it should help us predict their SAT score. So we would say that the GPA is the explanatory variable. So the other variable, the one that we are trying to predict here, is the SAT score. That is what's called the response variable. And we're always going to put our explanatory variable on the x-axis and our response variable on the y-axis. Now, we also have some computer output here, and it is super critical that you're able to interpret computer output quickly. You know what the values represent. So let's just do a quick high-level overview. If you're trying to find the equation for a line of best fit, I know I showed you in the homework problem that this is the typical form that we use, right? Y hat equals a plus b hat. Now that a value is the first number that's given to you in the computer output, and the b value is the value that's right below. And that's going to give us the numbers that we need in order to write the equation for the line of best fit. Now, I'm just going to give you that quick reminder again that the a value is the y-intercept and the b value is the slope. Now we're going to talk about some of these other values in this computer output as we work through the activity for today. All right, so let's get into the questions here. Question number 1: is this a positive or a negative relationship? Well, I think very clearly by looking at the scatter plot, you see that upward trend as we move to the right, which is in fact indicating to us that we have a positive relationship. But we also want to be able to explain that. And what it means to have a positive relationship is that as the GPA goes up, we are noticing that the SAT scores tend to go up. We're moving in this direction, right? So let's put that into work. What we're going to say here is that students with higher GPAs tend to have higher SAT scores. And actually, we could say it in the other direction as well, right? Students with lower GPAs tend to have lower SAT scores, right? That's explaining why we have a positive relationship. All right, let's move on to question number 2, which says, are there any unusual features of the scatter plot? So now we're just looking at the dots that are in the scatter plot and trying to see if any of them look like they're sort of out of place. And of any of the values that I see there, I'm a little bit worried about this value right here. That would be the student that had a GPA of about maybe 3.4. That seems to be pretty far away from that line of fit. And so I'm going to go ahead and call that an outlier. Sort of similar to what we did with one variable analysis, except we don't have a fancy rule for deciding outliers. So you sort of have to just eyeball. Does it fit the trend of the data? Does it not? How far away from the line of fit is it? But I'm going to call that an outlier. So I'm going to say that the student with a 3.4 GPA is an outlier. Now, in terms of this idea of unusual features, there's really a couple of vocabulary terms that you have to know, things that you could be looking for. The first of which is the one that I've already mentioned, which is an outlier. So let's get a little bit more formal with this, right? The definition for an outlier, first of all, is that it doesn't follow the trend, right? It doesn't follow the general trend of the rest of the data. But here's the other part that's really important. It has a large residual. And what I mean by residual is the difference between where that value is and how far vertically it is away from the line of best fit. In this case right here, this is the residual. And we do have a fairly large residual for that value. So that's why I went ahead and call that one an outlier. Now, one of the other vocabulary terms that you need is to be able to identify a point that is known as a high leverage point. Now, here's the deal with high leverage. It has to be way up here in terms of the x values or way down here in terms of the x values. So it's like way far out on either the low or high end of the x value. So I'm going to say that it has very large or very small x value. So you're looking for a dot that's sort of far away from the rest of the dots in the positive x direction or the negative x direction. We don't tend to have that here in the picture. Most of the dots are sort of fairly clumped together. We don't have one that's way far off on the right or way far on the left. So I wouldn't indicate here that we have any high leverage. Now, there's one other vocabulary term that you might need here, and that's to be able to identify a point as an influential point. And the definition for influential point says that if you were to remove that point, it would have a substantial effect. So there would be substantial changes to a couple of things. It could have a big change on the y-intercept A. It could have a big change on the slope B, and or the correlation value R. So if it had a big impact on one of those by removing that one point, we would say that that point is influential. And oftentimes an outlier or a high leverage point is also considered an influential. So let's move on to question number 3, which is what is the form of the relationship? Now, for AP statistics, in terms of the forms of the 2 variable data, for the most part, you're either going to say linear or nonlinear. Does it generally look like it follows a line or it doesn't follow a line? And in this case, I would say that it looks fairly linear. So we're going to record our answer for the form as linear. And then we have to give some sort of explanation. And this is just sort of a general explanation, but we're going to say the points generally follow a straight line. Now, there is a chance that you might get a data set that has a little bit of a curve to it, in which case you would say that the form is nonlinear. All right, let's move on to question number 4, which says what is the strength of the relationship? So here's the deal with this one. Once you have decided your form, and for us that was linear, the strength is an indication of how closely do all of those points fit with the form that you have selected. Now, because we've selected the linear form, we want to know how closely do all of these fit that particular line. While there are some that are above the line and some that are below, they are generally fairly close to that line of fit. So I'm going to say that the strength is fairly strong. Now, there's not a specific rule for deciding whether it's weak or moderate or strong or fairly strong. You sort of have to go by feel. I wouldn't call this one a very strong, but I think fairly using an ly word there is pretty safe. So we're going to call it a fairly strong relationship. And to explain why, we're going to say that the data points fall fairly close to the line. Okay, now we're going to take a little bit of a pause here before we summarize, and that's to notice exactly what we have commented on in the first 4 questions here, because each one of these questions is giving us something that's really important. In question number 1, where we indicated positive or negative, what we were describing there is the direction of the relationship. And generally, your direction is either going to be positive or negative. In number 2, we were trying to identify unusual features. In number 3, we were trying to define the form of the relationship. And in number 4, we were talking about the strength of the relationship. So listen, these are the 4 things that you want to make sure that you address when you see a question that says describe the relationship between 2 variables. Okay, this might look sort of similar to what we talked about on Monday. For one variable data, we had SOX, right? Shape, outlier, center, spread. Well, here we're going to use a different acronym. It is DUFS. That reminds you of the 4 things that you want to make sure you comment on. And just like we did with one variable data, we need to make sure that we include context of the problem. Right? That's just a general rule on the AP exam. So DUFS plus context is the way that we're going to remember what to talk about when we're describing the relationship. So in the summary here, what I'm going to attempt to do is to take all 4 of those ideas and put them into one nice, neat sentence. Okay, so here we go. Here's my best attempt. Describe the relationship between GPA and SAT. There is a fairly strong, positive, linear relationship between GPA and SAT with one outlier at a GPA of 3.4. There's my nice, neat, concise sentence. Now let's make sure that it has everything that we need there. All right, let's go in order of DUFs. D is direction. Yes, I see direction. My direction is positive. U, unusual features. That's down here. I talked about the outlier. F is form. The form here is linear. We've taken care of that. And then S is strength. We've used the word fairly strong to indicate our strength. And then context. Well, that's actually right here. GPA and SAT have clearly indicated the 2 quantitative variables that we're describing the relationship between. So what I like about this sentence is it takes care of all 4 of those things in one nice, neat sentence. Describe the relationship. Okay, let's go ahead and move on to number 5. Now for number 5, the equation of the least squares regression line. We need the numbers from the computer output, and really these are the 2 numbers that we need: the y-intercept and the slope. And so let's just copy those down here. We've got y hat equal our a value 724.4 plus our b value 169.0 times x. But here's the deal. I'd like to do a little better than that with our equation for the LSRL. I'd like to know what x and y represent in this particular context. So we're actually going to use contextual variables here. So we know that y, the thing we're trying to predict, is the SAT score. So I'm going to rewrite this as SAT, and I'm going to include the hat on it, which means predicted SAT, because we're trying to predict the SAT from the GPA, equals 724.4 plus 169.0. And now instead of x, I'm going to put in my x variable here, which is GPA. And now I have a very clear understanding of what we're using that line for, which is to predict SAT score. Okay, number 6 is to interpret the slope of the LSRL. Well, we've got our slope right here, 169.0. We talked a little bit about this already. And I guess the little trick that I'm going to give you is to think of it as being the change in y over the change in x, which for this particular context is going to be the change in predicted SAT over the change in GPA. And then to think of that number as actually being a fraction over 1. So 169.0 over 1. And we did this in the homework problem already. Now we just need to turn this into words. So the change in GPA of 1 corresponds to a change in predicted SAT of 169. Here's what it would look like in words. I would say that for every increase of 1 in GPA, the predicted SAT score increases by 169.0 points. Let me highlight a couple important parts of the way that we've worded this here. All right, we're talking about an increase of 1 in x, which in this case is GPA, but we've included context. Very important here that you say predicted or estimated SAT score. And then look, we've used this word increases. And the reason why it increases is because this 169.0 is a positive value. If it had been a negative value, then we would say decreases. And then we've also tried to include our proper units here. So that looks like a pretty darn good interpretation of the slope. Now, quick side note here, it says for an increase of 1 in GPA, the SAT would estimate it to go up by 169. Now, does that mean that if I took one of my students and I logged into the computer and I changed their GPA by increasing it by 1, would that cause them to do better on the SAT? Well, hopefully you said no here. We have a correlation here, but we don't have a causation. And that's because we didn't set up an experiment here. This is just observational study data. So that's the classic example of correlation does not necessarily imply causation. All right, now let's get to that y-intercept. So the y-intercept we know is the 724.4. And if you think back to your algebra days, the y-intercept was when the x value is equal to 0. And in this case, the x value would be the GPA. So I don't know that this makes a whole lot of sense, but we're going to write it out anyway. It says for a student with a GPA of 0, the predicted SAT score is, whatever the y-intercept is, 724.4. So while that doesn't necessarily make a whole lot of sense, I suppose it's possible there could be a student with a GPA of 0.00, but you do need to know how to interpret the y-intercept in context of a problem. All right, I think we're ready to move on to page 2 of the activity. So if you can flip to the next page here. Still the same context, still the same scatter plot, same computer output, but there is something that's new here, and that is this graph right here, which is known as residual plot. So we need to do some thinking about what this residual plot is showing us and what things we can get out of that particular residual plot. So let's just dig into the questions here. All right, question number 8 says predict the SAT score for a student who has a GPA of 3.4. Well, this is the whole point of finding a line of best fit, so we can make a prediction. So let's go ahead and see if we can predict the SAT score. And we have our equation here, right? We know our a value and we know our b value. So it is 724.4 plus 169.0 times the GPA, and this particular student has a GPA of 3.4, and that is telling us we have a predicted value of 1299. Now let me make a connection here to what you see in the scatter plot and the line of best fit. What we're trying to do here is to make a prediction for a student with a 3.4 GPA. So what we're really doing when we plug 3.4 into the line of best fit is we're going up to the line of best fit here, and we're looking for the y value that goes with that particular x value. And if you follow that all the way over, it seems reasonable that 1299 would be that y value right there. So we're actually just confirming something that we see in the graph from the line of best fit. All right, let's move to question number 9, which says the student with a GPA of 3.4 got an actual SAT score of 1113. Calculate and interpret the residual. Okay, we first of all need to know the formula for the residual. Right, I referenced it on the previous page, which is that it's how far away that point is from the line. And the way we calculate that, the way I like to write it, is actual y value minus the predicted y value. Right? And students often want to mix those up, but listen, it's very easy. If you look at the order of the AP, right? You're sitting in AP statistics class, that should come natural to you. At actual value minus the predicted value. So for us, the actual SAT score for the student was 1113. The predicted SAT score, well, we said we thought it was going to be 1299. And so that means that we're going to get a residual of negative 186. Now let's see if that makes sense in the picture here. All right, in the picture, look, here's the student that actually has the 3.4 GPA. And sure enough, if you follow that over to the y-axis, it seems reasonable that that student's actual score was 1113. Right? And what we're finding now is the difference between the predicted value and the actual value. And what we're getting is the residual. And so we're saying that this residual is equal to negative 186. And why is it negative? Well, that's because the actual value was less than the predicted value. And you can see that because that dot is lower than the line of best fit. So when we interpret the residual, we need to make note of that. So here's how we're going to interpret this. We're going to say the actual SAT score for the student with a 3.4 GPA is 186 points lower than predicted by the LSRL. And you'll notice here, very important is that I'm using this word lower. That explains why we have a negative value for our residual, because the actual value is less than the predicted. And so sure enough, if you look at the scatter plot, any of these values that are below the line of best fit, those are all going to have negative residuals. And all these values above the line of best fit, well, those are going to have positive residuals. All right, let's move to, oh, by the way, I want to note here, when you look at the residual plot, find the x value, the GPA of 3.4, and you can find that student that we just did the calculation for. And sure enough, if you look over here at the residual, it seems reasonable that that residual would be negative 186, right? You can see that in the residual. So let's talk a little bit more about that residual plot. Question number 10 says, what does the residual plot indicate about the use of a linear model for the data? Okay, a couple of things that I'd like you to notice in the residual plot. First of all, this value right here is always going to be 0. That's going to be at the center of the residual plot. And you're going to have some values above it and some below. Just like we said in the scatter plot over here, some of the points are above the line of best fit, which means they have a positive residual. Some are below the line of best fit, which means they have a negative residual. And the line of best fit will position itself so that if you were to add up all of those residuals, the sum of those residuals is always going to be equal to 0, which seems reasonable when you look at the residual plot, right? Some above, some below. If you were to take them all and add them up, you get 0. In fact, you get an average of 0 as well, right? But the average residual is 0 because adding them all gives you 0. And then the other thing I guess I want to make sure to make note of is that on the x-axis we are plotting the x variable, which is most common with the residual plot, and on the y-axis we are plotting the residual, which is what makes it a residual plot. Now, what is this residual plot telling us? Well, when you look at the residual plot, there's not really any pattern that's emerging out of that, right? We don't see a clear curved pattern in the residual plot, and honestly, this is a good thing. That means that in the scatter plot we have sort of an equal scatter above and below the line of best fit, which is good. That means that the line is a good good model for the data. So here's what we're going to say for that. We're going to say because the residual plot does not show a clear pattern, which is a good thing, does not show a clear pattern, that means that the linear model is appropriate for the data. So what would happen if we did have a pattern that was left over in the residual plot? I'm just going to put a little note here off to the side. These are what I call red flag. If you were to see a residual plot that looked like one of these, that's a red flag to you that the model you've chosen might not be that model. So here's the first example, residual plot, right? So zero's there. If you had a very clear, what I call smiley face pattern, right? You see the smiley face there? That is an indication to you that whatever model you chose that created that residual plot is not a good model for the data. Similarly, another red flag is the frown face. So listen, if you have smiley face or frown face in your residual plot, that is not a good sign to you. That is telling you that the model you've chosen is not necessarily a good model. Now for us, we've got an equal scatter above and below the zero line there. That seems to indicate that the linear model is a decent model for this set of data. Okay, so let's move on to question number 11 and 12, which is straight up interpretations that you just have to know. Gotta know a couple of interpretations here. The first one is for what's called the standard deviation of the residual path. Well, it's not likely you have to calculate that, but it's more likely you have to interpret it. So if you look up here, we know the value is 116.9. All right, you can get that right from the computer output, but we need to understand what that represents. Okay, it's the standard deviation of the residuals. But remember, the residuals have a mean of 0. So when we think about standard deviation, we normally think of it as being the typical distance away from the mean. Well, if the mean is 0 and it's the typical distance away from 0, it's sort of telling you what a typical residual looks like. And if we think of the residual as being the error in our prediction, what we have here is what's called the typical prediction error. Right? That's what S represents. So sometimes I'll even call it that. I will call it the typical prediction error. It's telling you what your typical residual might look like. And you probably want this value to be as small as possible. Now, in terms of interpreting it here, we want to talk about prediction error and sort of like what a typical prediction error looks like. So here's how I'm going to word it. I'm going to say the actual SAT score is typically about 116.9 points away from the score predicted by the LSRL with X equal to GPA. Right? The actual SAT score is going to be about 116.9 away from the score predicted by the LSRL. I'm just going back to this definition of residual, right? Actual minus predicted, and we have the typical residual here. Okay, so 116.9 points, that's kind of far off if we're trying to predict somebody's SAT score, right? So we would like that value to be as small as possible, right? The smaller that value is, the better our model is at predicting. Okay, let's move to question number 12, which is to interpret the coefficient of determination. All right, well, we're going to steal that value right from the computer output. Make sure you got R squared, not R squared adjusted. It is 77.8%. And just as it says right here, it is in fact the R value and then squaring it. So the R value, which is the correlation, if you were to just take that and square it, would give you 0.778 or 77.8. Now, in terms of interpreting it, you sort of have to know this one. There's a little bit of like a sentence frame that you're going to want to use here. We're trying to describe that percentage. So I'm going to say 77.8% of the variability in the Y values. And in this case, that's SAT scores. So I'm going to say of SAT scores is accounted for by the LSRL with X equal to GPA. That's just typical wording that you'll see even on the AP exam. Now, the other way that you'll see it every once in a while, instead of saying accounted for, they'll say explained by the LSRL. So I'm going to put that in there just as a quick reminder. But this is one of the ones that you sort of need to know the fill in the blank exercise of interpreting the R squared coefficient of determination. All right, we got one final question here. Number 13 says, do the data provide convincing evidence of a positive linear relationship between GPA and SAT for all seniors at this high school? Okay, we only have a sample of 10 students here, right? But based on our sample, do we have some evidence that there's a positive linear relationship? Well, sure enough, if you look at the slope value, right, our slope value was 169.0, which is very clearly a positive linear relationship, right? It's greater than 0. So we do have some evidence based on this sample of 10. But the question is not asking about the sample of 10, it's asking about all seniors at this high school. So this is where we would have to make an inference about the population from our sample. And we have to remember that every time you take a random sample, you're going to get different results. So if I were to select a different random sample of 10 seniors, I wouldn't get the same scatter plot, I wouldn't get the same line of best fit, and I wouldn't get the same slope value, right? So that value is going to vary because of sampling, right? Sampling variability. So the question is this slope value a strong enough slope value that we can say that there's convincing evidence of a positive linear relationship for all seniors? Well, of course, we need inference to answer this, which means a significance test. And specifically, the significance test that we would need here is what's called a t-test for slope. So we'd have to actually carry out the test and find a p-value and make some sort of conclusion after we did the significance test. So there is another video that you can watch that has the explanation of how to do a t-test for slope. But I do want to put a quick reminder out that for the 2020 AP Statistics exam, the t-test for slope will not be covered. On the 2020 AP Statistics exam. Okay, I think we got through what we needed to. We do need to try and summarize, hopefully, what we've taken away from today's lesson. So let's go to the last part of the activity here, which is to summarize the important ideas. And I'm going to break this down according to the learning targets that I presented at the beginning of the lesson. There were 3 of them. Learning target number 1 was for us to be able to describe the relationship between 2 quantitative variables. And we learned that there are 4 big ideas that we want to make sure that we address. And the acronym to remember that is DUFs. And let's make sure we know what each one represents. D is direction, U is unusual features, F is form, and S is strength. And let's just put up some quick notes about what you could say for each one of those. For direction, this one's pretty straightforward. You're either going to have a positive or negative direction there. Unusual features, we actually mentioned a few of them. We had outliers, which don't follow the general trend of the data and do have a large residual. We have high leverage points, which are going to be points way down on the x-axis or way up on the x-axis. And then we have influential points, which are ones that if you were to remove them would make big changes on the slope, the y-intercept, or the correlation value. All right, in terms of form, you sort of have 2 choices here in AP statistics, and that's linear or nonlinear. Now, if you take another statistics course in college, we'll get into those nonlinear relationships in a little bit more detail. And then finally, strength. We have different words to describe the strength, ranging from weak all the way up to strong. One thing that you can look at in order to try and determine strength is you can look at R, the correlation value, but make sure you're also taking a look at your scatter plot as well as your residual plot, not just the R value. And then the final thing I want to just make note of here is that you're going to want to address DUFs, but you got to always include context. All right, that takes care of learning target number 1. Learning target number 2 had to do with residuals and residual plots. So let's first just put a little reminder here of the definition of residual, which is the actual Y value minus the predicted Y value. And sometimes you'll see that written as actual Y value Y minus predicted Y value of Y hat. And then the other thing we looked at in this learning target was what a residual plot looks like. And so a couple important things with the residual plot. 0 is here. The residual is the thing that's being graphed on the Y-axis. Most often you have your X variable on the X-axis. And you know what we would like to see in a residual plot is no pattern. Right? If we had something like that, that would indicate to us that the form that we have chosen or the model that we have chosen is in fact a good model for the data. But we don't want to see the red flag ones we mentioned on the other page. Okay, got one last learning target, and this is all of the interpretations. And I'm not going to write out the entire interpretation because you can look back in the activity. I'm going to give you just the sort of what I call the quick note. Okay, so if you are asked to interpret the slope, the quick notes is to remember that that is the change in Y hat over the change in X, and to write your slope of B as a fraction over 1, and then you can say for an increase of X in 1, we predict an increase or decrease in Y of B. All right, for the Y-intercept, thinking back to your algebra days, that is the Y value when the X value is 0. So I'm going to say that it's the predicted Y value when X equals 0. But you would of course have to put that in the context of the problem. All right, the next one is S, which is the standard deviation of the residuals. And remember, I call that the typical prediction error. Right? It's what your typical residual is, or typically how far is the actual Y value away from the predicted Y value. And then finally, the last one that we talked about is interpreting R squared, which is the percent of the variability of Y, although you use the context whatever that variable is, explained by the LSRL with X equal to, and you would indicate whatever the explanatory variable was there. All right, so the next thing that you'll see on here is your homework problem, one simple multiple choice problem that I've taken from AP Classroom that I'd like you to try before you check in with Mr. Murphy tomorrow. I sure hope that today's lesson was valuable for you and a good reminder of some things that you learned earlier in the year. If it was helpful to you, please give me a thumbs up there in YouTube. I would appreciate that a lot. And I certainly hope that you will be back here tomorrow with Mr. Murphy, and then I will be back on Friday where we will do FRQ Friday. See you then. Good afternoon, AP Stats kids. It's Thursday, April 16th. Welcome back. I hope you were with Luke yesterday. Bivariate data, I think. Lisa Regression and I will take a look at his homework. I'm going to do planning and study and experimental
experimental design today. That's the goal. I got some really fun free response questions that we're going to go through. So thanks for checking in. Thanks for watching again, and hope you're safe. Hope you're healthy at home. We actually have our April break coming up next week. That's kind of a New England thing. So if you're not from New England, you might say, why do you have an April break? But it's Patriots Day next Monday, and that's a pretty big holiday in New England. It's when they run the Boston Marathon, which is sort of a fun day if you're ever in Boston, if you're going to school in Boston. Unfortunately, this year, obviously, there's no Boston Marathon. But anyway, I hope you're safe. I hope you're home. And thanks for watching, and we'll get started. So there's my intro slide as always. And again, my name's Brendan Murphy. I teach at John Batchelor High School. You're probably getting sick of the slide if you've watched many of our videos, right? And Luke Wilcox, he's wonderful. He's a good friend of mine. We worked together many times, spoken together at conferences. I really enjoy Luke, and I actually watch most of his videos myself because I can always learn something from him. He teaches at East Kentwood High School in Michigan. Here's the homework from last night. So I don't know if you were watching. If not, no big deal. A scatter plot of student height in inches versus corresponding arm span length in inches is shown below. So bivariate data. My x-axis is my explanatory variable. My y-axis is my response. And so I actually do this. So sometimes I do height versus weight, or height versus shoe size, or height versus arm span. And we usually have a good discussion. Why is height the explanatory variable and arm span the response? And honestly, this one probably could go either way. I don't know. You could probably talk to a medical professional. I'm going to say on an AP exam, if we ever asked a question about it, it would probably be pretty obvious what was the explanatory variable versus what was the response variable. So in this problem, we'll assume that the height is the explanatory and the arm span is the response. One of the points in the graph is labeled A. So A is over here, kind of on the right-hand side. If the point labeled A is removed, which of the following statements would be true? I'm just going to go to my problem here. Okay, if the point labeled A is removed, which of the following statements would be true? So let's say A. Let us keep A in for now. I'm just going to eyeball sort of the least squares regression line. That's all it is. Okay, the calculator would do a better job. But I'm just trying to eyeball what I think the least squares regression line would look like. And typically one above half the points above and about half below. So again, really bad eyeball. If the point A is removed, so if I take this away, well, the net line that I just drew doesn't represent the data very well, and so I'll kind of draw here in another color what I think that the new least squares regression line would be again if I move point A. So here's the original, and here's without. I have the cursor on the left, so you can't see what I'm doing. I'm slob. So it looks clearly like the slope is steeper, and my correlation coefficient R value would be stronger behind. So the slope of the least squares regression line is unchanged. That's not a true statement. The slope of the least squares regression line is unchanged. That's not a true statement. The slope of the least squares regression line increases. Yeah, that feels like it did increase. The slope did increase, and the correlation coefficient increases. I think that's a true statement, and C is the correct answer. Just because statistics is sort of a gray branch of mathematics, so just a gray topic area, shades of gray. I like to typically read through the others just to make sure that I've answered it correctly. So let's just keep going. I think C is the correct answer here. The slope of the least square regression line increases. Well, that's a true statement. And the correlation coefficient decreases. No, that's not a true statement. The slope of the least squares regression line decreases. That's not true. So I'm pretty convinced that C is the correct answer. And again, that's just a test taking strategy. And of course, this year there is no multiple choice. So we're not going to Luke and I will not spend time reviewing that. But just in the future, to me, it's always just a good strategy to read through all of them. And sometimes reading another answer, some kicks out my brain that I want to understand the problem a little bit better. Again, this typical slide you've seen it before. This is all the updates about what you can do on the AP exam. Can you use your textbook? All that stuff. Down the bottom here is the schedule for Luke and I's remaining week and a half, 2 weeks, 2.5 weeks. So you guys go back and look at that. I'll just keep moving and try to get into some math. So you've heard this probably thousands of times. Correlation does not prove causation. And I'm sure Luke mentioned it yesterday. He talked about correlation between two variables. Up until this point in the course, starting at let's say chapter 1 up to chapter whatever this is in your book, we've analyzed data numerically, graphically. We really haven't worried about where the data came from or how I collected it or how I got my data. And we haven't been able to say this causes that. We do want to get there. We want to get to the point where we say this new medicine causes you to get better quicker. This new toothpaste works better than the old toothpaste or something like that. And so to do that, we need to get into what we call a well-designed experiment. And to me, it's one of the really fun units when I teach this to my students. I enjoy this. It's not mathy. I'm not going to use the calculator today. I don't even have that up on my computer because I'm not going to use the calculator today. Many teachers I know teach this sort of chapter 4 in the textbook or whatever. Other teachers teach this day 1. So I'm not sure how exactly your teacher presented to you. By the way, it's perfectly fine. I've done it both ways, and there's benefits to both. So this could have been the first thing you learned last August or September, or it could have been something you were doing in December. But anyway, correlation does not prove causation. I'll try and build upon that today. We have 4 different ways in this course where we can randomly select our data. I guess so random sampling and data collection. We have a simple random sample SRS. That's an okay abbreviation on the AP exam. We know what that means. We try to discourage too many abbreviations. Please don't use text speak. We want you to communicate clearly using good statistical language. But SRS is perfectly fine. Stratified random sample is another way to randomize and collect our data. Cluster sampling is the third method, and systematic random sampling is the fourth method. That's newer to the curriculum, and so hopefully your teacher mentioned that to you. If not, maybe just make a note and go back and look at it. It's not complicated. It's a very easy way to collect data randomly, but it's newer to the curriculum, and so if you haven't read the book, it may not be in there. So just want to make sure that you do understand that those 4 methods, we expect students to know the difference and how to correctly use them in a problem. I like to say to my students, each method has its strengths and weaknesses, no different than most things in life. So there are times when some random sample is the easiest and best, and we want to use that. There's other times when the cluster sampling is really the best way. It's really topic specific, problem specific. So, and then here's sort of what the components of a well-designed experiment. Again, hopefully you've seen these before, but in A, we want comparisons of at least 2 treatment groups, one of which could be a control group. So like to summarize that, as we impose a treatment, we don't always need a control group in every experiment we run, and that's where sometimes my students will struggle. They look at control group, and then we'll get down to D, and so I'll try and see if I can work that into one of the examples I do. We do not need a control group at every single experiment that we run, but we do need to control for variables. How's that? We need random assignment, allocation of treatments to experimental units. I'd love to be able to randomly select my whatever in my experiment and then randomly assign. Many times that's impossible, especially with humans and medical studies, but we need some randomization. We need random assignment of the treatments to the different experimental units. We need replication, more than one experimental unit in each treatment group. More replication is typically always better, but there are times in the real world where if I was testing fertilizer on an acre field, it might not be financially feasible to test thousands of acres. So we need more than one. 2 is okay. Obviously, more is better, but given the constraints of the real world and things cost money, sometimes we're limited as to how much replication we can have. And then down here, D, we need to control the potential confounding variables where appropriate. I have a problem when we'll talk about confounding variables a little bit more. So, in summaries, we need to impose a treatment, we need some randomization, we need replication, and we need to control for outside confounding variables. So those are kind of the four components of a well-designed experiment. As we walk through problems today, I'll try and just repeat those 4. Do we have this? Do we have that? I have many students who take AP biology or AP chemistry or AP physics, concurrently with AP statistics. And I have had students say, Mr. Murphy, we do it a little bit differently in AP bio. That's perfectly fine. I don't claim to be an expert in experimental design. I just say to my students, whatever class you're in, please follow the rules of that class. And we'll actually get into a good discussion about how to do it in AP bio versus AP stats or some other class. It's really basically the same thing, but there are some subtle nuances there. I won't claim to be an expert. If your AP bio teacher says, do it this way, please listen to him or her. I'll defer to the experts on that. So let's take a look at some free response questions today. Try to get through as many as we can. So this is from the 1999 exam, AP stats free response question number 3. And as an AP reader, some of these problems sort of take on lives of their own. And you hear readers talk about the dentist problem in the boots, and so we each kind of get a name. And so this was the dentist and the apple problem. So a long-time reader will say, I remember that from years ago. So the dentist in a dental clinic would like to determine if there's a difference between the number of new cavities in people who eat an apple a day and people who eat less than an apple a week. Again, just setting the stage, that's all. So is there a difference in the number of cavities based on the number of apples you eat? That's all I get out of first sentence. They're going to conduct a study with 50 people in each group. Okay, so it feels like two groups, 50 people, 100 people in total. Again, I want more than that in a perfect world, but I can live with 100. That feels like my sample size is big enough. 50 clinic patients who report that they routinely eat an apple a day, and 50 clinic patients who report that they eat less than an apple a week will be identified. Okay, so there's my 100 people. The dentist will examine the patients and their records to determine the number of new cavities the patients have had over the last 2 years. So at first I was thinking maybe this is an experiment, and now I'm leaning more towards an observational study. It feels like we've identified some people, and the dentists have just looked at their records and made some notes or something. They will then compare the number of new cavities in the two groups. I'm just going to switch over to my overhead. We'll take a look at the same problem. Okay, question A. Why is this an observational study and not an experiment? So maybe my gut feel there was right on. And I like this problem for many reasons, but I always say to my students, the College Board is telling you that this is not an experiment. So it would be pretty much impossible for you to get credit in Part A if you tried to tell us it was an experiment. So we're not trying to trick you. When we say something like, why is this an observational study, not an experiment? Please just believe us, and it is an observational study, not an experiment, and don't try and read into the problem. Sometimes my kids feel like, they really want to read into it or something like that. We're telling you that this is an observational study and not an experiment. So this is an observational study and not an experiment because the patient's dental records were just observed and recorded. So one sentence, I did try and get, patients or dentists and cavities, some context in there, which is super important. Down here, parentheses, I kind of came up with some potential other ways to correctly answer this. So in many ways, there's probably, hundreds and hundreds of different sentences or sentences that you could come up with and correctly answer this question. You could say this is an observational study and not an experiment because there was no random assignment of subjects to treatment. So again, what do we have? We talked about, imposing treatment. We talked about randomization, replication, controlling outside variables. We don't have any randomization here, therefore it cannot be an experiment. You could also say this is an observational study and not an experiment because no treatments were imposed on 100 dental patients or something like that. So this is clearly an observational study. This is not an experiment. And there are many ways to correctly answer that. You don't need to list all of those. So don't worry about, having to make a list of all the different things. Typically one way to answer it is perfectly fine. Okay, part B, explain the concept of confounding in the context of this study. So sometimes I put a little one here. That's the first part of this question, including an example of a possible confounding variable. This has two parts to it, and we really need to make sure that we're answering both of those. And having read many AP stats answers over the years, it feels like many students, unfortunately, will answer one of the two, but not both, and maybe they don't realize there's two different questions here, two different things we're looking for. So if you're reading a question and it feels like there's more than one part, make a little note, 1 and 2, however you want to do that, I'll leave that up to you guys. But that seems to help my students. I want to make sure that we sort of have two different things here. So two variables are confounded. Their effect on the number of new cavities cannot be distinguished from one another. In other words, I don't know what caused the cavities. That's one way to phrase it. Or confounding variable is one that was related to the explanatory variable and possibly influences the response variable. So again, I sort of came up with two somewhat generic definitions of a confounding variable. Both of those are fine, but there's probably lots of other ways where you can also correctly identify it. But some of these definitional type questions are hard for my students, and they say, Mr. Murphy, you seem to be able to just rattle this right off, but we're newer to this. And I always tell them, if you forget sort of the statistical language, just say it in plain old English, okay? And you'll probably be okay on the problem. So if you forget the exact phraseology of the words, just say it in plain English. You'll probably be okay. So don't worry about that. We're not looking for this exact language. How's that? Well, that feels like it's the first half, but not the second half. So include an example. So I need one example, okay? There's many different rules of the reading. When we ask for one example, we want one example. If students give us 5 different examples, we actually read all 5 and we pick their worst answer. That may not seem fair, but we actually pick their worst answer. So when we ask for one example, give us one. Mean it, be committed to it, define it well, but don't make a whole list and sort of say, well, leave it up to the reader. They'll pick the right one. Well, we have to read them all. We have to read everything on paper. But we're not unfortunately pick not the best answer and grade that one. So one example of a possible confounding variable could be the number of times a day that patients brush his or her teeth. That seems to me to be another factor in the number of cavities that you might get. Eating the number of apples you eat. I don't know if that impacts or not, but I'm pretty convinced that every time I go to the dentist, he makes sure that I'm brushing 3 or 4 times a day. So and again, there's probably hundreds of different examples that could work here. And the readers are, we're well trained before we actually read a paper. And so if you have a different potential confounding variable here than mine, don't worry about it. There's probably hundreds of different potential confounding variables, all of which could get you full credit. Okay, back to part C. The mean number of new cavities for those who ate an apple a day was statistically significantly smaller than the mean number of new cavities for those who ate less than an apple a week. So there's a huge difference. How's that in plain English between two groups? Could one conclude that the lower number of new cavities can be attributed to eating an apple a day? Caused here might be another word. Attributed. Sometimes my students get a little tripped up with that. Could be attributed to eating an apple a day, caused by eating an apple a day. Explain. Well, to talk about causation, this caused that, we need to run an experiment. And in part A, we were told this is not an experiment. So my answer for part C is one cannot conclude that the lower number of new cavities can be attributed to eating an apple a day because this was an observational study where you cannot draw a cause and effect conclusion. So I many times just repeat the question, and I want to make sure that I get context in every part A, B, and C. Apples, cavities, dental clinics, something that relates to this problem. So I really like this problem. I do this every year with my students. There's many sort of things I'm trying to point out to them along the way. So this is the waterproofing of the boots. I'll cover up my answer here. This is from the 2002 exam. So this is the waterproofing of the boots again. This is sort of AP reader lingo. Some of the old times have been reading for a while. A manufacturer of boots plans to conduct an experiment. So that's a key word I'm going to underline now. To compare a new method of waterproofing to the current method. Okay, so I want to compare the old waterproofing to the new waterproofing. The appearance of the boot is not changed by either method. Super important sentence. Many times when I give this to my students, they sort of overlook that. When we talk about the best answer, someone will always yell out, "Oh, that's Mr. Murphy. Why that second sentence was there?" So I'll come back to that and I'll address that. The company recruits 100 volunteers in Seattle where it rains frequently to wear the boots as they normally would for 6 months. So that's just setting the stage. If we're testing waterproofing, I guess we want people to go out and jump in the puddles and see if the waterproofing works. And it does rain a lot in Seattle. It rains a lot in Maine, snows a lot in Maine. So you can do that experiment lots of places. But again, students may not know exactly how much rain happens in Seattle, so we're just setting the stage there. At the end of the 6 months, the boots will be returned to the company to be evaluated for water damage. Okay, so it feels like we have 100 volunteers. We're going to give them some boots. We're going to give them waterproofings on, old waterproofing, new waterproofing. We want to go out where? We want to go out every day. We're in the rain. They're fishermen. We want to wear them every day. If they're a high school math teacher, we want to wear the boots when it's raining in school. And then after 6 months, they come back and the company is going to evaluate. And I think we're trying to determine here, is the new waterproofing better than the old waterproofing? If it is, and they're going to make the new waterproofing put on boots. If not, they're going to stick with the old design. So describe a design for this experiment that uses the 100 volunteers. Include a few sentences on how it would be implemented. So I'm going to come up with a good design. I don't think it's the best, and I'll tell you why I'm coming up with it. While I'm kind of just working on it here, so see if you can think of, could there be a better design? So we always want the best design. So I call this an experimental design tree. I'm sure your books do this. And so here's my 100 volunteers. And using my kids, put a big R here, and I guess that means randomize. And here's my old waterproofing up here, and here's my new waterproofing. And they wear them for 6 months. They wear them for 6 months, and then they come back and they evaluate the boots, record any damage, leaks, those types of things. So I call this an experimental design tree. I don't know if it has a more formal name, but hopefully you've seen this before. Hopefully your textbooks all have this. The reason I wanted to do this problem this way at first, even though there's a better design, is right now this picture here is really worth nothing for credit on the AP exam. We think this is a good way to get your thoughts in order. We think this is a good way to set up the problem, but this picture here really isn't worth anything right now. I don't know what this bar means. I mean, I think it means random, right? But I don't really know. So I encourage my students to come up with these, again, experimental design trees. I don't know if there's a better name, but we need below in a sentence or two or three really what you've just done. So I might say something like, I took 100 volunteers and I randomly placed them into the two groups, and this is how I randomized. Usually just saying I randomly put them into the two groups isn't enough. We want you to actually tell us how you randomized. You could use a random digit table. You could use some sort of a calculator to randomize. I like to put the names in a hat, shake them up, and pick them out, but we want you to just not put the word R or the letter R. So 50 people got the old waterproofing, 50 people got the boots with the new waterproofing. They wore them for 6 months. They came back and evaluated. So again, I want to do this picture here. Unfortunately, that's not worth any credit on the AP exam by itself. Down here, we want a couple of sentences explaining what you did. Sometimes if the communication in sentences down here isn't quite so strong, but you have a really good picture, as a reader, I can kind of look at both and try and figure out your answer. There are other students who have no picture here. They just say it in words and they do a great job, and that's perfectly fine. So I encourage my students to draw this type of picture here. It does seem to help them get their thoughts in order. And it feels like when we grade exams, if we have a good picture here, the sentences down here tend to be better. Okay, so that's a good design, but unfortunately it's not the best design. So I came up with what I call the match pairs. So I said match pairs is the best design. Each of the 100 volunteers will be randomly assigned to either group 1 or 2 by picking a number from a hat. That was my first attempt. And actually this morning when I went back and tried to do it again, said, I think I need some more information. So I said, I'm going to put 50 number 1s in a hat, 50 number 2s in a hat, shake it up, and then ask each volunteer to pick a number. So I started out with my answer, and I actually read the second time, and I said, I think I need some more detail there, Mr. Murphy. So that's another strategy. When you finally come up with your answer, before you submit it or before you turn it in, just read it again and see if you've addressed everything that you want. So group 1, I said the left boot was old waterproofing and the right boot was new waterproofing. So there's your match pairs. Each of the 100 volunteers is going to leave with 2 boots. One of them is going to be the new waterproofing, one of them is going to be the old waterproofing. Group 2 is the opposite. Left boot new waterproofing, right boot old waterproofing. So that's a better design than this picture here. And if you came up with that while I was working, great. It's what we call a kind of classic match pair. Each volunteer will wear his or her boots for 6 months, and upon return, the boot evaluator, it's such a strange way to define that person, but I didn't know what else to call them. The boot evaluator will record damage, test for waterproofing leakage, etc., tears in the boots, and document their findings. So that's why the second sentence is just so important. And once I show my students this, and almost all of them kind of come up with this design here, and they get mad at me when I tell them it's not the best design, and then we talk about match pairs, and then they actually say, yeah, you're right, Mr. Murphy, that is a better design. So each person leaves with each of the different waterproofings. Here's my randomization. Some people get left old, right new. Some people get left new, right old. And that's important because when I've done this a million times in my life, every time I get out of the car, my left foot is the first one that hits the ground. That's just probably all of us are that way, right? When we get out of the car, your left foot is the first one out. And I put my left foot in many a different puddle and said, well, this was probably a super place to park, Mr. Murphy. Maybe I should have backed up with another foot or two. So there's my randomization. That's good. Each person leaves with the old and new waterproofing. And it's just a better, stronger design. Part B, could your design be double blind explained? So double blinding, if possible, is typically always better. So we do want to double blind this experiment if we can. There's probably some experiments in the world where we can't, but I'm going to say in AP stats that I tell my students to pretty much think about double blinding if at all humanly possible in all the different experiments. So I think we can double blind here. So I said, yes, my design could be double blind as long as 100 volunteers and the boot evaluator, again, that's such a strange term, isn't it? The boot evaluator do not know which boots were treated with which waterproofing they were old. So if I'm a volunteer, I go in, someone gives me a size 13 pair of boots, and I'm happy because I got a free pair of boots, and I go wear them for 6 months. So I don't know which boot got which waterproofing. I don't really care. I got a free pair of boots, and I'm good to go. So the boot evaluator, the person who actually gives me the boots, when I return them 6 months later, does some sort of testing. They don't know, and so therefore it is double blind. What my students get confused sometimes is, well, who knows what's going on then, Mr. Murphy? Like who really knows? And I like to say, well, there's a third person. There's the person in charge of the experiment. There's the person who's in charge of waterproofing for the company. So there's a third person who knows exactly what each one of those 100 volunteers got. I as a volunteer don't know. I shouldn't know. I don't really care. I got a free pair of boots. And the boot evaluator, as soon as I come in after 6 months, they're just going to test the boots. And it's actually better that they don't know because they can enter some bias into it and say, oh, Mr. Murphy, I can't believe the left boot is actually better than the right boot. It's something like that. If they knew which one was the old waterproofing and which one was the new. So it can be double blind. It should be double blind. And it's just a much better experiment that way. So I love the boots. It's sort of a classic. And I always have fun with that with my kids. And they say, you come up with the strangest examples, Mr. Murphy. You have a very creative mind when I talk about my left foot going out first. So I think this one is going to get into maybe stratified versus cluster sampling. Again, these were two of the randomization techniques that we want students to know how to use. We probably won't ever get a definition. We probably won't say, define the following word, but we do want to use it contextually in a problem. So there's a difference. We'll talk about which one is probably better here. So for the 2011 exam, an apartment building has 9 floors and each floor has 4 apartments. That's what we're trying to show you here. First time I did this problem, I actually had to spend a minute to try to figure that out. It took me a little while. It was a little slow, but I figured it out after a while. There's my 9 floors and each floor has 4 apartments. So I guess there's 36 apartments in total. Couldn't figure out what the asterisk meant. Of course, I just needed to read, right? So it has a little asterisk. There are children in the apartment. So apartment number 11, I guess, has children. 22 does, not on this floor, not on that floor, etc. So understand the problem before you go and actually start to answer any questions. And I think that it's well worth the extra minute or two up here understanding the problem before you actually start to answer the question. So I tell my students, you need to spend another minute, go back and read it, underline keywords, whatever, perfectly fine. The building owner wants to install new carpeting in 8 apartments to see how well it wears before she decides whether to replace the carpet in the entire building. Okay, that makes sense. Before the landlord does 9 floors of carpeting, they want to sort of test it out, see if the new carpeting works well. And so they're gonna pick 8 apartments, I guess 2 floors, and try and figure out whether the new carpet's worth buying. And that makes sense. The figure below shows the floors of apartments in the buildings with their apartment numbers, so apartment 11, 12, 13, etc. Only the 9 apartments indicated with an asterisk have children in the apartment. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. I missed one maybe there. 9 apartments. Okay, well, why is that important? Again, probably somewhere in the problem they're going to talk about the difference between children in the apartments. But my gut says the children are running around and probably having a good time and perhaps spilling stuff. And my little nieces and nephews, I love them to tears, but sometimes they can run around and make a mess, and that's just the way it is. And I love them for it. Okay, part A, for convenience. So I'm going to circle that word. Sometimes doing the easy way isn't the best way. For convenience, the apartment building owner wants to use a cluster sampling method in which the floors are clusters. So I guess that would be a cluster, that would be a cluster, that would be a cluster, etc., etc. So looking at it quickly, it looks like I have 9 clusters, right? With 9 different floors. Describe a process for randomly selecting 8 different apartments using this method. Okay, so I have 9 different floors, and it feels like I want to randomly select 2 different floors. And then what cluster sampling says, well, then I'm going to sample everything on that floor, and so there will be 4 apartments, 4 apartments. So before I even go to write anything, I just want to understand what's going on. I have 9 floors, each one I'll call a cluster. I want to randomly select, I guess, 2 floors, and then I'm going to put new carpeting in all 4 apartments on those 2 floors for total 8 apartments, and that's what the landlord wants to do. Okay, again, there's different ways to randomize. You can use a random digit table, you can use some sort of a calculator or a random number generator. I'm sort of a big fan of putting the names in a hat, the numbers in a hat. That's what I try to do here. So I said, put the numbers 1 through 9. Each number corresponds to the floor in the apartment. So number 1 is floor 1, number 2 is floor 2, etc., etc. In a hat, shake it up. That's actually important. So if you use the hat method, we need to shake it up, and that's important. And pick out 2 numbers. So I'm going to put numbers 1 through 9 in a hat. I'm going to shake it up, and I'm going to pick out 2 numbers. Those 2 numbers would correspond to the 2 different floors. And then for each apartment on these 2 floors, so 2 floors times 4, there's 9 apartments. These apartments would be selected for new apartment. Okay? So that's one way to do it. I think I've answered the question, but I'm not really sure I like that method a whole lot. I circled the word convenience, and I said to myself, could I randomly pick the 6th floor and the 4th floor here? And the answer is yes, I could. The problem with that is it doesn't look like there's any children in any of those 8 apartments. And as a landlord, I probably understand that there could be no guarantees. There could be different copper wear or copper usage if there's kids on the floor versus two adults or something, or 1 adult. So I think part B sort of addresses that. An alternate sampling method, so this was cluster sampling, would be to select a stratified random sample of 8 apartments, where the strata are apartments with children and apartments with no children. So stratified random sampling, I have different strata, different groups with similar characteristics. How's that? A stratified random sample of size 8 might include, so I still want my 8 apartments, right? Still want the 8, might include 2 randomly selected apartments with children. So I want 2 with children and 6 without children. And again, that's good. I want both, right? I want both. Hopefully they're somewhat proportional, right? In the context of this situation, give 1 statistical advantage. That's all I want to give. Maybe there's 3, maybe there's 5, maybe there's 10. I want to give 1. I want to commit to that. I want to be clear and concise in my answer, and I want to contextual. Give 1 statistical advantage of selecting such a stratified sample as opposed to a cluster sample of 8 apartments using the floors as clusters. So I think we already talked about it in part A, the convenience. I theoretically could have picked 2 floors randomly, nothing wrong with that. But if I pick those 2 floors, and maybe if I pick floors 3 and 6 or something like that, I wouldn't have any apartments with children, and that strikes me as not the best design. So 1 statistical advantage of the stratified sample is you would guarantee to get apartments with children and apartments without children, as opposed to the first design where we theoretically could have gotten 8 apartments with no children. So to me, that was the real benefit of the stratified random sampling there. It is reasonable to assume that where on the carpets could be, I don't know if that's a fact or not, could be different for apartments with and without children. And if you have younger siblings at home, or maybe when you were a younger person, you ran around the apartment and had fun. So that's really sort of testing, do you understand the difference between cluster sampling and stratified random sample? And again, the benefits of those 2 different methods or 2 different design techniques. So let's see if I can get into this last problem real quick. I'm watching the clock here in the corner here. I think I can at least try this and hopefully not go too fast, but hopefully I can put a good dent in this. So this was a more recent problem from the 2016 exam. Alzheimer's disease results in loss of cognitive ability beyond what is expected with typical aging. Terrible disease. I hope one of you go out and find a cure for Alzheimer's. How's that? Make the world a better place. A local newspaper published an article with the following headline. Study, I don't know what that means. Observational study, experiment, I don't know. Study finds strong association between smoking and Alzheimer's. Okay. Again, study, I don't really know what that means. Association, is this an experiment? Again, it's probably where the problem's going, but I'm just sort of thinking about the problem as I'm reading it. An article reported that a study tracked the medical histories of 21,123 men and women for 23 years. Okay. That's a pretty long time, so that's good. That's a pretty good sample size. That's good. But track the history sort of feels like an observational study to me. It doesn't really feel like an experiment to me. But let's keep going. Again, I'm just thinking about the problem as I'm reading it. The article stated, for those who smoked at least 2 packs of cigarettes a day, the risk of developing Alzheimer's disease was 2.57 times the risk for those who did not smoke. So if you were a smoker, you did, I guess, based upon the study, have a higher risk of getting Alzheimer's disease. But I don't know if we can talk about causation here. Remember earlier one of my slides was correlation is not proof causation. Okay, identify the explanatory and response variables in the study. So the explanatory variable, the degree or the amount of cigarettes that a person smokes, so the number of packs a day a person smokes or something like that. The response, whether or not a person develops Alzheimer's disease during the course of this study. So is the amount of cigarettes or the number of packs of cigarettes you smoke, is that helping to explain the whether you develop Alzheimer's disease or not? Is the study described in the article an observational study or an experiment explaining? So again, experiment, I'm kind of thinking about 4 things, right? I need to impose a treatment, I need to have some randomization, I need replication, I need control for outside variables, confounding variables. And I don't think we need that here. I don't think we need that at all. So this is an observational study and not an experiment because smoking status amount was just observed, not manipulated by the researchers. So we just recorded what those 21,000 people did for 23 years, which is a pretty big sample size in a really long time frame. But we were not manipulating or controlling how much or how little they smoked. And obviously there's some real ethical issues with that. So this is not an experiment. Exercise status, regular weekly exercise versus no regular weekly exercise was mentioned in the article as a possible confounding variable. So we talked about that. It's a good word to know, sort of definition on how to use it. Explain how exercise status could be a confounding variable in the study. Okay? So it looks like perhaps those who exercise may impact the response of whether they got Alzheimer's or not, and maybe that's kind of clouding up whether it was related to smoking or not. Every time I go to my doctor, he asks me, "Are you exercising, Mr. Murphy?" So it feels like every doctor I go to asks me that. So exercise status, and those folks who exercise more, they might be more health conscious and less likely to smoke cigarettes than people who do not exercise. It's also possible that the people who exercise more are just less likely to develop Alzheimer's disease than people who do not exercise as much. And then I sort of added this again kind of down the bottom here. This probably may not be needed, but again, I just wanted this sort of note to myself. A confounding variable is one that is related to the explanatory variable and possibly could influence the response. So the fact that you exercise or how much you exercise could kind of be related or somehow tied into how much or how little you smoke. I would assume that people who exercise all the time might not smoke at all or smoke less than people who don't exercise. So hopefully that helps a little bit with this experimental design. I'm planning a study. Those are 3 or 4 free responses that I found and used over the year, and I tried to pick different problems for different things. I don't think we did this one, but this one is talking about convenience sampling and wording bias. So you might want to go back and we're looking at the slide again or looking at the webinar. Maybe go back and take a look at this. This is from the 2004 exam. We did that one and we went through that one. Hopefully not too fast, but hopefully I did at least a decent job with that. So hopefully by now you're feeling more comfortable with using the different random sampling techniques again we talked about before and designing an experiment to show causation. That's kind of the big word. I want to be able to at the end of a well-designed experiment say this caused that. Similar to every single problem probably that Luke and I do in AP statistics, probably just in life, you should be able to write a clear, concise solution in context. It's so important that every part of your problem, part A, part B, part C, whatever, you relate it specifically to that problem. We don't like these generic answers that you can use year after year. So here's your homework for tonight from the 2012 multiple choice. Luke will go over that tomorrow. I think it's related to experimental design. I think tomorrow he's doing FRQ Friday, so free response Friday. I did one a couple weeks ago. He's doing one tomorrow. So again, we know that all students, do not have access perhaps to the internet or device, and of course this year's AP Stats exam will be taken at home most likely over some sort of a device, computer, laptop, phone. College Board's working on solutions to help students get what they need to show their best work. So if you're interested in taking the AP Stats exam, and we hope you all do, that if that's a problem, connectivity, or you don't have a device, please reach out to the College Board at the link below. Contact one of your teachers, your AP coordinator, your AP Stats teacher, someone from the College Board will work with you to make sure that you can. We'll try to get you a device in hand. So that's it for today. I went over a few minutes. I hope I didn't keep you too long. I hope this helped. So thank you very much again for sitting in. You'll be with Luke tomorrow. I'll be back with you guys on Monday. So please be safe. Please stay positive, and keep working hard. And we hope that all this work that Luke and I are doing is helping out, and we appreciate all the hard work that you and your teachers have done. So I'll sign off for today. I'll see you guys next Monday. Have fun with Luke tomorrow, and we'll see you on Monday.
Hello, AP Stats students, and welcome to the College Board Virtual Instruction Regression for AP Statistics. My name is Luke Wilcox. I'm an AP Statistics teacher at East Kentwood High School in Kentwood, Michigan. I'm very excited about today's lesson, and here's why. At this point, I hope that most of you know that the AP exam for statistics for this year is a modified version of what we normally do, and is going to include only two free response questions. So today's lesson is specifically dedicated to the free response question, and we call it FRQ Friday. And in honor of FRQ Friday, I'm wearing my special Friday flamingo shirt, which I hope will help us through these free response questions today. I'm going to try and take you through three free response questions in their entirety, including the rubrics that are used to grade those three questions. So let's go ahead and jump right into things here. Check to make sure that everybody is in the right place. AP Statistics. Hopefully you at this point know who I am, Luke Wilcox from East Kentwood High School. And I'll get a couple of quick announcements out of the way. Most of you know this stuff already, but if we have anybody that is joining us for the first time today, this is a regular occurrence Monday through Friday, 2 o'clock Eastern Standard Time until 2:45. We are right in the middle of our AP exam review here, which we started at the beginning of this week, and we're going to take that through May 1st. That is where we will cover units 1 through 5. And of course, this is all in preparation for the big day, May 22nd, where you will all take the AP Statistics exam, where you will see the two free response questions. Now, any of the resources that you might need for these lessons that you're doing on YouTube, you can download in PDF form at statsmedic.com/YouTube. There's a link below. And then finally, the last comment here is for any students who are planning to take that AP exam on May 22nd, who may not have a device or internet access in order to be able to take that exam. We want to make sure that we can have you take that exam. So if you go to cb.org/tech, there's a form that you can fill out. I know that the College Board is very committed to making sure that all students have access to take that AP exam on May 22nd. All right, so next we are going to check in with the homework that Mr. Murphy gave you yesterday. And this is a check-in on some of the things that he talked about in the lesson yesterday. This is an old multiple choice question. And I have had some students ask, like, why are we still doing multiple choice questions if the AP exam is free response? And what I say to that is that I think that multiple choice is still extremely important, because any one of these multiple choice could end up being one of the parts of the free response. So let's go ahead and see what we have here. A compact disc manufacturer wanted to determine which of two different cover designs for a newly released CD will generate more sales. The manufacturer chose 70 stores. I think that's important. What I noticed there is that they did not take a simple random sample of 70 stores. They just simply chose 70 stores to sell the CD. 35 of these stores were randomly assigned to sell CDs with one of the cover designs, and the other 35 were assigned to sell the CDs with the other cover design. So listen, the fact that they have random assignment of these two different album covers is important, right? This is part of the experimental design. And the reason why we do random assignment is so that we create two groups which are roughly equivalent, so that if in the end there's a difference between the two groups, we know that it was caused by the treatment. So this random assignment is what's going to allow us to show causation. And we'll see when we look at the answer choices that this is going to be very important. All right, to finish up, the manufacturer recorded the number of CDs sold at each of the stores and found a significant difference between the mean number of CDs sold for the two cover designs. Which of the following gives the conclusion that should be made based on the result and provides the best explanation for the conclusion? So if we just look at answer choice A, it says that it is not reasonable to conclude that the difference in sales was caused by the different cover designs. Well, I think we already decided that because of this random assignment here, that we actually can show causation. And so I don't like answer choice A because it's saying that it's not reasonable to conclude that there was causation. In fact, as I look at answer choice B, it is not reasonable, causation. And answer choice C, it is not reasonable, causation. I can get rid of answer choices A, B, and C right away, which leaves me with two answer choices, both of which are saying it is reasonable to conclude causation. But we have to look at the end of the statement to decide which one is correct. So if we look at answer choice D, it is reasonable to conclude that the difference in sales was caused by the different cover design because the cover designs were randomly assigned to stores. Well, that random assignment is in fact what allows us to show causation. And if I look at answer choice E, they're making reference to the sample size being large, which is a good thing and might help us determine a model for the sampling distribution, but that's not what allows us to say that the causation random assignment that allows us to show causation. And so the correct answer there is D. So hopefully you did okay with that one. And we are now ready to jump into today's lesson, which you already know what's coming at you here. Very straightforward with the learning target. I was careful to make sure that I selected one FRQ from each one of the first 3 units in the College Board CED that are very exemplary. That's sort of our common type FRQs that you might see. And actually had some help in choosing these problems, and I'll talk about that when we actually get to the problem. So there it is. Exploring one variable data or two variable data, and then what Mr. Murphy talked about with you yesterday on collecting data. And we're just going to go through one free response for each one. And so the way I'm going to handle it is I'm going to first take you through the thinking of the model solution, and we'll write up the model solution. But then equally important, I'm going to take you through the College Board rubric on how the graders actually go about assigning points to each one of these FRQs, which will give you some insight about how you should write your responses for the AP exam. All right, so let's jump right in here. Question number 1. And let me tell you first of all how I was able to select these questions. I went to some of my best friends in the AP statistics community, and I asked them, what is your absolute most favorite FRQ that might come from the first 3 units? And Mr. Darren Starnes was helpful enough to give me one of his favorite FRQs. Darren is an AP statistics teacher in New Jersey. He has also been a question leader at the AP exam for many, many years, so very well known within the AP statistics community. And he said his favorite problem of all time goes way back to 2005, question number 1 about caloric intake. So let's go ahead and jump right in and see what we can come up with first with the model solution, and then I'll take you through the rubric for grading. So here's what it says. Number 1, the goal of a nutritional study was compare the caloric intake of adolescents living in rural areas of the United States with the caloric intake of adolescents living in urban areas of the United States. A random sample is good of 9th grade students from one high school in a rural area were selected. Another random sample of 9th graders from one high school in an urban area was also selected. Each student in each sample kept records of all the food he or she consumed in one day. The back-to-back stem plot below displays the number of calories of food consumed per kilogram of body weight for each student. Okay, so we've got this back-to-back stem plot here. And just to make sure we know what stem plot represents here, like if we look at, say, this here 3 and this 7, what that's telling me, I'm going to give you a little bit of a key here. That 3 and 7 is telling me 37. So the number here is the tens, and then the number that is the leaf is the ones number. So this represents 37 calories. And on the other side, well, there's 37 calories on the other side as well. Okay, so we have a back-to-back stem plot here. So here, part A said, write a few sentences comparing the distribution of daily caloric intake of 9th grade students in the rural high school with the distribution of daily caloric intake of 9th grade students in the urban high school. Okay, the important words here are compare the two distributions. We actually talked about this on Monday when we did one variable data analysis. And there are some very specific things that need to be addressed when you are asked to compare distribution. And the acronym that we had to help us remember that was SOX, and then I actually added on the last part to make sure that we include context when we answer that question. So we're just going to go through an order here. All right, S represents the shape of the distribution. We want to make sure that we comment on both of those. So first, if you look at the urban, the shape of it, it looks like we have most values sort of in the 20s, and then as we get into the 30s and the 40s, it starts to taper off a little bit. So as we're moving to the right, we're getting less and less value, which is telling me that distribution is skewed to the right. So I'm going to say this, the shape of the distribution. And right here, I'm going to go ahead and take care of handling the context of the problem right away in the first sentence. The context here, it's the distribution of daily caloric intake. And listen, once we've established the context once, we don't have to continue to say it over and over again, right? So we're done with that. And we're going to start for the urban student. And for the urban student, we said that the distribution is skewed right. Now for the rural students here, if you look, it's maybe got a center somewhere between 30 and 40, and it seems to be sort of equally distributed on either side of that center. So I think I would call that symmetric, or maybe to be a little bit more safe, I'd say fairly symmetric, because it's not going to be perfectly symmetric. So I'm going to say, wow, the distribution is fairly symmetric for the rural student. So that takes care of comparing the shapes. All right, the next thing that we want to comment on is any outliers that we might see. And I'm looking at both of these distributions, and I don't see any single values that are far away from the others. So I'm just going to go ahead and say that I don't see any outliers. I'm going to say there are no outliers for either distribution. All right, that takes care of outliers. Next up is to compare the centers. Now we could use the mean or we could use the median to measure the centers, but the important thing here when you're comparing is that you don't actually have to do any calculations. You just have to make a comparative statement about the center of one distribution compared to the other. Now for urban, the center is going to be, I don't know, maybe somewhere between 20 and 30, and for rural, it's somewhere between 30 and 40. Clearly, the center of the distribution for urban is less than the center of the distribution for rural. So that's just what we're going to put into third. Okay, and we're not going to even specifically reference the mean or the median or give any values here. We're just going to say sort of generically that the center of the distribution for the urban student is less than, there's my comparative words, less than the center for the rural student. So that takes care of the center, and the last thing we need to take care of is the spread, which we could measure with, say, the range or the IQR or the standard deviation. But once again, we don't have to calculate specific value. And so let's just look in general at the spread. For urban, the lowest value we have is 26. The highest value is 42. For rural, the lowest value is 32 up to 51. So those are fairly close there. But I think that urban has a little bit less variability there if you were to just compare the range, right? So we're going to say the variability for urban students is less than for rural students. So that takes care of spread. We definitely took care of context right up front. So I believe that we have a model solution here for comparing those two distributions. All right, let's move to part B, which says, is it reasonable to generalize the findings of this study to all rural and urban ninth grade students in the United States? I think this is the word that's important here. Can we generalize to a larger population? Well, it depends how we took our random sample here. So I'm going to go back to the stem of the question and let's look at how they took these samples. Okay, we have, let's see, a random sample of ninth grade students from one high school in a rural area. One high school. If it is a random sample from one high school, then we can only generalize the results to that one high school. We can't say all rural high schools, but only this one rural high school. And for the other sample, random sample of ninth graders from one high school in an urban area, once again, it's one high school. So we're not going to be able to generalize this to a bigger population of all ninth grade students. So let's make that very clear here. First of all, answer the question. Okay, the question is asking, is it reasonable? And the answer is no, it's not reasonable. And then we have to give some sort of explanation. So we're going to say that the random samples were taken from one urban high school and one rural high school. So we can only generalize to those two high schools. And actually, I'm going to say, so we can't generalize to all ninth graders. Okay, so that takes care of part B, and we can move on to part C, which says researchers who want to conduct a similar study are debating which of the following two plans to use. Okay, plan one: have each student in the study record all the food he or she consumed in one day. Then researchers would compute the number of calories of food consumed per kilogram of body weight for each student for that day. Plan two: have each student in the study record all the food he or she consumed over the same 7-day period. Then researchers would compute the average daily number of calories of food consumed per kilogram of body weight for each student during that 7-day period instead of 1 day. Assuming that the students keep accurate records, which plan one or two would better meet the goal of the study? Justify your answer. Now, here's the deal: if they just did it for one day, it would sort of depend on the day. Like some days students eat more, maybe it's Friday night and they go out and have pizza, and their calories are higher, and then other days are lower. If we were to do it for 7 days, we would have the lower ones and the higher ones, and then we take the average of those. And that is going to be a much more precise measurement of daily caloric intake than the 1 day. So we definitely want to say that we like plan 2 better here. And then we have to explain why. And so I'm going to say that the reason it's better is because we're going to get less variability. If we only pick 1 day, that could be high, could be low. But if we pick the average of 7, it's going to be much less variable. So I'm going to say the lower variability of results in plan 2 would make it easier to determine if there is a significant difference between urban and rural. So that takes you through the model solution. We are now going to talk about how the AP exam graders would grade this. And I need to start by telling you some of the framework that graders use when they're looking at these group responses. And here's the first thing that you need to know. For each part of the question, they are going to give you either an E, P, or an I. And an E means that you have that essentially correct. A P means that you have it partially correct. And then an I means that you have it incorrect. And then at the very end, they'll look at the E's, P's, and I's, and they will convert that into a score out of 4 points. Okay, every free response question is worth 4 points. And I will show you how to do that once we get to the end of this here. So let's go through the grading for part A, and I'll let you know what is needed in order to get full credit on this here. And I'm just going to put this out in the margin here. So I'm going to start with what you would need in order to get an E essentially correct here. According to the rubric, you would have to compare, and there are 3 things that are found on the rubric. They want you to compare the center, the shape, and the spread. And so when we look at this model solution here, comparing the center, we have center here, and we have used comparative words, and the comparison is correct. For shape, we have shape here, and we have compared the shape for the one distribution versus the other distribution. And for spread, we called it variability, and we have a comparative word there that is correct. So we definitely would get an E for this part. Now, to get partially correct, you would have to have 2 out of the 3, right? So maybe you forgot to talk about the spread, but you talked about the other 2. That could still earn you a partial credit. And then, of course, an I would be 1 or less. Now, a couple of important things I want to point out. One thing you don't see on the rubric is anything about outliers. And there have been rubrics besides this one that have asked about outliers. Also, the other thing you don't see on the rubric is anything about context. And so sometimes it shows up on the rubric and sometimes it doesn't. But as a general rule, you absolutely want to include context, even though you don't specifically see it in this particular rubric here. Okay, so let's move on to part B and talk about the rubric for this one. And this one's pretty straightforward. In order to get an essentially correct, you had to answer the question by saying no and referencing the fact that there is one rural high school that was selected and one urban high school that was selected, which very clearly we've referenced that and we've answered the question of no, so we would get an essentially correct. There is no partially correct on this one. You either got it or you didn't. So if you didn't have those things, that would be incorrect, which means if you just simply wrote no and you didn't give an explanation, that would be considered an I incorrect. All right, and let's move down to the third part, part C, and let me talk about what you would need in order to get an essentially correct here. Well, the first thing is you have to pick the right plan, which is plan 2, and then you have to give an explanation, and the explanation has to be based on variability by saying that the variability is lower for plan 2 than it is for plan 1. You could also say more precise estimates. That's the same as saying lower variability. So partially correct would be if you did choose plan 2, you had the correct plan, but then you had some sort of weaker justification, and then you would get an I otherwise. So I think for our 3 solutions here, we did get an E on part A, an E on part B, and an E on part C, and then we can now convert that into a score out of 4 points. So here's how you convert the score, and you'll notice here that if you got 3 E's like we did, that would be scored as a 4. If you had 2 E's and 1 P, that drops you down to a 3. There are several different ways that you could end up with a 2 out of 4, 2 E's and no P's, or 1 E and 2 P's, and then also several ways that you could end up with a 1. And if you don't see your E's and P's on there, there is the possibility of being 0. Right? That is also possible. So that takes you through question number 1, and I think we are ready for our second FRQ of the day. And for this one, I went to my colleague, Lindsay Gallus, who is also the co-founder of StatsMedic, and I asked her, what is your absolute favorite FRQ? And instead of giving me her favorite FRQ, she gave me her least favorite FRQ. And her explanation was that when she gives this one on a test, it is very, very difficult to grade. It's a lot of work for the teacher. So I thought that we will just include her least favorite FRQ. This is 2017 number 1, known as the wolves problem. So let's go ahead and come up with our model solution first, and then I will take you through the rubric for grading. So here's what it says. Researchers studying a pack of gray wolves in North America collected data on the length X in meters from the nose to the tip of the tail and the weight Y in kilograms of the wolves. A scatter plot of weight versus length revealed a relationship between the 2 variables described as positive, linear, and strong. Part A. For the situation described above, explain what is meant by each of the following words. Okay, I will tell you that this is a little bit different than a traditional problem that assesses scatter plots and linear relationships. A lot of times you'll be asked to describe the relationship between the 2 variables. But look, they've done that for us. Positive, linear, and strong. What they want to know is what do those words actually mean? And we're going to look at each one of them in part A. So explain what is meant by the following words. So let's start with a positive relationship. And what a positive relationship means that as the X value goes up, the Y value tends to go up as well. But we want to put it in the context of the problem. So as the X value goes up, the wolves are getting longer and longer. So I'm going to say wolves with longer lengths, right? That's the X value increasing, tends to be paired with values of Y that are larger. In this case, their weight. So I'm going to say tend to weigh more. So the longer the wolf is, the more we expect the wolf to weigh. That's the positive relationship. Now for linear, we have to talk about why, what it means to be a linear relationship. And if you think back to your algebra days, linear means that as the X value increases, the Y value increases at a constant slope, right? So let's put that in the context of the problem. I'm going to say as length increases, the weight increases at a constant rate. And when I say constant constant rate, I'm referring to the slope. So I'm going to even make that very clear here that there is a constant slope. And then finally, to describe the relationship as strong. Well, the strength of the relationship depends on how close those points in the scatter plot are to the form that you've chosen. In this case, we chose linear as our form. And if it's strong, that means that those dots are all going to be fairly close to that line. So I'm going to say the points on the scatter plot are generally close to the line of best fit. And if the dots are relatively close to the line of best fit, then that means that those residuals, which is the error in the prediction, are all going to be generally pretty small. So I'm going to put a little add on here that we have small residual, right? If those points are close to the line, then we should have small residual. So there's our model solution for part A. Let's move on to part B. So the data collected from the wolves are used to create a least squares regression equation. Okay, a couple things we want to notice right away. First of all, y in this particular context is the weight of the wolf, and then x, the explanatory variable, is the length of the wolf. And we have our values there for the line of best fit. And it says interpret the meaning of the slope of the least squares regression line in context. Okay, first we have to correctly identify the slope, and hopefully you know that the slope is the value that's attached to the x there. And usually we denote that with the letter b, lowercase b. That is in fact our slope, 35.02. And just a reminder of something that we talked about earlier this week, that in general, the slope can be thought of as being the change in y over the change in x. But for this particular context, change in y would be the change in the predicted weight, and change in x would be the change in length. And we know that this value is 35.02, but I'm going to write it as 35.02 over 1, which is going to help us with our interpretation of the slope, because we know that for a change in length of 1, we predict the weight to increase by 35.02. So we just have to put that in words now. So here we go. For an increase of 1 meter in length, the predicted weight increases by 35.02, and our units for weight is in kilograms. So there we have our interpretation of the slope of the line of best fit. And we are ready for part C. It says one wolf in the pack with a length of 1.4 meters had a residual of negative 9.67 kilograms. What was the weight of the wolf? Okay, so this time we're given the residual. We don't have to calculate it, we're given. And I think what we're asking for when it says what is the weight of the wolf, what we want is the actual weight of the wolf. And so I have to understand how that residual value is calculated. And so just a reminder here that if you're trying to find a residual, it is the actual y value minus the predicted y value, right? A minus b, a b. And listen, we know the residual value, it's negative 9.67. Now the actual value we don't know, that's what we're trying to find. So this is the unknown value. So think of that as being like x, that's a variable, the unknown, minus the predicted value. Well, they didn't give us the predicted value for this wolf, but we can calculate the predicted value because we have up here, we have our equation for the line of best fit, which will allow us to find the predicted weight. So I'm going to do this work off to the side just a little bit here. What I need is the predicted weight for this particular wolf. And according to my equation up there, I've got negative 16.46 plus 35.02 times the length. And I know we're dealing with a wolf that has a length of 1.4. So I just plug in 1.4 correct. And if you plug that into your calculator, you're going to get 32.568 as the predicted weight. And that is exactly what we can now plug in for our predicted weight. It is 32.568. And we're left with a very simple algebraic equation to solve here. If we want to solve for the actual value, we need to add 32.568 to both sides of the equation. And this will cancel. And we will be left with an actual weight of 22.898. And I want to make sure I include units in my answer. This is a actual weight. So the units on it should be kilograms. So I'm going to say 22.898 kilograms is my final answer here. So now we need to go back and take a look at the rubric for how this thing was graded. Okay. And you're going to find out real quickly here why Ms. Gallus said that this was her least favorite in order to grade. And it has to do with part A here. Okay. For part A, in order to get your essentially correct, you have to have a reasonable definition for three different things. The three things you see right here: a reasonable definition for positive, a reasonable definition for linear, and a reasonable definition for strong. And the rubrics on this are a little bit lengthy. And I'm just going to quickly highlight a couple of things. All right. For positive, if you look at the rubric and they want you to describe a positive relationship, here are acceptable responses for that. As length increases, so does weight, which is very close to what we wrote in our model solution. Longer wolves weigh more. Another way of saying the same thing. And the points on the graph go up as you move left to right. Those are all acceptable responses. Unacceptable responses: as length goes up, weight changes. Well, which way does weight change? Does it go up or does it go down? Both length and weight get bigger. Well, does that happen together or in opposite directions? We don't know. And then the correlation is greater than 0, also an unacceptable response. So I would say that our solution looks okay here because we said longer lengths tend to weigh more. Now for linear, let's look at the rubric for linear relationship. Here are the examples of acceptable responses. The points generally follow a straight line, which is fairly close to what we wrote. The relationship between x and y is straight, or length and weight have a constant slope. And we did reference the constant slope in our A. And now the unacceptable responses. The points all line up. Not quite enough there. You can draw a straight line through the point. Well, it turns out you can draw a straight line for any point, whether they're linear or not. There's a positive correlation, or every increase in x yields a 35.02 increase in y, also unacceptable. So I think our response looks okay here. We definitely reference the idea that there's a constant slope. And then finally the strength. If you look at the rubric here, strong, the acceptable responses for that one. Observed values are close to predicted values. Deviations from the least squares regression line are small, which is about what we wrote. And then you could reference the correlation coefficient being close to 1. Unacceptable responses is to just simply say all the points are close together. Doesn't quite tell you about strength. And the scatter plots are clustered together. Doesn't quite make sense. So you can see why Ms. Gallus had trouble with this one, because the grading of it is kind of a mess. Now for a partially correct here. Oh, I'm sorry, I didn't give you the last thing here. Number 4, it has to be in contact. And we definitely included contact by talking about the wolves and their lengths and their weight. So partially correct would be 3 out of the 4. So maybe you forgot contact, or maybe one of your descriptions didn't quite fit in the acceptable bin. And then for an I, it would be 2 or less. Okay, let's move on to part B and let's talk about the rubric for grading part B. In order to get an essentially correct here, there are 3 components that are necessary to get full credit. The first of which is to correctly identify the slope, 35.02. The second is to talk about how there is an increase of 35.02 for each increase of 1 in x, which is really sort of word for word what we said. We said increase, we said 1 meter in x, and then 35.02 in y. And then finally, and this one's really important, number 3, the language you use. It is not the weight that goes up by 35.02. It is the predicted weight, or you could say on average, or estimated. So you have to have one of those types of words in there, rather than saying specifically the weight would increase by 35.02. So partially correct would be to have 2 out of the 3, and an incorrect would be 1 or 0. And then we are ready for part C. In order to get full credit here, essentially correct, there are 2 components that you need. Number 1, the correct calculation for the predicted value of 32.568, and we had our work shown over here. And then the second component is to have the correct answer in the end of 22.898, which we have here. We have both of those components that would be essentially correct. Partially correct, you have to have just one of those 2, and then incorrect would be 0. So I sure hope that we have essentially correct here, and we can now convert that into a score out of 4 points, and that is going to look very similar to the other rubric that we looked at. In order to get our 4, you're going to have 3 essentially correct. 3, you're going to have 2 essentially correct and 1 partial. Several different ways of getting a 2 out of 4, and a couple of different ways of getting a 1 out of 4. And remember also that you could get a 0 out of 4. So that takes us to our third FRQ, and this is the favorite FRQ of Josh Faber, who is an AP statistics teacher in Arizona, has also been a question leader at the AP exam for many years. And if I remember correctly, I think this may have been his question, and I certainly remember spending many days grading this particular question. Now, this should look familiar to you if you were here with Mr. Murphy yesterday. He used this as one of his example problems in the lesson. And so I'm not going to focus as much time on the solution here because he's already gone through that with you. What I would like to talk to you about is the rubric that's used to grade it. So I'm going to show you the solution first, and then let's talk about the rubric that would be used to grade it. So in part A, you had to identify the explanatory variable and the response variable. In part B, you had to describe whether it was an observational study or an experiment. And then in part C, you had to explain a confounding variable. So let's talk about how this would be graded. So for part A, let's start with what is necessary for an essentially correct. Okay, so this one for essentially correct, both variables are correct. Now there is a little bit of a hang up on this one. The explanatory variable, a lot of students, I remember this over and over again. I had students that wrote smoking and wrote Alzheimer, and that was not enough to earn full credit. That was actually a partial credit. And the reason is that if you just say smokes, that's not really a variable here. The variable is a categorical variable, which is yes or no to smoking. So you have to say something like smoking status or smoking yes or no, or in this case, I've written whether or not the person person smoked, which is making it a variable, a categorical variable, where you would record yes or no. And the same thing goes for Alzheimer's. So you can't simply write Alzheimer's. You have to say something about Alzheimer's status, or yes or no, or whether or not. So both variables correct. You get an E. If you had one variable correct, you would get a P. The other way that you get a P, as I mentioned before, is if you simply wrote smoking and Alzheimer's, that would be good for a partial credit. And the other way you could get a partial credit actually is if you had flipped the two, explanatory and response, but you had defined them both correctly, you could still get a partial credit on it. And then an incorrect would be anything else. Now moving on to part B, grading this one here. In order to get essentially correct, you definitely had to say, oh, this is not correct. We need to fix this here. This is not an experiment. This is an observational study. And the reason it's an observational study is because there was no random assignment of treatment, specifically the treatment of smoking. They didn't tell some people to smoke and some other people not to smoke. So for full credit here, you have to say observational study, and then you would have to say that smoking was not assigned. Okay, one side note here, it was not enough to just say a treatment was not assigned. You have to identify what the treatment is. The treatment here is smoking. And that was the treatment that was not assigned or imposed on the men and women. So a partial credit here is maybe you said observational study, but then you left off the smoking part. So smoking was missing. You said something about no assignment of treatments, but you didn't specifically say the treatment was smoking. And then I would be otherwise. All right, and that takes us to the last part C. And for this one, in order to get full credit, there are two components that have to be included. Component one is that you have to link exercise to smoking. And the way that you see that in the model solution here is saying people who smoke might exercise, and actually I wouldn't say that they would exercise more. I would say that they exercise less. Right? You think that people who smoke more would exercise less, and so that's component one. Component two is that you have to link exercise to Alzheimer's and say that it influences the risk of Alzheimer's. And you're gonna see that in the second part here. Exercising more might lower your risk of Alzheimer's. So you have to have a connection between exercise and smoking, and then you have to say how that exercise might influence the risk of Alzheimer's. Now for partial credit on that, you would just have one of the two components, and for incorrect, you would have zero of those components. So after a few corrections on this one, it appears that we have an E now, and an E, and an E, and we can now turn that into a score out of 4. And this rubric is going to look the same as the one we just went over, right? In order to get a 4, you have all 3 parts essentially correct. 3 would be 2 essentially correct, and 1 partial. Several different ways of getting a 2 out of 4, several different ways of getting a 1 out of 4, and of course there is the possibility of getting 0 out of 4. All right, I do have a homework problem for you that I'd like you to do before Monday, where you will join Mr. Murphy and he will go over that with you. I certainly hope that this FRQ Friday is something that is helpful for you, looking at the model solutions, but even more importantly, understanding how the graders are going to be grading that, so that you know what you have to include in your responses. So if you felt like this video was helpful for you, please in YouTube there, give me a thumbs up to let me know that this was helpful for you. And I certainly hope that you will join us again on Monday, where you will be with Mr. Murphy, and then I will be back on Tuesday. So have an excellent weekend.
Good afternoon, AP Stats kids. Monday, April 20th. Hope everyone's safe and healthy at home. Thanks for stopping in again this afternoon. Happy Patriots Day. I know that may not mean anything to most of you, but I grew up in the Boston area, and I now live in Maine. You hear the Boston accent, and Patriots Day is a holiday in those two states. I don't think it's a holiday anywhere else, but it's a big day in New England, kind of a fun day. Most years they run the Boston Marathon. This year, of course, they're not running that marathon. So anyway, happy Patriots Day from New England. And if any of you end up going to school in the Boston area, you'll see next year it'll be a super fun day, and they run the marathon, and everyone has day off. So anyway, welcome back. So today, tomorrow, and Wednesday, Luke and I are going to do probability. That's one of the big, what I call one of the 4 themes or threads of the course. You know, most typical years it would be 10 to 20% of an AP exam. I don't even want to speculate on this year's test because it is different. But you know, somewhere in one of those 2 free responses, you know, I'm going to stick my neck out and say you'll get some probability. So Luke and I wanted to spend 3 days on it. So today I'm doing conditional probability, two-way table, maybe the basic probability. He's going to do binomial and geometric probability tomorrow, and then Wednesday I'll be back to do random variables. So we want to do a good job of probability. It tends to be perhaps a more difficult theme or thread for students. So we decided we wanted to do a pretty good job of it. So anyway, there's our intro slide as always. Again, I'm Brendan Murphy. I teach at John Baptist Memorial High School in Bangor, Maine. It's school vacation week this week. Luke is from East Kentwood High School in Michigan, and hopefully you've seen both of us. So I think this was your homework problem from Friday, and Luke did some pre-response questions. So the seniors at 3 high schools were surveyed about their plans after graduation. The table shows the responses classified by high school. So I like to call this a two-way table. And many times we're trying to see is there some relationship between your high school and maybe your plans after graduation or something like that. These totals over here on the right and down the bottom, it feels like sometimes we give you those totals, and sometimes we just give you the table without the totals. If we give you a table without the totals, I think it would probably make sense to just have all of those different totals. It won't take that long, especially with a calculator. Almost always I need at least some of those totals. So one senior from the high schools will be selected at random. What is the probability that the senior selected will not be from high school B, given that the senior responded with a choice other than college? So that last sentence, you know, that you might need to read that twice. There's kind of a lot going on in that last sentence. So I'm going to read that last sentence again. What is the probability that the senior selected will not? So that's nice. I mean, that was underlined for us. If not, I probably would have circled it. Be from high school B. So I'm going to focus kind of on high school B over here. Given that, so that's kind of the key words. That this is what we call conditional probability. And I'm going to do some more with that today. So what we call conditional probability. There's a constraint, there's a condition, there's a limiting factor on how I calculate my probability. Given that the senior responded with a choice other than college. So I guess I'm not going to worry about this column here. It's other than college. So I just said, well, we're not going to worry about those 418 students who went to college. So it felt like my denominator wanted to be all of those students who either chose work, chose military, or chose undecided. So down here, that was my denominator. And I added those up and I got 538. And I actually could have gotten the correct answer based upon that. But you know, let's keep going and really understand the problem. So going back to this sense, what is the probability the senior selected will not be from high school B? So I guess I'm not going to worry about those students. I guess I'm not going to worry about those students. I guess I'm not going to be worried about those students. So I guess I'm not worrying about college, right? And will not be from high school B. So I actually had almost 2 things here that I didn't really need to take into consideration. This felt like a harder one to me. So some of them, I'm going to do a couple multiple choice in that for response to. This one was a little bit harder for me. So it looks like I need those 99 students and those 83. And I need those 49 and those 31. I need those 63 and 71. If I did my math correct, I get 396 over 538. So two-way table. Again, these totals were given to us. If they weren't given to us, I think it's well worth your time to add those in typically. And then really make sure that you understand the questions. Sometimes the wording, it feels like students kind of reverse what we're asking them. And that can be easier to do than you think. So really spend time just understanding the question and making sure you're addressing that question. So that was the homework for Friday night, I guess. Again, here's a couple of websites. I think I've gone through these, so I'll just go through these really quick. But any questions about this year's exam, please, all this information is here at College Board's done a wonderful job of trying to get that information out to everyone. So I'm going to try and address the 2 concepts of mutually exclusive and independence today. They're 2 completely different concepts. My students will struggle with these, and it feels like in most books they're sort of introduced maybe in the same section of your textbook or right next to each other, and they can be a little bit confusing. So I'm going to try and tackle both of those today. 2 events are mutually exclusive or disjoint. Those 2 terms mean the same thing. And I think I've seen both of those on previous AP Stats exams. So feel comfortable with both terms. So 2 events are mutually exclusive or disjoint if they cannot occur at the same time. So the probability of A and B equals 0. So you cannot be in the state of Massachusetts and the state of Maine at the same time. You can't do it. You're either in Maine or you're in Massachusetts or you're in either place. But you can't be in both states at the same time. Mutually exclusive events are not independent of each other. And I capitalize that not for a reason. That's harder for kids, I think. And my kids sometimes will struggle with that concept. Okay, sorry about that. So mutually exclusive events are not independent of each other. And that may be not what your brain is telling you. So here's a Venn diagram, and I say to my students, let's assume that the only two grades you could get in my class are A and B. And they love that. They say, yes, Mr. Murphy, we love that. That's great. So let's say you can either get just an A or a B. There's no other options. So there's no overlap. Like that Venn diagram where it looks like, you could be in both A and B. So you get an A or you get a B. Okay? So those two events are clearly mutually exclusive or disjoint. There's no overlap. So I say to students, at the end of the 45 day, quarter 3 or quarter 4, whatever, there's a whole bunch of grades in the grade book. We'll do a little math, and but the numbers are there, and your grade's already predetermined. I just maybe need to worry about some percentages or adding some final homeworks or something. So let's say you get a 96 at the end of quarter 3. Well, that's an A in my school, probably an A in all of your schools. Well, those numbers again are really predetermined. I'm not really doing anything other than going to my computer and maybe finishing up a few little odds and ends. Well, if you get a 96, that's an A. Well, the probability of you getting a B is going to be 0. You're not going to get a B. You're going to get an A. So those events are mutually exclusive. There's no overlap, but they are not independent of each other. Independent events, the probability of the second event isn't impacted by the probability of the first event or something like that. So your eyes are telling you that they're independent. They're not hitting each other. There's no overlap, but there's no overlap. But that's really not what independence means. So I have my little coin here and my six-sided number cube. If you ever hear that term, six-sided number cube, I guess some of us might call that a dice or a die. I think those two events are independent of each other. If I were to shake them in my hands and roll them or throw them, the outcome of this coin is clearly not impacted by the dice or die or vice versa. So most students say, yeah, that's pretty obvious that those are independent events. Probability of one isn't impacted by what happens with the first event. So I have problems to deal with both mutually exclusive and independence. I'll get to all of them. So here's a multiple choice question from the 2007 exam. A fair coin is to be flipped 5 times. And so again, a fair coin just means that the probability of heads is equal to the probability of tails. You don't get one more than the other. So that's all a fair coin means. The first 4 flips land heads up. So I guess I get heads. What's the probability of heads on the next 5th flip of this coin? So I usually just put a little dash there. That would be my 5th flip. And probability of getting heads here is 1/2, 50-50, whatever you want to phrase it. Only because each one of those flips is independent of each other. So the 5th flip here is not impacted by what's happening to any of those first 4. So the answer is B here. Relatively straightforward. 76% of the students in 2007 got that problem correct. If we start to look at some of our distractor answers, well, probability of 1 means it has to happen. So that doesn't make sense. I don't have to get heads even at first 4. E0, well, that means I can't get a heads. Well, I guess I could flip a coin 20 times and get 20 heads in a row. I don't really know. I think C, so it's like the binomial formula. I think Luke will tackle that tomorrow. And D here, I guess it's trying to mimic maybe what I did here. I have heads, and the probability of each one's a half. And just, I'm going to raise that to the 4th power and to get my 5th head. I think that's the probability of getting 5 heads in a row. So that was a relatively easier one. Let's keep going and they will get a little bit, I think, more difficult here. This is from 2007 exam. An experiment, so I think I'll underline that word, has 3 mutually exclusive outcomes, A, B, and C. Okay, mutually exclusive, there's no overlap between those 3 different outcomes, A, B, and C. The probability of A is 0.12, the probability of B is 0.61, the probability of C is 0.27. Which of the following must be true? That's strong language. I think I'm going to underline that must be true. So you can see down here, I've drawn my Venn diagram. Clearly my circles, they're not proportional to the probabilities. It doesn't matter. This is just a working diagram for me to sort of solve the problem. So here's outcome A, here's outcome B, here's outcome C, and there's the associated probabilities. Just for the heck of it, I added those up and I did get 1. So those are the only 3 outcomes that I could get. If it wasn't 1, I might have put a little number kind of out here, the rest of the Venn diagram, but it's 1, and so I have my 3 circles, and I think I'm good. Well, Roman numeral 1 says A and C are independent. Well, we just talked about mutually exclusive events are not independent of each other. So let me go back to that slide. Mutually exclusive events are not independent of each other. That's an important concept, and there's 2 different major concepts going on here. So make sure you're comfortable with that. And I think in some ways that's really what this problem is testing. Do students understand that mutually exclusive events are not independent of each other? Mutually exclusive events are not independent of each other. So A and C are independent. Well, that's false. That's false. Because of that, I can actually circle the answer D here because all the rest of them have a Roman numeral 1. And so literally, if students could understand that mutually exclusive events are not independent of each other, this problem wasn't all that hard. But let's keep going and see if Roman numeral 2 and 3 makes sense. Well, the probability of getting A and B is 0. Yeah, that makes sense. You're either an A or B. There's no overlap. You have to be an A or B. So you can't be in both at the same time. So the probability of A and B is 0. That makes sense. The probability of B or C is the probability of B plus the probability of C. Again, that's a true statement only when there's no overlap. If there was an overlap, we have to worry about subtracting the overlap, but there isn't. And so I have Roman numeral 1 is false. Roman numeral 2 is true. Roman numeral 3 is true. So I got D. So you can see that 35% of the students got that right. That's a lower scoring multiple choice. And again, I think it's this sort of confusion about mutually exclusive events and independence. So hopefully you're feeling a little bit better about that. Mutually exclusive events are not independent of each other. That slide was there for a reason. Hopefully that makes a little bit more sense. And I think we got some free response coming, so I'm going to try and tackle that as well. So one more free multiple choice, and then we'll dive into some free responses from 2012 exam. So a complex electronic device contains 3 components, A, B, and C. So I'm making some sort of device, and there's 3 different things that go into it. The probability of failure for each component in any one year, 0.01, 0.03, and 0.04 respectively. I guess if I owned a company that was making this complex electronic device, it would be great if that was 000, meaning every single part was perfect. That's not the world we live in, unfortunately. So we're going to get some parts that aren't perfect, unfortunately. If any one component fails, the device will fail. Well, that makes sense. If either A, B, or C doesn't work, it makes sense to me that the complex electronic device is not going to work either. So that makes sense. If the components fail independently of each other, so the outcome of A is impacted by B, or B is impacted by A, vice versa for all 3. So that's super important. It's super important to solve this problem. What is the probability that the device will not fail? Again, College Board seems to be underlining not fail or not pass or whatever. So that helps. That's important. We're not trying to confuse or trick kids here. What is the probability that the device will not fail in 1 year? So I said the probability of A failing is 0.01. So the probability of A succeeding or success, I guess, is 0.99. It either fails or doesn't fail. The probability of B failing is 0.03. So the probability of B success is 0.97. The probability of C failing is 0.04. The probability of C succeeding is 0.96. So I think those are the 3 numbers that I need. I could see very easily students maybe multiplying those 3 numbers here and getting one of the distractor answers or adding them or something like that. But those are the 3 numbers that I need. Success, success, success. Not fail means success. So I said PA success times PB success times PC success. I got 0.921808 or something like that. Those 3 numbers. I'll go to the calculator real quick just check myself. And I'm hoping that that's a relatively high number, i.e. close to 1. I want to make all of my different machines, whatever complex electronic device is. And I would love it if every single one of them was perfect. That would be dynamite. That's unfortunately not the world we live in. But I still want this number to be relatively high. And I can live with that 0.92, 92% of the time, or over the long term, 92 out of 100, 920 out of 1,000. Probably only works the long term, of course. Again, I would like that number to be 1 exactly. But we know in the real world that nothing's perfect. And in manufacturing, we know that we're going to get X amount of whatever that aren't 100% perfect. And we just sort of have to unfortunately live with that. I wish every single problem I ever did every single day in the classroom was perfect, or my students understood it perfectly. And unfortunately, I don't know if I'm a good teacher. So that doesn't happen every day in my classroom, unfortunately. So okay, so let's see if we can tackle a free response here. This is from the 2002 Form B. We used to call it the international exam. We used to release 2 exams. I wouldn't worry about it, but that's what Form B means. This is free response number 2. So airlines routinely overbook flights because they expect a certain number of no-shows. So well, I haven't flown in a long time and may not fly for a couple months, but I fly a reasonable amount, and many times the airlines oversell and they ask for volunteers, and my wife and I have taken advantage of that. Many times we've gotten X amount of dollars from the airline by voluntarily giving up our seat, and given that opportunity, sometimes it's a great deal. So an airline runs a 5 p.m. commuter flight from Washington D.C. to New York on a plane that holds 38 passengers. Okay, what we would call a regional jet. I live in Bangor, Maine, and every plane that comes in and out of Bangor is a regional jet. Smaller planes. Past experience has shown that if 41 tickets are sold for the flight, so again, there's only 38 seats on the plane. The airline wants to or does sell 41 tickets, and they do that because they know some of the businessmen or whatever just miss the flight because of traffic or the meeting went longer or whatever. They decide to stay another day in the city or something. And the probability distribution for the number who actually show up for the flight is shown in the table below. So again, if probability of 36 people showing up is, I guess, 0.46, and 37 people 0.30, et cetera, et cetera, et cetera. Again, I think I would add up those 6 probabilities, and I want to get 1. If I got 0.999 something, I'm not sure I would be overly upset about it, but I want that number to be 1. So that 41 tickets are sold for each flight. So every flight, every day, 38 seats, the airline sells 41. Okay? I think I understand the problem, and again, I think I've said many times that it's well worth spending another 20 seconds, 30 seconds, whatever, really understanding the problem before you actually sort of dive into the problem. So you can see my little signal there, I did add up, and I got 1, so I felt pretty good about that. So assume 41 tickets are sold for each flight. Okay? There are 38 passenger seats on flight. What is the probability that all passengers who show up for this flight will get a seat? Okay? Well, if 36 people show up, and that's it, all 36 people are going to get a seat on the plane. If 37 people show up, all of them get a seat on the plane because there's 38 seats. And if 38 people show up, they're all going to get a seat again because there's 38 seats on the flight. So I think I just added those 3 probabilities and got 0.92. I almost walked away from it, and then I said, no, Mr. Murphy, you really need to sort of put a sentence there or something like that. Make sure it's in context. So many times I just kind of repeat the question asked. The probability that all passengers who show up for this flight and will get a seat is equal to 0.92. So in some of these probability problems, it's easy enough to just kind of look at the table sometimes and get the correct numerical answer. But again, super important. We want some context there. We want to relate it to this problem. What is the expected number of no-shows for this flight? So I've done this problem many times, and I'm not going to say what I'm going to do is incorrect, but what I didn't exactly address the question. I had to think a little bit, and I could get there relatively quickly. So I said the expected value X is the outcome times the probability plus the outcome times the probability plus the outcome times the probability. So I felt comfortable with that. You can see here's all my math. So I said 36 people showing up times 0.46 plus 37 people times 0.30, et cetera, et cetera. And I got 36.9. That didn't feel good to me. And I said to myself, wait a minute. On a 38 passenger plane, the expected number of no-shows is 36.9. It took me a couple seconds. I calculated the number of people who theoretically will show up. So I didn't actually address what they wanted. So 41 minus 36.9, 4.1 is the expected number of no-shows. So my math is correct here. I guess maybe I was just answering the wrong question. I'll show you how to do it so correctly down below. I don't want to round that number. Many times on the AP exams when we're grading these, we'll see students, come up with the correct math. 4.1 is over here. They say, 4 is the number of no-shows because they say things like, well, you can't have 0.1 of a person. Well, this is an expected value, an average, and we don't want to round those. We don't want to round expected values or averages. The average American family has 2.2 kids or something like that. We don't want to round that to 2. So be careful and make sure that you understand that. Don't round an expected value unless specifically told otherwise. So again, in the full sentence, the expected number of no-shows for this flight is 4.1. So what I did wasn't wrong. I guess I was just answering the wrong question. I had to do a little bit more math to get the right answer. I guess I could have done 41 minus 36, 5 times 0.46, 41 minus 37, or 4 times 0.30, 41 minus 38, et cetera, et cetera, et cetera. Ian gotten that number 4.1 directly. Same answer. I felt confident that I had done something correct up here, but I just really wasn't answering the question that they asked. So just be careful about that. And again, show your math and notice that I'm trying to answer the question with a full sentence. So given that not all passenger seats are filled on a flight, well, that sort of feels like a conditional probability, right? Those 2 words, given that's the tell, that's the red flag. Given that not all passenger seats are filled on a flight, what is the probability that only 36 passengers showed up for this flight? So I'm just going to go up to my table here and say, well, given that not all passenger seats are filled, I'm not going to worry about the rest of the table here because 38 all seats will be filled, 39 all seats will be filled. So for the last half of the problem, many times I just cover that up. 36 not all seats are filled, 37. So I think I just added the 0.46 and 0.30 right down here. Where's the probability that only 36 people show up? There's my 36. So that's my 0.46 down here. Sorry about this. Hard to get the whole problem in here. I tried to write out sort of in words maybe the formula that I'm using. And again, I just don't want to show these numbers here. That wouldn't be a very good answer, or just that wouldn't be a very good answer at all. The reader's going to say, where did you get that number? We want to see your backup. We want to see your math. So here, as opposed to saying words, I try to say it in big symbols. What's the probability that x equals 36? Given that, that's what this vertical lines mean. Given that not all seats are filled, 0.46 over 0.46, 0.30. That's an acceptable answer right there. That's an acceptable. That's an acceptable. All of these are perfectly fine. So 0.605. So that's a nice little problem. Very real world. Every flight I get on leaving Bangor, Maine seems to be one of these regional jets. And my wife and I have been lucky enough at times to take advantage of an oversold flight and get some money from the airlines, I guess. So let's go look at another pre-response question. This is from the 2003 Form B exam. Again, 2-way table. Looks like I'm trying to see is there some relationship between age and income? I have my thoughts about that, but perhaps there is, perhaps there isn't. Again, these totals are given to us, marginal totals. If those weren't given to us, I think the first thing I do is pull out my calculator and add those up. So simple random sample, that's good. I like the randomness of adults living in a suburb of a large city was selected. Okay, so I'm taking perhaps a small sample of a large city. The age and annual income of each adult in the sample were recorded. All these numbers down here. The resulting data are summarized in the table below. So 2-way table, and very typical question, and we're going to ask a couple 2 or 3 questions based upon that table and those different numbers. Okay, so same problem. Part A, what is the probability that a person chosen at random from this sample will be in the 31 to 45 age category? So 31 to 45 age category, 89 or 207. That's relatively easy for me to do, and for most of my students actually, it can be relatively easy for them to do as well. And unfortunately, sometimes we see an answer like this on the AP exam, and that's all the work that students give us. And traditionally, that has not gotten full credit. Later on, I think next week, Luke did some of that on Friday. I'm going to spend a day on actually how do we grade the AP exams and what are we looking for. We call that a bald answer. We want to see some work. We want to see some sentence. We want to see some communication. And sometimes my students fight me a little bit on this, and they say, "Come on, Mr. Murphy, it's really easy. I can read this number from the table, and I can read that number from the table, and I think that's the right answer. Why can't I get full credit?" Again, we want to see your work, and we want to see that you communicated this well. So I try to write out in a sentence the probability that a person chosen at random from those of the sample will be in the 31 to 45 age category is 89 divided by 270 equals 0.43. In many ways, clearly the same number, right? That hasn't changed. But I've related it to this problem, and I guess I don't know if I've shown any more work, but I clearly communicated my answer better. Feeling that maybe I still needed to show a little bit more work. I did what's the probability that you're in the 31 to 45 age group, 89 over 207. I keep getting that number, and I'm pretty sure that's the correct number. But we don't like these ball answers. This 89 over 207, I'm going to strongly recommend that you don't do that. I think you run the risk of not getting full credit on that problem. Even though it's relatively easy, relatively fast to read those numbers direct from the table, I'm trying to teach my kids to just follow it up with a sentence or work. Give us some supporting work. Give us some numbers. Give us something. Okay, part B, what's the probability that a person chosen at random, so that random is good, from those in the samples whose incomes are over 50,000 will be in the 31 to 45 age category. Show your work. Okay, well there's crystal clear. We wanted you to show work, and so you're not gonna get full credit there if you don't show your work. I like to say to my students, even if we don't say show your work, please show all of your work. I think that really makes sense to do. And sometimes if you make a little math mistake, sometimes we call it a typo. If a reader can look at your math, there's times where you might get partial credit or sometimes even full credit. So we don't want to penalize for small typos. But if there's no work there, then we can't see what you did. So down here I try to write it maybe more formula based. What is the probability that you're in the 31 to 45 age group, given that your income is over 50,000? Well, what sometimes confuses my kids is the way I wrote that feels like it's sort of opposite of the way the question was asked. They said, but Mr. Murphy, the $50,000 was first, so they want to do, what's the probability that you make over 50,000, given that you're in the 31 to 45 age group or something like that. So sometimes students reverse the order, and it's not the order that we presented the information. You're really going to read the language there. Whose incomes are over 50,000. So that feels like that's my condition, over 50,000, right? I think I only want to look at those folks over 50,000. You will be in the 31 to 45 age category. So conditional probability, there's sort of my formula, 35 over 96.364. Again, please show us some work, whether it's in words or math symbols or something. We really don't like it. We don't typically give full credit for what we call ball answers. Based upon your answers, part A and B, is annual income independent of age category for those in the sample explained. So let me do another example before I tackle that. So I want to flip a coin. Here's my coin in my die, right? I think I showed you these earlier, right? I need to get heads or tails. And we'll roll a six-sided number cube. Again, if you see a six-sided number cube, other people call it die or dice. They mean the same thing. I need to get 1, 2, 3, 4, 5, 6. So my students are 100% convinced that these two events are independent of each other. The probability of the second event isn't impacted at all by the first event, vice versa. So they're pretty convinced that those are independent of each other. So there's two options or two outcomes when I flip my coin. I get heads or tails. There's 6 outcomes when I roll my six-sided number cube or die. So there's a total of 12 different outcomes when I flip my coin and roll that die. So I do a little diagram down here. Sometimes I call this probability tree diagram. I get heads in a 1, heads in a 2, heads in a 3, heads in a 4, etc., etc. I get tails in 1, tails 2, tails 3. Those are my 12 outcomes. If I were to list out my 12 outcomes, I would call that my sample space. Heads 1, heads 2, heads 3, etc., etc., etc. So what is the probability that I get a heads given that I got a 6? Well, there's 1 6 here, there's 1 6 here, and so I can get a heads in a 6 or tails in a 6. So what is the probability I get a heads given that I got a 6? Well, I got a 6, I got a 6. What's the probability I get heads? It feels like 1/2. The probability of heads given that I got a 6 is 1/2. What's the probability that I just get heads? So same scenario, but just different question. What's the probability I get heads? Well, that's 1/2. So from a formula point of view, we say P of A given B is equal to P of A. P of A given B, if that's equal to P of A, then those events are independent. Knowing, well, the second event here didn't impact what was happening to A, that's sort of the definition of independence. So I was pretty convinced that flipping this coin and rolling that die, we're independent of each other. So down here I said if probability of heads given a 6 is equal to the probability of heads, then the two events are independent of each other. If they're equal, they're independent, not equal, not independent. So that's kind of what this part C. So going back to that problem that we were working on with annual income and age, it says based upon your answers to part A and B, which feels pretty typical. We've calculated some two probabilities here, and sometimes in part C we want you to tie it all into the problem. Based upon your answers to part A and B, is annual income independent of age category for those in the sample explained. Many times we see kids trying to sort of answer this in words. Yes, they're independent because one doesn't impact the other, or no, they're not independent because one impacts the other. It's impossible to answer part C on the AP Stats exam without some numbers and some backup. So you really can't just answer in words. We need you to take a look at some numbers and tell us what's going on and make a decision. So I said if annual income and age were independent of each other, then the probabilities in part A and the probabilities in part B would be equal to each other. Okay? P of A given B, if that's equal to P of A, then those events are independent of each other. So I went back in part A and said, well, part A was 0.43. Since 0.43 is not equal to the number that I calculated in part B, 0.364, then annual income and age category are not independent for the adults in the sample. So again, this mutually exclusive and independence are harder concepts for my students, I think. I hope I do at least a decent job teaching it to them, but really make sure that you understand those. Maybe go back and watch this again. These are very typical questions that we've asked before on previous AP exams, and again, I have absolutely no idea what will show up on this year's exam, but I'm reasonably confident, no pun intended, that there'll be some probability on one or two, maybe one or both of those 3 responses. Again, I'm totally speculating. I have no idea. Real quick, I don't have a chance to walk through this whole problem, but let's see if we can just start it and then I'll kind of wind down. This is from the 2010 Form B, lots of Form B, I guess. I don't know why that happened. An advertising agency in a large city is conducting a survey of adults to investigate whether there's an association between high level of education achievement and primary source for news. So I don't know where we're going based upon that. I see survey and I saw association, maybe chi-squared, but it's usually just setting the stage. The company takes a random sample of 2,500 adults in the city, so the random's good. That's a reasonably big sample size. I'm happy with both of those things. There's my 2,500 again. The results are shown in the table below, and so now it's sort of maybe feeling a little bit more like probability to me. And again, I'm really trying to see if there's some relationship between the primary news, where you get your news, what source, versus your highest education level. So I think there's going to be a couple of probability questions, and I'll try and wind down quickly. So if an adult is to be selected at random from the sample, what is the probability that the selected adult is a college graduate, or, so that's kind of a key word, and I don't know if I've done much with that, or obtains news from the internet, okay? Well, what is the probability that it is a college graduate? So the 693 college graduates, I wrote that number down, so that felt okay to me. Or obtains news primarily from the internet, so I kind of went across for that row there, and I had 687. But unfortunately, I'm not done here because I guess these 245 people, I can't count them twice. So when I wrote the 693 down, I added up all of those numbers, right? When I wrote the 687 down, I guess I added up those numbers. It feels like I added those 245 people twice. So I took all the people who were college graduates, 693. I took all of those who got their news primarily from the internet, 687. I subtracted the 245. So sometimes I call that double dipping. I counted those twice. I divided that by my total, 2,500, and I got 0.54. And again, I was trying to see if I can come up with a sentence here. So the probability that a selected adult is a college graduate, or, that was kind of the key word, or obtains news from the internet is 0.454. And again, I showed my math and I tried to answer it in full sentence. Part B, if an adult who is a college graduate is to be selected at random, what is the probability that the selected adult obtains news primarily from the internet? So if an adult who is a college graduate is selected at random, the probability that this adult obtains their news primarily from the internet is, well, again, it says if an adult is selected who is a college graduate, lost my breath there for a second. There's my condition, there's 693 who are college graduates. What is the probability that the selected adult obtains the news primarily from the internet? Again, 245. So my final answer is 245 divided by 0.693, 0.354. And then it sort of feels like part C in the last problem that we did. When selecting an adult at random from the sample of 2,500 adults, are the events is a college graduate and obtains news primarily from the internet independent. Okay, so there's that independence again, super important. There are a number of ways to show or prove independence, but I really like the P of A given B. If that's equal to P of A, then my events are independent. If that's not equal, then they're not independent. So I try to do it in words and maybe math symbols variables, I guess. The probability that you obtain your news from the internet, given that you're a college graduate, is 0.354. That's what we did in part B. What's the probability that you obtain the news from the internet? That's 0.275. Well, I guess we hadn't calculated that. So I guess we weren't going to compare just A and B here. We needed to use what we had done in B and maybe add a third number in here. So what's the probability that you obtain your news from the internet? Well, there's 687 folks who obtain their news from the internet out of a total 2,500. So that number is 0.275. I compared those and said these events is a college graduate and obtains news from the internet are not independent. Why? Because 0.275 is not equal to 0.354. So that was kind of a nice little problem. In part A, we had to do something a little different there. I had to subtract out that 245. I didn't want to sort of double dip. Part B felt sort of like we'd done. In part C here, I need to compare the two probabilities to see if those events were independent. But I guess I hadn't calculated that number right there. So I had to go back and calculate that. So let's find out real quick for the day. Back to my PowerPoint here. So hopefully you're feeling more comfortable with solving some different types of probability questions again. Luke's going to do, I think, binomial and geometric tomorrow. He'll be back with me Wednesday on random variables. So we're not done. And we understand that probability can be more difficult for many students. Similar to all problems in AP statistics, you should be able to write a clear, concise solution in context. Super important. And sometimes when I'm going fast, I tend to forget to do that. But I go back and read my answer again. And I want to make sure that there's some context in there. Super important. Here's your homework for tonight from the 1997 multiple choice. I'm kind of an oldie but goodie. I really like this, so I'll let Luke tackle that tomorrow when he starts out. So again, I finish up every one of my sessions because I think it's super important from an equity point of view. We do want all students to take the AP Stats exam this year. We realize this is an interesting year, and almost all of my kids, not all of them, are going to take the exam. And I'm really happy about that. And we're reviewing almost every day. They have a lot of work to do between now and then, and many of them are watching these videos. But they see me every day, so it's not quite as fun as to see me on YouTube. The College Board knows that not all students have access to the internet or a device. College Board is working on solutions to help students get what they need to show their best work. If you need mobile tools or connectivity, or know someone who does, you can reach College Board directly at that link below. Please talk to your teachers, talk to someone in your school. College Board will bend over backwards and really try and help you. So we want you to take the exam. We realize that this is an interesting year, and we don't want any of those issues to be the reason that you don't take this year's exam. So thanks for watching. Happy Patriots Day. I know that doesn't mean much if you don't live in New England, but it's a big day for us in New England. Luke will be with you tomorrow. He'll be doing binomial and geometric. I'll be back on Wednesday for random variables. And the next week is going to be really test-taking strategies and things, how to write good answers, really focusing on this year's exam. So we're trying to finish up the mathy component this week, and then next week will be some strategies for taking the exam. So thanks. Have a great afternoon. Please be safe. Please take care of each other. Be positive, and we'll see you on Wednesday. Thanks.
Hello, AP Statistics students, and welcome to the College Board virtual instruction for AP Statistics. My name is Luke Wilcox. I am an AP Statistics teacher at East Kentwood High School. Quick shout out to my students at East Kentwood. We officially started our online schooling yesterday, and they are now definitely reviewing for the AP exam that we know coming up on May 22nd. So today's lesson, we are going to cover binomial and geometric distribution. So let's just go ahead and get right to it. So a quick check to make sure you're in the right spot. AP Statistics. Hopefully you at this point know who I am, Luke Wilcox, East Kentwood High School. And I'm going to start with a couple of reminders here, which many of you at this point know, but if we have anybody that is new joining us today, I want to make sure that they know where we are and where we are headed in this review. We do meet every day, Monday through Friday at 2 o'clock Eastern Standard Time, where you will be with either myself or my colleague, Mr. Brendan Murphy. Right now, we are in the week of April 20th, and that means that we're covering units 4 and 5 from the College Board CED. If you recall, we have already covered units 6 and 7. You can find those previous videos elsewhere on YouTube. The plan after that next week, we're going to be doing some general review strategies. Mr. Murphy and I are making some big plans for things that we're going to do next week. And we are going to add on one more week, May 4th through the 8th. We're still waiting to get some details, but we do know that week is going to be reserved for students getting a chance to try some practice problems that might look like problems that you'll see on the AP exam for this year. And then, of course, the big day is May 22nd, 2 p.m. Eastern Standard Time for the AP Statistics exam. Now, for this lesson and all previous lessons, if you want to actually download and print out the lesson, you can find that resource at fxmedica.com/YouTube. You'll find a PDF there that you can print out. And then finally, if you or another student that you know is in need of a device or internet access in order to be able to take that AP exam at home on May 22nd, the College Board wants to make sure that you have access to that. So if you go to td.org/tech, they will make sure that you have what you need to take the exam. I do know that the College Board is extremely committed to making sure that all students have access to taking the AP exam on May 22nd. Okay, next up, we're going to check in on the homework problem that Mr. Murphy gave you yesterday. You went over some probability concepts yesterday, and sure enough, the homework problem is a classic probability question. So let's take a look and see how you did on it. So here's what it said. Joe and Matthew plan to visit a bookstore. Based on their previous visits to this bookstore, the probability distributions of the number of books they will buy are given below. So it looks to me like this first distribution is the distribution of number of books for Joe, and the second distribution is the number of books for Matthew. And it looks like they're either going to buy 0 or 1 or 2 books total. So here's what the question says. Assuming that Joe and Matthew make their decisions independently, what is the probability that they will purchase no books on this visit to the bookstore? Okay, let's think about it. If they purchase no books on this visit to the bookstore, that means that Joe is buying no books and Matthew is buying no books. So if I were to use some probability notation here, I would say it's the probability that Joe is going to be purchasing no book and that Matthew is purchasing no book. Now we are told here that those decisions are made independently, which means that for an and problem like this, we are allowed to just simply multiply probability. So if you look at Joe's distribution, there's about a 50% chance that he would buy no books, and for Matthew, 25%. We want both of those things to happen, the first one and the second one, and because they're independent, we can just simply multiply those two together. 0.50 times 0.25, and that'll give us an answer of 0.125, which if we look at our answer choices, sure enough, answer choice B is the correct answer there. So hopefully you did okay on that homework problem from yesterday, and I think we are ready to jump into our new learning for today. And as usual, I'm going to start out with some very clear expectations for what we're going to accomplish today. And today we have only 2 learning targets. All right, so here's what they say. The first one says describe a binomial distribution and be able to perform probability calculation for binomial distribution. And then the second learning target is just a parallel learning target. It looks almost the same as the first one, but now we're talking about geometric distributions. And once again, we need to be able to do probability calculation. So we're still under the general umbrella of probability, much of the stuff that you talked about yesterday with Mr. Murphy, but very specifically today we're going to be talking about the binomial distribution and the geometric. And I will make sure that at the end of the lesson today we come back to these 2 learning targets to make sure that we have what we need. So let's jump right in. So here's the question to be answered for today, which I think is one that you can relate to. The question is, how many AP Stat students are you 2? And what I'm wondering is how many of you AP Stat students out there in the country are actually using these videos as part of your AP exam review in order to prepare for the AP exam on May 22nd. So here's what it says. It says, according to YouTube Analytics, 30% of all AP Statistics students are using YouTube as part of their AP exam review. Okay, now this number right here, 30%, is a proportion rather than a mean, and it is a proportion that is claimed to be made for the population of all AP Stat students. So if we're being careful about our notation here, we know that it's a proportion, and we know that it's a population proportion, so we should be using P here rather than P hat, and we're going to say that our P is 0.30. Now let's continue reading here. To investigate this claim, the College Board is going to take a random sample of 80 AP Statistics. Okay, let me pause right there. 80 is our sample size, so typically we will use lowercase n for our sample size. We're going to have, a sample of 80 AP Statistics students, and then use a survey to count the number, this is important, the number that are using YouTube as part of their review. So let X equal the number of students in the survey that are using YouTube as part of their review. So the College Board is going to reach out to 80 students, get their survey results, and count up the number out of those 80 students, how many of them are using these YouTube videos as part of their exam review. So question number 1 says that show that X is a binomial random variable. Well, if you want to show that something is a binomial random variable, there are 4 conditions that must be met. So let's list out the 4 conditions, and then we'll go through and check each one of them individually. So the first condition is what we're going to call the binary condition. And binary means that each trial can either be categorized as a success or a failure. And when I say trial here, I mean each individual AP Stat student that's part of the sample. And sure enough, we can categorize them as a success if they're watching YouTube, a failure if they're not. So we're going to say here that each trial is a success, and we're going to make it clear that a success here means that the student is using YouTube, or a failure, no YouTube. So we would say that that condition is satisfied. The second condition is what's known as the independent condition. Now what we want to know here is that the result from one student is independent from the result of the next student. So we're going to say here each trial is independent. Now there's a couple of things that we need to consider in terms of independent. The first of which is that we do have a random sample here, which is going to ensure that the results of one student are not going to impact what the next student might say, because it's just a random sample of 80 stat students from around the country. So that's good. The random sample ensures are independent. But there is one other thing that we need to consider when it comes to independent, and it's the fact that here we are sampling without replacement. In other words, once a student has been selected as part of the sample, they're not put back into the pool to be selected again. They can only be selected once. And so we know that when we take a person out, that is going to change the probability that the next person would be a YouTuber by just a tiny amount, right? And the amount is small because this sample size that we have, 80, is very, very small relative to the whole population of over 200,000 80 stat students. So we actually need to check something here that is called the 10% condition. And this is true anytime you're sampling without replacement, we want to check the 10% condition, which just says that the sample size is less than 10%, which I'm going to write as 1/10, the population size. And in this particular case, 80 is our sample size, and the population here is all 80 stat students, and there are well over 200,000 80 stat students. So I would definitely say that the sample is less than 10% of the population, and therefore we're going to say that the independent condition is satisfied. Next up, condition number 3, we're going to call it number, but then I'm going to finish the statement in here and say that the number of trials is fixed. So the number of trials here is the sample size, right? We have 80 students, which represent the 80 trials, and so we do know that that number is fixed because we are taking a sample size 80. So we would definitely say that that condition is satisfied. And then finally, condition number 4, which is known as the same probability condition, says that the same probability of success on each trial. And actually, we know according to YouTube analytics, 30% of 80 stat students are using YouTube. So that probability of success is 30% for each student. And so we would definitely say that the fourth condition is satisfied there. And sure enough, we have a binomial random variable. So let's move to question number 2, which says, what is the shape of the distribution of x? Well, very often with a binomial distribution, you're going to have one value that has the highest probability, and then as you move farther away from it, the probabilities get less and less. And sometimes the shape of that distribution is going to be approximately normal. And the way that we can check that is using what's called the large counts condition. So let's go ahead and check the large counts condition here to see if that's satisfied. And the large counts condition says that n times p is greater than or equal to 10, and that n times 1 minus p is greater than or equal to 10. Let's plug in some numbers here. N times p is just going to be 80 times 0.30, and that's going to give me 24. And sure enough, 24 is greater than or equal to 10, so we're good there. Now let's check n times 1 minus p, which is going to be 80 times, and 1 minus 0.30 is going to be 0.70. And for this one, we're going to get 56. And sure enough, that's greater than or equal to 10. And if we just think for a second here what these numbers represent, 24 is really the number of successes that we expect to get, right? 80 trials, 30% of them should be successes. That would be 24 successes. And this number over here, 56, represents the expected number of failures. So if the expected number of successes and the expected number of failures is greater than or equal to 10, then the large counts condition is satisfied. And what we can say then is that the distribution of x is approximately normal. So we have now the shape of our distribution. Okay, next we're going to move into the mean and the standard deviation of a binomial random variable. And I'm going to give a little bit of a hint here on the formula sheet, which you will be allowed access to on the AP exam. There is a section of the formula sheet that you can see right here, shows you everything that you need to know for a binomial distribution, including the formula for the mean of a binomial distribution and the formula for the standard deviation of a binomial distribution. So let's go ahead and record that in our activity here. The mean from our formula sheet of a binomial is n times p, and the standard deviation is the square root of n times p times 1 minus p. And so now it's just a matter of plugging in some values and seeing what we get. So let's start with the mean, which is n times p, and we know n is 80 and p is 0.30. In fact, we already talked about this value, right? 24 is the expected number of successes. So if the College Board were to take random samples of 80 over and over and over and over again, then on average they would find 24 students that are YouTubers. Now to the standard deviation, according to our formula here, we need the square root of, and then we need n, which is 80, times p, which is 0.30, times 1 minus p, which is 0.70, and then we take the square root of that whole thing. And I've already put that in my calculator. I got an answer of 4.1. So what that standard deviation is telling us is that if the College Board was to repeatedly take samples of size 80, then the number of students that are YouTubers is typically going to be about 4.1 away from the mean of 24. So it seems reasonable that we would get values a little bit bigger than 24, a little bit less than 24, right? They typically vary from that value by 4.1. All right, now let's move on to number 4. We're going to do our first probability calculation here. It says find the probability that the sample has exactly 32 students who use YouTube. Well, once again, I'm going to take you back to this formula sheet here because it has something that's very useful to us, and that's the probability of getting a certain number of successes. So we need this big crazy formula that you see right here. So let's go ahead and copy that formula to start back in our activity page here. So I'm going to put this on the margin. The probability that we get x successes, right, out of our n trial equals. Now the first thing that you see there on the formula sheet is this n over x with the parentheses around it. Now, some of you may know that as n choose x, right? That's a combination, or you can use the calculator to help us find that. And then let's finish the rest of the formula here. The probability of success raised to the number of successes times the probability of failure raised to the number of failures. So even though it looks kind of crazy, that formula, once you plug the numbers in, it seems to make quite a lot of sense. So let's see what it looks like for this particular problem where we're trying to find the probability of 32 successes. So here's what it would say. The probability that x is equal to 32 successes. Well, according to the formula, we need to do this combination first, which is really just going to tell us how many different ways are there of getting 32 successes out of 80 trials, times the probability of success raised to the number of successes, which is 32, times the probability of failure raised to the number of failures. Well, 32 successes means we're going to have 48 failures in order to add up to 80 there. Now, this is something you would definitely need your calculator to help you with. So let's just go ahead and jump over to the calculator now. If you have yours available, you can grab your calculator. If you don't, just follow along with what I'm going to show you here. We're just going to take that whole formula there and plug it into the calculator. So the first thing we need is the combination. So you're going to find that over here if you hit math, and then you go over to probability, and it should be the third one down there where you see n choose r. And for us, n, there are 80 trials total, and we want 32 successes. So you're going to do 80 choose 32. And then we want to multiply that by the probability of success, which is 0.3, raised to the number of successes, which is 32, times the probability of failure, which is 0.7, raised to the number of failures, which we know is 48. And we have our final answer here, which looks like it's about, let's say, 0.015 would be the value that we're getting here. Now, I'm going to show you a little bit of a calculator shortcut here, another function that you can use in order to find the same value. So here's where you're going to find it. If you go to second bars, which is your distributions menu, and you scroll down a little bit, you're going to find a couple of commands here that include binomial. And I'm going to tell you we want the first one, which is a binomial PDF for probability distribution function. And I'll explain why in just a minute. But we're going to use binomial PDF. Now, the calculator is going to ask us for a couple of things. We know that the number of trials is 80. We know that the probability of success is 0.3. And the x value, which is the number of successes that we're looking for, is 32. Go ahead and paste that onto the main screen. And sure enough, we get exactly the same answer as if we had used that big, long, crazy formula. So we know for sure that 0.015 is the correct answer on it. So let's jump back to the activity and fill in our answer for that. And then I'm going to give you a little bit of an AP exam tip if you want to use that calculator function as part of your work. So in the activity, let's record our final answer here, which we got 0.015 was the answer from the calculator. And then I'm also going to record the other way that we did it on the calculator, which was using this function called binomial PDF. Now, if you're going to use this on the AP exam, you have to be very clear on what each one of the values represents that you typed into the calculator. So that first thing the calculator asked for was the number of trials. So I'm going to clearly indicate here that we typed in the number of trials n is 80. And then it asked for the probability of success, which I'm going to write in as p equals 0.30. And then it asked for the number of successes, which for this particular problem is 32. And sure enough, the calculator reported the same value as if we had used the formula. So your AP exam tip here is if you're going to use this calculator command as part of your work, make sure that you're identifying each one of those parameters inside the parentheses. Okay, we are ready for number 5, which says find the probability that the sample has at least 32 students. Okay, which is not the same as the previous question, which asked for the probability of exactly 32 students. Now I want at least 32. So if I were to write a probability statement here, what I'm looking for is the probability that x is greater than or equal to 32, right? At least 32. And if you think about that, at least 32, well, that means that it could be 32 or 33 or 34 or 35. So I'm going to write that out here. here by saying that this is just the probability that x equals 32 plus the probability that x equals 33 plus 34, 35, 36, 37, all the way up to the highest possible value that x could be was that all 80 students were YouTubers. So the final term here would be the probability that x is equal to 80. Now we could go through and calculate each one of these probabilities. In fact, we've already done this one above, right? We know the probability of exactly 32. But then we would also need 33 and 34 and 35. And you can quickly realize that we are not going to do this by hand. We need some technology help here from the calculator. In order to use the calculator, we have to turn this into a statement that uses less than or equal to, because that is the command on the calculator. Binomial CDF gives you less than or equal to. Well, it's pretty easy to flip this one around, right? If I want 32 or higher, the values I don't want are 31 or below. So I can use the complement rule here and say 1 minus the probability that x is less than or equal to 31. And that should give me the right answer. Now that x is less than or equal to 31 is where we're going to use the calculator function. So let me just set this up for you, and then we'll jump to the calculator to see what the answer is. We're going to do 1 minus, but this time we're going to use binomial CDF for cumulative distribution because of the cumulative probability all the way up to and including 31. And remember, we would have to indicate our values here. So n equals 80, p equals 0.30, and x equals 31. And well, let's go to the calculator and see what the calculator would give us for this one using the binomial CDF. So I'm going to do 1 minus, and then remember it's second vars, that's your distribution. And also remember that this time we want binomial CDF rather than PDF. Still got 80 trials, probability of success is still 0.3, and the x value this time we want 31 and below. And we're going to subtract that from 1, and we're going to get an answer here of 0.036. 0.036 is our answer here. So let's jump back into the activity and fill in our answer there. And then we got one last question to fill out for this binomial distribution. So our final answer here is 0.036. All right, on to the last question here. Number 6 says College Board selected a random sample of 80 stat students and found that 32 of them were using YouTube. Okay, let's just pause for a second here and think about this. They took their sample of 80, they got 32. Well, how much were we expecting them to get? If I look back up here at my expected value or my mean, we expected them to get 24. So 32 seems a little bit high, which maybe gives us some evidence that the true value might be higher than 30% for the whole population. In fact, let's just think about what that percent is based on the sample. The sample was 32 out of 80, and sure enough, that's actually 40%. Based on their sample, they're saying that they think 40% of the population is using YouTube. So here's the question to answer now. It says, does this result provide convincing evidence that more than 30% of AP Stat students are using YouTube? Now, hopefully you're familiar with this language of convincing evidence, and I hope that it makes you think about inference, and specifically a significance test. And in order to come to a conclusion in a significance test, we need a p-value or probability, and specifically we need the probability of getting that result or more extreme, assuming some claim is true. Well, assuming that the original claim was true, 30%, this outcome of 32 or greater is not very likely. In fact, that's what we calculated in number 5. That only happens 3% of the time, 3.6% of the time purely by chance. So let me write that out in words here. Okay, what I'm trying to do is to interpret this probability that we calculated in number 5. So here goes. Assuming the 30% claim is true, there is a 0.036 probability of getting 32 or more YouTubers in a sample of 80 purely by chance. Now, I will tell you what, that sounds very, very familiar to me. And if you've been all the way through the course, hopefully you clearly see that this, people, is the holy grail of AP statistics. It is the interpretation of p-value, which is the thing that allows us to make a conclusion at the end of the significance test. And here, the probability or the p-value is very small, less than 5%, right? Which means we do have some convincing evidence here. We don't think this happened purely by chance. So my final conclusion here is going to look similar to a conclusion that you might write for a significance test. I'm going to say because my p-value is less than my alpha level of 0.05, we do have convincing evidence that more than 30% of AP Stat students are using YouTube. All right, so that wraps up the big idea of a binomial random variable. And remember, the second learning target we have is to investigate this idea of a geometric random variable. So let's slide over to page 2 of the activity here. I got a little bit of a setup here. It says, based on the College Board sample, 40% of AP statistics students are using YouTube as part of their AP exams review. Assume now that this claim is true. Okay, so no longer are we going with the first claim that was made of 30%. We are now saying that we think that the true population proportion of AP Stat students that are using YouTube is now 40%. And the setup here is going to be a little bit different. It says, Mr. Wilcox decides to try and find one student who is using YouTube as part of their AP exam review. He will randomly select AP statistics students one at a time until he finds a YouTuber. So another way of saying this is I'm going to keep taking trial after trial until I get my first success, where the success is defined as the person being a YouTuber. And here's the random variable. Y represents the number of students it takes to find a YouTuber. Now, right away, I want you to recognize that this is not a binomial random variable. And the reason is because for a binomial random variable, you have to have a fixed number of trials. And in this case, we don't know how many trials. I might find my first YouTuber on the first try, or the second try, or the 18th try, but we do not have a fixed number of trials here. So this is what's called a geometric random variable. And sure enough, to check that we have a geometric random variable, there are 4 conditions, which look almost the same as the 4 conditions for a binomial random variable. So let's list them out here. 4 conditions, and 3 out of the 4 are exactly the same as they are for binomial distribution. So that first one, the binary condition, where each trial is a success or failure, same condition. Second condition, independent, where we knew this was satisfied because we had a random sample, and also the 10% condition was satisfied. That's the same. And then number 4, the same probability of success for each trial. That's exactly the same as it is for a binomial. So the condition that's different is condition number 3, which I'm going to write as the trials condition. And what it says is that the thing we're measuring here, the variable, is the number of trials until a success. So we do not have a fixed number of trials here. We are looking for the number of trials until we get that first success. And so this right here is the condition that makes a geometric random variable different than a binomial random variable. Okay, so I'm going to go through actually the same set of questions that we did for binomial, but now for geometric. Number 8 says, what is the shape of the distribution? We're going to need to do a little bit of work to think about this one. So here's what I'm going to have us think about first. Let's first think about the probability that y is equal to 1. Now realize y can't be equal to 0, right? If we need the number of trials until we get the first success, if the first trial is a success, then our y value is equal to 1. Okay, so what's the probability of that happening? Well, we have to have a success on the first trial, and we know that happens 40% of the time. So that's easy enough. Now, if we think about y being equal to 2 people in order to get our first success, well, that means that the first person was a failure and the second person was a success, and they're independent. So we can just multiply probability. So we have a failure for the first and a success for the second. And if you put that in your calculator, you're going to get 0.24. Now let's just do one more of these, thinking about the probability that it takes 3 people to get our first success. Well, then we're going to have a failure and then a failure and then a success. So it would be 0.60 times 0.60 times 0.40. And sure enough, that's going to be 0.144. Now, what I hope you're noticing here as we move from one to the next is that our probabilities are decreasing. And the reason is because each time we move down one, we're adding one more failure at the front end, which has a probability of 0.6. So if we're multiplying by 0.6 every time, we're getting a smaller and smaller probability. This is also why it's called a geometric distribution, is because those probabilities have a common ratio, which is the probability of failure. Now, let's think about the distribution of y. If we were to graph it, 1, y equals 1, y equals 2, and y equals 3. Well, 1 would have the highest bar, right? The probability is represented on this axis here. And then 2 would be less than that, actually 60% of the previous bar. And then 60% of the previous bar. And you can just imagine what the rest of this distribution is going to look like. So now very clearly, I can identify the shape of the distribution as skewed to the right. Okay, next up, we are looking for the mean and the standard deviation of y. And our formula sheet here is going to give us some help again on this one. Right below binomial distribution, we have formulas for a geometric distribution. So here's your formula for the mean. And then quick note here, this formula for standard deviation is brand new to the formula sheet for 2020. This was not on previous versions of the formula sheet. It is not part of the formula sheet, and we are responsible for it. So let's write those formulas out in the margin here. The mean of a geometric random variable is just 1 over p. And the standard deviation, according to the formula sheet, is the square root of 1 minus p all divided by p. So now we just have to plug some numbers into this one, right? The mean is going to be 1 over 0.4, and that's going to give me 2.5, which is telling me if we were to do this over and over again, we can expect about 2.5 trials in order to get the first success. And the standard deviation, square root of 1 minus 0.40 all divided by p. So this one is going to give us 1.94. So the number of trials until the first success is typically going to vary by about 1.94 away from the mean of 2.5. Okay, up next, find the probability that it takes exactly 5 students to find the first YouTuber. Well, once again, our formula sheet here actually has the formula, although I think we were just about to arrive at this formula in the activity. But let's go ahead and record it. The probability of getting X trials until the first success is 1 minus B, which by the way is the probability of failure, raised to the X minus 1. That's actually how many failures. And then it's going to be followed by 1 success. So for this particular problem, we can very easily find the probability that it takes exactly 5 students to find our first YouTuber. So that means that the first 4 students were failures. So I take the probability of failure raised to the 4, and then the final student number 5 was a success. So we multiply by P at the end there, and this is going to give me 0.052. All right, moving on to number 11, the probability that it takes now at most 5 students, which is different than exactly 5 students. So now I'm looking for the probability that Y is less than or equal to 5. Well, I could just find 5 and 4 and 3 and 2 and 1 and add them all together. But once again, just like for binomial, there is a calculator function which can help us here, which is called geomet CDF. And the arguments that you need to know for the calculator here, you have to tell it the probability of success, 0.40, and you have to tell it the number of trials there, which would be 5. And let's go ahead and see what the calculator is going to give us here. So it's found in the same menu. If you go to second bars, there's your distribution. You have to scroll down a little bit further past the binomial ones until you can find geometric. And once again, you have PDF if you're trying to find exactly one value, or CDF if you're trying to find cumulative up to and including one value. And we want CDF here. And our P is 0.4, and we want 5 trials. So the calculator will tell us that we have an answer of 0.922. So let's jump back into the activity and record that. And then we have one final question to answer based on that answer. So our final answer from the calculator here was 0.922. And our final question here says, suppose that it takes Mr. Wilcox 6 students to find the first YouTuber. Does this result provide convincing evidence that less than 40% of AP Stat students are using YouTube? So we see this language of convincing evidence, which I hope makes you think inference and significance test, and maybe even p-value. So we need to know how likely is it that this would happen or more extreme, assuming that the claim is true. Well, let's just pause right here. That value or more extreme, we are looking for the probability that it would take 6 or more students to find YouTube. Well, we know from question number 11, the probability of getting less than or equal to 5. This is just complement of that. So I just want to do 1 minus probability that Y is less than or equal to 5, which we just calculated as 0.922. And so now I'm getting my p-value here of 0.078. So let's start with an interpretation of that. All right. So we're going to say, assuming the 40% claim is true, there is a 0.078 probability it would take 6 or more students to find a YouTuber purely by chance. Now this p-value is greater than our alpha level of 5%, which means that we think that this result could have happened purely by chance, assuming that the 40% claim is true. So that's going to change our final conclusion here. Our conclusion now is going to say, because our p-value is greater than 5%, we do not have convincing evidence that less than 40% of AP Stat students are using YouTube. All right. So that takes care of the activity. I'd like to check back in now with those learning targets that we started the lesson with and make sure we got everything that we needed to. So any important ideas here, I'm literally just going to cut this right in half, and we're going to have one half over here addressing learning target number 1, which was about the binomial random variable, and then this one over here on the right, we're going to take care of learning target number 2, which is about the geometric random variable. So starting with binomial, I'd like to first record the 4 conditions necessary for a binomial, and remember that's binary and independent and number, so that the number of trials is fixed, and then same probability of success for each trial. Now, quick little acronym here. Some students will use bins to help them remember the 4 conditions needed for a binomial. Now, the one thing I want to add in here is that if you are sampling without replacement, then we need to check the 10% condition to say that the independence is okay. So 10% condition when sampling without replacement. Okay, now to describe a binomial distribution, I'm just going to handle this by going shape, center, and spread. And we decided that the shape is hopefully approximately normal, but we do have to check the large counts condition in order to be convinced that that's true. So just as a reminder, the large counts condition says that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Okay, for the center of the distribution, I'm just going to write out the formula for the mean for a binomial, which we can get from the formula sheet, and then the formula for the standard deviation, which we can get from the formula sheet for n times p times 1 minus p. And then finally, the last thing I want to record here is how to calculate the probability of getting exactly x successes out of n trials, which comes from our formula sheet. N choose x times the probability of success raised to the x times the probability of failure raised to the n minus x. Okay, let's see if we can do the same thing over here on the right for the geometric distribution, starting with our 4 conditions, which are almost exactly the same. We got binary, we got independent. The third one is the one that's different because there are no longer a fixed number of trials. We care about the number of trials until the first set, and then the fourth one is the same probability of success for each trial. And sure enough, there's an acronym here that might help you remember the 4 conditions for geometric random variable, which is BIDI. And I just want to note here that we do still have to check the 10% condition if we are sampling without replacement. Okay, once again, let's describe the distribution by talking about the shape, the center, and the spread. The shape we decided for a geometric random variable is skewed right and will always be skewed right. The mean and the standard deviation here, the mean is given on the formula sheet. It is 1 over p. Standard deviation is also given on the formula sheet, square root of 1 minus p, all divided by p. And the last thing I want to include here is how to calculate probabilities for a geometric distribution. So the probability takes exactly x trials to get our first success. Well, we have a bunch of failures to start. Probability of failure raised to the number of failure, which is x-1, followed by a success at the end. All right, so your homework problem is here is a sample multiple choice question, which you can try at home, and then Mr. Murphy will go over that with you tomorrow. I certainly hope that you got something out of today's lesson. If it was helpful to you, make sure that you give me a thumbs up in YouTube. You'll be with Mr. Murphy tomorrow, and I will be back on Thursday. So I just want you to know that leaving today's lesson, I am 40 years old. And when I return back to you on Thursday, I will be 41 years old. So I got a birthday tomorrow. I'm going to try and enjoy it, and I'm looking forward to seeing you all back here on Thursday. Have a good night. AP Stats kids, Wednesday, April 22nd. Thanks for coming back. Hope you have a good day. Today's day 3 of probability. I did probability on Monday. I don't want to say basic probability, but you know, some more general terms. We did conditional probability from two-way table, those types of things. Mutually exclusive versus independence. I think we talked about. Luke did binomial and geometric yesterday, which is always kind of fun. I actually still like those two. And today I'm going to do what we call random variables. So we're going to wind up with probability today. Again, 3 full days of probability, which hopefully helps. It was a topic that students in a survey, we all consultants had training last year. It was a topic that the students struggled with. So Luke and I really want to do a good job with that. I think tomorrow Luke has sample distributions and central limit theorem, super important for statistical inference. Really sets the stage. Friday is I think response to FRQ Friday. So Luke's going to do Thursday and Friday. And the next week we're going to shift towards sort of reviewing for the exam and how you should calculate efficiently and formula sheet and all that good stuff. So let's dive right in for today. We'll look at the homework. Again, my name's Brandon Murphy. I teach at John Baptist Memorial High School in Bangor, Maine. Cold up here today. We had a dustin, as we would say. It's kind of a New England saying. I think a dustin of snow means when you wake up, there's just a really thin film of white on your cars and grass, and it's already since melted. But it's kind of cold up here. Still feels winterish, unfortunately. Luke, he teaches at East Kentward High School in Michigan, and he and I were talking today, so he and I are good friends. So this was the homework from last night. This was the problem that Luke left with you. So a popular computer card game keeps track of the number of games played and the number of games won on that computer. Okay? Again, I just call this setting the stage. It feels like you either win the card game or you don't win. You win or lose. The cards are shuffled before each game, so the outcome of the game is independent from one game to the next and is based upon the skill of the player. Okay, that makes sense. I like that independent word. The X represent the number of games that have been won out of 100. So we're playing just 100 games or a total of 100. That's a finite number. So I'm leaning towards binomial here, but let's keep reading. Under which of the following situations would X be a binomial random variable? Okay, so we're in a binomial setting here. Again, here's the same problem. So before I actually started to work on the problem, I just made some real quick notes down here to myself. When I think of a binomial setting or binomial probability, I think of four things that I need. And I know Luke talked about this yesterday. We have 2 outcomes: a success and a failure, win, loss, in, out type of deal. We have independent trials. Well, we did see that word up here somewhere, so that was good. So it feels like we met that condition. The number of trials is finite, meaning fixed, or we can count them. It stops. Determined in advance. Well, I think we had that, right? Didn't say we're going to play 100 games. So that feels good. It feels like I've met those 2. I guess I have met the first one as well, right? We either win or lose the game. It didn't actually
say lose, but it feels like we win or lose. And so I kind of focused in on this fourth one here, the same probability of success for each trial. So that's sort of what I was looking at before I did the problem. So A, all games were played by the same player whose skill improved over the course of the 100 games. Well, if your skill is improving, that feels like your probability of success is changing. So I don't think it was that one. A group of 5 players of different skill levels. I think I honestly stopped right there and said, well, different skill levels, that means different probability. It's not going to be that. A group of players of different skill levels. Again, that was sort of my little clue there. So I think I crossed that one out. 2 players of equal skill each played 1 game a day for 50 days, and their skill level did not change from day to day. So I sort of like that one. But to be honest with you, I said, well, 2 and 50, is that going to be the same as one person playing 100? So I want to keep reading. D felt pretty good to me, but I did want to just sort of keep reading and see what he told me. So 2 players of different skill levels competed, and so I actually did cross that one out. And so the answer is D here. I actually really like this. Luke and I sometimes talk about the problems we're going to pick, and sometimes we don't. We just surprise each other with what the homework is for the next day, and I have to sit down and do it. I really like that. I can't remember, or probably in my textbook where we said 100 games where we had 2 people. So that felt really cool to me. It was a little different, and so I really like that. Well, you guys really like it as well too. I think about it, and it was a good little problem. So anyway, that was from Luke's session yesterday. So again, this is just some websites. I think this is a typical slide of mine. Anything, all updates on your exam are here. You can find the schedule for what we're doing. There's more information coming, so stay tuned. And I do think at some point we're gonna have like a practice that is how you can upload, some more details as to how you can upload your answers. So stay tuned for that. College Board's working probably 24/7 to try and get this ready in a short period of time. More good stuff coming. Stay tuned. How's that? So today we're going to talk about random variables. And so the value of a random variable, the values of a random variable, are the numerical outcomes of random behavior. Okay, makes sense. A discrete random variables. So discrete just means that there's a finite number of outcomes. I can count them, et cetera, as opposed to infinite. So we do a lot of discrete random variables in this class. So a discrete random variable is a variable that can only take a countable number of values. We know how many there are. Each value has a probability associated with that, so I can calculate the probability of that. And we talked about this, I think, on Monday when we talked about the sample space. The sum of the probabilities over all of the possible values must be 1. Super important, and I'm going to use that when I actually start to do some problems later this afternoon. I want to make sure that all of my outcomes add up to 1, and that sometimes helps me solve problems. So, I like to think of a random variable in its super simplest terms is a random event where I perhaps know what the outcomes could be, but I just don't know what's coming next, and that's the random behavior. So if I flip a coin, I realize I'm going to get heads or tails. I just don't know what the next outcome is going to be. If I roll a 6-sided number cube, a dice or die, I know I can get a 1, 2, 3, 4, 5, or 6. I just don't know what's coming next. I can quantify each one of those outcomes and put associated probability. So I would define those as random variables. We're going to talk about adding means and standard deviations and whatnot. And so for 2 independent variables, x and y, we can add the variances. We cannot add the standard deviations. That's a little tricky. My students will sometimes struggle with that. And I think I have 2 multiple choice that try and get right to that topic. So I can add and subtract means. That's logical. I can add variances, assuming my events are independent. I cannot add my standard deviations. And so I have a couple problems that we'll hopefully get to that. And that's a little bit at times difficult for my students. Listen, only but goodie. This is from the 1997 exam. I actually the Acorn book, and actually sometimes give this to my students before we've talked about random variables. I just sometimes like to give them a problem and see what they can do with it. How's that? And so this one is oldie but goodie. I really like this. And that being said, my students don't like this. They don't like this nomenclature here at the top. X and probability that big X equals little x, y, probability of big Y equals Y. They don't like the nomenclature at all. And so sometimes this is, what I might call like, a good classroom problem where we do it together. But when I give this to them and give them 5 minutes to do this, they typically do not like this at all. So give me just a second here. Okay, so there's the same problem here. Sorry, there's like a little green outline on my screen. I don't know if you saw that. So here's the same problem. So we have some tables up here. X, probability of X equals little x, probability of Y equals little y. I'll demystify that. The tables above show product of the probability distribution for random variables X and Y. So the big X and the big Y, those are my 2 different random variables. That's all I have. If X and Y are independent, super important, and I'm probably going to underline that. And the joint probability that big X equals 3 and big Y equals 4 equals 1/16, and the probability that big random variable Y is equal to 1 is equal to, and honestly, my students struggle with this. So big X, that's one of my random variables. Big Y is my other random variable. And over here on the side, I've just tried to demystify. The probability that big random variable X is equal to 1 is 1/6. That's what that line's trying to tell me. The probability that big random variable X is equal to 2 is 4/6. I think I just made 2/3 4/6. The probability that big random variable X is equal to 3 is, I don't know. Well, you can see that the little sigma equals 1, meaning if I add up my 3 outcomes, my only 3 outcomes, I have to get 1, right? We talked about that a little earlier. So that was 1/6. So this first question mark over here is 1/6. I think if these numbers were all the same, which they're not, that's a good thing. I think it's real easy for students to say 1/4, 1/4, 1/4, 1/4. That doesn't have to be true, but the probability of each one of these outcomes in a random variable does not have to be the same. And that's why I like X so much over here is those 3 probabilities are not all the same. So I set up a little equation here and I said the probability that big random variable X is 3 times the probability that big random variable Y is 4 is equal to 1/16. I was given that, so I was told that. Well, the probability that big random variable X is 3, that's 1/6. So I felt comfortable with that. Feels like I'm kind of solving for this. So 1/6 times this number here is 1/16. I think I just multiply both sides by 6. Multiply both sides by 6. I get 6/16 is the probability that big random variable Y was a 4. So I'll just go and fill that up in here. So 6/16. And again, I do know that if I add these 4 numbers here, I would get 1. I know that the sum of my discrete outcomes is always going to be 1. So I think I just made that 4/16, 4/16. So this number plus 4/16 plus 4/16 plus 6/16 has to be 16/16 or 1. So when I was sitting down, I did the math. I said, well, the probability that big random variable Y was equal to 1 is 2/16 or 1/8. So my answer was A. I just love this problem. It really helps my kids sort of feel comfortable with this nomenclature. My students, what this nomenclature is, they don't like it at first. And if I can demystify it, then they feel much better. So here's a multiple choice problem, actually from the same booklet. So this is another oldie but goodie. And my students will get mad at me on this one. So we've talked about at this point in the course adding means. Can we subtract means? Can we add standard deviations? The answer is no. We can add variances, assuming my events are independent. So I usually give them this problem the next day. And unfortunately, many of them get it wrong and they get really, really mad at me. And we'll talk about it and then they'll sort of maybe reluctantly agree that, yeah, you're right, Mr. Murphy, we should have known better. So for college-bound high school students in 1996, the nationwide mean SAT verbal score was 505. So the average standard deviation of about 110. And the SAT math score was 508 with a standard deviation of about 110. The math score over the last 20 years, that average has actually creeped up a little bit, which is actually fantastic. I think it's around 510 or 511. Please don't quote me on that, but it's gone up a little bit. It may not seem like 3 or 4 points is that much, but when millions of students take an exam, to get any increase at all, it is actually fantastic. So we've been doing a good job getting that math average SAT score up a little bit. English, I don't know as much about, so I'll leave that up to my colleagues who teach English. But so the average verbal score in English was 505, and the average math score was 508. So that's good. Students who do well on the verbal portion of the SAT tend to do well on the mathematics portion. Super important sentence. Unfortunately, sometimes my students sort of overlook that, but we'll come back to that. If the two scores for each student are added, the mean of the combined scores is 1,013. And so that's just adding this 505 and the 508. So I can add means. What is the standard deviation of the combined verbal and math scores? Well, I can't add standard deviations, but I can add variances. And just if I square a standard deviation, I get a variance. If I take the square root of a variance, I get a standard deviation. And so almost to a student, they want to circle C, and they'll say, well, Mr. Murphy, we have a standard deviation, so I squared that. Well, now it's a variance. Yep, that's a true statement. We have another standard deviation, Mr. Murphy. We squared it. Yep, so we can add the variances, and they like C. Unfortunately, that's not the correct answer. The answer is E. And again, they sometimes get a little vocal with Mr. Murphy and say, Mr. Murphy, we just covered that. You told us yesterday that you cannot add standard deviations, but you can add variances. Yep, that's a true statement. Assuming my events are independent. And I always stress that. I really stress that. Well, if we go back to that sentence, students who do well on the verbal portion of the SAT tend to do well on the mathematics portion. I think that sentence right there is basically saying that those two events are not independent. And so that's why the answer is E. And super important. So before we can add variances with random variables, we need to make sure that my events are independent. And so they sort of reluctantly say, yeah, you're right, Mr. Murphy. We did talk about that. And almost inevitably one student will say so. So every sentence is important. And I like that. I think that's a real important point to make. That sentence was there strategically. It's there for a reason. And read each sentence and say, is there important information here, or is it just setting the stage or what? So super important sentence. And that's what led me to E. How's that? So another great problem that I really like. So this is from the 2007 exam, and this starts out and says random variable X is normally distributed with a mean of 10 and standard deviation of 3. So I'll just underline those. Random variable Y, again, many times our random variables are uppercase letters. We saw that I think in the first problem. Is normally distributed with a mean of 9 and a standard deviation of 4. Okay, so I have two different random variables. I know the two different means. I know the two different standard deviations. If X and Y are independent, okay, that opens up the door, allows me potentially to do some mathematics. Super important. Which of the following describes the distribution of Y minus X? Y minus X. Well, I can add means, and so I can probably subtract means. So I think I said 9 minus 10, -1. So that felt good, but my students don't struggle with that. So I think I'm just going to cross out a couple of answers here. I don't think it can be A, or I don't think it can be D because they said 1 and 1. So -1, -1, -1. I can't add standard deviations, but I can add variances. So I think I squared my 3, and I think I squared my 4. Now, many times my students want to subtract here. Mr. Murphy, you subtracted the means, the averages. Why don't you subtract the standard deviations? We just finish the problem, and I'll address why we can't do that. So I did add 3 squared, which is now a variance, to the 4 squared. Now it's a variance. So I guess 25 is my combined variance, but ultimately I want a standard deviation. So if I take the square root of the variance, I get a standard deviation. So I think my mean was -1 with a standard deviation of 5, and so the answer is C. C as in cat. And that year, 2007, 39% of the students got this problem correct. So this was considered a harder problem. So there's some nice distractor answers up here. -1 if we just maybe subtract the standard deviations or something, or add them. And so just be careful here. So I guess the question is, when we're subtracting means, why are we adding the variances? So I have a good friend Dave Bach. He's a college board consultant, and he's very active in the AP stats world. This is an example that I think I probably took from Dave, so I'll give Dave credit. So if I have a 20-ounce box of cereal here, I'm pretty convinced when I buy it at the grocery store, there's 20 ounces of cereal. We're pretty close. I know that it will vary. I know that it's probably not exactly 20 ounces in every cereal box, but I'm reasonably convinced that's pretty close to 20. How's that? So if I want a bowl of cereal in the morning, let's say I have a 3-ounce bowl of cereal. No, I'm going to pour some cereal into my little bowl here, right? Now, when I say I want 3 ounces of cereal, I don't measure it. I don't shake the bowl and level off the top. I flip it over and I dump it in. When it looks like it's about full, I kind of stop. So I've subtracted from my original 20, and I was reasonably confident that there was pretty close to 20 ounces of cereal in there. After I've taken away, I think there's around 17 ounces of cereal left, but I'm less confident with that. Okay, I'm less confident with that. There's potential more variation there, right? Like there's probably not exactly 20, but I'm reasonably confident close. I definitely didn't pour exactly 3 ounces in unless it was just dumb luck, right? So even though I'm subtracting here, actually maybe greater variation or greater variance. And so that's why even though we were subtracting the means, we're going to add the variances. So one of my students yells out, so Mr. Murphy, we're pretty much always going to add variances, whether we're adding or subtracting the means. And I think in this course, that's a true statement. So hopefully that helps a little bit. It demystifies that concept. And I will say that that's harder for my students. They will struggle with it. I use all 3 of those problems every year with my students, and I'm hoping that after doing them, they feel a little bit more comfortable. So I got a couple of free response. We'll finish up today doing some free response. This is from the 2001 exam. This is sort of a maybe business type problem. So very real world. So a department supervisor is considering purchasing one of 2 comparable photocopy machines, A or B. The photocopier at my school breaks down all the time, especially when I need it. I don't know if your teachers complain about it, but it's just one of those things. Maybe it's Murphy's Law. It never seems to work when I need it to work. And it feels like the copy repairman is in almost every day, and I know him by first name. We're like best friends. Machine A costs $10,000, so they're not inexpensive, and machine B costs $10,500. Those 2 different costs for the 2 different machines. This department replaces photocopy machines every 3 years. In a large school, it would be not atypical to get over 1 million copies in 3 years at school. So they get a tremendous amount of use. Lots of teachers make lots of copies. They get used quite often. The repair contract for machine A costs $50 per month and covers an unlimited number of repairs. So if it breaks down once in a month, I pay $50. If it doesn't break down at all, I pay $50. If it breaks down every day, I pay $50. So that's one plan. That's one way that our school could purchase a copy machine. The repair contract for machine B costs $200 per repair. So I guess I'm trying to figure out which plan is going to be more cost effective for my school over the next 3 years. There's 2 different initial costs for the machines. I guess there's 2 different potential repair costs for the machines. Based on past performance, the distribution of number of repairs over a 1-year period for machine B is shown below. So it looks like maybe machine B, we can either have 0, 1, 2, or 3 repairs. I wish our machines were that good, were that dependable. It feels like ours break a whole lot more than that. Here's the associated probabilities. And again, I would probably just add those up like 75.901. So we talked about that, the sum of the probabilities, which is random variable always needs to be 1. I just want to kind of confirm that. You are asked to give a recommendation based upon overall cost as to which machine A or B, along with its repair contract, should be purchased. So you have to make a recommendation to your principal in your school. Should you purchase machine A or should you purchase machine B? This is super real world. Do we get a variable mortgage or a fixed mortgage when you buy a car? So this is a great problem. Anyone who's heading off into the business world or studying business in college, you'll do thousands of these problems. What would your recommendation be? Give a statistical justification or support your recommendations. Even if that last sentence wasn't there, please always show your math. I'm sure Luke is the same exact same thing. So for machine A, it cost $10,000 to buy. It was $50 a month. It was 12 months in a year. And it was over a 3-year window. So I multiplied 50 times 12 times 3, and I got $1,800. So the total cost for machine A with repairs for 3 years is $11,800. Keep in mind that that's unlimited repairs with this option. Okay, machine B's initial cost was $10,500, so a little bit more. But the repairs, we don't really know perhaps how many repairs there would be. So I had to calculate the expected value. So down here I said, the outcome times its probability plus the outcome times its probability plus the outcome times its probability. And so we would call this the expected value, right? Expected number of repairs. We would expect 0.85 repairs a year. I mentioned, I think on Monday, we do not want to round that number. Okay, and students say, but Mr. Murphy, you can't have 0.85 repairs, and that's a true statement. But we do not round expected values unless specifically told otherwise. So I think there's my initial cost for machine B. There's my expected number of repairs per year, 0.85. We were told it was $200 a repair. So we want to do this for 3 years. So when I did that math, I got 10,500 plus 510, 11,010. So if I'm looking at these two numbers here, clearly machine B is, well, let me rephrase it. We think that machine B will be less expensive, but there's no guarantees. But most of my students will say, let's pick machine B. And so over here, I just added a sentence and said, I would choose machine B as I would expect to pay around $11,010 over the 3-year window as compared to $11,800 for machine A for initial purchase and repairs. So that's what most students will pick. That's what most of my students will answer. You could make a strong argument that this is a better plan because it has unlimited repairs. So in other words, machine B, if you have not 0.85, that was what we expected, but maybe you could have 10 repairs a year. Well, that would be 10 times 200 times 3. That would be a whole lot more expensive. So this is a problem that you could actually answer two different ways, depending upon your perspective. I argued on what I expect to spend. This would be less than what I would spend here. But I think you could have a strong argument saying, even though this plan is around $800 more expensive, it's safer perhaps, and the fact that it covers unlimited repairs. It's a really neat problem because I think you can argue it or present your answer sort of two ways, and that's very, very real world. Fixed mortgage versus variable rate mortgage. Do you lease a new car? Do you buy a new car? Do you rent? I mean, there's all these options, and some of it depends upon your financial comfort level. So kind of a neat problem where I had to use expected values and probabilities and whatnot. And so I really like that one. Let's see if we can do at least one or two more. So this was from the 2015 exam. Sorry. So a little bit more recent. The shopping mall has 3 automated teller machines, ATMs, just setting the stage. Because the machines receive heavy use, they sometimes stop working and need to be repaired. Okay, that makes sense. It is frustrating, right? You go to an ATM, you put your card in, it tells you that the machine's not working. Let the random variable X, okay, so again, typically uppercase, represents the number of ATMs that are working when the mall opens on a randomly selected day. So I like the randomly selected. Big X is my random variable, and I have three machines, 3 ATMs at this specific mall. So this little table down here, number of ATMs working when the mall opens, none, 0. That is an option, and sometimes students forget that. Sometimes students say 1, 2, or 3, Mr. Murphy. Well, I guess none of them could be working, and that would be terrible, right? I have to walk around and go to 3 or 4 different machines, and none of them would be working, right? Probability of that is 0.15, 1 machine working, 0.21, 2 machines, 0.40, 3 machines, 0.24. When I first did that, I thought that actually number might be higher, but it does look like, just looking at these numbers, that many times not all 3 machines are working. How's that? I think I'll add those up real quick, and looks like I get 1. That's so good. That happens with random variables, so I felt comfortable about that. And so part A, this maybe was I don't know if I did this one on Monday, but maybe part A and part B are more what I did Monday, but it's a nice problem, so I want to do all 4 parts. What is the probability that at least 1 ATM is working when the mall opens? Well, 1 working is at least 1, 2 working is at least 1, 3 working is at least 1. So I think in part A, so the probability that my big random variable X is greater than or equal to 1, at least 1 machine is working. I just added those 3 probabilities and got 0.85. Again, notice that I have those numbers on my paper. I want to make sure that I'm showing the reader my mathematics. And then sometimes I step back and say, is that enough, or should I probably include a sentence? And I don't want to include a sentence. So the probability that at least 1 ATM is working when the mall opens is 0.85. So that felt relatively easy. I was confident that I could do that relatively quickly, but sometimes we just see 0.85 and students have added those 3 numbers on the calculator. And I'm going to say to be safe, show us your work. How's that? Almost never will showing your work hurt you, and almost always showing your work will help you. So just be careful about that. I think I would show that work, and that's what I tell my students. What is the expected value of the number of ATMs that are working when the mall opens? Okay, so outcome times probability plus outcome times probability plus outcome times probability plus outcome times probability. So you see, I did that math here, and I think I had the expected number of the number. Well, that didn't make sense. So I crossed that out and said, well, the expected value, much better, Mr. Murphy. The expected value of the number of ATMs that are working when the mall opens is 1.73 machines. And again, I do not want to round that. I know that 1.73 machines cannot be working at one time, but that's not what the expected value or mean or average tells us. So I'm going to leave that alone. I'm not going to round that at all. And if you did, you lose some points. We consider that a not fully understanding the concepts. And so please don't round expected values. I'm specifically told to. What is the probability that all 3 ATMs are working when the mall opens? So all 3 are working. Given that, well, boy, that sounds like that conditional probability that we talked about Monday, doesn't it? That's my red flag right there. Given that at least 1 ATM is working. Well, at least 1 ATM is working. I sort of just cover up the 0 and say, well, at least 1. I want to know all 3. So the probability that X is equal to 3, i.e. 3 machines are working. Given that at least 1 is working, X greater than or equal to 1. I had my 2.24 was my numerator. That's 3 working. My denominator was adding up those 3 probabilities. I got 0.24, 0.85, and I just went to my calculator and said that's equal to 0.282. That's actually lower than what my gut would have said, but it feels like these machines break often. And they said up here that they sometimes stop working and need to be repaired. So my gut said it would have been higher, but that's the numbers. That's what it is. And again, I wanted to have a sentence here. The probability that all 3 ATMs are working when the mall opens, given that at least 1 ATM is working, is 0.282. And in some ways, I'm just repeating the language in the question. But I have my context in here. I've shown the reader some math, etc. And I think hopefully that's a relatively strong answer that would get a lot of credit, not full credit. Given that, well, it sort of feels like another conditional probability. Given that at least 1 ATM is working when the mall opens. Okay, so I guess I have either 1, 2, or 3. Would the expected value of the number of ATMs that are working be less than, equal to, or greater than the expected value from part B? Well, the expected value from part B was 1.73. My gut said it was going to be more. If I say, well, we can't include 0, and these are my only 3 options, it felt like each one of those probabilities might have to proportionally be greater or larger because those 3 have to add up to 1. So if each one of those numbers gets a little bit bigger proportionally, it feels like when I multiply 1 times a little bit bigger number, plus 2 times that number, which is a little bit bigger, plus 3 times that number, which is a little bit bigger, it feels like my expected value wants to be a little greater. So given that at least 1 ATM is working, again, that means I cross out that column right there when the mall opens, the expected value of the number of ATMs that are working would be greater than the expected value from part B, which is 1.73. So I'll answer the question, but I think I want to get a little bit more info. By eliminating the probability of 0 ATMs working, the probability for 1, 2, or 3 ATMs working would all increase proportionally, and so therefore I would have a higher expected value. So that was a little different. That wasn't sort of a standard or typical answer. That one I had to think about, and I actually really like that one. Every once in a while it's really nice to have a challenging problem, even as a stats teacher. So I don't know if I can walk through this one in its entirety, but I'll do my best. This is from the 2002 exam. There are 4 runners on the new high school team. Team is planning to participate in a race where each runner runs a mile. So I don't know what you call that, the 4x1 mile or something. I guess runner A runs a mile and runner B runs a mile. So it's gonna take a while. It's gonna take a while for all 4 runners to run a mile. The team time is the sum of the individual times for the 4 runners. So I had runner A, runner B, C, and D, or 1, 2, 3, 4. Get the team time. That makes sense. I can add these, right? We talked about that. Assume that the individual times of the 4 runners are independent of each other. Super important. I'm gonna underline that. The individual times and minutes of the runners in similar races are approximately normally distributed. That's good. With the following means and standard deviations. So runner A runs a mile in 4.9 minutes. That's actually a pretty good mile. That's really hard to do. These are all under 5-minute miles. These are pretty good runners. And there's their associated standard deviation. So it looks like runner 3 is perhaps the fastest runner. Runner 3 thinks that he can run a mile in less than 4.2 minutes in the next race. A 4-minute mile is 4.2 minute miles really hard for high school students. I have for anyone. My guess is it's not likely to happen. But of course, I need to do some mathematics. Explain. So I said the probability that the time is less than 4.2 minutes is the probability that the z-score is less than. I just calculated a quick z-score 4.2 minus 4.5 over standard deviation of 0.14. What's the probability that the z-score is less than 2.14 or more than 2.14 standard deviations below the mean? So I just went to my calculator real quick. Normal CDF negative 10, comma negative 2.14. Now your teachers may have taught you to type in a different number here. Negative 1,000, comma minus 2.14. You can see that this number really isn't going to change much, if at all. No matter what my lower bound is. I know sometimes teachers do 1 times 10 to the negative 99. I'll leave it up to you and your teachers. What I actually want my kids to think about is, well, why isn't that number? Why is that probability going to change? Right? You change the lower bound, Mr. Murphy. Well, 10 standard deviations below the mean is pretty much not likely to happen, almost impossible. And so 1,000 standard deviations below the mean is even less likely. There's not much area under the normal curve. How's that? So sometimes I will say to my class, everyone pick a different lower bound, negative 10, negative 20, negative 30, negative 5,811, really doesn't matter. So I said it is unlikely that runner 3 would run a mile in less than 4.2 minutes. This would only happen about 1.6% of the time. So this is very likely. So could it happen? Yes. Is it likely to happen? And the answer is no. So runner number 3 probably is not going to run in the next race a sub 4.2 minute mile. The distribution of possible team scores is approximately normal. That's good. What are the mean and standard deviation of this distribution? Well, I can add and subtract means, and so I just found the 4 means for the 4 runners and I added those. And so I felt pretty confident that 18.9 minutes would be the mean or average time. Again, each runner runs a mile, the next one runs a mile, next one runs a mile, next one runs a mile. I add up those 4 different times. So I can add means. I can't add standard deviations, but I can potentially add up the variances, assuming that my events are independent. Well, their times in this case are independent. So I did underline that, I circled that. So I felt good about that. I felt like, okay, we were told that each one of those runners' times is independent. So I took the first standard deviation and squared it. I took the next standard deviation and squared it. Took the next standard deviation and squared it. So that's a variance, that's a variance, that's a variance, that's a variance. I add it up, I guess my combined variance. I take its square root and I get the standard deviation. So that's part B. There's the mean and standard deviation of this distribution. The mean would be 18.9 minutes. Standard deviation will be 0.3003 or 0.30 or something like that. We can finish last real quick. Suppose the team's best time to date is 18.4 minutes. So their mean or expected time is 18.9 minutes. Can they run at 18 combined 4 miles? 18.4. My gut says no, but again, I need to do some mathematics. What's the probability the team will beat its own best time in the next race? So the probability that team time is less than 18.4 minutes is equal to the probability of your z-score being less than 18.4. That's the time they want to beat. That's the mean or expected value time 18.9. There's my standard deviation. Probability that z is less than 1.655. So smaller than 1.665 standard deviations below the mean. Again, I went to my calculator and I typed in negative 10. But you can type in negative 100, negative 1,000. Whatever your teachers pretty much taught you to do that. That's perfectly fine. Your answer's probably not going to vary. That was 0.04795. And as a stats teacher, we just did inference a couple weeks ago, and I wanted to compare that to 0.05, but this problem didn't really ask me to do that. So I wanted to, and there was no need to do it here. So the probability that the team will beat its own best time, 18.4 minutes, in the next race is 0.04795. I have context, I have a full sentence, I have some mathematics. And I sort of went down the wrong path here with the 0.05. And I was thinking alpha is 0.05. That's the inference teacher in me. And I don't need to worry about that for this problem. But if it were an inference problem, boy, that's really close to that typical standard alpha 0.05. And I have to make a decision. If it was lower than that, I would reject the non-hypothesis. But it's nothing to do with this problem, so let's not go there. So anyway, those were, I think, all of the problems that I had for random variables. So let's just check to see if we've done them all. I think we have. So that was good. So real quick, hopefully you're feeling more comfortable with solving different types of random variable questions. I'll just open that up and say probability. Between the probability I did Monday, Luke did binomial and geometric yesterday, and I did some random variables. Hopefully probability you're feeling much more comfortable with. Similar to all problems in AP Stats, you should be able to write down a clear, concise solution in context. It's so important. And every year when we grade problems, we see unfortunately students will lose sometimes 2 points, for lack of context. They don't have context. They have some numbers, they have some math, but there's no context. It's super, super important. So here's tonight's homework. It's for the 2012 exam, and we're doing some sort of a transformation here, and we want to know what happens to the standard deviation. So Luke will do a great job with that tomorrow. So let's just find out for today. Hopefully you have a good day. Hopefully I help with some probability and random variables. College Board knows that not all students are going to have access to the internet or device for the exam, and we really, really want you all to take the modified AP Stats exam. I think it's on Friday, May 22nd. College Board's working on solutions to help students get what they need to show their best work. So please, 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 if you have internet problems at home, you don't have a device, you need a calculator, reach out to your school, your teachers, your administrators, the College Board, the link below, and the College Board will bend over backwards to make sure that we get you what you need. So if you're having mobile tools or connectivity issues, or one of your friends does and they're not quite so comfortable asking for help, please, please, please reach out to the College Board, and we'll try and make it happen. How's that? So thanks for watching. Luke's going to finish up the week. It's our school break up here in Maine, and so I want to see if I can go out and enjoy some of the nicer weather. My wife and I have been doing some day trips around Maine. So we hope that we'll see you again. Luke is doing sampling distributions and central limit theorem tomorrow, and then pre-response Friday, FRQ Friday. And then next week we're going to focus on strategies for doing well in the AP exam. We're going to actually create some FRQs. So Monday I'll be back, and I'm going to make you like AP readers. We're actually going to read some student samples and grade them and see what mistakes they made, if they made any at all. So please be safe, please stay positive, please take care of your family and yourself. We'll get through this. We really appreciate you watching, and Luke and I sincerely hope we're helping you. So let's call it a day. Thanks for watching. You'll see Luke tomorrow and Friday, and I'll be back on Monday. So have a great day. Be safe. Thanks for watching.
Hello, AP Statistics students, and welcome to the College Board Virtual Instruction for AP Statistics. My name is Luke Wilcox. I am an AP Statistics teacher at East Kentwood High School in Kentwood, Michigan, and it is Thursday, April 23rd. I'd like to start today by saying a big thank you to those teachers and students who wished me a happy birthday. Yesterday was my 41st birthday, and we celebrated in style with a Star Wars themed birthday. My children made me this excellent Luke Scott cake, and they watched Return of the Jedi, and I'm feeling very grateful at age 41 to be where I am today and to be with you all today. So thank you for that. We do have a lot lined up for today. We're talking about sampling distributions, so I'd like to go ahead and just jump right into the lesson for today. So checking to make sure I'm in the right place. This is AP Statistics. You all know who I am at this point, I hope. A few quick reminders for those that may be here for the first time. This is a daily meeting that we have at 2 o'clock Eastern Standard Time. We are reviewing for the AP exam, and we are in this week right here, April 20th to the 24th. We're covering units 4 and 5 from the College Board CED, which will complete our review of all of the content contained within the CED, which means that next week, Mr. Murphy and I have some special things planned for you, some general review things that I think are going to be super helpful. And then that final week, we're actually going to give you some practice questions that might look very similar to the questions that you're going to see on your modified AP exam here. And of course, the big day, May 22nd, is when you all will be taking your AP Statistics exam for 2020. So a quick note here that all of the lessons that you see on YouTube Live are available to download at statsmedic.com/YouTube. There, you just have to know the date, and you'll be able to find the resources to be able to print those out. And then a final reminder here that if you or another student that you know is in need of a device or internet access in order to be able to take that AP exam at home on May 22nd, the College Board wants to make sure that you have that. So if you just go to cd.org/hat, there's a form that you can fill out, and they will make sure that you are taken care of. All right, so let's take a look at the homework from the previous lesson. This is the assignment that you got from Mr. Murphy yesterday, and it's a good lead-in to some of the stuff that we're going to talk about today. So here's what it says. A company sells concrete in batches of 5 cubic yards. The probability distribution of X, the number of cubic yards sold in a single order for concrete for this company, is shown in the table below. So we see there are only a certain number of values possible for X, which would be 10, 15, 20, 25, and 30. And then we see those respective probabilities for each one of those values, the random variable X. Okay, the rest of the question says, expected value of the probability distribution of X is 19.25. Okay, so what they're giving us there when they say expected value is they're giving us the mean of that value. And they're also giving us the standard deviation of X. There is a fixed cost to deliver the concrete. The profit Y in dollars for a particular order can be described by Y equals 75X minus 100. What is the standard deviation of Y? Okay, very important here. The relationship that they've given us for Y is that Y is equal to 75X minus 100. Now let's think about how the distribution of Y is going to compare to the distribution of X. Well, really there's two things that we're doing to that X value in order to turn it into a Y value. The first step is to take that X value and multiply by 75. So we could take each one of these X values and multiply by 75. And what we want to know is what is that going to do to the standard deviation? Well, if you take a list of numbers and you multiply them all by 75, sure enough, that's going to multiply the standard deviation by 75. So we know in order to get the standard deviation of Y, we're going to have to take 75 times the standard deviation of X. But now we need to consider the next step here, which is to subtract 100. Well, here's the deal. If you subtract 100 from all of the values in the list, all you're really doing there is shifting the distribution 100 units down. That's not going to change the variability. So really, this part here does not have an impact on the standard deviation of Y. And sure enough, this is all we need in order to find the standard deviation of Y. So I'm just going to take 75 5 times the standard deviation of x, which we know from the problem is 5.76, and we're going to get a standard deviation of y equal to $432. So looking at my answer choices over here, I can see that B is the answer that I'm looking for. Now, the most common incorrect answer, I will tell you for sure, because I've seen students make this mistake, is they will subtract 100 because they think that this minus 100 also subtracts 100 from the standard deviation, which is not true. So this is definitely the incorrect response there. The correct answer is B. So hopefully you did okay with that, and I think we are now ready to talk about some new learning for today. So here's the quick lesson overview where I will start with the learning targets, and there are 3 of them today. The first 2 are very parallel, so let's take a look. Learning target number 1, describe the sampling distribution of p hat and then p1 hat minus p2 hat. So this first learning target is all about proportion, and it's about sampling distribution for proportion. Now look at the second learning target. Once again, sampling distribution, but this time x bar and x1 bar minus x2 bar. So this learning target is all about sampling distribution for mean. And then sort of a sub-learning target underneath that is to understand the central limit theorem, which is going to relate back to the sampling distribution for mean. So let's go ahead and jump right in on this one. Okay, page 1 of the activity here today. The question that we're trying to answer is, do you like Reese's Pieces? And I will be honest with you, my 11-year-old daughter Reese, yes, her name is Reese. Guess what? Her favorite candy is Reese's Pieces. And one day she claims to me that she really likes the orange ones better than the other 2. Now I'm not convinced that that's true, but I started to wonder about the distribution of the color of Reese's Pieces. And I looked it up, and it turns out that the candy manufacturer claims that 40% of the candies are orange, so they're not equally distributed. Okay, so first of all, you can see we are in the world of proportions here. 40% is our proportion that's being claimed for the whole population of all Reese's Pieces. And so let's be careful with our notation here. The notation we should be using here is p for the true proportion for the whole population, as opposed to p hat, which would be the sample proportion. So we're going to use an applet to simulate taking random sample of 50 Reese's Pieces. Well, this very clearly is our sample size, and we're going to use lowercase n to represent that sample size of 50. So here's the definition of the random variable. It says let n equal the number of orange candies in a sample. Number of orange candies. So we're looking for how many out of those 50 are orange. So question 1 says use the applet to take 100 samples of 50. Sketch the result below. So I'm going to take you now to the applet, and you can just follow along on your screen here. And you can find this on the internet if you just type Reese's Pieces applet. This will be the first one that comes up. And I've already set our probability of orange to 0.4 and our number of candies to 50. And let's just go ahead and take one sample and see what it looks like. What I really like about this applet is that there's an animation, so you can physically see the random sample of 50 Reese's Pieces, and we're splitting them into 2 buckets, the orange ones and then the not orange ones. And then you can see here that the applet will count up the number of orange candies. In this case, 16 out of the 50. And then down here on the bottom, you can see it's putting a tiny little dot right at 16. So let me show you one more of these. We're going to take another random sample of 50 Reese's Pieces, count up the number of orange Reese's Pieces, and for this particular sample, we got 19. And down here, you can see that there's a dot that appeared at 19. Now, the nice thing about technology is that we can do many samples very, very quickly, and we want 100 total. We've already done 2. So I'm going to add 98 more samples here, making sure to unclick the animation, otherwise we'd be watching this for the rest of the hour here. I'm going to draw those samples real quick, and here is the distribution. And so let's notice a couple of things here. First of all, it appears that the center of this distribution is looks like it's about 20, and as low as maybe 10 is the lowest value, 29 is the high value. And I'm starting to see a little bit of a normal distribution here. In fact, I can click this, and it shows me that there is a little bit of a normal distribution that's appearing there. So let's go ahead back to the activity, and let's copy this down. And here's the thing. We don't have to copy it exactly what we saw. We just need the general idea of what that looked like. So here's what I remember. I remember that the tallest stack of dots was at about 20. So I'm just going to draw some dots at 20. I knew the lowest one was maybe about 10, and the highest one was maybe about 29. And then it appeared to have somewhat normal distribution. Certainly not perfect, but I'm just going to sketch this in. And this just has to be a sketch. Certainly does not have to be exactly what you see in the applet. This is just giving us an idea of what this distribution looks like. So the first question to answer here is name the distribution. Well, I'm hoping that this looks very familiar to the lesson that we went over on Tuesday, where we talked about binomial distribution. Sure enough, this is in fact a binomial distribution. And just as a quick review, to make sure that this is a binomial distribution, there are 4 conditions that need to be checked. And we remember that with the acronym BINS. B stands for binary. So each trial is a success or failure. In this case, a success is orange and a failure is not orange. I stands for independent. Well, we have a random sample, so each trial should be independent. And because we're sampling without experiment, the 10% condition should be checked. And certainly 50 is less than 10% of all Reese's Pieces. So I'm going to say the independent condition is met. And the number of trials is fixed. Well, here the number of trials is 50 because we're sampling 50 Reese's Pieces. And then S, we have the same probability of success for each trial, and the probability of success here we know is 0.40, and so that condition is satisfied. So we have a binomial distribution. So we're going to be able to use some things from Tuesday to help us answer the rest of the questions of this video. Now, what does each dot represent? Well, let me take like this dot right here, for example. What does that dot represent? Well, it represents a random sample of 50 Reese's Pieces, and then we count the number that are orange. In this case, there were 12. And then this dot represents a different random sample of 50 and counting up the number of orange. And this is a different random sample, and this is a different random sample, and this is a different random sample. So to answer the question here, what does each dot represent? It represents one sample of 50 Reese's Pieces, and then what we're going to do with that sample is we're going to count the number of orange. And we are calling this random variable n. And so what we have in this distribution is many samples, right? So there is another name that we could give this distribution, and that is what's called a sampling distribution. And in this case, each dot represents a different n value. I'm going to call this the sampling distribution of n. Now, a little bit of a disclaimer here. In order for this to be the true sampling distribution of n, we must have all possible samples of size 50. Well, obviously, there's like an infinite number of samples of size 50, so we don't have the true sampling distribution here. But I think that these dots give us a good enough idea about the sampling distribution that I'm comfortable calling it a sampling distribution, even though it's not the true sampling distribution of n. Now, I'd like to be able to describe that sampling distribution. And let's start with the shape. And we've already mentioned here that we think that the shape of this thing is approximately normal. And actually, if I remember back to the lesson from Tuesday when we talked about binomial distributions, there's actually something that we can check to make sure that the normal approximation is appropriate here. That's what's called the large counts condition. And remember, the large counts condition says that n times p, 50 times 0.40, which is 20, and then n times 1 minus p, which is 30, has to be greater than or equal to 10. And that's really telling us the expected number of successes and the expected number of failures are both greater than or equal to 10. And sure enough, they are here. And so I'm comfortable saying that this distribution is approximately normal. So that takes care of the shape. Now let's talk about the center of the distribution by thinking about what the mean is. And just by looking at the picture here, I can see that the mean is 20. Right? You can very clearly see that. But if you recall from Tuesday, we did have a formula for calculating the mean of a binomial distribution, which is n times p. And actually, we know n times p over here is equal to 20. So that confirms our answer and what we see in the dot plot there, that 20 is the mean of this distribution. Now let's go ahead and move to the standard deviation of the distribution. And once again, I'm going to go back to our previous lesson on Tuesday. There's a formula for calculating the standard deviation for a binomial distribution, which is square root of n times p times 1 minus p. So all we have to do here is plug in some numbers. Square root of n is 50, p is 0.40, and 1 minus p is 0.60. And if you plug that into your calculator, you're going to get a standard deviation of 3.6. Now, one little warning here is that when you're plugging in a number for n, you want to be careful that you're using the sample size there. And often students will have trouble deciding whether it should be 100 or 50. We want the sample size, not the number of samples. So 50 is the appropriate value for n, which is what we used in our calculation. So we're ready to move on to number 2, which says let p hat equal the proportion of orange candy. Notice what's changed here. We are no longer looking for the number of orange candies. We are looking for the proportion of orange candies in the sample. So the question is, what needs to be done to each value of n to change it into p hat? Well, if I look at my values for n, which represent the number of orange candies, and I want to change that into a proportion, all I need to do is divide by the sample size, 50. So the answer here is that we just need to divide each n value by 50, and that'll change it into a proportion. So number 3 says in the applet, change from the number of orange to the proportion of orange. So I'm going to take us back to that same applet that we were using. We've still got our dot plot here. And what I'm going to do is I'm going to change from the number of orange candies into the proportion of orange candies. And what I want you to do is I want you to watch this dot plot here. Okay, watch what changes. So here we go. I'm going to go ahead and change to proportion. And what did you notice? Let me do it again. There's the number of orange candies. There's the proportion of orange candies. Hopefully what you noticed is that the dots did not change at all. They were exactly the same as they were before. But what changed was the values on the x-axis. Instead of being the number of orange candies, we now have the proportion of orange candies. So let's go ahead and copy that into the activity here. And once again, this is just a sketch. And hopefully you noticed in our simulation there that 0.40 was right about the center of the distribution. So I know I have my tallest number of dots there, and I had dots as low as this and maybe as high as this. And really what I'm trying is to copy the dot plot from above, but just put it on the new scale here where we have proportions instead of the number of orange candies. All right, so there we go. So before we name the distribution, I actually want to think about this question first. Okay, what does each dot represent? So let's take, say, this dot for example. Well, that is a random sample of 50 Reese's Pieces and the proportion of orange calculated from that sample. And this is a different random sample of 50 and the proportion calculated from that sample. And this is a different sample, and this is a different sample, and this is a different sample. So we're going to say here each dot represents one sample, and then what we're going to do with that sample is we're going to calculate the proportion of orange. And usually be careful with our notation here because it's a sample proportion. That would be p hat. So over here, each dot represents a different sample and the proportion calculated from that sample. So we can call this distribution the sampling distribution of p hat. Remembering that it's not the true sampling distribution because we don't have all possible samples of size 50. So that is the name of the distribution. This is what's called the sampling distribution of p hat. Now let's see if we can go ahead and describe that distribution. I'm going to start once again with the shape. And of course the shape is exactly the same as the shape of the one above it because it's the same distribution, just a different scale. So of course I can say this is approximately normal. And my justification would be the large Helms condition. We already checked that above. So the large Helms condition also allows us to say that the sampling distribution of p hat is approximately normal. All right, now let's move to the mean of the distribution. Okay, the mean of the distribution. Let's think about this. What did we do to all of the values here in order to turn them into these values here? We divided each one of them by 50. So what do you suppose that's going to do to the mean? Probably going to divide it by 50. So what I'm going to do is I'm going to take the mean from above, which was 20, and I'm just going to divide it by 50, and that's going to give me 0.40, which sure enough is exactly the value we see at the center of the sampling distribution. And so this is actually giving us an important formula here. It's the formula for the mean of the sampling distribution of p hat. And what we did was we started with the formula for the mean of a binomial distribution, which is n times p, and then we divided it by 50. Well, in this case, if we're generalizing, we're dividing by the sample size. The n's cancel out, and what we end up with is that the mean of the sampling distribution of p hat is just equal to p, the true proportion. Okay, let's go ahead and move to the standard deviation. And we want to know the standard deviation of the distribution. Well, once again, what did we do to all of these values to turn them into these values? We divided them by 50. What do you think is going to happen to the standard deviation? It's going to be divided by 50. So I'm going to take my standard deviation from above, 3.46, and I'm just going to divide it by 50, and that's going to give me an answer of 0.07 for my standard deviation. Now let's see if we can generalize that into a formula here. Okay, the formula for the standard deviation of p hat. Well, we started with the formula for the standard deviation of a binomial distribution, which is the square root of n times p times 1 minus p. And then we divided it by 50. Well, to generalize, we're going to divide it by n. And instead of dividing by n, I'm just going to put a 1 over n out in front of it, which is the same as dividing by n. Now here we're going to have to use a little trick from our algebra class, which is to take this 1 over n and put it inside the square root. Now when it goes inside the square root, it becomes 1 squared over n squared, or just 1 over n squared. And then we still have n times p times 1 minus p. Well, we can do a little simplifying here. One of these n's down here is going to cancel with this n. And look, we are left with a formula now for the standard deviation of p hat. It is the square root of p 1 minus p on the top and then n on the bottom. So this is the formula for the standard deviation of the sampling distribution of p hat. Okay, we've got one final question here, and here's what it says. Suppose that we took an SRS of 50 Reese's Pieces and calculated the proportion that are orange, and an independent SRS of 100 Skittles and calculated the proportion that are orange. Describe the sampling distribution of p1 hat minus p2 hat. So look, now we have two samples. So this 50 is the sample size of the Reese's Pieces. I'm going to call that n1 because that's our first sample. 100 is the second sample. I'm going to call that n2. And then we've got sample proportions for each one of those. And we want to be able to describe the sampling distribution of the difference between the two sample proportions. Well, let's go ahead and handle this like we do anytime we describe a distribution. Let's start with the shape. And sure enough, it turns out that this shape, well, you can check to see if it's going to be approximately normal in the same way that we did up above, but we have to do it for both sampling distributions. So that means that n1 p1 and n1 1 minus p1 for the sample of Reese's Pieces has to be greater than or equal to 10. But we also have to check if the second sample, n2 p2 and n2 1 minus p2 have to be greater than or equal to 10. If all four of those are true, we can say the sampling distribution is approximately normal. Okay, next we're going to move to the center of this sampling distribution, and then in the end here we'll also get to the variability. Now, in order to get some formulas for the center and the variability, I have to take you back to something that Mr. Murphy talked about yesterday. We were talking about combining random variables. And here's what we're going to do. We're going to think of this as being random variables here, and what we're doing is we're taking the difference between two random variables, x minus y. And if you recall from yesterday's lesson, if you want to get the mean of the difference between two random variables, very straightforward. You just take the mean of x minus the mean of y. So that means for us, if we want to get the mean of p1 hat minus p2 hat, we just need to take the mean of each one of those distributions and subtract. And we know from above this formula here, the mean is just the true proportion. So we have the true proportion for the first population minus the true proportion for the second population. And there's our formula for the mean of the sampling distribution of p1 hat minus p2 hat. Now for variability, once again, you got to go back to yesterday's lesson with Mr. Murphy, and hopefully you remember that when you have the difference between two random variables, it actually increases the variability. There's more variability. And so the question is whether you want to add the standard deviations or add the variances. And very important here, one does not simply add standard deviations. What we do add is we add the variances. So we know here that we want to go ahead and add the two variances. So the formula is to get the variance of x minus y. We do the variance of x plus the variance of y. Now what that looks like here, if I'm trying to find the standard deviation of p1 hat minus p2 hat, I need to add variances. Well, right here I have the formula for standard deviation. In order to turn that into a variance, I have to square it. Well, squaring it is just going to get rid of the square root. So the square root goes away, and what we end up with is p1 1 minus p1 all over n1. That's the first variance plus the variance of the second population, p2 1 minus p2 all over n2. Now that's giving me the variance. In order to now turn that back into the standard deviation, I need to take the square root of that big long formula there. And so now we have a formula for standard deviation. So a lot of formulas that you see here, but no fear, these formulas are in fact provided for you on the formula sheet for the AP exam. So if you go to the second page of the formula sheet, the very top here, you are going to see all of the formulas that you need for the sampling distribution for proportions, which is what we just talked about. So if you have one sample or one population, there's your mean and there's your standard deviation. And then if you have two samples, there's your mean and there's your standard deviation. And those match with the formulas that we came up with in the activity. So that completes page number 1, dealing with proportions. You probably know what's coming ahead here on page number 2. We are now going to enter the world of means. So there's a little bit of setup, and we're going to use a different applet for this. So here's what it says. Follow along with me. Reese's Pieces are available in snack size bags. Assume that the number of total candies in each bag follows a normal distribution with a mean of 16 and a standard deviation of 5. Okay, let me pause right there. The mean of 16. Now they're talking about the mean of the population of all bags of these snack size. So we're going to use the right notation here, which is mu, and we know that's equal to 16. And then this is the standard deviation of the population, so we're going to use sigma, and we know that's equal to 5. So we will use this applet to simulate taking random samples of snack size bags. All right, so here we go. Let x equal the total number of candies in a randomly selected snack size bag. Sketch the distribution below. Okay, you're going to have to see what this looks like in the applet here. So let me jump over to the applet. applet, and this is the applet that we're going to be using here. And that first distribution that you're seeing right on the top there, that's the distribution of all of the bags of snack size Reese's Pieces. I'm counting up the number of total candies in each bag. And sure enough here, you'll see that on average, there's going to be 16 candies in each bag with a standard deviation of 5. So they're calling this the parent population. We're going to call it the population distribution. And so the first thing we need to do in the activity is we sketch this distribution here. And once again, this is going to just be a sketch. It does not have to be perfect, but we clearly know that it looks like a normal distribution. So we know 16 is the mean. So I'm going to draw the biggest bar at 16. And then the bars get lower and lower as we move to the right. And they get lower and lower as we move to the left. So it looks something like that. Don't worry about that being perfect. Just get the general idea down there. And first we want to name the distribution. And I told you already, we are going to call this the population distribution because it represents the population of all snack size bags of Reese's Pieces. Now, what does each black box represent? Well, you can't really see it in the applet, but there's really a bunch of black boxes stacked on top of each other here. And the idea is that, say, this black box right here represents one snack size bag of Reese's Pieces with maybe 14 total candies in it. And this one has 20 candies in it. And this one has 25 candies in it. So we're going to say that each black box represents one snack size bag. And what we're going to do is we're going to count the total number of candies. And we're calling that random variable x. Okay, let's talk about or see if we can describe this distribution now. The first thing that we want to talk about is the shape of the distribution. And we actually already know that the shape of this distribution is approximately normal. And the reason I know that, if you look above, they actually tell you this right in the problem. So I'm going to say that this is given in the question. Okay, we are given that the population distribution is approximately normal. Now, what does the mean? Well, we can see here by the picture that the mean is 16, but we also knew that the mean is 16 because that was given in the problem. So let's identify the mean here as being 16. And what's the standard deviation? Well, that's also given to us in the problem. We know the standard deviation of the population is 5. Okay, so now let's move down to the next part where it says let x bar equal the mean number of candies from a random sample of 5 snack size bags. So we are going to take a sample of 5 snack size bags, count the number of candies in each one, and find the average from those 5 bags. So it says use the applet to take 10,000 samples of size 5. Well, let me jump back to the applet here and let's see if we can take a bunch of samples here. So we want to start out with a normal distribution here. And I'm going to go ahead and click animated here and notice what happens. We've got a sample of 1, 2, 3, 4, 5 bags of Reese's Pieces, and then this blue box represents the average number of candies for those 5 bags. Let me show you another one. Here is a different random sample of 5 and the mean calculated from that sample. And this is a different random sample of 5 and the mean calculated from that sample. And what I can do is I can do this over and over and over again 10,000 times, each time taking a sample of 5 and then dropping down the mean from that sample of 5. And so this is the new distribution that we want to look at. And the first thing that you'll notice is it does look like it's approximately normal, just like the population distribution, but very clearly it has a lower variability there. So let's take some of those ideas back to the activity now. And the first thing we want to do is to just sketch the picture. Now it still appeared to have a mean around 16, and so my tallest bar is going to be there, but it had a lower variability. So I'm going to make this distribution much skinnier than the one above it. Right? It definitely had a lower variability than the population distribution. So let's go ahead and answer some questions about this. The first one, I'm going to actually start here. What does each blue box represent? Well, let's say we look at this one blue box right here. That box represents a random sample of 5 bags and the mean number of candies calculated from that sample. And this is a different random sample of 5 and the mean calculated from that sample. And this is a different sample, and this is a different sample, and this is a different sample. So what does each dot or blue box represent? Represents one sample, and then from that sample we're going to calculate the mean number of candies. And the correct notation here for the mean number of candies from the sample is x bar. So what we have over here are many samples of size 5 and a mean calculated from each one of those samples. And so sure enough, we can call this a sampling distribution. Okay, once again, it's not the true sampling distribution, but I'm comfortable labeling it as such. So to name the distribution, we're going to call this the sampling distribution of x bar. Now let's see if we can describe that distribution. And I'm going to start with the shape, and we notice right away the shape was also approximately normal. And if I had to justify that, I would say because the population distribution is approximately normal, which we were told in the problem. Now, what is the mean of the distribution? Well, you can tell just by looking at it that the mean is 16, just like the mean of the population distribution. And so we actually have an important formula here, which is the formula for the mean of the sampling distribution of x bar, which is just equal to the mean of the population mu. Now, when we move down to standard deviation here, we know the standard deviation of the population distribution is 5, and very clearly the variability has decreased, right? So we want a number less than 5. So it might make sense to divide by something, and it seems reasonable that the sample size has something to do with it. The bigger the sample size, the lower the variability. So you might think that we would want to divide that by the sample size. Well, it turns out that it's actually divided by the square root of the sample size, and that has to do with that whole business about adding variances. But that's going to give us the correct value of the standard deviation here, which is 2.24. And so the formula, if we generalize this for the standard deviation of x bar, is to just take the standard deviation of the population and divide it by the square root of n. All right, now let's move on to number 7. It says change the parent population to be skewed instead of a normal distribution. All right, so I'm going to go back to the applet now, and I'm going to change the parent population instead of being a normal distribution. Let's say that we're skewed, and you can see here skewed to the right. Now, first, let's just acknowledge that this would be unfortunate because now the average number of candies you're getting in a bag of Reese's Pieces is only 8. A little bit unfortunate. So let's see what happens when we take samples of size 5. So once again, sample of 5, find the mean, drop it down. Right? I'm going to do that 10,000 times real quick. And what do you notice? Well, definitely less variability, but I still think I see a little bit of a skew to the right on this one. Okay. Now let's see what happens when we increase the sample size. So down here, I'm going to change my sample size to 25, and it's going to do 2 different distributions for me. The first one is samples of size 5. The second one is samples of size 25. And what do you notice down here? Well, once again, less variable because our sample size went up, but also it's starting to look like it's approximately normal. So the amazing thing here is that even though the parent population is skewed to the right, the sampling distribution is approximately normal if your sample size is big enough. So let's go ahead and capture those thoughts in the activity here. All right. Number 7, samples of size 5. Describe the shape of the sampling distribution. Well, for the first one, the samples of size 5, it was still a little bit skewed right. So I'm going to say slightly skewed right. But the amazing thing was when we jump down to samples of size 25, the sampling distribution appeared to be approximately normal. So number 9 says what happens to the shape of the sampling distribution as the sample size increases? Well, here's the deal. As the sample size goes up, the shape of the sampling distribution becomes closer to a normal distribution. And this very, very impressive fact is one of the biggest ideas in introductory statistics and is what is called the central limit theorem. The central limit theorem says as your sample size increases, the sampling distribution gets closer and closer to normal, no matter what the population distribution looks like. Skewed left, skewed right, bimodal, doesn't matter. Now, how big of a sample size do we need in order to be comfortable saying the sampling distribution is approximately normal? Kind of depends on who you ask or what book you look in. One of the generally accepted values is that if n is greater than or equal to 30, you're usually pretty safe. All right, last question here, number 10. Suppose that we took an SRS of 25 Reese's Pieces snack size bags and calculated the mean number of candy, x1 bar, and an independent SRS of 40 Skittles snack size bag and calculated the mean number of candy. Okay, you can see the parallel to what we talked about on the previous page. We now have 2 samples. So let's go ahead and talk about the shape, the center, and the spread for this distribution. I'm going to rate it as variability here. Okay, first of all, for the shape, we're going to hope that somehow we can arrive at the fact that it is approximately normal. And there are a couple different ways to arrive at that, which I will summarize when we get to the important idea. Now, for the center of the sampling distribution here, we want the mean of x1 bar minus x2 bar. And really, we just need to take the mean of the first distribution minus the mean of the second distribution. And we know up here that the mean is just mu, so it's just going to be the mean of the first population minus the mean of the second population. Now, for the standard deviation of x1 bar minus x2 bar, you might think that you need to subtract standard deviations, but we know that the variability increases, so we need to add. But remember, one does not simply add standard deviations. We have to add the variances. So I need to take this and turn it into a variance by squaring it. So that's going to give me sigma 1 squared over n because the square root is going to go away. And then I need to add the variance of the second distribution, to be 1, this should be 2. Now that gives me the variance. In order to turn it back into standard deviation, I just need to take the square root of that whole thing. Now once again, a lot of formulas there, but the nice thing is that on your formula sheet here, the next thing you see is sampling distributions for means. If you have 1 sample, there are your formulas. If you have 2 samples, there are your formulas there. So let's see if we can go ahead and summarize our learning from today's lesson. So here's how I'm going to organize the important idea. Of course, this is all about sampling distribution, but there are 2 different worlds in of sampling distributions. There is the world of proportion, and there is the world of means. And what I'd like to do here is to compare how those two sampling distributions look in terms of three very important things: the shape, the center, and variability. So let's start with the shape of the sampling distribution for a proportion, and we decided that hopefully we can arrive at the fact that it is approximately normal. And the way that we check that is by using the large counts condition, just like we did for the binomial distribution, which says that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Now for the sampling distribution of the mean, once again, we would like to arrive at the fact that that sampling distribution is approximately normal. We have a couple of different ways that we can arrive at it. The easiest way, and the way we use in the activity, is that we were given in the problem that the population distribution is normal. So of course, if the population distribution is normal, then the sampling distribution is approximately normal. The second way, which we arrived at the end of the activity, is using this idea of the central limit theorem, that if your sample size is large enough, so I'm going to say here sample size is large, and for most textbooks that's n greater than or equal to 30, then by the central limit theorem, CLT, we know the sampling distribution is approximately normal. Now there's a third special case where you don't know anything about the population distribution, and your sample size isn't big enough, or less than 30. In that case, you need to make a graph of your sample data, a dot plot, a histogram, a bar plot, and what you'd like to see is that the sample data show no strong skew or outlier, which would mean that it's reasonable to assume that that sample came from a population distribution, which is approximately normal, which then allows us to say the sampling distribution of x bar is approximately normal. Okay, now let's move to the center. This one will go pretty quickly. The center of the sampling distribution for p hat is just the true parameter, the true proportion of the population. Over here for means, the mean of the sampling distribution of x bar is just equal to the true mean of the population mu. And then finally, let's write our formula for standard deviation as a measure of variability. Standard deviation of p hat, which we arrived at in the activity, is the square root of p1 minus p all over n, which we derived from the binomial distribution formula for standard deviation. And then over here for means, the mean of x bar is equal to sigma over the square root of n. Now I'm just giving you the formulas for one sample. We did also derive the formulas for two samples. I'm not going to put those into the important ideas. You can always look those up in the formula sheet for the AP exam. Now we have one more question for you here. It is a multiple choice. You could try that before tomorrow's lesson. I will be with you once again tomorrow. Tomorrow is going to be FRQ Friday, which means I'm going to bring 3 of my favorite FRQs, and we're going to go through how to look at a model solution, but also the rubric that are used to grade those. So I certainly hope that you'll be with me again tomorrow, and have a good evening. Hello, AP Statistics students, and welcome to the College Board virtual instruction for AP Statistics. My name is Luke Wilcox. I am an AP Statistics teacher at East Kentwood High School in Kentwood, Michigan. Very happy to be here with you today. It is a very exciting day today because it is Friday, so happy Friday to you all. And what that means today is that we are going to be doing FRQ Friday, which means that I'm going to do my best to try and take you through 3 response questions from released exams in the past and talk our way through the rubric so that you can see exactly how those are graded. So let's go ahead and jump right into things today. Quick check to make sure we are all in the right location here at AP Statistics. Hopefully you all know who I am at this point. A couple of quick announcements to start out here. If you are new to us for some reason today, you should know that we do this meeting every day, 2 o'clock, Monday through Friday, Eastern Standard Time. We are approaching the end of the AP exam review unit by unit through the College Board CED. Right at the end of this week here, where we're finishing up units 4 and 5. So the FRQs that you see today will be coming from those 2 units that we talked about this week. Then looking forward to next week, Mr. Murphy and I have some excellent review activities planned for you for next week. And then this week of May 4th through the 8th is going to be AP prep week, where you are getting ready for all of your AP exams. And then the big day for AP Statistics is May 22nd for our AP Stats exam. Now for all the lessons that you see here on YouTube, if you want to download the lesson in order to print that out, you can go to statsmedica.com/YouTube. Just find the date, today's date, and you will find the resources that you need in order to access for today's lesson. And the final announcement here: if you or a student that you know is in need of a device or internet access in order to be able to take that AP exam on May 22nd, make sure that you go to cd.org/tech. There's a form that you can fill out there to make sure that you have everything that you need in order to take that AP exam at home on May 22nd. Okay, so we're going to jump right back to the homework problem that I assigned you yesterday, where we talked about sampling distributions. We've got this multiple choice question to take a look at. So let's dig in. Here's what it says: a large school district held a district-wide track meet for all high school students. For the 2-mile run, the population of female students participating had a mean running time of 8.8 minutes with a standard deviation of 3.3 minutes. Okay, let me pause right there. They're giving us the mean of the distribution for the females, and they're giving us the standard deviation of the distribution for the female. And the population of male students participating had a mean of 7.3 with a standard deviation of 2.9. So this 7.3 is going to be the mean for the male, and this 2.9 is going to be the standard deviation for the male. Now it says, suppose 8 female students and 8 male students who participated in the 2-mile run are selected at random from each population. Let x bar sub f represent the sample mean running time for the female student, and x bar sub m represent the sample mean running time for the male student. So here's the question: what are the mean and the standard deviation of the sampling distribution of the difference in sample mean? So we know right away that we are in the world of means instead of the world of proportion. And it is also very clear here that this is a 2-sample problem rather than a 1-sample problem. So there's a couple of formulas that we're going to need to remember here. The first of which is how to calculate the mean for the difference in sample mean. So the mean of x bar sub f minus x bar sub n is really just equal to the mean for the female minus the mean for the males. And we actually know those two values are given to us in the problem. The mean time for the females was 8.8 minutes minus the mean time for the males was 7.3 minutes, which is going to give us a value of 1.5. So as I look at my answer choices here, this one is incorrect, this one is incorrect. So A and B are no longer options for us here. Now it appears that we have to find the standard deviation in order to get the correct answer here. So in order to get the standard deviation of x bar sub f minus x bar sub n, remember, this is where we want to add the variances. Okay, so if I take the variance for the female, that would be sigma squared f over n f, and then I'm going to add the variance for the males, which would be sigma squared n over n m, and that gives me the variance. But I want to turn that back into the standard deviation, so now I need to take the square root of that whole thing. Well, now I just have to plug in the values that were given to us in the problem. So it's going to be the square root of the standard deviation for the female, 3.3 squared, over the sample size of 8, and the standard deviation for the males is 2.9 squared over the sample size of 8. And so when I look at those remaining 3 choices there, I see an issue right here in answer choice C. We would not subtract the variances. We know we need to add the variances. And the thing that I see missing here is I'm missing the squared in D, and it appears to me that answer choice E is going to be the correct answer. So hopefully you did okay on that homework problem, and we are ready to jump into FRQ Friday. So let me start with just a quick overview of what we are trying to accomplish here today. You know what to expect. You're going to be looking at some FRQs. What I'm going to do is I'm going to give you 2 of them from Unit 4, and then I'm going to give you 1 of them from Unit 5. And my general approach on these is to start by talking my way through the model solution, but then after that, equally important is talking through the rubric that was used in order to grade that particular question, so that you know exactly what has to be included on the AP exam in order to get full credit. So let's jump right in, and we're going to start, like I said, in Unit 4. And this particular question is 2011, number 2, and the context of it is political party registration. So here's what it says: the table below shows the political party registration by gender of all 500 registered voters in Franklin Township. And so what I see here is a 2-way table, and I notice that we've got male, female over here, and then if I look across the top, it looks like we've got the particular political parties. I guess the 3 of them: party W, X, and Y. And then also just to make sure that we know that this 2-way table has already calculated totals for us that we may need in order to solve some of the questions. So here's part A. Part A says, given that a randomly selected registered voter is a male, what's the probability that he is registered for party Y? Okay, this is a probability question, and it definitely sounds like a conditional probability because there is a given condition, and the given condition here is that the registered voter is a male. Now what that means is that this is really the only row that we need to look at, the row for male. So given that we are in that row, we want to know what the probability that he is registered for party Y. In probability notation, what we're looking for is the probability that the person selected is in party Y, given that they are male. Well, since we are given that they're male, we only look at that row, which means that the total here is out of 200. So that goes in the denominator. And then in the numerator, we want to know of those 200 males, how many are in party Y? Well, it looks to me like there are 48 that are in party Y. And if I plug that into my calculator, that's going to give me a value of 0.24. Okay, on to part B. Among the registered voters in Franklin Township, are the events is a male and is registered for party Y independent? Justify your answer based on the probabilities calculated from the table above. Okay, we want to know if these 2 events are independent. So you have to think about the meaning of independent. What that means is knowing whether or not the first event has occurred does not change the probability that the second event has occurred. Well, we've already done a little bit of work on this, right? We've already calculated the probability that the person is in party party Y given that they are a male. We did that in part A, and we know that's 0.24. So the natural question is, what if they weren't a male? What if they were a female? Would that change the probability that they're in party Y? So what we need to find out then is the probability that they're in party Y given that they're female. Well, we can calculate that. This is just another conditional probability, but this time the condition is that they are female. And so now my total is going to be out of 300. And of those 300 females, I can see that 120 are in party Y. So that's 120 out of 300, which is going to give me 0.40. Now very clearly I can see here that if I know that the person is a female, the chance that they are in party Y is increased quite a bit. It goes from 24% all the way up to 40%. In other words, knowing whether or not a person is male changes the probability that they are registered for party Y. This means that those two events are not independent. So let's make sure we answer the question here. The answer to the question is no, and then we need a good justification here. So I'm going to say because the probability of party Y given that they're a male does not equal the probability that they're in party Y given that they're female, these two events are not independent. Okay, so let's move on to part C here, and here's what it says. One way to display the data in the table is to use a segmented bar graph. The following segmented bar graph constructed from the data in the party registration Franklin Township table shows party registration distributions for males and female in Franklin Township. And so we see the distribution for females as well as the distribution for male. And actually I think I can see our calculations here. This party Y here is for the females, and that's the 40% that we calculated in part D, and then this is party Y for the males, and that's that probability that we calculated in part A. And because those two were not equal to each other, we said that those two events were not independent. Now the next part of the question says, in Lawrence Township, the proportion of all registered voters for parties W, X, and Y are the same as for Franklin Township, and party registration is independent of gender. So this is a different township, but in this township, the two events are independent. Complete the graph below to show the distribution of party registration by gender in Lawrence Township. Well, in order for these two events to be independent, then we know that the probability that they are in one of the parties, given that they're male or female, has to be the same. And so what we need to do then is we need to calculate the overall probability of being in each one of these parties up here. So I'm going to show my work down here, and what I'd like to find is the overall probability of being in party W. Well, if I look at my table up here, party W has a total of 88 out of the 500. So if we turn that into a proportion, 88 out of 500 is telling me that 0.176 are in party W. And if those two events are independent, that should be true whether they're male or female. It should be the same proportion that are in party Y. So down here in my segmented bar graph, I'm sorry, party W out there. We want party W to be 0.176. Well, maybe that's right about here. And I need that to be the same proportion for the females as it is for the males. So this little block in the segmented bar graph represents party W. And we're setting this up so that those two events are independent. Now we need to do the same thing for the other two parties. So let's find the probability of party X. If I go back to my table, party X has a total of 244, and it's still out of this 500 here. So I'm going to do 244 out of 500, and that's giving me a probability of 0.488. Now in order to draw that in the segmented bar graph, I actually need to know the total of these two. So the total of those two is 0.664, which would be, I don't know, about right here in the segmented bar graph. And so that means I can draw my next little breaker line there here, and then we can label this one as party X and this one as party X. And let's just go ahead and calculate that last probability, the probability of party Y. And if I look at my total up here, the party Y is 168 out of the 500. And if we turn that into a proportion, that's going to be 0.336, which we hope is what's being represented in this final little chunk here. Let's just go ahead and label that as party Y and party Y. And now, because these two conditional distributions look exactly the same, we can say that party registration is independent of gender. So that takes you through the model solution. What I'd like to do next is to talk through the rubric on how this would be graded. And just a quick review about how these rubrics work. The first thing that you need to know is what E, P, and I represent, because we're going to give each part an E, P, or an I based on the rubric. And what E represents is that you've done that problem essentially correct. P means that you've done that part of the problem partially correct. And then of course I means that it's incorrect. So we'll go through grading each section with an E, P, or an I. And then at the very end, we need to turn that into a score out of 4. All 3 response questions are worth 4 points. And so I will show you the way that you can convert that into a score out of 4 after we grade each part. Now this one has 3 parts. So let's start by looking at the rubric for part A. What you needed in order to get E for essentially correct on this one is you had to have the correct answer. But not only the correct answer, you have to also have your work shown here. So the correct answer is 0.24. The work that I've shown is just this fraction here. That is sufficient for showing work on a probability question. The probability notation that I've included here is not necessary for full credit. What is necessary is the correct answer and then this fraction representing the work. Now you could earn a partial credit if you gave a correct answer of 0.24, but you didn't show any work. That would be worth a partial credit. And anything less than that would be an I for incorrect. Okay, let's move down to part B and talk about how this one was graded. So I'm going to write the rubric down here. This is the grading for part B. So here's the important thing to know for this rubric. There are 3 different probabilities that could have been used in order to answer this question. We looked at the probability of party Y given that they are a male, and we compared that to the probability that they are party Y given that they're a female. The other probability that could have been used to compare to either one of those is just the overall probability of Y, which we did calculate down here at 0.336. So here's what's needed in order to get full credit here. You have to have 3 components in order to get an E. So let me tell you what each one of those 3 components is. The first component is to have the correct computation of 2 of the values. And it doesn't matter which 2 probabilities you chose of those 3, as long as you've chosen 2 of them and you've done the correct computation for those 2, then you get component 1. Component 2 is that you have to state the 2 probabilities are not equal. So somewhere in your solution, you have to state that those 2 probabilities are not equal. We did that right here. So we have our 2 probabilities calculated, and then we've stated that they are not equal. And then the final thing, component number 3, is the conclusion, where you're going to have to conclude that they are not independent. And we did that sort of a couple different ways. We said no first, but then we made it very clear that those 2 events are not independent. So you have to have all 3 of those components in order to get an essentially correct. For partially correct here, you got to have 2 of the 3 components. Anything less than 2 components, and you're going to be stuck with an I for incorrect. Okay, and let's move down to the last part here. This is part C, and let's talk about the grading for part C. In order to get an E on part C, you have to show that the 2 distributions are the same. So it has to be the same distribution for males and females. And there are 2 components, right? So component number 1 is you have to have the correct proportion. And you can see those proportions here where we've calculated them, but you can also see them in the segmented bar graph, which matches the values that we calculated by hand. So we do have the correct proportions there. And then the second thing that you have to have is the correct labels on the segmented bar graph. So party W, X, and Y must be labeled in the segmented bar graph there. Now, partially correct would be if you showed that they are the same distribution for males and females, and then you just had one of the 2 components. So maybe you forgot the labels, and that would drop you down to a partially correct on that. So you have 3 different parts that you graded, each one with an E, P, or an I. And here's the rubric for turning that into a score out of 4. Pretty standard rubric here. You can see if you got all 3 parts essentially correct, that's what you need in order to earn a 4. A 3 would be 2 parts essentially correct and 1 part partially correct. And then there are several different ways of getting a 2 and a couple of different ways of getting a 1. Now, it is also possible to get a 0 if you don't meet any of the criteria. Okay, onward. Let's move on to free response number 2 for today, also from Unit 4. One of my favorite questions here, one that I often give my students on a chapter test. It says here, a local arcade is hosting a tournament in which contestants play an arcade game with possible scores ranging from 0 to 20. The arcade has set up multiple game tables so that all contestants can play the game at the same time. Thus, contestant scores are independent. I'm guessing that they're probably going to become important later. Each contestant's score will be recorded as he or she finishes, and the contestant with the high score is the winner. After practicing the game many times, Josephine, one of the contestants, has established the probability distribution shown in the table. Crystal, another contestant, has also practiced many times. The probability distribution for her scores are shown in the table below. Part A, calculate the expected score for each player. Okay, well, I'm going to start by calculating the expected score for Josephine. What we have here, we have Josephine's distribution. We could think of this as being a random variable X, and then this as being the probability of each one of those values. And we know that we can calculate the mean, and I'm going to call it mean of J, by just taking the sum of all of the X value and multiplying them by their respective probability. So in this case, we take each X value, like 16, and we multiply it by its probability, plus the second X value, 17, multiplied by its probability, and the third, and the fourth, and you type that into your calculator, and you're going to get an average value or an expected score of 17.7 for Josephine. Now let's do the same thing for Crystal. So for Crystal, it's going to be the mean of, I'm going to use a subscript of C here for Crystal, and we're just going to take each value and multiply it by its respective probability and then add those up. We only got 3 values to work with here. And sure enough, you plug this into your calculator and you're going to get exactly the same expected value for Crystal. So to start out, it appears that these two players are equally good at this particular arcade game, right? They have the same expected value or expected score. All right, let's move on to part B. Part B says, suppose that Josephine scores 16 and Crystal scores 17. The difference, Josephine minus Crystal, of their scores is -1. List all combinations of possible scores for Josephine and Crystal. It will produce a difference of -1 and calculate the probability for each combination. Okay, they've already given us one here in the problem. They said if Josephine scores a 16 and Crystal scores a 17, then we would get a difference of -1. Well, we need to calculate the probability of that. So what I'm looking for here is the probability that J is 16 and C is equal to 17. So this is an AND problem where we would think about multiplying probabilities. And they actually told us in the problem that their scores are independent of each other. So we just need to simply multiply the probability. So the probability that Josephine gets a 16 is 0.10 and the probability that Crystal gets a 17 is 0.45. So this is just going to be 0.10 multiplied by 0.45, which is going to give me 0.045. Now that is not the only way of getting a difference of -1. One of the other ways we could get a difference of -1 is if Josephine has a 17 and Crystal has an 18. 17 minus 18 would give me a difference of -1. So we need to calculate the probability that Josephine gets a 17 and that Crystal gets an 18 by just stealing those numbers from the probability distribution. So that's going to be 0.30 multiplied by 0.40, which is going to give me 0.12. And there's one more possibility. That would be if Josephine scored an 18 and Crystal scored a 19. So the probability that Josephine gets 18 and Crystal gets a 19 equals, let's see, 0.40 multiplied by 0.15, and that's going to give me 0.06. And I think those are the only ways that we can end up with a difference of -1. All right, so let's move on to the next part. Part C. Find the probability that the difference Josephine minus Crystal, their scores, is -1. Well, we just did a whole bunch of work on that. They want us to find the overall probability that Josephine minus Crystal is going to equal -1. Well, we know there's 3 different ways that this could happen. It could be this, or this, or this. Because I'm using or here, that means I need to add the probabilities, also noting that they are mutually exclusive. So we're just simply going to take those 3 values that we calculated in the previous question, and we're going to add those 3 together. And that's going to give me a value of 0.225. Okay, on part D. The table below lists all the possible differences in the scores between Josephine and Crystal and some of their associated probabilities. Complete the table and calculate the probability that Crystal's score will be higher than Josephine's score. Okay, they provided most of the values for us here, but there's 2 that we need to calculate, and that's the probability that Josephine, so we're trying to do Josephine minus Crystal, -2 and -1. Well, hold up here. We just finished calculating the probability that the difference is -1. All I need to do now is to copy that value down, right? So here's a little AP exam tip. If for some reason you were really stuck on part C and you had no clue, you could just make up a value that's reasonable and carry that value down into the next part and still get credit for part D. But I think we have the right answer here, 0.225. Now to get that remaining value in the table there, we have to note that adding all of those probabilities, we should get a value of 1. And so if I add up all those probabilities and I subtract them from 1, I'm going to get a value of 0.085. And now all of those probabilities will in fact add up to 1. And now we answer the final question. Complete the table and calculate the probability that Crystal's score will be higher than Josephine's score. Okay, we want Crystal's score to be higher. Well, if that second number is higher, when I subtract J minus C, I'm going to get a negative value. So what I'm really looking for here is the probability that J minus C is negative or less than 0. Well, looking at my possibilities here, negative values, I could get a difference of -3 or -2 or -1. Those are the 3 possibilities. They are all mutually exclusive, so we simply need to add those 3 probabilities together. 0.015 plus 0.085 plus 0.225 gives me a final answer of 0.325. So remember, at the beginning of the problem, we thought that these players might be equally likely to win this game because they had the same expected value, but it turns out that the probability that Crystal's score will be higher, that Crystal will win, is 0.325. Okay, now let's talk about how this one's going to be graded. And this one works just a little bit different than the previous problem that we talked about in the way that it breaks down. For the grading, we're going to call these sections. Section 1 is part A. Section 2 includes part B and part C. This is section 2. And then the third section includes all of the parts of part D there. This is section 3. For each one of the 3 sections, we are going to give a grade of E, P, or I. So let's talk about what's needed in order to get an E, P, or an I on each one of these. So let's start with how we grade section 1, which is part A. In order to get section 1 correct here, in order to get an essentially correct, you have to have the correct mean for both and work shown for at least one. So you don't have to have shown for both of them. You only have to have work shown for at least one. And when I say work shown, it could be the actual calculation with the numbers, which is like what we showed here, or you could show a formula that counts as your work shown. Now, partially correct would be if you made like a little bit of a mistake. One of the mistakes that students often make is that they round expected values. You do not want to round expected values or mean. You can leave that as a decimal. It should stay 17.7, not 18. And then one of the other errors that students sometimes would make on this problem is if they only calculated one of the expected values. So those are a couple of different ways that you can end up with a partially correct. Anything else would be an I for incorrect. Now let's move down to section 2 and talk about what's needed for full credit in section 2. So here's what you need in order to get an essentially correct. And this is a pretty long list here. There are 5 components that are needed for full credit here. So let's talk about these 5 components. Component number 1 is that you have to have listed all combos to get a difference of -1. Well, that's what we did here. There were 3 different combinations that would give you a difference of -1. Component 2 is that you have to have the correct answers for part D. And there were 3 answers for part D. This one, and this one. So that's component 2. Component 3 is that you have to show your work for part D. Well, showing the work is showing this multiplication that's happening here and here and here. So we do get credit for component 3. Component 4 is to have the correct answer for part C. Well, the correct answer for part C was this right here, 0.225. And you can probably guess what's coming next for number 5. You have to show your work for part C. Well, showing the work in part C is showing that you are adding those 3 probabilities. So hopefully you're getting the message here that showing your work on your probability questions is very important. So you gotta have all 5 of those components in order to get an essentially correct. Partially correct if you have 4 of the 5 components. Anything less than 4 components, you are stuck with an I on this one. And let's get to section 3, the very last part here. Talk about how we would grade section 3. So in order to get an essentially correct, there are 2 components that are needed. First of all, you have to have the correct values in the table. And there were 2 of them, right? This value and this value have to be correct for component 1. And then number 2 is to have the correct final answer and shows work. So the correct final answer is here, showing the work is here. You have to have both of those in order to get component 2. And if you have both components, that gives you an E essentially correct. Partially correct would be if you had 1 of the 2 components. So we have graded this in 3 sections, each one giving an E, P, or an I. And then you would take that now and let's look at the rubric, which is going to look very similar to the one that we looked at before. In order to get a 4 here, of course, you got to have all 3 parts essentially correct. 2 parts essentially correct and 1 partial would give you a 3. Several different ways to get a 2, and then a couple of different ways to get a 1. Also remembering that you can in fact earn a 0 if you have less than what is established here. Okay, we have one final remaining FRQ for today, and it is from Unit 5 on sampling distributions. This is question 2014, number 3, context of which is 6 days. So here we go. It says schools in a certain state receive funding based on the number of students who attend the school. To determine the number of students who attend the school, one school day is selected at random. One school day is selected at random, and the number of students in attendance that day is counted and used for funding purposes. The daily number of absences at high school A in the state is approximately normally distributed with a mean of 120 and a standard deviation of 10.5 students. Part A. If more than 140 students are absent on the day the attendance count is taken for funding purposes, the school will lose some of its state funding in the subsequent year. Approximately what is the probability that high school A will lose some state funding? Okay, this is a very classic normal distribution calculation problem that hopefully you are comfortable with. I would always suggest that you start with a picture, and here's the picture of my normal distribution, and I always label it as capital N for normal, and then identify the mean and the standard deviation, which we know is 120 and 10.5. And I want to make a special note here that this particular distribution is the population distribution. All of the possible days, and we are going to choose one of those possible days out of the population distribution. So the thing that we're trying to find here is we are trying to find the probability of 140 or greater. Well, let's make note that the center of this value is 120. That's the mean. And what we are looking for is 140 or greater. So I'm going to shade that in red. We are looking for that probability. Well, hopefully you feel pretty comfortable with area under a normal distribution. I'm going to use a z-score here. And in order to turn that 140 into a z-score, I need to subtract the mean and divide by the standard deviation, which is going to give me a z-score of 1.90, meaning that 140 is 1.90 standard deviation above the mean. And we should be able to now turn that into an area. Now, we need a table A for that, which of course will be given to you in your formula sheet in tables. Here's my table A. The z-score was 1.90, 1.90. Gives me this value for an area, 0.9713. So let me go back, 0.9713. But remember, table A tells you the area to the left. We're looking for the area to the right. So I need to do 1 minus that value. And that's going to give me a final answer of 0.0287. Now, some of you may have been trained or familiar with calculator function, which will do the same thing for you. So let me make note of that. The calculator function is normal CDF. If you were using this as work shown, you need to make sure that you clearly identify your input. So 140 up to some very, very large value with a mean of 120 and a standard deviation of 10.5. I'm going to label each one of those: lower bound, upper bound, mean, standard deviation. And the calculator is going to give you almost exactly the same answer here. 0.0284 would be the calculator answer. All right, let's move on to part B. The principles association in the state suggests that instead of choosing one day at random, the state should choose 3 days at random. With the suggested plan, high school A would lose some of its state funding in the subsequent year if the mean number of students for the 3 days is greater than 140. Would high school A be more likely, less likely, or equally likely to lose funding using the suggested plan compared to the plan in part A? So now instead of picking one day out of all the days, we're going to pick 3 of the days at random and find the average of those 3. So listen, this is a different distribution than the one that we drew above. This is now a sampling distribution of the sample mean. And we know that the sampling distribution should be less variable than the population distribution. So I'm going to draw a little bit skinnier there. Clearly identified as normal. And it will have the same mean as the population distribution, but the standard deviation is no longer 10.5. It is going to be 10.5 over the square root of n, which in this case is 3. So just in case you wanted to know, that gives us a standard deviation of about 6.06. So the difference between this distribution and the one above it is that now we are looking at the sampling distribution of the sample mean x bar. Now we still want to know the probability of getting that 140 or greater. So we're looking for that area as our probability. We're going to go through the same steps as I did just above. We're going to calculate the z-score, but of course the z-score is going to be different now because my standard deviation is now 10.5 over the square root of 3. I'm going to get a z-score of 3.30, which means now we are 3.30 standard deviations above the mean, much farther above the mean, which I think means we're going to get an area that is much smaller. So let's go ahead and turn this into an area. Well, we're going to have to go back to our table here, and we need 3.30 at the time. So let's see, 3.30 is 0.9995. Once again, we subtract that from 1, and that is going to give me a very small area here of 0.005 as a final answer. Now, very important here, we need to make sure that we answer the question being asked, which is we want to know if it's more likely, less likely, or equally likely to lose the funding. Well, this probability we got here is much, much smaller. So we want to make it very clear here that the answer is less likely. And let's make sure we give a good justification here, because the probability that we just calculated, 0.005, is much less than the probability we calculated in part A, 0.0287. All right, and let's move into part C, which says a typical school week consists of the days Monday, Tuesday, Wednesday, Thursday, and Friday. The principal at high school A believes that the number of absences tends to be greater on Mondays and Fridays, and there is a concern that the school will lose state funding if the attendance count occurs on a Monday or Friday. If one school day is chosen at random from each of the 3 typical school weeks, what's the probability that none of the 3 days is Tuesday, Wednesday, or Thursday? So we want to know the probability that none of the 3 days chosen are Tuesday, Wednesday, or Thursday. Well, what that really means is that the first day that is selected is not Tuesday, Wednesday, or Thursday, and the second one selected is not, and the third one selected is not. Well, this is an and problem, and we can say that each of these days is independent, so we need to just multiply probability. So the probability that the first day is not Tuesday, Wednesday, or Thursday, well, that leaves me with only 2 days out of 5, right? Monday and Friday. And then that second being not Tuesday, Wednesday, or Thursday, of course, is going to be the same, and the third is the same. And because they're independent, we can multiply those 3 probabilities, and that's going to give me an answer of 0.064. So that takes care of our model solution. Let's now move to the rubric that's used to grade it. Pretty straightforward here. 3 parts, part A, B, and C. Each one has its own rubric for giving an EP or an I. So let's start with part A. In order to get a full credit E in part A, there are 3 components. Component number 1 is that the student has to clearly identify that they're using a normal distribution, and then also identify the parameter, which would be the mean and the standard deviation. Now we've done that in a couple of different ways. Right here, we actually took care of everything. We've got the normal distribution, and then we have our 2 parameters. The other way that students can get credit, if they're calculating a z-score and they have clearly shown where they put in the mean and the standard deviation, that would also give them credit for component 1. And even if they use the calculator function, here's your normal, here's your 2 parameters, so they still get credit for component 1. Component 2 is to clearly establish what they call the boundary value. Well, the boundary value is this value right here, 140, which you see here and here, also shown in the calculator function. And then of course the third is you gotta have a correct answer on this one, and either the answer from table A or the answer from the calculator would be acceptable as a correct answer. All 3 components get you an E for this one. For a partial, you got 2 of the 3 components. Okay, let's move to part B. In order to get an essentially correct in part B, well, first of all, you have to clearly say or answer the question. Right? The answer to the question is to say less likely, and you have to have the following 2 components. Component number 1 is you have to have calculated the correct probability, and the correct probability here is the 0.005. And then number 2, you have to compare this probability to the probability in part A. Well, that's what we've done right here by making the comparative statement that that value is less than the value calculated in part A. Now, partial credit on this one is if you missed component 2. Now, there was another way described in the rubric in order to get full credit here on part B that had 3 components. Number 1, somewhere you had to clearly identify that this is the sampling distribution for sample means as opposed to the population distribution. 2, you had to say that the mean is the same as the mean of the population at 120. And 3, you had to say that the standard deviation of the sampling distribution is less. That was the other way that you could get full credit without actually doing the whole calculation. You could have just explained in words what's going on in it. And then the third part, part C here. In order to get an essentially correct, pretty straightforward here, you gotta have the correct answer. And guess what? Shows work. We're definitely seeing this trend amongst the probability question. So this, of course, would count as showing our work, and this would be our correct answer. Partially correct is if you have the correct answer and no work. There is one other way you could get a partial credit. If you use the multiplication rule like we did here, but maybe you had the wrong probability there, at least you understood that you're supposed to use a multiplication rule here, and you could still earn a partial credit. So we got our 3 components there, our 3 parts that we graded E, P, or I. We need to now convert that into a score out of 4, and I think that this rubric is going to look very similar to the first 2. All 3 parts essentially correct for a 4, 2 parts essentially correct, and 1 part partial for a 3, and then several different ways of getting a 2, a couple different ways of getting a 1, and even a possibility of getting 0. So that was pretty quick. We hustled through 3 FRQs along with the rubrics for those 3 FRQs. Listen, I hope that that was beneficial for you to see how those are going to be graded by the graders. If this was beneficial to you, please give me a thumbs up there in YouTube. It is Friday, so I wish you all a happy weekend. We will be back again on Monday, and I look forward to seeing you all next week.
So good afternoon, AP Stats kids. Monday the 27th. Hope everyone had a good weekend. Hope everyone is safe and healthy at home. We actually have 2 more weeks of this. So originally we were going to end on May 1st, which is this Friday, and Luke and I had planned on this week being sort of prep for AP exam review, those types of things. But the College Board decided to add another week, and that was based upon when the actual AP exams are. So this week we're going to pretty much do, for all intents and purposes, review for this year's modified exam. Now tomorrow Luke had originally scheduled, which has been changed. So if you haven't seen all the changes on YouTube or AP Central, I just want to let you know sort of verbally. Tomorrow was originally going to be know your calculator and what buttons and what's the best features and functions to use. That's changed because the decision this year is to make the exam sort of calculator neutral, for lack of a better term. You can and should use your calculators. If you have one, that's great. If you don't have one, the exam's going to be written this year so that the calculator probably won't give you any advantage at all. So sort of calculator neutral. So then we decided, well, if the exam's going to be relatively calculator neutral this year, I'm looking to do another session on p-value, and is that currently the best method to make decisions in the real world? And so kind of an interesting little topic tomorrow, perhaps a little bit different. Then a week from today, and we're still sort of designing as we move, so it's not 100% finalized, but a week from today, we're actually going to have you do two problems sort of in class. So on Monday, you'll do the 25-minute FRQ with Luke, and then on Tuesday, he'll walk through the answers with you. A week from Wednesday, you'll do the 15-minute FRQ with myself, and then Thursday, I will go through the answers with you. And then next Friday would be kind of the May 8th would be kind of wrap up, and Luke and I want to kind of wish you all good luck, and thanks for listening in, and some of the lessons we learned, some of the things we did well. well, and perhaps some of the things we didn't do as well. So stay tuned for that. That's coming next week. We actually want you to pretty much go through a mock exam, perhaps no different than you would do in your classrooms if we were all back at school. And for most of us, I don't think that's going to happen. So anyways, welcome back. Hope everyone is safe and healthy. Give me a second here to get my PowerPoint and we'll get rolling today. So again, welcome back. My name is Brendan Murphy and I teach at John Baptist Memorial High School in Bangor, Maine. Very interesting school, great place to work. And I miss my kids. You probably miss your friends and your teachers. Luke Wilcox teaches at East Kentward High School in Michigan. And probably hopefully you've seen both of us. So hopefully that's hopefully we've helped. Here's the homework that Luke assigned on Friday. So based upon records kept at a gas station, the distributions of gallons of gas purchased by customers is skewed to the right with a mean of 10 gallons and a standard deviation of 4 gallons. So I think I would draw a quick sketch maybe down below. But again, this is a multiple choice and this year's exam is going to be all free response. But Luke and I still feel this is real important concepts that we can address in a multiple choice, even though this year's exam will be all FRQs. And this year's exam is different, it's modified. I don't know exactly what's on the exam, nor does Luke. It will be different. And so perhaps it could be, parts A, B, C, D, E, F or something. And maybe one or two of them feels a little bit more like a multiple choice question. But again, total speculation on my part, so let's not go anywhere with that. So a random sample of 64 customer receipts was selected and the sample mean number of gallons was recorded. So I'm taking a sample size of 64, so N is 64. That's pretty good sample size and I can live with that. I'm pretty happy about that. Suppose the process of selecting a random sample of 64 receipts and recording the sample mean number of gallons was repeated for 100 samples. So I'm taking a random sample of 64, I'm finding the mean, I'm doing that 100 different times. So I'm clearly not doing a full-blown sampling distribution. I don't know that for a fact because I don't know how big the population is, but I don't think I'm doing a full-blown sampling distribution here. But it feels like I'm starting the process of trying to do a sampling distribution. Which of the following is the best description of a dot plot created from the 100 sample means? So I'm just going to go to my document camera here. Okay, same problem. So I can say what, skewed to the right, so it may look something like that. I guess I don't know. And we know the mean is 10. Well, if I take 100 samples of size 64, the central limit theorem says that the shape of my sampling distributions of a sample means will become more and more approximately normally distributed as my sample size gets larger and larger. So I'm feeling that the shape of my sampling distribution, well, in this case, the dot plot, right? Same thing, will be approximately normally distributed. So I canceled out that one, and that one, and that one. So those three, I felt pretty confident that I could get rid of those relatively quickly. So the dot plot is approximately normal with 10 gallons and a standard deviation of 0.5 gallons. So I'm going to figure out that. I'm going to figure out the standard deviation of the sampling distribution based upon my sample size or using my sample size. And E here, the dot plot is approximately normal with a mean of 10 gallons and a standard deviation of 0.4 gallons. So the difference here was, which one of those is correct? So I said the standard deviation of all my sample means would be 4, which was the standard deviation that I had started with, 4 gallons, over the square root of n, and n we said was 64. So I said 4 over 8, or 1/2. I got the answer D here. And that's really a nice problem. And my students, I've given them something similar to this in the past. And I think what they always say to me is, Mr. Murphy, we have the 64 and we have the 100 here, and they don't know what's what. They don't know which one's the sample size and which one's how often we repeat it and those types of things. So I really like this problem that Luke picked and hits upon a pretty important concept. So hope that helped. We'll get back to my PowerPoint here. And so the goal of today is to go through 2 free response questions. Hopefully I have enough time, and actually then grade some student papers. So I'm going to, I guess, make you AP readers. Not really, but talk a little bit about the reading, what happens, how we grade your papers, what goes into it, what happens if you do this. And the goal was Luke and I really wanted you to see how easy it is to perhaps lose a point or lose some points by imprecise wording, or perhaps on the flip side, sometimes how easy it is to get the point or how easy it is to get context in or something like that. So I'm going to do 2 free response questions, and we'll look at some student samples. We'll grade those, where we'll become AP readers, and hopefully you can get some benefit out of it. I like to do this with my students as we get closer and closer to the AP exam every year. A lot of AP teachers do the same thing. So again, here's some links to updated info. We talked about it, so for the sake of time, we'll move on. So the AP reading, each year about 700 to 800 high school and college professors, get together in June to grade all of your AP exams. We've been reading in Kansas City the last few years. This year is going to be a virtual reading. We're not going to Kansas City. Many of us are a little disappointed with that, although clearly the right decision by the College Board. But it's kind of a fun week. So the College Board likes to have a 50-50 split between high school and college professors. So at the reading, I have a partner all week. He and I, or she and I, will work together. And almost always my partner is a college professor because I'm a high school teacher. And we've been a great week together. We work really hard. We have some fun. And we're constantly talking back and forth about, how do we grade this? So we want to make sure that we're giving all students the points that they've earned. We can't give you points. You earn them. I tell my students. I can't mark it wrong or right until I fully understand 100%. And at times I'm confused and I talk to my partner and vice versa. So very collaborative week. This is some of the best professional development that high school teachers can go to. And many of us enjoy this week year after year after year. I have what I call my reading friends. I might see them literally once a year at the reading, and we have a lot of fun. So maybe your teachers are readers. If so, great. Have look up Luke and I. If not, maybe mention to your teachers, hey, Mr. Murphy said the reading's kind of fun. Maybe you can become a reader. We're always looking for new readers. We work hard all day, but there are plenty of fun things to do at night. And it's one of the best weeks of the year for many of us. We really enjoy it. My wife thinks it's a little weird. My students definitely think it's weird that I want to go grade papers for a week. And that doesn't sound fun at all, but it really is. We have a good time. We work really hard. And so this year's reading will be virtual. We'll be reading at home this year. Maybe one of your teachers is a reader. Luke and I have worked with them in the past. Who knows? So this is what we call a pre-reading phase. And the leadership team actually uses randomly sampling. You guys would understand that. Student papers. And we're basically trying to see how our scoring guidelines are working. So we've come up with the problems, and the test development committee has come up with scoring guidelines. And we don't really know how they're going to work until we start grading student papers. So we actually start randomly sampling papers, and we want to see how well the scoring guidelines are working. There's many good discussions, back and forth, debates. At times we need to make tweaks to the scoring guidelines, or as we like to say, the what if game. What if a student wrote this? Would this be enough to earn full credit? Or what if a student did this? How are we going to handle this? So the pre-reading is designed to see how well the scoring guidelines are working. The readers show up usually on day 4 or 5, and the readers get trained for 3 to 4 hours before they actually read any student papers. So it's a very intensive, long, very detailed training before we actually sit down, grab a student's paper, read it, and come up with a score. So good training could be 3 to 4 hours. We talked about partners. Readers are encouraged to work with their partners all week. Usually high school teachers get paired with college professors. We ask each other's questions. We resolve issues, discuss the scoring guidelines. Readers must follow the scoring guidelines. So it's not how I would grade it in my classroom. It's not what I would want to do. It's I follow that scoring guidelines. And my job as a reader is to make sure that I'm scoring consistently from day 1 all the way to day 7. Very complicated process. I'm just giving you the tip of the iceberg, but it works. And it's really cool to see it all come together on day 7. Each grading room has 2 what we call table leaders. These table leaders act as kind of quality control. They make sure that the readers are following the scoring guidelines. Table leaders also answer questions from readers on student responses that are perhaps a bit hard to score. No matter what we do in that 3 to 4 hour training, we're going to run up on student papers that are just we haven't seen anything, and how do we handle it? So very collaborative process for the whole week. And there are times where we might spend 10 minutes on one student paper for 1 point. I mean, we really will spend the time needed to make sure that you're getting all the points that you've earned. And today, I think you'll see how easy it is sometimes to get those points, and perhaps sometimes how easy it is to lose those points. So I found 2 free response questions that I've used in the past, and there's some good student samples that we'll practice. So this is from the 2005 exam. Some boxes of a certain brand of cereal include a voucher for free video rental inside the box. It'll toy on the bottom. The company that makes the cereal claims that a voucher can be found in 20% of the boxes. So when I see the word claim, I I think I know I'm leaning maybe towards the hypothesis test, but let's keep reading. However, based on their experience eating this cereal at home, a group of students believes that the proportion of boxes with vouchers is less than 20%. Right now, I know it's a one-sided test. We don't do one-sided confidence intervals, so it's probably a hypothesis test. But let's keep reading, and then I'll ask my 4 questions like I always do. This group of students purchased 65 boxes of the cereal to investigate the company's claims. That's my sample size. Students found a total of 11 vouchers for free video rentals in the 65 boxes. So p hat's going to be 11 over 65. Suppose it is reasonable to assume that the 65 boxes purchased by the students are a random sample of all boxes. I always like that random of the cereal. Based on this sample, is there support for the students' belief that the proportion of boxes with vouchers is less than 20%? Provide statistical evidence to support your answer. So hopefully by now you're seeing that this can't be a yes/no. This has to be a full-blown inference problem. And I'm going to walk through all of the different steps real quick, and then I'm going to ask you to become AP readers. So I asked my 4 questions. Does this feel like a hypothesis test or a confidence interval? I was pretty confident, no pun intended, that it was a hypothesis test. We have 1 or 2 samples, but we have 1 sample. We're dealing with means of proportions. We're dealing with proportions. And so I would read a Z-table or T-table based upon that. So I labeled this test a 1 sample hypothesis test with proportions. There's plenty of other ways you can identify this test, but that's the language that I've used with my students, and it seems to make sense. If I do that, then when I get down to the math mechanics part, I do not need to write the formulas. I think when we do the student papers, you're actually going to see that all of them or most of them do that, but you don't have to. So I'm going to do my null hypothesis first. That would logically be my first step. You'll see when we grade student papers that that's not always what students do, and that's okay. So I said my null hypothesis P is equal to 0.2. My alternative is P is less than 0.2, and I got that from the wording up here. I just want to identify the parameter, so I said P equals the proportion of all boxes of this brand of cereal that contain a voucher. When we go to student papers, that year this was not needed, but I'm going to say keep doing it, and I think rubrics have changed over the years. I'm going to say that please keep doing that. This year in 2005, students didn't have to have that, but I'm going to say take my neck out a little bit and say we want you to do that moving forward. So I need to check my conditions and assumptions. So over here I said P hat was 11 over 65 or 0.169. Well, that is a little bit less than the 0.2 that the manufacturer claims. Is that enough? And I just don't know. I need to run the test. So the data was randomly selected as stated in the stem of the problem. So that's always good. That randomness there is nice. I want to make sure the population is greater than 10 times my sample size. So is the population greater than 10 times 65? The population of cereal boxes greater than 650. I guess that's an assumption. I have no way of proving that. I don't know by reading this problem. So I said, the population is probably greater than 650 cereal boxes. That's a reasonable assumption. How many boxes of cereal does General Mills make in a day? I have no idea, but it's probably more than 650. NP greater than 10 and N1 minus P or NQ depending upon how your book does it. So I said 65 times 0.2 is 13, and that's greater than 10. Down here I said 65 times 0.8 is 52. Both of those greater than 10. We need to see that math. We need you to see that you plug in those numbers. You just can't put a check in, say greater than 10. So it feels like we're okay with the conditions and assumptions. Since I named the test up here, I don't need this formula down here, but I figured I would do it anyway. So I just said my Z is equal to my sample statistic minus my population parameter over my standard error. Did some quick math, and I said my Z score is negative 0.62. I went to the calculator and said what's the probability that Z is less than minus 0.62. So I got a p-value of 0.2676. That's pretty big, and so I don't think the evidence is strong enough. So my conclusion again, my first, if you sat through any of my sessions when I was doing inference, my first sentence is maybe a little generic, but since our p-value of 0.2676 is greater than our assumed significance level alpha is 0.05, we failed to reject the null hypothesis. That's every time I do a hypothesis, that's basically my first sentence. Notice I had no context in there. So my second sentence tries to get that in there. So the data does not provide convincing evidence to support the student's belief that the proportion of cereal boxes with vouchers is less than 20%. I haven't proved anything. It's not an experiment. The evidence doesn't lead me to believe that the evidence isn't strong enough for me to refute the manufacturer's claim. So now let's look at some student papers. And before we do that, here's the official College Board scoring rubric. For the sake of time, I won't walk through everything here, but this is sort of what a reader is going to be looking at. That much more detail, but that's pretty much what we're going to look at. This is how we're going to grade your papers. And again, I need to follow scoring guidelines, not do what I want to do. I think Luke, I watched him the other day a little bit. He talked about typically we grade things. Each part of a problem we grade EPI, essentially correct. Doesn't have to be perfect, partially correct, incomplete or incorrect here. And so for each of those 4 components, we're going to walk through a student's paper and give them an EPI, EP or I. Sorry. So the first thing I look for is sort of the name of the test. So the student here says I will do a proportion Z test. Okay, different how I would say it, but nothing wrong with that. I'm okay with that. Up here that looks like P hat, and then the student actually looks like they're doing the standard error or something here. Spec 0.2. I don't really know, like specification maybe. I don't know exactly what that is. Looks like they're doing the assumptions first, which is not wrong. I wouldn't do it that way, but that's okay. But down here there's a box, and so the student does say HOP is 0.2, HAP is less than 0.2. That year we did not ask students to define the parameter, so I'm going to give the student an E for that first component. Have they correctly done the null and alternative hypothesis? So students earn an E. Generally, an E is worth a point, P is worth half a point, and I is worth no points. We're simplifying again, but generally that's sort of the rule. But I'm not going to get into all the nuances of the reading here for the sake of time. Look at the student's conditions. Assume the sample of boxes is an unbiased estimator of the true proportion. Assume that the population is greater than 10N. Population, yes, that's okay. That's good. Here's my NP check. Here's my N1 minus P check. Student plugs in the numbers. That's good. Student does not talk about it being randomly selected. The old rule way back when was if it was in the problem not to repeat it, but follow the new rules. The new rules we would want to see the student do that. But this year in 2005, that's the student met all those requirements. So I'm going to give him a second E for those assumptions and conditions. Again, I really want to see that random, and please put that. That looks like a student's drawn a normal curve, way better than my normal curve, so good for the student. Z test stat equals stat minus statistic minus parameter over standard error. Not needed because the student named the test, but it's not wrong. I see where the student plugs in the numbers. I see the student got the same Z score minus 0.6210 that I got, so that's good. What's the probability that P hat is less than 0.1692? Is the probability that Z is less than minus 0.620? Student is actually giving me sort of the calculator speed. That's not really needed, but it's not really wrong. And students done a really good job of telling me where they're getting all those numbers. The student basically got the same p-value that I did, so we're good there. So for that third piece, what I call math mechanics, I'll give the student an E. And then down here, I'm hoping this is kind of their conclusion, in context, what decision are they going to make? Assuming the proportion of vouchers found in boxes is 0.2, there's a 0.2673 chance of getting a sample with a proportion more extreme than 0.1692. Okay, different than how I phrase it, but I can live with that. Again, that 0.1692 was just my p hat. Large P failed to reject the null. Again, I probably would have tied that into, my alpha is 0.05, but that's a pretty high p-value, pretty large p-value. We're not going to reject very often. It's got a p-value that big. There's insufficient evidence to claim that the proportion of boxes with vouchers. I actually always put a U there, and at first I said futures, but vouchers, that's fine. I'm pretty messy, so I'm not going to worry about the students writing. The proportion of boxes with vouchers is less than 20%. That's a pretty good conclusion, different than mine, clearly different than mine. This student earned an E. The readers will get pretty good with that after a couple days. That student earned 4 out of 4 points. Is it perfect? No. Is it pretty good? Yes. Very good paper. We read thousands. This student really understands it. I think it's done a pretty good job. Very clear, easy to read. I'm good with that student. So that student earned 4 out of 4 that year. Okay, here's the next student. If I say, the student should have done this or that, I'm not making fun of these students. please. That's not the intent. These students work really hard. You work really hard. So this is just an educational exercise. I'm not making fun of these students. I should have said that earlier. So hopefully that was clear. The student is circling lots of good things up here. I actually tell my students to do the same thing, so that's good. One proportion test. That's weaker. I don't love it, but it's okay, and I think I know where the student is going to go with it. If the student correctly names the test, they do not have to write the formula. Well, this student does a pretty good job with the formula there, so that was good. I was not 100% comfortable with this. Maybe a nice recovery here. So HL and HA, student has it. So that's an 8. Again, really simple. If that was down here at the bottom of the paper, I still have to read it. So it doesn't matter where it is in your paper. The readers have to read your whole paper. Look at there's something written up here, down the side. I have to read it. I cannot. So I fully understand what the student's trying to say. I can't either give you points or take points away. So the student does a great job here. I'll give you an E for that. Let's look at their assumptions. Student says it's a random sample. Okay, that's good. Population is sufficiently large. Again, years ago we were maybe not as strict as we are today. I think today we would have wanted to see population is greater than 10 and with numbers plugged in. But the student is saying probably more than 650 serial boxes, and so we're pretty good there. I'll give my NP and Q checks or NP and N1 minus P checks. Student plugs in the numbers, both greater than 10. Student earned an E that year for the assumptions and conditions. Pretty good job here. Again, I would like to see this. I think today we would want students to do that and plug in the numbers. But this was 15 years ago, and rubrics change over time. So up here it looks like student is just doing P hat, does the math for me. Here's the math mechanics. There's your formula. Student plugs in the numbers, comes up with a Z-score, minus 0.6202. That's the same one I got. Circles the P-value, didn't copy very well. Gets the same P-value, 0.2676 that I got. Give me student's doing great. E, parts A, B, and C. Therefore, we fail to reject the null hypothesis. Okay, I agree with that. The proportion of boxes with vouchers is equal to 0.2. That I don't like. We can't make that definitive of a statement. I haven't proved anything. This is an experiment. There's no causation. The evidence is not strong enough for me to reject the null, but I definitely can't say that the null is true. So the student actually gets an I here. I can fix this with one or two words. This is just too definitive, too strong for us. The proportion of boxes with vouchers is definitely equal to 0.2. I added the definitely there to make it a little bit stronger, but that student understands the problem. They've done a great job here, and literally they're one or two words away from getting an E here. And so this student only got 3 out of 4 points that year. And at times we feel bad for the students when we're grading. One or two words, if they had changed, they probably could have gotten another point or two, but we just felt that was just too strong. That's really not what's happening in the hypothesis test. I can't say that the null is definitely exactly equal to whatever. So third student here, again, hopefully you guys are getting the hang of this from being a reader. You can tell your teachers now you're an approved AP reader. Only kidding. Okay, here's the name of the test. Use a 1 proportion Z test. Okay, that's good. Yep, student names the test correctly. Therefore, they don't need this formula. Although again, that student does a really good job with the formula. Here's my null and alternative. P is equal to 0.2. P is less than 0.2. Okay, I'll give him an E for that. That should be an easy E. This year was an easy point, we hope. Again, students did not have to define the parameter that year. But moving forward, please do that. So it looks like this is their assumptions and conditions. Sample size is N is 65. Okay, that's a true statement, but I'm not sure that's a condition. P has 11 over 65 or 0.1692. Again, these are both true statements, but they're really not the conditions. Boxes are SRS, so that was good. That was given to us. But notice the student doesn't have your what I call your NP and NQ checks. Population is greater than 10 times the sample. So the student got an I here. It's just not. They really didn't do a very good job with the assumptions and conditions. Again, I'm not picking on the student here. They thought they did, but they really didn't. So they didn't get that point there, unfortunately. Let's go down to the math. So the student has the Z-score formula, plugs in. Looks like the numbers are all in the right place. Z is equal to minus 0.6202. Yeah, we've seen that number before. My P-value of Z is 0.2676. Yeah, that's all good. I'll give the student an E. So the student has EIE. So far, so good, except for the assumptions. So I guess this is going to be my conclusion. What are we going to do with all this information? So C is 0.95 default, alpha is 0.05. I guess confidence level is 0.95. Again, I would write it this way, but I'm okay with it as a reader. Our P-value of 2676, greater than 0.05. That's a true statement. Accept the null. Boy, unfortunately, that word right there is really bad in statistics. We don't accept the null. I don't like to accept the alternative. I either reject the null in favor of the alternative or fail to reject the null. So student loses it really based upon that one word. There's not enough evidence to reject the null. Again, there's no context here. There's no serial boxes, there's no vouchers, anything like that. So unfortunately, the student got an EIEI 2 points. And unfortunately, I on some level really think that the student sort of understands the problem. It has actually made the correct mathematical what we call linkage here. But this word here is just not a good statistics word, and there's no context. And so the student earns 2 points out of 4. And you see how easy it is to have a wrong word, and that's enough to cost you a point or two. So we feel bad for the students, but we have a lot of students to read our grades, so we keep moving on. How's that? So I think I did this problem the other day with probability. I'm 99% sure, confident, no pun intended, that I did this one. So I'll go through the answers real quick because I want to make sure we have enough time for the student responses. So a shopping mall has 3 automated teller machines, ATMs. Because the machines receive heavy use, they sometimes stop working and need to be repaired. Okay, that makes sense. We're just setting the stage here. But the random variable capital X represent the number of ATMs that are working when the mall opens on a randomly selected day. So we talked about random variables. I think that was last Wednesday. So I did this problem on Wednesday. The table shows the probability distribution of X. That's your random variable. So it looks like we have 0, 1, 2, or 3 ATMs working. 0 would be a bummer, right? You go to the mall and there's just no ATMs working. You need to get some money. Here's the associated probabilities with each one of those outcomes or ATM machines working. I'm going to add those up and they do equal 1. So that's good. That's one of the requirements of a random variable, right? So what is the probability that at least one ATM is working when the mall opens? So again, many times I just repeat the question and I'm guaranteed to get context in if I can do that. The probability that at least one ATM is working when the mall opens is 0.21 plus 0.40 plus 0.25, 0.85. Okay, keep that number in mind and keep this sort of context in mind. Part B, what is the expected value of the number of ATMs that are working when the mall opens? Again, I'm just going to repeat the sentence. The expected value of the number of ATMs that are working when the mall opens. And I like to say, outcome times probability plus outcome times probability plus outcome times probability plus outcome times probability. That's going to give me my expected value. I did that math and I got 1.73 ATMs. You do not want to round that. I will leave that number alone. I'm specifically told to round. We want to leave that there. So that's a mean or average, and we just don't want to round that. And I have graded papers where students might have rounded different problem and they lost points for that. So leave that alone, don't round. Let's keep moving forward. I think we earned some points. What is the probability that all 3 ATMs are working? So all 3 ATMs are working. Given that, well, that sounds like a conditional probability, right? Given that at least one ATM is working. So I said the probability that all 3 ATMs are working when the mall opens, given that at least one ATM is working. Well, all 3 are working is the 0.24. All 3 working is 0.24. And I added up at least one working, so I didn't need to worry about 0. So I added up those 3 probabilities. 0.24 over 0.85, 0.282. Again, going fast because I want to make sure that we actually look at the student papers, and I think we'll be okay. Given that at least one ATM is working when the mall opens, would the expected value of the number of ATMs that are working be less than, equal to, or greater than the expected value in part E explained? Well, the expected value in part B was 1.73. Given that at least one ATM is working, well, I guess I'm going to worry about 0. I'm not going to worry about 0 ATMs. I'm told either 1, 2, or 3 are working. Well, if this was sort of my revised random variable, those 3 probabilities would have to add up to 1. So each one, my gut says, would be proportionally higher. And so it feels like the expected value will be larger. Why? Because I'm taking the 4 events, just using 3 of them. Those 3 probabilities need to add up to 1. So each one would be proportionally larger or bigger. When I multiply it, it feels like it would be greater. So the expected value would be greater than the expected value in part B. Again, I just wrote that down. Since the probability for 1, 2, 3 ATMs would be proportionally maybe larger or something would be a better word than increase. Okay, so we did that the other day. 4 parts. Again, we're going to grade each one of these either EPIs, essentially correct, partially correct, or incorrect. So let's look at student 1. Again, student makes a mistake here. I'm by no means making fun of these students. My students, I wish were all perfect. They're not. I wish Mr. Murphy were perfect, and he's far from that. So the probability that at least 1 equals 1 minus the probability of no ATMs, 1 minus 0.15, 0.85. Well, that's different. That's actually kind of a cool way of doing it. Perhaps maybe a little bit easier than the correct number. I see some math there. Give the student an E. I'm happy with what they've done. What is the expected value? What is the expected value of the number of ATMs that are working when the mall opens? EX, expected value of random variable X. Student does the right math. 1.730 ATMs. I've seen the work. In a perfect world, I'd love maybe some words, but it's there. I'm going to give that student an E. Again, E doesn't mean perfect, and 4 out of 4 doesn't mean perfect. There's a probability that all 3 ATMs are working when the mall opens, given that at least 1 ATM is working. Student does a very good job here of sort of the conditional probability in words. Has the correct numbers, 0.24 over 0.85, 0.282. Excellent job right there. Very, very nice answer. Clean, easy, perhaps better than mine. Down here, student needs to talk about less than, equal to, greater than. The expected value for the number of working ATMs would be greater than that in part B. Okay, so that's good. Student has the right answer. Because at least 1 ATM must be working, there is no longer the X value in the probability distribution. So I think the student is saying, we're getting rid of that 0. Thus, in this distribution, the probabilities of having 1, 2, 3 ATMs all go up. Okay, that's what I talked about. That's good. When finding the expected value by doing EX equals X times probability of X, student actually gives me the formula because all the probabilities values increase, the sum increases, and EX is greater. That's really nice. Yeah, student probably didn't need all of that. Probably didn't need the formula, but that student got 4 out of 4. Very, very nice paper there. Yeah, very nice paper. Okay, next student. Student has the 3 probabilities, 0.85. I'm going to give him the E. It's there. Problem says, what is the probability? The student gave me the probability. I can follow their math. I can see where they got that number. I wish there was some more words or a sentence, but it's there. So I'm going to give him the E. That's what the scoring rubric says. Scoring guidelines. What is the expected value? Expected value. Student does all the math, gets the same number, does it round. Give him an E here. What's the probability that all 3 ATMs are working? Student has the right numbers. I wish they had over here maybe a formula or some words. 0.282. Student gets it. Give him an E. A little bit of a minimalist here. Maybe some more words would be nice, but it's there. It's marginal. I think you can see the first student was a little bit stronger from a communication point of view, but this student's doing okay. Student's doing okay. Part D, student says it would be equal to. We said greater than, so I don't think this is going to be right here, but I need to read it. Equal to because expected value was calculated by gives me the formula. And I think the student was confused that since 0 times any number is 0, that it wouldn't change. And so that's actually an incorrect answer. The student got an EEEI. Student earned 3 out of 4, which is still a very good score. Absolutely nothing wrong with that. And that was kind of a common mistake that year. I think students said, oh, well, if that's 0, 0 times any number is 0, so the number won't change. They didn't see that these probabilities would proportionally increase. So that student earned 3 out of 4. Okay, here's the last student, I think. And in part A, we see no math. We see a number. We call that a bald answer. My students get a kick out of that every time I say bald answer. They ask me if it was named after me, and I say no, it was named after Mr. Murphy. I don't like that. I know where they got the numbers from, right? It's the right answer. Student doesn't give us any words, doesn't give us any context, doesn't show me where that number comes from. A student earned a P. Think of P as a half point. It's not quite that simple. E is 1 point. Again, not quite that simple. But you see how easy it is to lose, to go from an E to a P. If the student had just added those 3 numbers and put it down here, that student would have gone from a P to an E. So please show us your work in context. Use the calculator to check your math, but always show us your math. How's that? I think Luke says it like that. What's expected value? Really hard to read the numbers here, but student does have expected value 1.73. Here they show me the math, so I'm gonna give that student an E. That's what the scoring guidelines say. I'm good with that. I'm student show me the math. Part C, what is the probability? P of A given B. Again, I wish it was more contextual, but 0.24 over 0.285. These are the right numbers. That's actually the wrong number there. I think I got 0.282. So it was weaker here. A and B. I don't really know what A and B is. Student has the right numbers here. That's good. Wrong math there. Student earned a P there. And again, if that number were correct, 0.282, the student probably would have gotten an E here. That's weaker. I'm not thrilled with it, but it's okay. The student has shown with those 3 added those 3 numbers, they probably would have gotten an E here. The student may have gotten an extra point on this problem. How's that? So hopefully this is helping you some, exactly what the reader's looking for. Show us your math in context, all that good stuff. Part D, the expected value would be equal to. Well, that's the same mistake that the previous student made because the probability of 0 working when the mall opens does not affect the expected value, et cetera, et cetera, et cetera. I would read it, but for the sake of time, I won't. Student got an I there. That was very common that year. Student said, oh, it's going to be the same. 0 times anything is 0, so the numbers won't change. So this student got a PEPI 2 points. And I would like to say, they left some valuable points on the table there. The student had only showed us the math here and added those 3 numbers. And if you checked it on the calculator, the student very easily could have gotten a 3 out of 4. So let's kind of wind down for the day here. Hopefully that was an exercise that you found helpful. So we did the serial boxes, right? We did that one. So hopefully now you're feeling a little bit more comfortable with the scoring guidelines, rubrics, how they're developed and how readers are trained to grade, read your free response questions. It's really quite a logistical exercise to get 700 to 800 people in a room. Last year, I think it was around 250,000 students. So 250,000 times 6, 1.5 million if my math is correct answers. We have to grade all those in a week. We want to finish on day 7 right around the same time. So it's an unbelievable logistical problem. Fun to solve. Extensive training. We need to follow the scoring guidelines, not do what we think. Okay, so we're trained to follow the scoring guidelines, and the training is very extensive and very detailed. All week long, I'm working with my partner. My partner is typically college. If we have questions, we go find the table leader. We can go up to the question leader. There's sort of a hierarchy of different positions when we run into problems. Again, similar to all problems in AP statistics, you should be able to write your answer in a clear, concise solution and context. And hopefully you saw that literally on some student papers and how they left us. We like to say some valuable points on the table. How's that? Here's your homework for tonight. Luke will take over tomorrow. Now again, Luke's is going to be a little different tomorrow. I'm talking about p-value and statistics, and is that the right sort of way we should be right process for hypothesis testing. So I'll leave that up to him. Hopefully he likes the problem that I picked. So I just wanted there's I think 8 or 9 slides here, and we won't go through all of them. But some students have some sort of the college board. We want more practice. Brendan and Luke are doing lots and lots of questions, but we want to sit down and do some of our own. So these next few slides to talk about how you can go on to AP Classroom and find some additional FRQs for response questions to do, how you can check your answers, all of those things. So I won't walk through each slide here, but it's there if you want to go back and look at my my little talk today and walk through some. By all means, practice make perfect. My students are doing lots and lots of free response these last few weeks, and hopefully watching me on some of these as well. So thanks for watching. Hopefully you'll keep watching. Tomorrow is Luke. I'll be back on Wednesday. And Fridays I'll do Monday, Wednesday, Friday this week. Luke is doing Tuesday, Thursday. Again, this week is predominantly tips for the AP exam. How to do well, how to write good responses, how to use your formula sheets, and those types of things. Common errors you saw that today. Some common mistakes that we see over and over again, and how you can really 1 or 2 words can sometimes cost you a point on a problem. We don't want that to happen. Again, next week wasn't originally part of the plan, but the plan has changed, which is great. So next week Luke and I will be the same thing every day at 2 o'clock. Monday we're going to give you the 25-minute FRQ to do. We actually want you to work on it during our live session from 2 to 2:45, or if you're watching it through tape, whenever. But we want you to sit down and literally walk through the problem. Tuesday Luke will go through the answers. Wednesday I'll do the 15-minute FRQ. Thursday I'll do the answers, and then Friday the 8th we're going to kind of have sort of the graduation ceremony, whatever. We'll have a little Luke and I will both be there that day, and we'll talk about wishing you good luck, and hopefully we helped in those types of things. So hope we helped today a little bit, and you understand a little bit more about what happens at the reading and how we actually go through student papers and determine how many points the student earns. So be safe, take care of yourself. Hopefully you can tune in tomorrow or later on this week. I'll see you. So have a good afternoon, and we'll see you tomorrow. Thanks.
Hello, AP Statistics students, and welcome to the College Board Virtual Instruction for AP Statistics. My name is Luke Wilcox. I am an AP Stats teacher at East Kentwood High School in Kentwood, Michigan. My colleague Brendan Murphy Murphy and myself have taken you all the way through all of the content that will be covered on the AP Statistics exam at this point. And this week we are dedicating to big review ideas. And I'm very excited about the topic of today's lesson. It is my favorite topic in AP Statistics and what I call the holy grail of AP Statistics, and that is the p-value. So I hope that by the end of today's lesson you have a different understanding and a better understanding of the p-value. So let's go ahead and jump right into things here. Quick check to make sure that you are in the right location. This is AP Statistics. My name is Luke Wilcox. A couple of quick announcements to get started here in case we have anybody that is new that is joining us. We are meeting on a daily basis, 2 o'clock Eastern Standard Time, Monday through Friday. As I mentioned before, we have finished the review of the specific content, and what you're going to be seeing this week are what we're calling general review strategies, sort of some big ideas, I think. And then next week, very specifically dedicated to doing some practice FRQs that should prepare you for the AP exam, which is May 22nd for AP Statistics. So any of the resources that you might need for these lessons, you can download at statsmedic.com/YouTube. You just look it up by the date, and you should find downloadable PDFs of the lesson as well as the homework problem. So speaking of homework problem, Mr. Murphy gave you a homework problem yesterday. It was a multiple choice question from a previous exam. So we're going to start by checking in on this multiple choice before we move into anything new for today. So here's what it says. When using a one sample t procedure to construct the confidence interval for the mean of a finite population, a condition is that the population size be at least 10 times the sample size. The reason for this condition ensures that. Okay, before I even look at the answer choices, I'm going to take this condition and state it in a different way. I'm going to put it in the reverse order. Instead of saying that the population size is at least 10 times the sample size, the other way of saying that is to say that the sample size is less than or equal to 10% of the population size, which is maybe the way that you saw it in your course. So the 10% condition is what we're talking about here. And what we want to know is why is it that we actually check the 10% condition? And just to remind you where this first showed up, it showed up with binomial distribution when we were checking the 4 conditions that are necessary in order to say that a distribution is binomial. And the second condition is the independent condition. And what we said here was that if you're sampling without replacement, then we have to check the 10% condition to be sure that one trial is independent of the next trial. In other words, knowing the outcome of one trial does not change any probabilities or give us any information about the next trial. So we know that the 10% condition has something to do with this idea of independence between the trial. Now let's look at each one of the answer choices and see what we have here. Okay, answer choice A, the sample size is large enough. Now that is a condition that we'd like to be met in order to use a one sample t procedure, but it's a different condition. That's what's called the large sample condition. So that one's out. Choice B, the central limit theorem is applicable for the sample mean. Well, that's actually still part of the same condition that I just mentioned, the large sample condition. If we have a big enough sample size, the central limit theorem says that the sampling distribution is approximately normal. That's not what we're going for here. And now I'm actually going to take us down to choice E, the sampling method is not biased, which is very important. That's part of a different condition, which we call the random condition. And so we're left with only 2 choices here. So let's look at each one of them. Answer choice C says that the sample standard deviation is a good approximation of the population standard deviation. Well, for this, we actually want our sample size to be bigger, not smaller. We wouldn't want it to be less than 10% of the population. It would actually be best to have the biggest possible sample size there. So this one's incorrect. And I'm hoping that answer choice D says what we need it to do. The degree of dependence among observations is negligible. That's exactly what we were talking about here way back in the binomial condition. And so answer choice D is the reason why we check the 10% condition. So hopefully we did okay on that practice problem. And I think we're ready to jump into today's big topic. So I'm going to start with a lesson overview where I'm going to provide you with a couple of learning targets. And then at the end of the lesson, we'll come back to those learning targets and make sure that we got what we needed to. So there are 2 of them. And of course, as mentioned, both related to the p-value. And so the first one says, understand how to calculate a p-value for a significance test. And the second learning target, which I think is the more important learning target, is to be able to interpret a p-value for a significance test. And then of course, be able to use that p-value to make a conclusion for a significance test. So I'm going to say right here that this is the big goal of today's lesson, to be able to interpret a p-value so that we can make a proper conclusion. So let's go ahead and jump into today's activity. So I've called the activity tracking the p-value through AP Statistics. And the idea is that the p-value, while you learned it formally at the end of your AP Statistics class, chances are you had been developing your thinking and understanding and reasoning about the p-value all the way throughout the course. And so what I've done is I've put together 4 example problems that would come from 4 totally different parts of the course. One from the beginning, one from towards early on, a little bit later, and then one towards the end. And we're going to see how our progression of understanding of the p-value happens throughout the school year in AP. So let's start with this awesome quote that I got from Wikipedia as I was preparing for today's lesson, which says, the term holy grail is often used to denote an elusive object or goal that is sought after for its great significance. And listen, the p-value in AP Statistics is exactly that. It is the holy grail, right? It is the often elusive object, the thing that we are trying to understand, and ultimately like what we're working towards for the end of the year is to be able to understand the p-value. I also very much appreciate that this quote just happened to have the word significance. So the goal of today is not to have some memorized thing like if the p-value is low, then we're going to reject the null hypothesis. That is not the goal. The goal is to understand what that p-value is telling you. What is the interpretation of that p-value, which ultimately will lead to your conclusion to reject the null or fail to reject the null. But I just want to make sure that we have proper understanding of the p-value. So we're going to start with number 1 here, and this comes from an awesome lesson that AP Stats teacher from Pennsylvania, Doug Tyson, all-star AP Stats teacher, created this lesson, and is one that is very commonly used throughout the country. So there's a good chance that you may have even seen this example in this activity in your own class. So here's what it says. Joy Milnes participated in an experiment in which she correctly identified 11 out of 12 shirts by whether or not they were worn by Parkinson's patients. To investigate if Joy can smell Parkinson's, an AP Stats class simulated what the results might be if Joy had been simply guessing on all 12 shirts. Here are the class results. So a little more detail about the experiment. Joy Milnes claimed that she could smell Parkinson, and so experimenters set up an experiment with 12 t-shirts, half of which had been worn by Parkinson's patient, half of which did not have Parkinson's. Then they gave the shirts to Joy, she smelled them, and then she tried to identify whether they had been worn by Parkinson's patient or not. And it turns out that out of the 12 shirts, Joy was able to correctly identify 11 of them. So we got a couple of questions to get us started here. The first one is the claim, and this is the claim that we're going to assume to be true in order to carry out the simulation. And for the simulation, the stats class wanted to know what would happen if Joy just simply guessed on all 12. She couldn't smell Parkinson's, she just totally guessed on all 12. So the claim here is that Joy was just simply guessing. And the other way of saying that she was just simply guessing, that means that she can't smell Parkinson's. All right. Now the statistic is the observed result that you get from the sample or from the experiment. Well, in this experiment, the observed result was that Joy got an amazing 11 correct out of 12. Now the next question is, does this provide some evidence that Joy can smell Parkinson's? Well, definitely, right? 11 out of 12 is really, really good. If she were simply guessing on all 12 of them, we would expect her to get about half of them right. So certainly 11 is much better than if she had just simply guessed, where we would expect her to get 6. So we do have some evidence that Joy can smell Parkinson's. The next question is whether we have convincing evidence. And in order to answer that question, we have to have a p-value. We have to know how likely is it that we could have seen this observed result purely by chance. Then we can make a decision about whether or not we have convincing evidence. So we're going to use the dot plot here in order to estimate our p-value. And we just have to understand what each one of those dots represents. So for example, this dot that you see here at 8 means that that student in class did a simulation. So they could have maybe tossed it 12 times and tried to guess whether it be heads or tails. Or maybe they had little cutouts of t-shirt. Half of them said Parkinson's, half of them said no Parkinson's. And somebody had to simply guess what each one of the 12 was. And for this particular simulation, out of the 12, that person guessed 8 correct just purely by chance, by guessing, right? And right away you'll notice that at the very center of the distribution is 6, which is what we would expect if somebody was just simply guessing that they would get about half right. Now we know because of sampling variability that it might be a little bit higher than 6, it might be a little bit lower than 6, which we see in the dot plot here. So the next question then is how likely is it that we would get Joy's result? Well, let's make sure that we clearly identify that here. And Joy's result is this right here, the 11. And that's what I'm going to call the statistic. That was the observed result from the experiment, right? Now remember, one thing I want to make note of here, this simulation was done assuming that this claim is true. In other words, we created this dot plot by assuming that Joy was guessing. These are the possible values that we might get when Joy is guessing. Well, how many times did the class get that 11 or better, right? If 11 is convincing evidence, then 12 would also be convincing evidence. But we see here that 11 or higher only happened one time, and there are 30 dots total there. So that's going to allow us to make an estimate of what the p-value. And I'm going to say approximately here because it's an estimate, which is 1 out of 30 or about 0.03. Very, very unlikely to happen purely by chance. So let's go ahead and see if we can interpret this p-value. And when we're interpreting the p-value, I'm trying to interpret what this 0.03 is telling me. So to start the interpretation, I need to make note of what we assumed to be true up front. So that's the first part of the interpretation, is to say that we were assuming that Joy was guessing. And so assuming that Joy was guessing, there is about a 0.03 probability that she would get 11, and let's be careful here, 11 or more, it could have been 12, even though that didn't happen in the dot plot, that she would get 11 or more correct purely by chance. Now that is a very, very low probability, which is suggesting to us that maybe the assumption that we made up front is not really true, and that we have convincing evidence for the other claim, which is that Joy can smell Parkinson. So because this p-value is so small, so unlikely to happen purely by chance, we do in fact have convincing evidence. So I'm going to say here, yes, we have convincing evidence because the p-value, which is very small, 0.03, is less than alpha, which I'm just going to use 5% as our alpha value for all of the problems that we're going to go through today. So based on the observed outcome of 11 out of 12, we do in fact have convincing evidence that Joy can smell Parkinson. Side note, the 12th one that she got incorrect, she had said that person had Parkinson's and that person did not have Parkinson's. But several weeks or months later, that person did in fact develop Parkinson's. Crazy story, you can look it up on the internet. All right, let's move on to question number 2. And there's a new scenario here. This would likely be a little bit later in the course, whereas the Joy Parkinson's activity you might have even done in the first week of school. This is something that you would have done several months later. Okay, so here's what it says. According to YouTube analytics, 30% of all AP Stats students are using YouTube as part of their AP exam review. College Board believes the true percent is higher and selects a random sample of 80 AP Stats students to survey. In the sample, 32 students were using YouTube. Okay, let's think about a couple of things here first. The first thing to identify is that the thing that the College Board is measuring is the number of students that are using YouTube here. Okay, the number of students. That's like the number of successes in a fixed number of trials, which is 80. And I'm hoping that's triggering to you that this is in fact a binomial distribution. Now, just to make sure, we know that there are 4 conditions that are necessary for this to be considered a binomial distribution. So let's just check those real quick. Okay, for B, each trial is binary as either a success or a failure. Well, a success here would be that the person using YouTube, and a failure is that they are not. So that condition is. For the independent condition, a couple of things to think about. First of all, it is a random sample, so that should help us with independence between each trial. And then again, we do have to check the 10% condition here because we're sampling without replacement. But certainly 80 is less than 10% of the population of all AP Stats students. And so we would say that the I condition is satisfied. And says that there's a fixed number of trials. Well, sure, there's a fixed number of trials. The sample size is 80. And then as we need the same probability of success for each trial, if we assume that the YouTube analytics are correct, then the probability of success for each trial would be 0.0. And so all 4 conditions are satisfied, and we know we have a binomial distribution. Now, one thing that I hope you remember about binomial distributions is how to calculate the expected value, which is just n times p. So in this case, 80 times 0.30, which is telling us that we would expect out of the 80, about 24 would say that they use YouTube, right? So let's move into our next set of 4 questions here. The first question says, what is the claim that we're trying to find evidence against here? Well, the claim is the YouTube claim that they made right up front, which is that 30% of AP Stat students are using YouTube. So the claim is 30% of Stat students are using YouTube. And the College Board wants to try and collect some evidence against that claim. So they did, and that's where we get our statistic, which is the observed outcome from the sample survey. And what we got there was that there were 32 students that are using YouTube. So the next question is, does this provide some evidence that the true percent is higher than 30? Well, we know that if 30 is true, we would expect to get about 24 successes out of the 80, and we got 32. So certainly 32 is bigger than 24, and we do have some evidence to suggest that the true percent is higher than 30%. So the follow-up to that is, do we have convincing evidence? And once again, in order to answer that question, we need a p-value, which will tell us how likely is it that we could get this result or more extreme purely by chance. So let's take a look at the distribution here. And one thing I want to make note of is the fact that we have to assume that this claim is true in order to make this distribution here. So we're going to assume here in this picture that 30% use YouTube. That had to be assumed in order to create this distribution that you see here, right? So this claim is assumed to be true. Now you can actually see that because if you look, the value right at the center of this thing is 24, which is what we would expect if the 30% claim is true. Now the next thing we need to identify is where our statistic is in this distribution. And it's 32. So I'm going to look here and I see 32 is right about here. That is the statistic that the College Board got when they took their sample of 80 students. So in order to calculate the p-value, we want to know how likely is it that we would get that observed result or farther from what's expected purely by chance. So not only do we want 32, but we want 33 and 34 and 35 and 36 and all the way up, right? This right here is going to give us our p-value. And if you recall from when we were studying binomial distribution, this is one of the cases where we use the calculator to help us to find the probability of 32 and 33 and 34 and so on. The trick is to use binomial CDF on the calculator. And we are going to have to use the complement rule as well because we want the values 32 and higher. So we're going to subtract out the value 31 and lower. So I'm going to do 1 minus binomial CDF. And the commands that we would need here in the calculator is the number of trials, which is 80, the probability of success for each trial, which is 0.30, and then the number of successes. And we want to subtract out 31 and below, which would leave us with 32 and above. So if you plug that in your calculator, you're going to get a p-value of about 0.036. That's our p-value. So I think we are now ready to try and interpret that p-value. I'm going to try and use a similar interpretation as we did in the Joy Parkinson's example. And I'm going to start out with the claim that we assumed to be true. So we're going to say, assuming that 30% of AP Stat students use YouTube. And then we want to try and interpret this p-value here of 0.036. So we're going to say there is a 0.036 probability of getting, now let's look at our picture here. And our picture says 32 or above. That's what we have shaded in purple here. So it's a 0.036 probability of getting 32 or more who use YouTube in a sample of 80 purely by chance. Now, just like the Joy Parkinson's activity, we've got a p-value that is very small here. It is very unlikely that we would get this result, assuming that that claim was true, which is telling us that this claim, we have some evidence against that claim, and convincing evidence to the alternative, which is that the true percent is higher than 30%. So once again, do we have convincing evidence? Yes, we do have convincing evidence, and that's because the p-value is small, 0.036. Specifically, it's less than our alpha value of 0.05. So that takes care of number 2, and I think we are ready to move into the more formal significance tests that you started seeing towards the end of the year in AP statistics. So let's go ahead and jump to number 3, and let's take a look at the context. Here's what it says. Mr. Wilcox believes that 12 hours of preparing is needed to prepare for the AP statistics exam. A random sample of 20 AP stat students from last year revealed a mean of 11.4 hours spent preparing with a standard deviation of 3.72 hours. Do the data provide convincing evidence that last year's students spent less than 12 hours preparing on average? Assume the conditions are met. Okay, now that we're into the more formal significance test that you saw towards the end of the year, I think we can officially write a null hypothesis and an alternative hypothesis for this. Okay, so the null hypothesis is going to be the claim that's made right up front by Mr. Wilcox that it takes 12 hours on average to prepare for the AP exam. So I'm going to make sure I'm using the correct notation here for the population, which is mu, and say that that's equal to 12. Now for the alternative, we have to look at the wording of the question to decide whether it's one-sided or two-sided. It says very clearly here that we're looking for evidence that it was less than 12 hours. So that tells us our alternative hypothesis is going to be mu is less than 12. Now anytime you're writing out your hypotheses, you need to make sure that you clearly define what your parameter is here. I'm going to say that mu represents the true mean time preparing for last year's AP stat student. Okay, so let's jump into our 4 questions here. The first one is the claim that we're going to assume to be true in order to come up with our distribution here. And we know that that's going to be the null hypothesis. So it says that the mean is 12. So I'm going to say here the claim is that students average 12 hours preparing. Okay, that's the claim that we're going to assume to be true. That 12 is actually the true mean for the whole population of all AP stat students. Now the statistic is the observed result that we got from our sample here. And we know that that is 11.4. Making sure that I'm using the correct notation here. This is a sample mean. So I'm going to use x bar. And the statistic here is that x bar is 11.4. Now, does that provide some evidence that the true mean is less than 12? Well, sure it does, right? 11.4 is in fact less than 12. So we do have some evidence that the true mean is less than 12. But do we have convincing evidence? Or could this result have happened purely by chance just because it was a random sample? Well, this is why we need a p-value in order to answer that question. So let's jump over to the picture here, the distribution. And first, I want to make sure that we recognize that this here is the sampling distribution of X bar. In other words, what are all the possible X bar values if we were to continuously take random samples of size 20 from the population, assuming that this claim is true, that the true mean is 12. So sure enough, you see that the mean of the sampling distribution is the mean of the population under the assumption of the null hypothesis. Now the next thing we need to do is to identify our statistic here, which was 11.4. That's this value right here. That is our statistic based on our sample of 20 students. And in order to get the p-value, we need to know how likely is it that we would get that value for the statistic or farther from what's expected. In other words, we want all of this area underneath the curve. So there's some calculations that need to be done here, but that's not the focus of this lesson. So I'm going to tell you that the calculator gave me a t-test statistic of negative 0.72, which means we're about 0.72 standard deviations or standard error below the mean. And the calculator gave me a p-value here of about 0.24. So let's see if we can interpret that p-value here. And just like we did in the first two examples, I'm going to start with my assumption. And here we are assuming that this claim is true. So we're going to assume that last year's AP Stat students spent an average of 12 hours preparing. And if we wanted to write that in symbols, we know that's of course our null hypothesis. I'm just going to put that in parentheses here, that the true mean is equal to 12. Now let's get to the interpretation of the p-value. There is a 0.24 probability. And now let's look at our picture. Look at the shaded region that we have there, which we know is our statistic of 11.4 or lower. So let's put that in words. There's a 0.24 probability of getting a sample mean of X bar equals 11.4 hours or less, right? Because we're going to the left here. That's important, purely by chance. Now for this one, the p-value is fairly large. 24% of the time when you take a random sample of 20 students, you're going to get an X bar of 11.4 or lower when we assume the null hypothesis is true. Well, that very well could have just happened purely by chance. So do we have convincing evidence for the alternative? No, we do not here. And that's because our p-value is large, 0.24, which I'm just going to say is greater than a traditional alpha value of 0.05. So we do not have convincing evidence that the true mean is less than 12. Okay, this leaves us with one more example problem to go through, which would be likely a little bit later in the course, probably something you covered right towards the end of the course. Here's what it says. The curious AP Stat student wonders if the proportion of Reese's Pieces that are orange is different than the proportion of Skittles that are orange. Suppose she took an SRS of 50 Reese's Pieces and found that the proportion that are orange, P1 had 0.42, and an independent SRS of 100 Skittles and found the proportion that are orange 0.20. So let's start again with our hypotheses here, just to make sure we have those written. And so we've got a null and an alternative. Very clearly here I can see that this problem is about proportions and that it is a two-sample problem. And so I know that my hypotheses are going to be about the difference between the two proportions. And we know that the null hypothesis would say that the two proportions are equal, which would mean that the difference between the two proportions is equal to 0. Now to get our alternative, we have to look back at the wording of the question here. And it says different than. So we don't really know if it's going to be higher for Reese's Pieces or higher for Skittles. This is a two-sided alternative, which says not equal to 0. Now we do need to clearly identify our parameters here. So I'm going to identify P1 as being the true proportion that are orange for Reese's, and P2 is going to be the true proportion that are orange for Skittles. Okay, so now let's get to the claim that we're going to assume to be true in order to come up with our picture here. And that claim we're going to assume to be true is the null, which would say P1 minus P2 equals 0, meaning that the two proportions are equal. So I'm going to say the claim here is that the orange proportion is the same for Reese's Pieces and Skittles. That's the claim we're going to assume to be true. Now the statistic is the observed result that we got from our two samples here. And so what we're looking for here is P1 hat minus P2 hat, which we can calculate very easily. 0.42 minus 0.20, which is going to give us a difference of proportion of 0.22. Now does that provide us with some evidence that the alternative hypothesis is true? Well, the alternative says that it's not equal to 0, and sure enough, when we took our samples, we got a difference of proportions that is not equal to 0. So that 0.22 difference in proportions that we got there isn't equal to 0, which gives us some evidence for the alternative. But do we have convincing evidence, or could this result have happened purely by chance? Once again, this is why we need the p-value. So let's move over to the picture here, and let's first identify what this distribution is. Once again, this is the sampling distribution, but this time it's the sampling distribution of P1 hat minus P2 hat. And because we're assuming the null is true, you will see at the very center of the distribution is our null hypothesis that P1 minus P2 is in fact equal to 0. Now let's identify our statistic from the sample. That statistic is 0.22. Well, that value is right about here. 0.22 is our statistic. But remember that this was a two-sided alternative, so we need to do the same thing on the other side of the distribution, which is just negative 0.22. And now to get the p-value, I needed this area over here in purple as well as this area over here in purple. So I did this on a calculator, and I'm going to give you the results. The z-test statistic for this was 2.85. It means we're 2.85 standard deviations above the mean, pretty far above the mean, which tells you the p-value is going to be pretty small. And even when I take both sides, right, and I add those two areas together, I get a p-value of 0.004. Very small p-value. So let's see if we can interpret. Same sort of setup as before. We need to start out with our assumption to be true. So what we assumed here was that the claim was true. So assuming that the orange proportion is the same for Reese's Pieces and Skittles. And then I'm going to put in parentheses like the more formal way of saying that, which would be P1 minus P2 equals 0. And now let's get to the interpretation of the p-value. There is a 0.004 probability of getting, now let's look at our picture here, of getting this or greater or this or lower. So we have to accommodate for both sides of this distribution here. So I'm going to say of getting a difference of sample proportion of P1 hat minus P2 hat equals 0.22 or farther from 0. So that's taking care of both sides of the distribution here, 0.22 or farther from 0. And then we are purely by chance. Now because this p-value is very, very small, very, very unlikely to happen purely by chance, we have convincing evidence against the null hypothesis and in favor of the alternative. So do we have convincing evidence? Yes. And that's because the p-value is very small at 0.004, which is clearly less than our alpha value. So we do in fact have convincing evidence that the proportion of orange Reese's Pieces is different than the proportion of orange Skittles. Now a couple summary questions here. For all four of those problems that we did, we had a claim at the very front end that we were assuming to be true, and hopefully you know that this is the null hypothesis. And then the last idea here, because the p-value is calculated, that is a probability calculated by assuming some claim is true. Well, that's a condition, right? We're assuming that that condition is met. So that p-value, which we know is a probability, is in fact a conditional probability. Now let me show you another way of thinking about the p-value as a conditional probability. We could think of the p-value as being a probability, so I'll use capital P here. And what it is it's the probability of getting the observed statistic, right, or more extreme, given that the null hypothesis is true. So I'm using that conditional probability notation that you learned way back earlier in the year. The p-value is in fact a conditional probability that is calculated assuming the null hypothesis is true. Now just to be very clear here, it's the observed statistic or more extreme. So sometimes that means shading to the left, sometimes to the right, and sometimes both sides. So let's see if we can summarize hopefully some big ideas about the holy grail of AP statistics here, the p-value. And I'm going to go back to the two learning targets that we started with here. The first of which was to be able to actually calculate a p-value. That was the first learning target, to calculate a p-value. So I'm going to give you sort of like a list of steps that you need to do in order to calculate a p-value. Okay. The first thing that we did for all four of those examples is we assumed some claim to be true, which we are now just going to call the null hypothesis. So we assume the null hypothesis is true. With that assumption, we can then look at the distribution where we'll calculate our p-value, which is going to be the sampling distribution. So I'm going to say draw the sampling distribution. Okay. Next, on your sampling distribution, you have to identify the statistic or the observed result that you got from your sample or from your experiment. Then the next step is to shade in the distribution. And you're going to shade, generally, I'm going to say away from the center. If you were shading back over the center, that would be a problem, which you would very likely catch when you ask yourself whether or not you had some evidence, because in that case, you wouldn't even have some evidence. And then finally, once you've shaded, you want to find the area or the probability of that shaded region. So I'm going to say here, calculate the probability. So in general, this set of steps is going to allow you to calculate p-value. Now the second learning target, which I think happens to be the more important learning target here, was not only that you could calculate a p-value, but that you could interpret the p-value. And after going through four of these examples, you notice that it really sort of follows the same structure every time. So let's write that structure down here. Okay, you always start out with your claim that you are assuming to be true. So in this case, it would say assuming, and then you're going to put the claim there. And the claim is always the null hypothesis, so you would put the null hypothesis is true. And this is where I like to put the context of the problem, right up front when you're stating your assumption. Okay, then the next part of the interpretation is where we get to the p-value. There there is a, and then blank, this is where you're going to input whatever your p-value is that you calculated. There is a, whatever the p-value is, probability of getting a, and then you're going to have to fill in the blank here again. And what's going to go on this blank is whatever your observed statistic is from your sample or from your experiment. So of getting a statistic of, and then you're going to have to write out whatever your statistic is, maybe x bar, maybe p1 hat, maybe p2 hat. And then we're going to say or more, or less, or farther, depending on whether our alternative hypothesis is greater than, or less than, or not equal to, from expected purely by chance. So there we have sort of like a template that you can use in order to interpret the p-value. Now, once you have the p-value, you do have to be able to turn that into a conclusion about the null hypothesis. And so this is the part that you likely know from your class already, that if the p-value is low or less than the alpha value, then we do in fact have convincing evidence for HA, the alternative, which means that we would reject the null hypothesis. If on the other hand, your p-value is greater than the alpha level, then we do not have convincing evidence for the alternative. And in this case, instead of rejecting the null hypothesis, we would fail to reject the null hypothesis. So listen, I hope at this point you understand, first of all, how important the p-value is for AP statistics. It is the holy grail, the thing we've been working towards the whole year. And it is the understanding of that p-value that ultimately leads to the conclusion that you're probably used to writing at the end of a significant. Now, I do have a homework problem that is, of course, related to the p-value that I'd like you to try, and Mr. Murphy will check in with you on that one tomorrow. I will be back with you on Thursday this week, where we will talk about how to identify the right type of inference procedure, whether it's a confidence interval or a significance test. But you should join Mr. Murphy tomorrow at 2 o'clock, and then I hope to see you again on Thursday. Have a good evening.